Hello everyone, I will be your instructor in this DSA course. In this DSA course, we are going to see the 8 most asked DSA patterns in any technical interview across the globe. Whether it is MNCs or it is startups, we are definitely going to see these 8 patterns repeatedly asked again and again and again. The motivation to create this course is actually a personal one. A few months ago, I actually tried to give an interview for a simple company, and that company actually asked me a very simple question. It was a very simple question, and it took me an entire hour. I was struggling for entire 60 minutes just to figure out how to make this code compiled. Can you imagine? Like in that entire interview, there was just one question and I was struggling to complete that question. And that really just destroyed my week at that time. Entire week, I was like, why could not I do this? Because I knew that it was a very simple problem. I could definitely do it. I had 3 years of experience, but I still could not do it. Can you imagine it? I was looking at code all the time, 12 hours a day, and I still could not do that. And then I was like, okay, I have to learn DSA. I have to understand what is really this thing. And from that point onwards, I started learning DSA. And today, after solving hundreds of DSA problems on LeetCode, and after understanding what is the base requirement of those problems, I'm going to pour everything I learned inside of this video. This video took me almost 4 weeks just to prepare, just to record everything. Like almost an entire month just went into recording, editing, posting, and just making sure that this video is the best video out there. It will actually help you to understand what is DSA and help you crack the technical interviews. Now understand that this video is about cracking the interviews. It's not about getting the interviews. Getting the interviews is a completely different thing. Okay, that's a marketing and sales thing. This is a technical thing. In this video, you are going to understand the DSA and how to crack the DSA questions. What are the patterns that you are going to be asked in the interview questions and all that stuff. But before we go into these 8 patterns, it is important for us to understand what lead code problems really expect us to do. What is the difference between easy, hard, and medium problems? Like what is really being asked in those problems? What is the thing that we need to understand at the base level to be able to differentiate that, okay, this is an easy problem, this is a medium problem, this is a hard problem, and then we can actually go ahead and approach these problems in a different way. Right? So that is what we are going to understand in the first section of this course. So let's go ahead and understand what is the difference between easy, medium, and hard problem, and what is really expected from us to be able to solve this question. So what really is the difference between the easy, medium, and hard problems on LeetCode or Code Forces or any other platform? Well, the difference is not about difficulty, to be honest. You think that it is a difficult problem. You think that a hard problem should be more difficult than an easy problem, but it's not really the case. Because even after you learn all the algorithms, all the data structures, the same thing happens. People who know everything in DSA, they still face and struggle with the problems. Which means it's not about knowing more at this point. It's not about you knowing just one more algorithm or just one more data structure that will help you to solve the problems. There's a different thing that is being targeted here. These lead code problems are asking us for a different thing. It's not just about algorithms or data structures. So after solving 250 questions on lead code, my conclusion is that these problems are asking us for one simple thing. That is observation skills. This is the crux of all the questions. Every question that you will see on lead code or code forces or some other platform like CodeChef, most of them are just asking you this simple thing. The observation skills. Can you observe what's really happening in the question? Because let me tell you, when you're solving something like easy question, the easy question are just about formula. Okay, you know some algorithm, you know some data structure, and you just need to use that data structure, apply in the question, and then just get the answer. You will be able to get the answer just by applying the formula. The formula can be DFS. Okay, it can be BFS. It can be binary search. It can be arrays. Okay, so it's a simple thing. You will simply have an algorithm or a data structure, and you just need to use that algorithm and data structure directly without thinking, and that will give you the answer in most of the time. That is what the easy problem is about. Easy problem is teaching you how to really use these data structures and algorithm. It is basically building this habit or this muscle memory that, okay, this is how you implement the DFS, this is how you implement the BFS. Here you are just learning the ABCs. Just like in school, we had entire books teaching us A, B, C, D, E, F, G, right? These are all basic things. But when we were learning them, they were so difficult, man. Like just drawing this A was so difficult in the school, right? Because we were learning this thing, we were learning it, right? So that's what easy problems are made to do. Their goal is to make sure that you understand these basic things: the DFS, the BFS, the binary search, the arrays, the hash maps. the greedy algorithm. These are the ABC, these are the tools, these are the ingredients that you are going to use to solve problems. Okay, and that's what the goal of easy problem is. Here you just need to observe that, okay, what is the formula that I can use to apply this problem and get the answer? Because these are direct formula based questions. But here comes the next level. The next level is medium questions. The medium questions are a little bit more difficult. Why? Because you need to observe more. Here you cannot just create a formula or just use a formula and get the answer. That's not going to happen. Here you need something more. You need to understand what is really happening in the question. What kind of formula should you use and how you are supposed to use that formula to get that answer. Here also the premise is very simple. You will have a question in which a particular type of formula, a particular type of algorithm, a particular type of algorithm will be used. For example, you have a graph problem, this kind of, right? Okay. So you have a graph problem and then you will simply have to use a particular DFS, a particular BFS, and that will simply give you the answer. Here also, it's a simple formula to answer question. The thing is that here you are not just using the formula. You are using a formula to get an answer somehow. For example, you can have two graphs or you can have two trees and you have to decide whether these two trees or two graphs are same or not. So yes, you are going to use the BFS, you are going to use the DFS again, but you will have to use them and you have to decide how you are going to get the answer with the help of these algorithms. Because the algorithm DFS and BFS simply goes from one node to another node, right? That's all they do. But checking the equality of these two trees is completely on you. So we have this tree, right? And then we have this tree, right? We have one and then we have two. How are we going to make sure that these are equals? We are going to use this BFS and DFS, but we have to observe the other properties also. And so here we need a little bit more deeper understanding, not knowledge. Remember this thing. Knowledge is something like an information that you use. Knowledge you will gain, okay? But here you need to understand that, okay, if you want to compare two trees, their starting nodes should be decided, right? If I try to go from here, this is the starting node here, and this is the starting node here, then I can decide, okay, I want to now compare the trees, right? If I go here in this tree, then I also have to go here in this tree, right? I have to check this node, I have to check this node, and I have to check, are these equal? Do they have the same value? If they don't have the same value, we know that it's not equal tree, right? So do you understand? Now it's not just about formula. Yes, you are going to use formula to get the answer. But it's not just about formula. It's about you being able to observe the other properties also, the other things also that you need to observe to make sure that you are able to solve the problem. Just like we have observed that if you want to compare the two trees, you need to decide their starting node, you need to decide their left and right children, right? If you are going in the left direction first, you have to go in the left direction for this tree also in the DFS. So that is the medium level. Here you need to observe more than just formula. You need to observe what is really happening in the question, what are the properties that you can use to decide the solutions or to decide the answer. Basically, you will have to use formula like DFS, BFS, binary search, and then get the answer using the properties that are given in the question. Properties are nothing more than rules. Okay, just they are simple rules. That's all they are. You will have simple rules that will help you to get the answer. It is your observational skills where you need to understand or you need to observe what those rules are. They will be written in the question for sure, but you need to be able to understand what those rules are by making sure that your observational skills are high. Then comes the hard problem. This is like the holy grail of LeetCode, right? The hard problem that everyone wants to do, but they are not able to do it, right? And the hard problems, I'm gonna tell you guys very clearly. This is purely observationals, okay? If you do not have any observation skill, you will not be able to do it, okay? You need to have observation skills. Why? Because in the hard problems, you are again going to use the same algorithms. You can use DFS, you can use BFS, okay? You can use binary search, you can use arrays, you can use hash maps, you can use heaps, you can use many other things. The formulas are going to be same, right? The properties are going to be the same, right? There will be rules in the question, right? So you will have many things in the question itself that will help you to use these formula or understand that, okay, you need to use this particular formula to solve this particular question. The thing that changes in the hard question is that there will be some trick. Okay, it's no longer just about you being able to observe property from the question or rules from the question and just get the formula and then use the formula with those rules to find the answer. It's now more about you understanding, you really understanding the things Okay, for example, most people do not understand what is a graph. A graph is not a set of nodes, guys. This is not a graph, right? I mean, this is just a drawing. This is not a graph. It's not a graph. It's a drawing. What is a graph? Do we know what really is a graph? We don't. We just say, okay, anything made up of nodes and edges is a graph. But do we really understand what is a node? Do we really understand what is an edge? Can we just get a crazy example where we are supposed to use DFS and BFS, where we actually have to deal with graphs, but that is not inherently told to us. For example, suppose we have a 2D grid. Let's just say we have a 3 by 3 grid where we need to do something. So we have this particular 3 by 3 grid, right? It's a 3 by 3 grid. It's a 2D array, right? And there will be some values like 0, 1, 2, or maybe 3, 2, 4, 7, 8, 9, 10. Okay. And now we have to do something with it. Suppose I say that you can start from any node and you can only go to the next node if that node is actually greater than the current node. So I can go to 1 from here, right? Because 1 is greater than 0, so I can go here. I can also go here down, right? Because 9 is greater than 0. So can you imagine how you're going to use graph in this problem? Because it's a graph problem. Okay, this will be a graph problem. And most people don't understand. Most people do not know what really is a graph because this thing itself is a graph. But people do not know how. What makes this particular thing a graph, right? So here what you truly need is a deeper understanding. You have the knowledge. You definitely have the knowledge that okay, we have a node, we have an edge, and that's how a graph is made. But what is this node? What is this edge? What does these two things mean? Like how can you notice that okay, some problem is a graph problem? And this is the hard level. Here you will need to have observational skills like crazy. You need observational skills, guys. That's what you're being tested on. You're not being tested on DFS. You're not being tested on BFS. You're not being tested on the knowledge of arrays or hash maps. This, this is the main thing that you're being tested on. Observational skills. Can you observe? Can you see? Can you find the hidden patterns? That is what the LeetCode questions are designed to do. They are designed to gauge your observational skills. In hard questions, your observational skills are exactly what's tested. Your ability to understand what is a graph, your ability to understand the concept in a deeper level, plus there will be tricks. Okay, there will be tricks in the hard question. There will be some kind of trick that you need to use that will help you to gain or get to the answer. And that trick, how are you going to figure that out, right? I mean, it's a trick that is decided by the question setter. The person who made the question had some kind of trick and they decided that, okay, if the person can figure out this trick, they will be able to solve this question, right? That's the kind of hard difficulty we are talking about here. So how will you be able to decide or figure out that trick, right? That trick is nothing more than some observation, some rule that has not been explicitly told in the question description that you can figure out on your own somehow. But it is on you to be able to figure that trick out. And that is where your observational skills are truly important. You need to observe things piece by piece, little by little. And let me tell you guys, that trick is not something that you cannot figure out. You can definitely figure out by taking examples. Suppose that you have been told that there is a graph, okay? There is a graph and we have many nodes in that graph, okay? And now you have to tell us the minimum height that you can get from this graph, right? So one way is to just go for every node and start a DFS from everywhere and then decide which is the minimum height or what are the two minimum nodes they will be. But that will be like order of 2 raised to the power and that will be a very high time complexity because you will have to go through each and every node once and then run the DFS from that node. So DFS will be run for n times and that will be a very hard thing, right? I mean, that will be a very bad time complexity. So in these kind of questions, there will be tricks that you can figure out by taking simple examples, by taking your own test cases. You can start with a simple node one, okay? A single node and observe what is the situation in this node. Then you can decide to add another node and then observe what is happening in this set of nodes, right? Then you can try to add another node and see what is really happening in this set. Then you can try to add another node and see what is happening in this set. And once you start taking examples, you will be able to figure out the hidden conditions in the question. These hidden conditions are exactly the trick that you need to know. But you can only know these tricks once you have the patience and you have the observation skills to actually analyze your own test cases, your own things. The example that you're creating in the real time, you need to be able to analyze what is really happening in that example. And that is what the hard level of LeetCode is. It's just more observational skills and deeper understanding of what you already know. The easy questions will help you memorize and will build a muscle memory in your mind to implement solutions like DFS, right? It will help you implement BFS. Like easy problems are just a practice book where you can just go ahead and practice all these algorithms and data structures. Then comes the medium problem where you need to understand how to use these algorithms and data structure to get a particular solution. And then comes the hard question where you will have some kind of hidden trick in the question itself, but that trick will not be written in the question description anywhere. You will need to take test cases, very simple test cases, and then you will have to make those test cases a little bigger. You will have to observe what is really happening in those test cases, and if you can try to get some kind of property, some kind of rule that will help you solve the question. That is what you need to solve these hard problems, just a higher level of observation skills. And how can you develop these observation skills? Well, let me tell you this thing very clearly, guys. Okay, there is no replacement for grinding. Okay, you have to go through these solutions, you have to go through these crazy problems, you have to go through these to understand what you actually need to observe, because there can be multiple or a bazillion things going on in a problem, right? But you don't need, or you are not supposed to observe all of it. At the end of the day, you have a single brain that have a very limited resources when you're trying to solve problems, and you need to be able to observe things properly. I was watching an interview of Magnus Carlsen where he was saying that he does not need to think what he need to do. He just knows what he need to do, right? Magnus Carlsen, if you don't know, he is a famous chess player, like one of the best chess players of the world. And he is saying that he does not think what he needs to do. He just knows what he needs to do. And how do you think that comes? That comes with years of practice, right? Here in LeetCode, you don't need years of practice. Like 6 months is more than enough to make you a monster in LeetCode. But I'm telling you guys that you need to put in the reps. You need to go through the questions. You need to go through them. Otherwise, you will only just be in a tutorial loop. I'm telling you guys, this tutorial is nothing more than a help. Okay, if you just keep watching tutorials, that's not going to help. That's never going to help. Tutorial is like an information book. You get the information, and now it's up to you to make sure that you understand how to use that information. And making yourself better at using information is a skill, because everybody have information is already there everywhere over the internet, all over the world. There is crazy amount of information, and people have a lot of it, but people are not able to use it, right? People don't know how to use that information. People don't have the connections in their mind to use the information. And in order to build the connections, you need a long-term memory. You need a long-term memory that is filled with a situation where you had to deal with crazy problems, right? And then you actually figure out the solution, and then you make sure that you don't forget that solution, because that is already in the long-term memory. Okay, you will not forget the solution. Even if you forget the solution, you will not forget the approach that you took. Okay, so don't worry about forgetting things. That will be fine. But you're not supposed to waste your time in tutorials all over the internet thinking that watching tutorials will make you better. It will not. Observation skill is something that tutorials cannot help you with. You need to go ahead in the trenches. You need to go ahead and solve the problems. You don't need to solve them by yourself all the time. Okay, it's okay to watch a video that helps you and explain the solution to you, but understand that you need to spend at least 1 hour, actually at most 1 hour. So if you cannot solve a problem in 60 minutes, okay, put this ballpark timer. If you cannot solve a problem in 60 minutes, you can go ahead and watch a video on how to solve that problem. Because if you cannot solve it in 60 minutes, well, you don't have what it takes to solve that problem right now, which means you need to increase your understanding on that concept. And that is why it is okay to watch a video that will help you, okay, that will explain you how to solve that particular question, because that video will now actually feed your brain a new pattern, a new thing that you can use in other problems also to solve those problems. I'm telling you guys, like most of the lead code problems are just repetition of the 8 basic patterns. Like almost 90 to 80% questions on lead code are nothing more than repetitions of 8 basic patterns. But you need to be able to understand those 8 basic patterns in depth. And then every problem that you will find on LeetCode will simply feel familiar. It will not feel a difficult problem. It will simply feel a familiar problem that you can solve. You just need to implement the same formula, the same algorithms, the same properties in a different way. That's all. So here is what you need to do, guys. Whenever you're trying to deal with easy, medium, or hard problem, what you need to understand is you are supposed to observe. Okay, in easy problem, all you are supposed to do is observe the formula. Okay, in medium problem, you are supposed to observe the formula plus how to use it. How to use it to get the answer. Okay. Then in hard problems, you will have a trick. Okay. You will have to understand this trick by taking your own test cases. Okay. Understand how to make test cases and try to observe what is happening in those test cases, how things are changing, how new properties are getting added when you are adding new things in those test cases. That will help you understand the trick. Okay. And basically, you also have to need a better understanding or higher understanding of concepts. Okay, you need to understand what things really are. You are not supposed to know more concepts. You are supposed to know them in depth, in detail. And that is what separates this easy, medium, and hard problems on LeetCode or Code Forces or CodeChef or any other platform. All you are being tested on is your observational skills. All of these platforms are just trying to test your observational skills. If you have observational skills, you are the gold. Okay, simple as that. And the way to increase your observational skills is to understand what you're supposed to observe. Okay. You're not supposed to observe everything. And the way you learn what you're supposed to observe is actually through practice. You really have to go through 250 questions and you really have to understand things to really become able to see the hidden patterns in those questions, because those patterns are exactly what's repeated over and over and over again on many, many, many questions in these platforms. So now that we understand what is the expectation of these questions from us, we can move on to the different patterns. So yes, now we understand what is the difference between easy, medium, and hard problems, and now we can get into the course right away. Let's get started. Today we are not solving LeetCode. Today we are going to understand what is two pointers. This is one of the most asked DSA patterns in the interviews, and people still have many confusion between two pointers and sliding window, and when to use two pointers, why to use two pointers, how does this actually make n square complexity into order of n, how does all this happen, and we are going to understand everything in depth. This video is going to be the last video you will need to see on two pointers. Now before we go ahead, I am assuming you have basic understanding of programming. You know how loops work, you know what is big O of n square, you know all this basic stuff. I am assuming you understand them, and then only you are able to come to this point to learn two pointers. So now let us understand two pointer approach. So what is two pointer approach? So two pointers is actually a technique in DSA that helps us to solve particular type of problems that involve pairs of elements, not range of elements. Do you understand? We are going for pairs of elements. That is important. This range of element is not our concern. So what this simply means is that in any question in DSA, if you have to deal with A comma B, this kind of pair, then you can actually go ahead and use two pointer technique. It's a very strong indication that you are supposed to use two pointer technique. So anywhere you see that you have to deal with two elements and you have to find their sum, you have to find their subtraction, you have to find their multiplication, you have to find their division, you have some kind of condition that you are supposed to check for it. The question has given you some kind of condition that you are going to check for this particular pair, then there is a high chance that you are supposed to use two pointers. Now understand the meaning of this thing. We are not dealing with ranges here. What this means is that we will have some kind of linear data structure. Maybe we have an array, we have a string, and we are only considered or we are only concerned with the pairs of elements. So I have 1 comma 3, that is a pair. I'm checking the condition, or I'm getting the sum, or I'm getting the division, or I'm doing something with the pair. What it means is that the conditions of the questions will apply to the pairs in isolation. It means any element or a range of elements between the pairs does not matter for checking the condition on this pair. This is going to be in isolation. But if the question says that this element is also going to be somewhat responsible for you to check the condition, then that will actually become a sliding window. Sliding window deals with a range of elements, not just pair. But two pointers, yes, two pointers only deal with pairs. Now sliding window is actually an extension of two pointers. Sliding window is like a child of two pointers, but that sliding window is used in different use cases. So this is like a very important difference that you need to understand between sliding window and two pointer approach. Now the next question is, where do you really use it? Of course, I mean, it's a technique, right? It is supposed to be used in some kind of situation, not every time. So you can use a two pointer technique whenever you see linear data structures. That's a very big indication that you are supposed to use two pointers. So if you see linear data structures like arrays, linked lists, or strings, it's a very good indication that you can actually go ahead and use two pointers. And it is because you can easily create and go through the pairs of elements, because it is easy to get access to elements. For example, if you have something like graph, one node here, one node here, one node here, then one node here, then one node here, it actually becomes very hard to get access of like this element and this element in constant time and then just make their pair and then do something with that. It's very hard, and usually it is not possible to optimize it using two pointers. That's why it is usually used in linear data structures like arrays, linked lists, and strings. Now understand that you are supposed to go through the entire question and know what the question is telling you. So if your question is saying that you have to deal with pairs, right? If your question is saying that there is a linked list or an array or some kind of linear data structure, then on the basis of both these things, you can make a guess that, okay, you are supposed to use two pointers here. Nothing works in isolation. Two pointers does not work in isolation. Two pointer is a technique that actually relies on the conditions given in question. So it is important that you understand what the question is saying. And based on the conditions given in the question, you judge whether you want to use two pointers or not. The next question is, why do we really use two pointers? What is the need? What is the reason that actually drives us to use two pointers? What is the kind of problem that we are trying to solve by using this particular technique, two pointers? So there are two reasons why you would want to use two pointer approach. Suppose if you have a brute force solution of order of n square and you want to optimize it to order of n, then you can try to use two pointer. Otherwise, if you have an order of n solution and you are currently doing the solution in two passes, that means first you are running a for loop and you are doing something with the data, right? And after that, you are again running a for loop outside of this for loop, and then you are doing something again with the data, and then basically you are getting the solution. You can eliminate need of one for loop and do everything within this for loop. That is basically doing it in one pass. So if you want to remove this two pass solution and turn it into a one pass solution, you can use two pointers. Now I'm going to elaborate on both of these points in detail with the help of examples. How are we even able to reduce order of n square into order of n, right? Because this is not going to work for every order of n square solution. If you have something like graph and you are getting like order of n square, two pointers is not going to work. So in what kind of situation are we able to convert this n square solution into an order of n? And in what kind of situation are we able to convert this two pass solution into a single pass solution? We are going to understand that with the help of an example. But understand, guys, that these 2 points do not work in isolation. If you do not have pairs in your question, if you do not have linear data structures like array or strings or like linked list, right? Then these 2 points does not matter, right? Because you don't have the prerequisite to actually use two pointers. So all these points that we discussed till now, you need to combine all of them and then make a judgment that whether you can use two pointers or not in this situation. Nothing is working in isolation. Everything builds on top of everything else. And the next point is types. What are the different types of two pointer approaches? Understand, guys, that two pointers is just two pointers. We will simply have P1, P2, right? And they can be anywhere in the data structure. They can move in any direction. They can work however we want them to work based on the conditions of the situation. So these charts is basically a way for us to kind of segregate the different ways we can move the pointers. Otherwise, everything involving two pointers is simply two pointers. There is no point in having types. So that's why the type that we are going to discuss right now is something that we created for our convenience so that we will remember in what kind of situation or how we can actually use two pointers. So we have two types, the converging or diverging pointers, and we have another type that is parallel pointers. Now we are going to understand these techniques with the help of examples, okay? So don't worry if you don't understand them right now. So in converging two pointer technique, we will have P1 and P2 at different places in the array, and we will be moving these pointers towards each other based on the conditions that have been provided in the question. In terms of diverging, we will have the two pointers somewhere in the array and we will move them away from each other based on the conditions provided in the question. Conditions provided in the question. So conditions will determine how the pointers are going to move. In the same way, we have parallel pointers. So we will have pointer P1 and we have pointer P2. They will be moving in the same direction, in the parallel direction, either in this direction or they can also move in this direction, but they will be moving in the same direction. So they will have a parallel direction to move. Now, this may not make sense right now because it is very abstract because we are not dealing with any examples here. But in the examples, I promise you, you are going to understand each and everything about it. Now, before we move on to the examples, there is one thing I would like to discuss, and that is how. How are we able to actually take an order of n square time complexity and convert it into an order of n? How is it even possible for two pointers? And yes, you get it right. It is possible in a certain kind of situation. So it's a very specific situation where you can actually do this. You cannot do this in every kind of situation. So based on the discussion we had till now, we know that two pointers is used when we are dealing with pairs of elements, right? So suppose that I have an array like 1, 3, 5, 7. So there will be some pairs of these elements, right? How many pairs will there be? Well, we have 1 and we can make a pair with each of these elements. We have 3 and then we can make a pair with each of these elements. We have 7, we can make a pair with this, right? So how many pairs can we make? All in all, we can make n square pairs. We will have pairs like 1 comma 1, then 1 comma 3, then 1 comma 5, right? We are actually having pairs 1 comma 7, then we have 3 comma 3, 3 comma 5, and so a simple array of 4 elements actually end up creating these many pairs, right? These are so many pairs for 4 elements, and this is where we actually make the optimization. So in these kind of questions, you will be going through each and every pair and you will be checking for something or some condition in those pairs. And because we are going through all of these pairs, we end up running the loop for n square times. Hence, we actually get the n square time complexity. But what happens is that when we use 2 pointers, we actually use or we actually leverage the conditions given in the question to actually skip some of these, actually many of these pairs. So a huge subset of these pairs will be skipped, and that's why this entire order of n square will be converting to order of n. Now, which pairs will be skipped and how they will be skipped depends on the conditions of the question. And one thing is that you are not actually doing it consciously. It is going to happen automatically. The skipping is going to happen automatically if you understand the conditions of the question. We are going to understand, or we are going to take an example to see how this really happens in action. So right now it's a very abstract explanation that, okay, we have a few pairs and we just somehow skip a lot of pairs, which makes this n square into n. But now we are going to understand how it happens in action with the help of examples. Suppose we have a sorted array of height of people, and we are supposed to give the pair of people whose sum of height is actually a given number x. So the x will be input. The x can be 4, 5 or anything else. This will be given as input. And here you can see that we actually have a linear data structure, right? We have height of people, right? And we have this condition in the given question. We have a sorted array. Okay, it's really important. If you ever see a sorted array or sorted data structure, it's very likely that you are going to use 2 pointers. But make sure that you are taking all the points into account that we have discussed till now, that is having pairs, right? So here you can see that we are explicitly saying that we need to find the pair of people whose sum of height is actually x. So we have linear data structure, right? We have pairs. We have a condition like sorted array. So we can be sure that, okay, we are going to use 2 pointers. So now how are we going to use 2 pointers? Well, let's take an example. Suppose we have an array like 1, 3. So we have this array, and now we want to find out the pair of elements whose sum will be, like, just say x equals to 9. So we want to find the pair of people whose height sum will be 9. So what we can do is we can try to use 2 pointer here. So which one are we going to use? Converging or diverging, or we are going to use parallel? That's the question. We can try both right now. If I have parallel, then I will have a P1 here. Then suppose I have P2 here. And now I actually check the condition. We have 1 and we have 3. What is the sum of 1 plus 3? Well, it is 4. So it is not 9, correct? It's not 9. Now we know that this 4 is less than 9. And so this is the point where you will use the given sorted array condition to decide which pointer is going to move. So here, since it is less than 9, we know that we need to get a bigger number. And in order to get a bigger number, we need to shift the pointer towards this direction because it's a sorted array. So this element is going to be bigger than this element. So we shift the P2 here, and now we have 7 plus 1. So we will have 7 plus 1 equals to 8, right? So we have 8, which is still less than 9. But one thing you need to notice is that what about 3 plus 7? When are we going to increment the P1? That's not clear, right? Yes, I mean, it's a sorted array, but it is still not clear when or how are we going to use, or how are we going to increment P1 to get this 3, 7 pair. How are we going to do that? How are we going to check that? And here you can see that, okay, parallel might not actually work. So we may try to use converging. So once again, we will have pointer P1 here and we will have pointer P2 here. Now we will try to actually get the pair. Right now the pair will be 1 and 12. What is the sum of 1 plus 12? It is 13, right? Which is greater than 9. Since it is greater than 9, we are going to use the given condition of sorted to actually decide which pointer is going to move. Since it is greater than 9, we need to get a lesser number, right? So how are we going to get a lesser number? Well, we need to reduce the biggest number in our pair. In the pair, we have the biggest number 12. It means we are supposed to reduce P2. So P2 will be here and we have 11. Now 1 plus 11, still 12, right? It is still greater than 9. We will again shift the P1, and 1 plus 10, well, 11. We will again shift it and we will be here now. 1 plus 9 is 10. We will again have to shift it, right? So we will shift it to the 7. Now P1 is still at 1, right? So 1 plus 7 is equals to 8. It is less than 9. So 8 is less than 9. It means we should now get a bigger number. To get a bigger number, we need to increase the minimum number in our pair. So the minimum number is what? 1. We need to get a bigger number than 1, right? So we will shift the P1 to this place. So now we have 3. 3 plus 7, it is 10. Now it is greater than 9. So we will reduce P2. So P2 will be reduced and P2 will be here. So P2 and P1 are at the same position and we have not found this particular X. It means we can actually stop the loop, and we know that there are no two pairs in the given array that actually sum to the 9. So this is an example where we don't get any pair that is actually going to give us the sum of 9. Now here's one thing you need to notice. When we were shifting P2 from 12 to 11, what do you think we were doing? Well, we were actually skipping the pair like 3, 12, right? Because once we shift the pointer to 11, we will never ever be able to calculate this or get to this pair, right? 3 is here, so we can, yes, shift the pointer to 3 and we will get the 3. But in order to get the 12, the P2 needs to be at this position, right? But we shifted the P2 to 11, so it means we essentially end up skipping this particular pair. Similarly, when we shifted the P2 here on 10, so what we did is we ended up skipping 3, 11 also, right? In the same way, we ended up skipping a ton of pairs. I'm just giving you a few examples, but we skipped 3, 12. We skipped 7, 12, right? We skipped 9, 12. We skipped 10, 12. And this happened by the given condition, that is the sorted array condition. So we did not actually skip these pairs deliberately. They just got skipped automatically because we used the given condition to actually decide how we are going to move the pointers. And while moving the pointers, we just automatically end up skipping many of the pairs that would not have been able to give us the proper answer. Now, of course, if we were actually had x equal to 8, then eventually when the P2 was here, we would just get 1 and get 7, and that will actually be like 1 plus 7 equals to 8, and we will simply return this 1 comma 7 or P1 comma P2, and that will be answer. But even in that case, we would be actually skipping many of the pairs, just like this. If we did not use two pointers here, what do you think we will be doing? We will take each and every element and we will create a pair with each and every element in the array, and that will give us around n square pairs. And then we will go through each of those pairs just to see if the sum is actually 9 or not, and that would have caused order of n square time complexity. But here in the pointer approach, we just went through each and every element only once, which actually reduced the time complexity to order of n. Why? Because we actually skipped a ton of pairs, and we only dealt with the pairs that have some potential or that could have been the part of the answers. And we were able to do this just because of the given condition in the question. So the conditions in the question will determine how the pointers will move. Make sure that you understand the conditions in the question. Now here's another example. Find if a given string is a palindrome or not. So this word palindrome actually consists of many conditions. What is a palindrome? So basically we will have a string like race car, or we will have a string like noon, and we have to tell whether these two strings are palindrome or not. So to solve this question, we will need to understand what is a palindrome. Palindrome is simply any string that if you read it from left to right, it will be same as reading from right to left, which basically means if you take a string like race car, you reverse it and you actually compare it with the original string, they will be same. So I have the race car string here. I will now reverse it. So I will take R here. Okay, R will be here. Then A will come here. Then C will come here, right? Then E will come here, race. Then again C will be here. Then A will be here. And then R will again come to here, right? So you see this string, race car, and this one is also what? Race car. They are basically the same string. Similarly for noon, if I take N here, then O will be here, then O will come here, and then N will come here. I have reversed the string and it is still the same string. That is what a palindrome is. Now, how will you use two pointers? Well, understand the brute force solution. What you will do in the brute force is you will take the string, you will reverse it, and then you will what? You will compare it, right? You will compare this word with this word, right? So P1 will be here and P2 suppose will be here. So we are comparing whether this is equal to this or not. If they are equal, P1 will be incrementing, P2 will be incremented. A will be compared, right? Then C will be compared with each other. Then E will be compared, right? In the same way, you are taking pairs of two things and you are comparing them, correct or not? Yes, you are comparing them, which is amazing. So now you need to observe something. This R, this particular R, what is it that you are comparing it with? You are comparing it with this R alphabet, right? And this R alphabet is actually coming from where? It is coming from the end of the original string. So what you are really doing is that you have a string like race car and you are actually comparing the end elements. Okay, so this element is compared with this element is compared with this element, This C is compared with the ending C, right? This E will be compared by itself. So that's how you are basically comparing. So what if instead of creating another array and actually taking order of n space complexity, what if I just use pointers? So we again have the same string. We will have pointers P1 here. We will have pointers P2 here. We will compare the element at P1 and P2. So P1 element is R, P2 element is R. They are same, right? So based on the properties of this palindrome, which actually turns out to be conditions of the question, we know that we need to shift the P1 to next because we want to compare the next element because these elements are just fine, right? We don't have to worry about them. So we shift the P1 to the A and we shift the P2 to this A. Then we compare, is this equal to this? They are the same, correct? So we again shift the P1 to C and P2 is shifted again to this element. So P2 have C. Is this equal to this? Well, yes, it is equal. Then again we shift the P1 to E and we shift the P2 to E again. Now we check, is the element at P1 and P2 equal? Well, it is the same element, so yes, it is equal. So we can say that, okay, given string is palindrome, so we will simply return true. And here you can see that by using two pointer approach, what we did is very simple. We did not reduce the time complexity from order of n square to order of n. That did not happen. The original time complexity, the OG time complexity was also order of n, right? All you were doing is that you were just reversing the string and then comparing it. So you reverse the string and then you compare it. These were the two steps that we were following in the original solution, the brute force solution. So reversing will take what? Order of n, and comparing will take what? Order of n time complexity, right? So we did not really improve the time complexity because the time complexity in two pointer is also order of n. So what did we really optimize? We removed one of these steps. We removed the step for reversing, right? The reason we had to reverse it is because we wanted to compare this one with this element, right? So we removed this particular steps. This got removed, which means earlier we had to run the loop two times. We had to run the loop two times. Now we only have to run the loop for comparing. That is the only thing we are doing. We are taking these elements, right? And then we are comparing, and that is the only thing we are doing in the loop. So that means the solution that was two pass, it got converted into this one pass solution. And this was actually the second reason to use two pointers. The first one was to get the time complexity from n square to n. The second was to actually convert the solution from two pass into one pass. So what this means is that in a two pass or three pass solution, you will have a few steps. You will be doing something in all those steps. You will need to understand based on the given condition what is the step that you can actually skip. What is the step that is a redundant step? And here the reversing of the string was actually redundant. It was not necessary. So we removed that and we just focused on the comparing part. And by doing so, we also saved space. So in the original, the space complexity was actually order of n because we were creating a new string. We were reversing it, and that reversed string was actually a new string taking up as much space as the original input. But right now we are not reversing the string. So the space complexity for us, the two pointer, is order of one, that is constant. Isn't that crazy? So here we have another question. Suppose we have an array that contains numbers and zeros, okay? We have to place all the zeros at the end of the array. Okay, first of all, we have a linear data structure. Great. Now we don't have pairs here. So nothing in the question actually talks about pairs, and we just have numbers and zeros. So first of all, we should try to actually get a brute force approach, right? So the input will look something like this, right? We will have 1, 0, 7, 0, 0, 8, 9, right? Something like this. And we have to place all these zeros to the end. So what we can do is that we can create a list. This is going to be a list. And we can actually go through this array. We will have a loop on this original array. And we will check if the current element, that is the ith element, is actually a number or a zero. So currently it is a number. I will take 1 and put it into the new list. Then I will go here. It's a 0. I will not put it. Then I will be here, right? It's a 7. I will put it here. Then I will be here. 0, not going to put it. 0, not going to put it. Then I will be here. 8, right? So 8, I will place it in the new list. Then I will be here in the loop. 9, I will place it in the new list. So I have a list of what? I have a list of numbers, right? And now what I can do is very simple. I can simply go ahead and actually make modifications in the original list, or I can create a new list. But let us try to make modification in the original list to save some space. So what I will do is very simple. We have original list 1, 0, 7, 0, 0, 8 and 9, right? All I need to do is get all the zeros at the last. So what I can do is I can take this one and override it here. So 1 will directly go here and nothing happens because it was already 1. But if I take 7 and try to override this position, I will have 7. Now I can take 8 and over at this particular position. So we will have 8 here. Now I take 9 and over at this particular position, we have 9 here. Now what I can do is that I can overwrite everything else or every position else with a 0. So it means we took all the zeros, placed them at the end, right? That basically solves the problem. This is a brute force way of doing it. So now let us start to see what we are doing here. First of all, we are creating a list. The reason we are creating a list is to get access to the numbers, right? Make sure that we have access to the numbers all the time. And then we are just overriding the original list. So what we have here, we have step 1 and we have step 2, right? So if we can actually somehow remove one of these steps, we will have what? A single pass solution, right? And we can use 2 pointers to actually get this one pass solution. So this actually gives us a hint that we can actually use 2 pointers to solve this particular question. Now, if you really look at it, what is happening here? Well, we had 1 here, right? And we placed it here, it is same. But we had a 0 at this position and we placed a 7 at that position. What happened is that this 7 shifted. Basically, in a sense, that's what happened, right? This 7 came to this particular position, right? And since it came to this particular position, we actually had a 7 in this place, right? We had a 7. But this 7 was what? It's a copy, it's a duplicate. So we could override this 7 safely with some other number. So what we did is we simply took this particular number and we override this position with this number, right? Then again, we had 8 here and we again have an 8 here. And then what we did is we took this 9, right? And we override this particular 0 with 9. And once we are done with this 9, the ending number, what we did is we simply took all these numbers that were at the end and we just made them 0. We override them with 0. That's pretty much what we did. So how we can do this with the help of 2 pointers? So we again have the same array, the same input, and we will have P1 and P2 at the starting. Both of them are pointing to 1. Now what we can do is we can check if the current element is a 0 or not. Since it is not a 0, we will take one of these pointers and we will shift them to next one. So we will have P2 shifted here. So P1 is at 1, P2 is at 0, right? So it means we have found a 0. Now that we have found the 0, what we can do is we can simply shift the P2 again. So we did not do anything when P2 was at 0, right? But now that P2 is at 7, we found a number, right? Now we want to take this number and put it at the start so that all the zeros will be at the end. So what I know is that P1 will be at a number, at a particular number, and the next position is going to be 0. So what I will do is that I will take the 7 and I will replace or swap it with this thing. So here's what I will do. The element at P1 plus 1 will be swapped by element at P2. Remember, we are not swapping P1, we are swapping P1 plus 1, the next index from P1. Now when the swapping happens, we will have 7 here and then we will have what? 0 here, correct? And then we will shift the P1 to this place. So P1 is at this place right now. So we have removed this 0 from here and we have shifted it to this place. The 7 has also been removed from this place and it is now here. So now the P2 is pointing to 0. We will do nothing. We will just shift next, right? P2 is again pointing to 0. We will do nothing. Shift. P2 is pointing to 0. We will do nothing. Then shift. P2 is now pointing to a number. Now we have a number and we can actually swap it again. We need to put it at the start so that we will have all the zeros at the end. So we will take this 8 and we will swap it with the P1 plus 1 index. That is P1 plus 1 is what? This one. This is the element at P1 plus 1 index. So again we will swap. So after swapping, what do you think will happen? After swapping, this 0 will be gone and we will have 8 here, and this 8 will be gone, we will have a 0 here. So now P2 again points to a 0 and the P1 will be actually shifted to this place. So P1 is now pointing to 8. And then since it is 0 right now, we will simply shift P2 again to this place. It is 9. We have again a number 9. We will take this number 9 and we will swap it with the P1 plus 1 index. That is this one. So we will take this 0 and we will take this 9. We will swap them. So 9 is here and 0 is here. And then the P1 will be shifted to this place, right? And the P2 will be shifted next place. So P2 after this 9, well, it is going to go out of bounds. So we can simply stop the loop. So at this point, we have what? We have 1, we have 7, we have 8, we have 9, and then we have 0, 0, and 0. So all the zeros have been shifted towards the end of the array. So now do you understand how we are using the 2 pointers? So we knew that P1 will always be at a number, right? And the next element of P1 is going to be 0. That's why we had a pointer P2 that was going ahead of P1, exploring all the next elements. And as soon as it finds a number, it was used to swap this 0 from the element at P2, the number at P2. And then we would also increase the P1 so that the P1 will always be at a number and the next to the P1 will be a 0. So that's how we were able to solve this particular question. So the question that was actually a two pass in the original solution is now a one pass or a single pass solution. This is where we are actually using the two pointers. So I hope you understand how the two pointers is used. And now I would like to show you one more example, that is merge to sorted array. So here we will have arrays like 1, 3, 7, 9 or 8 maybe, and 10. And then we have another array that is 2, 5, 6, 9, 12. So we will have two sorted arrays. Both of them are sorted in ascending order, right? And we have to merge these sorted arrays into a single array. So how we can do that? So the brute force way is to just combine these two arrays into a single array, and then we will simply apply the sort function on those array. And that will cause what? That will have order of n log n time complexity, which is too much for this kind of problem. We can actually do better. We can do it in order of n. So we will again have to create a new array, of course, but now we will have pointers. P1 will be here and P2 will be here. And now we will check which of these elements is smaller. So one is smaller. So we will take P1 element and we will place it here. And then we will shift the P1 to the next element. So P1 is now at 3. We will take which one is smaller, 3 or 2? 2 is smaller, so we will take 2 here and we will shift the P2 to the next element. Now we will check which one is smaller, 5 or 3. 3 is smaller, so we will take 3 and shift the P1 to the next element, that is 7. Which one is smaller, 7 or 5? 5, right? So we will take 5 here and then shift the P2 to the next element, that is 6. So P2 is at 6. Now which one is smaller, 7 or 6? Well, clearly 6. So we will take 6 here and we will actually shift the P2 to the next element, that is 9. Which one is smaller, 7 or 9? 7, right? So we will take the 7, we will shift the P1 to 8. Now which one is smaller, 8 or 9? 8. So we will take the 8 and we will shift the P1 to the next element, that is 10. Which one is smaller now, 9 or 10? Well, 9. So we will take 9 and we will shift P2 to the next element, that is 12. Which one is smaller now, 10 or 12? It is clearly 10. So we will take 10 and we will shift the P1 to the next element. It is out of bound. We will stop the loop and we will take all the remaining element in the other array. We will place them in the final array. So here you can see that we were able to merge the two arrays into a new sorted array with the help of two pointer approach. And the time complexity here is order of n. N is basically the length of this array and the length of this array combined, because we have two pointers going through each and every element of the two arrays. So that's why n is basically the combined length of both the arrays. Now I wanted to show you this example because I wanted you to understand that two pointers simply means two pointers. Okay, they do not have to be in the same array. They can be in different arrays, because here what we are doing is that we have two elements, okay, 1 and 2, which actually creates a pair, 1 comma 2. And then we are actually comparing, or we are actually putting some kind of condition. We are checking them against a condition, and then we are actually placing the result of that condition here. So we have pairs, we are checking a condition on those pairs, then we are putting the result here. We have linear data structure here, correct? It's a linear data structure. It is basically a recipe for two pointers, right? Do you understand it? It's a recipe for two pointers. And this is what you have to notice in question. You have to see the question. You have to notice what are the elements that I have to deal with. Do I have to deal with the pairs, or do I have to deal with the ranges of elements? If I have to deal with the ranges of elements, you will be using sliding window, not two pointer. So make sure that you understand all the points that we have discussed till now. Everything we discussed till now, the order of n square, time complexity to n time complexity, two pass to single pass solutions, the linear data structure. So you need to understand that in order to find out whether you can use two pointer or not in a given particular question, you really need to observe different things. Like, have you been given a linear data structure, right? That's one point, or that's one indication. Are you dealing with the pairs of elements? Well, that is another indication. Are you having one pass or two pass solution? That is another indication, right? So if you have many of these indications, then you will be able to say, okay, I can go ahead and use two pointers in this particular question. And yes, guys, there is no guarantee anywhere. Like, these kind of techniques are very, very, very common. There can be many different ways to use them, but I have talked about the most common ways to use them. Like, the most LeetCode questions are like these questions. You will be able to understand whether to use two pointers or not. So today we have LeetCode 27, that is remove element. This problem is very similar to LeetCode 26, in which we had to remove duplicate elements from a sorted array. In this problem, we have been given nums array and an integer val. Now we have to remove all occurrences of val in in the nums array, and we have to do it in place, so we cannot create any extra array. Now after removing all the occurrences of val from nums, the order of the elements may change. It means we don't have to preserve the order like ascending or descending or the original order. And after all this, we just have to return the number of elements in the nums array which are not equal to val. So at this point, a lot of people think that we can simply go through the nums array, we can count how many val are there in the nums array, and we can simply return the count. But no, that's not how it is working actually. So the reality is that we actually have to remove the val in place in this nums array, and then we have to return the count of elements that are not equal to val, because it actually check this particular nums array in the backend, since we are actually removing elements in place here. So even though we don't return the nums array, it can still check in the backend whether we change the nums array in place or not. So we do have to remove the elements anyways. To get accepted, you need to do the following things. Change the array nums such that the first k elements of nums contain the element which are not equal to val. We have to group all the elements which are not equal to val to the start of the array, and that length will be k. So k elements will be there which are not equal to val. The remaining elements of nums are not important, as well as the size of the nums. So it is saying that after you have grouped all the elements which are not equal to val in the starting of the nums array somehow, then the rest of the array does not matter. We will not check anything in the rest of the array. And finally, we have to return the k, the number of elements which are not equal to val. After submission, the online judge will check this particular k value. If this is correct, then it will go to the nums array and it will check whether the k element in the nums array are correct or not. It means we will have to modify the nums array to make sure the first k elements in the nums array are elements which are not equal to val. Now let us try to understand how to solve this problem. One way to solve this problem is to first of all sort it, so that we will have a sorted array, and then we can use LeetCode 26 problems solution to get all the unique elements at the starting of the array, and then we will simply remove val from this particular range and we will return the k by counting the range. But sorting the array will take order of n log n time complexity, and we don't want it. We can do better. We will have two pointers, a and b. The a will be at start, b will be at end. And suppose that the val for us is equals to 2. So 2 is something that we don't want in the array. So first of all, we can check whether this particular element at a index is 2 or not. If it is 2, we will have to do something, right? But currently it is not 2. So we will simply shift a to here. Now again it is not 2. Again shift a to here. Now it is 2. Now what do we do? Well, we will definitely have to have some element here that does not equals to 2. It can be any other element from the array. So for swapping, I will check b. Is this particular b equals to the val? If it is equal to val, there is no point in swapping, right? So I will shift it here. Now the b is here and b is 4. So 4 is not equals to val. So I know that I can swap this 4 with this 2 to make sure that this particular range does not contain val. And since we know that we have swapped something, so it means that this particular element will be val. So we will anyways go ahead and shift the b to this next index. Now the next index can be val, cannot be val, that doesn't matter. We will simply decrement by 1. Now the loop will go again and we are still at this particular position. We see that, okay, now this is 4. We will shift to next one. We saw it is again 2. Now we will check b. If b is val, it is not, so we can directly swap. This particular 2 will become 0. This will become 2, correct? Now again a is here, the loop will again run. The loop will see, okay, now it is 0. We will move a to here. We see 3. We don't have to do anything. We will again move here. So now at this point, we see that it is 2. We will have to swap it with something, but we see that a and b are basically the same. If I try to swap it, it won't matter. So I will simply go again. Now at this point, a will become greater than b. So we can simply stop our loop. And then we will have a new array of 0, 1, 4, 0, 3, and then we will have 2, 2, and 2. So as you can see that we have grouped these elements here that are not equals to val, and all the val elements are basically at this point. So now the a pointer right now is at here and b is here. The b came here because when a came here, we saw that, okay, it is 2 and b and a are same. So for b also this will be simple 2. So we will decrement the b, try to get some other element. So in the code, we will have a condition to decrement b by 1 and not swap this 3 with this 2. That we will have to deal with in code. That's a simple thing to deal with. You will be able to understand it just fine. But at this point, we have a here, b here. Now the indexes here are 0, 1, 2, 3, 4, and then 5. 5 elements are not equals to val. What is the index of a? 5. So we can simply return a. That will be our answer. So we have updated the array in place and we are returning the number of elements which are not equals to val also. Now let us go through the code also. We will have a is equals to 0, b is equals to the ending index of the array. Then we will run a loop while a A is less than or equal to B. Now, if the value at current index is equals to val, we will try to figure out an element from the ending of the array that is not equal to val, and we will try to swap it with. That's why we have this while loop here. We are checking while B is greater than 0 and B is greater than A. We are trying to figure out if the nums of B, that is the element at B, is equal to val. If it is val, then we will simply decrement B by 1. And after this entire loop runs, we will have a B that is either equal to val or not equal to val. So if A and B become same, at that time only B will be equal to val. But that does not matter because we can swap the elements and then we will decrement B by 1. If B is equal to A, the entire while loop will terminate after this. Otherwise, the nums of A will have an element that is not equals to val and we can continue with our while loop. Now, in case we find an element at A index that is not equal to val, we will simply increment the A index because we don't have to do anything. Now, after this entire while loop runs, we can simply return A because A is now the number of elements that are not equal to val in the array. Now let's try to run this and see what happens. So it runs in 0 milliseconds and beats 100% of the solution. You can really not trust the LeetCode compiler for these kind of things. Now let us look at the time and space complexity for this solution. Now even though we have a while loop inside of a while loop, the time complexity is order of n. Why? Because at each iteration of any while loop, we are either incrementing A or decrementing B. And once they are incremented or decremented, we are not doing it again and again. We just increment or decrement, increment or decrement. So we actually traverse the entire array only once. It's just that the outer loop is traversing it in this direction and the inner loop is traversing it in this direction from behind. But as soon as the B becomes less than A, we know that we have traversed all elements of the array, so we can simply break the loop and return. Now, in terms of space complexity is order of 1, that is constant space complexity because we are only using 2 pointers. We are not using any extra space. The space of output array is not considered in space complexity, only the space that we use to reach the solution. Now I discuss this particular solution here because I feel in my opinion that this particular solution is easier to understand for people, especially for beginners. But there is another way to implement a solution also. That solution is easier to write also, and I believe it is also easy to understand. This one is more easy to understand because you can understand when I'm incrementing A, for what reason I'm incrementing A, and for what reason I'm decrementing A and how. So this is the other way of implementing the solution. Here we are simply using a single while loop. We are not using the inner while loop. Now, in order to understand this particular solution, I would highly urge you to take a test case and do a dry run on your own to make sure that you understand how this problem is solved properly. Hello everyone, let's solve some LeetCode today. So today we have LeetCode 3 sum, which is one of the most popular problems after 2 sum problem. In this problem, we will be given an array and we need to find the triplets whose sum is basically 0. So you will be given an array like this and you have to find the triplets, basically a set of 3 elements whose sum is 0. So for example, -4, then we have 1 and then we have 3. So -4, 1 and 3, if you add them, they will result to 0, right? And currently this is the only triplet that we have in the array, but we can have more. We can have multiple triplets, and that is why we are going to send a list of these kind of triplets. So how do we solve this problem? Well, one of the brute force way to solve this problem is to find all the triplets. And so what is a triplet? A triplet is nothing more than a set of 3 elements A, B, C, right? So it means we just need to find all the possible set of 3 elements that we can create from the given array. And how we can do that? Well, we can do that with the help of nested for loop. We will have a for loop here with I, right? Then we will have another for loop here with J, and then we will have another for loop here with K. And in the K for loop, you will have access to I, J, and K. And then you can just check each and every triplet whether the sum of that triplet equal to 0 or not. If it is 0, you simply append or add this triplet into the result list. So you will simply do res.append and the triplet. But this is not a very optimal way to do this. For instance, the time complexity is what? Order of n cube, because you are having 3 loops, so the time complexity is very high. Plus in the question it is already instructed that we cannot have duplicate triplets, and this way will actually give you duplicate triplets, and it will be very hard for you to actually maintain whether you have duplicate triplets or not. So can we do better? Can we do actually a better solution with better time complexity and easier implementation? Well, yes, we can. But before we go ahead, let us understand how we can actually avoid duplicates. So for example, here we have 4, then here we have 3, and then here we have 1, right? So one of the triplets is -4, 3, and 1. So this is a triplet, and if you add -4 with a 3 and 1, it will result in 0. So it's okay, it's a valid triplet, correct answer. But then again, we have -4, okay? Then we have 1, and then we have 3 again here. We will have a -4, 1 and 3. So we actually have a duplicate scenario again, right? This is actually a duplicate. We just change the order of these elements, but it is still a duplicate, right? So this is the type of situation that we are supposed to avoid. Now let's make it a little bit more interesting. If I remove 0 here and I add -4 again, then what? Well, earlier you were using this 4 to actually make these two triplets, right? But if you actually shift the pointer now, this element is also 4. So this element will actually create its own triplet with 3 and 1 and with 1 and 3. So it's going to have its own two triplets, right? -4, 1, 3 and -4, 3, 1. So it means we actually end up having the same triplet 4 times and we don't want that, right? So to understand how we can avoid duplicates, we need to understand how the duplicates are formed in the first place. So if I just go ahead and actually remove the 0 and add -4 here, and we actually remove 1 and 3 also here, just for the simplicity's sake, we will add them later on. So right now we have a 4 here, okay, and I want to make triplets. So I will have 4 here fixed, okay, and then I will go through these elements, right? So in the remaining elements, I found 1 and 3 to be the elements that I add with 4, and they will give me a result of 0, right? Great. And so we append this into our result variable. Now this 4 is done, okay, we try to find all the possible triplets with this 4. Now we will actually shift to this 4, okay. Now this is the 4 that we are dealing with, and this is the remaining set of elements that we will have to actually get the remaining elements from. So in this remaining set, we again get these 1 and 3, and then we again end up making -4, 1 and 3 triplet. The reason this happened is because we use the same element -4 again in the next iteration to find the triplets. What we should have done is we should have skipped this -4, right? Because -4 element is already done. We have found all the possible triplet with -4, so we don't need to do that again. So better thing would be to just skip the -4 and go to the 2, and this would actually result in a new triplet if there was any. So what we need to do is we need to skip the duplicate elements together, right? We will take -4 only once, and then we will skip all the rest of the instances and get to the new element or the new number. But remember that in our array, we can actually have -4 here, then 0, then -4, then 1, then 3, right? So if we are at this position, we have no way to find out that there is another -4 outside, that we have another -4. So what will happen is that we will end up using this -4 to create triplets with 1 and 3. Then we will shift to 0, we will not have any triplets. Then we will shift to this -4, and we will end up creating again the same duplicate triplet. So how do we solve this issue, right? Well, we can only solve this by sorting it. So sort this thing so that all the same elements -4, -4 will be together, and then you can actually go ahead and skip those elements altogether. So we have sorted the array, we have all the common elements together. We will now be able to avoid duplicates. So our duplication problem is solved. Now how do we solve this order of n cube time complexity problem? I would like to reduce this time complexity somehow. So in order to reduce this, we need to observe our original brute force solution. In the original brute force solution, we were actually having for loops, right? We had 3 for loops, and then we were just getting these I, j, and k to create the triplets, right? But if you would have solved a 2-sum or 2-sum 2 problem, you would know that we can take these 2 for loops and just convert them into a single for loop. Yes, we can do that. We will have a for loop here, okay? We will have I index. So this for loop will start from here, I, and then we will actually use 2 pointer technique. So we will have an L pointer here, and we will have an R pointer here. And then we can simply have a while loop inside of the for loop, and we will have L less than equal to R. So while L less than equal to R, we will run this while loop. Now in the while loop, we are going to check if the sum is actually equal to 0 or not. So suppose that we have 4, we have -4, and we have 3. So what is the sum of -4, -4 and 3? It is -5, right? So -5 is what? -5 is less than 0, correct? If it is less than 0, we need to find a way to increase the sum, right? To increase the sum, what we can do? I is fixed. I is going to be at this position. So the only thing that we can move is L or R pointer. Since it is less than 0, we need to increase it, right? So currently in our triplet, we have -4, then -4, and then 3, right? This is fixed, so we have to move this or this. So we found a pair of 2 elements that we are dealing with. That's why we are using 2 pointers here. So we will take this minimum element and we will increase it so that the overall sum will increase. So I will take the L pointer and I will increase it to 0. Now what is the sum of -4, 0, and 3? Well, it is -1. So our sum is increased from -5 to -1. Great. But it is still less than 0. It means we still need to increase the L pointer. We take it here. Great. Now we have -4, 1 and 3. The sum is going to be 0. So we found a triplet and we will add this into the result variable. So one of the triplets we have found. Great. And the reason we were able to actually increment L is because this portion, okay, this entire thing is sorted. Do you understand it? We have a sorted array at this point. That's why we were able to increase L, because we knew if we increase L, we will get a bigger number, and that bigger number will help us increase this overall sum. In the same way, we can decide to decrement R, because we know that if we decrement R, we will get a smaller number most likely, and that smaller number will actually help us to reduce the effective sum. So now I believe you are able to see why we are using two pointers. We are using two pointers because we have sorted condition, we have a linear data structure, we have pairs. We are dealing with pairs of elements. So that's basically a recipe for two pointers. But currently we are at 1 and we are at 3, right? We found that the sum was 0 at this point. So which pointer should we move? Should we move L pointer or should we move R pointer? Well, we can move any pointer because we need a new triplet, right? So if I try to move L, L will be at 1, right? It's a new index. The value is still the 1, but the index is new. So we will end up adding -4, 1 and this 3. This will again result in the same triplet. It will again give us 0. We will again end up putting the same triplet in the result variable. That we do not want to do, right? It means once we found this one, we need to skip all the remaining ones. Okay, so we will skip all the remaining ones and we will come to 3. Then 3 plus 3, then plus -4. What is this? It is simply 2, right? It is greater than 0. So we will end up shifting R to this 3. So R is now here. L is also here. So L and R are actually at the same position. So L basically is equal to R. So we will end up stopping this while loop and then we will increment this I. Now we found the I to be -4 again, which is basically equal to the previous value. So we will simply again shift it to this one. So I will here, and then we will again go through this entire remaining set. And in this way, we will end up going through each and every element and we will find all the possible triplets. Now, all of this may seem a little complicated, but let me tell you, if you know how to solve two sum, and if you know how to solve two problem, this problem would be very straightforward. So I would highly recommend you to solve two sum and two problems if you want to get a better understanding of this problem. So in essence, what we did is very simple. We just avoided duplicate by shifting through the entire range of the same elements, correct, for both I variable and for L and R. Now let us go through the code. We have the result variable in which we will store all of the triplets. Then we are sorting the given array so that we will have all the common elements together, so that we will be able to skip the elements to avoid duplicates. Then we have the for loop. We are enumerating over the nums array and we have this index and the element A. So I represent the index and A represent the element. So if the I is greater than 0 and the element A is the same as the previous element, we will continue. So we are going to skip the entire range of the same element. Now we are saying I greater than 0. Well, if it was 0, we would actually be at the -4 for the first time, and in that case, we would actually like to run this entire loop and get all the triplets with -4. So that's why I greater than 0 here. So after skipping the duplicates for I, we will have L and R pointer. So here L is equal to I plus 1 and the R is equal to the ending element. So we are running while L is less than R, we are calculating the three sum. So the element A plus the element at L plus the element at R. If the sum is basically greater than 0, we know that we need to effectively reduce the sum. We know that we have to effectively reduce the sum to reach 0, right? That's why we are reducing the R pointer, because we know that the array is sorted, and if we reduce the R pointer, we will get a smaller element. Otherwise, if it is smaller than 0, we will increment the L pointer to get an effectively bigger sum, the bigger 3 sum, because we know the next element to L will be bigger than the current L. Otherwise, if it is neither too small nor too big, we know that we have found the sum to be 0. In that case, we will simply append this triplet into the result variable. Remember that we are not appending the indexes, we are appending the elements. So A is an element, nums of L is an element, and nums of R is an element. That's what we are appending to the result variable. And then we are only incrementing the L by 1. And then we are skipping all the duplicate L's. Just like we had L here, and then we are skipping all of these ones. Then we will reach 3. And that is what we are checking here. If the current element at L is basically same as the previous element, then we will simply increase the L pointer by 1. And also we need to make sure that L never becomes bigger than R. So we have this condition while L is less than R. And this condition will also help us to decrement R pointer automatically. So for example, suppose that L was here, we will check, is the current element same as previous element? Well, yes, it is. So we will increase the L to here. we did not do anything to r, right? But in the next iteration, in the entire loop, something will happen. So suppose that I was actually not -4, it was -1. Okay. So currently we are trying to find the triplet of -1, then L, then R, right? Now currently the L is at 0. So we will sum -1 plus 0 and the R is at 2, correct? So we will have like 1, which is bigger than 0, right? In the next iteration, this is what we will find. So we will simply end up decrementing R automatically here. Then again, this is basically duplicate of this one, right? Then again, the same condition or the same result will happen in the next iteration. Then again, we will end up basically shifting R to this side. And then we will have like 0 here. And since they are at the same position, we can simply end the loop. So we ended up skipping the duplicates for R pointer automatically. We just had to manually shift the L pointers properly. That is why here we are only shifting the L pointer properly, because the R pointer will be shifted if needed to be shifted in these conditions in the next iteration automatically. And once this entire thing runs, we will simply return the result variable. So now let us try to run this thing and see if it works. And so yeah, it works. Our solution runs in 525 milliseconds, beats 74.73% of the solutions on LeetCode. So it's a pretty efficient solution. Now let us talk about the time and space complexity. So the time complexity will be order of n log n, because we are sorting. Okay. So sorting steps gives us order of n log n, and then we have two nested loops, for loop and then while loop. So that will actually end up giving us order of n square time complexity. So overall, this is far bigger than this. So we will simply say time complexity is order of n square. That's it. Now the space complexity is what? Well, space complexity can be order of 1 or it can be order of n. And this confusion is arising because of this sorting step. So in some languages, you can actually have functions that will actually sort the array in place. That means they will not use any extra memory. So at that time, we will have order of 1 space complexity. But in some languages, they may actually use extra space to actually sort the array. So in that scenario, the sorting function in that language will take order of n space, resulting in order of n space complexity. Hello everyone, let's solve some LeetCode today. So today we have LeetCode 42, that is trapping rainwater. In this problem, we have been given n non-negative integers which represent the elevation map where the width of each bar is 1, and we have to compute how much water it can trap after raining. So it will look something like this. Here we have an array that is 0, 1, 0, 2, and this is representing an elevation map. Okay, what this means is that if we start here on this line, then the first block is 1 width height and its height is 0, right? So there is no block right now. The width is 1 width, but the height is right here, 0. Then we have a block of 1 height. So the height is of this block is 1. Then we have another 0 height block. So here we don't have any block. That's why the rainwater can come and trap in here. Okay. Then we have a block of height 2. So as you can see here that the width is 1, but the height is 2 for this block. Then after this we have a block of 1. So as you can see here we have a 1. Similarly we have 0 again. Okay, so this particular block, this have a height of 0, but as you can see that the amount of water it is holding is basically twice. There are 2 units of water here, right? Now the next block has a height of 1, as you can see in the array. Then we have a block of height 3, just like this one, and so on. We have the next block of height 2, then next block of height 1, the next block of height 2, then again next block of height 1. So in this way we have been given an elevation map, or basically a map of height of each block that is present in this line. Now, whenever the rain will happen, some of the water will trap in this structure, right? So some water is right here, then some water is right here, correct? Then some is right here. Now we have to figure out how much water the structure will contain after rain. So let us start with starting, okay? So here the block is height 0 and there is nothing on this side. Yes, there is a particular block of height 1 here, but there is nothing on the left side. It means nothing will stop the water from the left side. It means the whole water will simply go away. What it means is that there will be no water in the first position. We can always ignore this position safely because there will be no water here. Then we have a block here. Okay, now how much water can we store on top of this block? Well, nothing, right? Because there is nothing on the left side that is going to hold this water, right? Yes, there is a block on the right side that can help hold the water, but there is nothing on the left side. So all the water that will hit the top of this particular block will again go away. It will not stay. Now we have this block and it actually contains some water. So the reason it is containing water is because there is a boundary on its left side that is helping it to hold the water, right? So the boundary of height 1 is right here and then there is another boundary of height 2 right here, which is helping to hold the water. So the amount of water here is basically equal to the boundary here, right? You can also try to do 2 minus 1, that is 1. So that is also equal to the amount of water that is being held in this particular position. But we can see that the amount of water can never exceed the minimum of this boundary and this boundary. If the water try to exceed and actually comes here, the water will simply go down, right? Because there is nothing on the left side at this height to hold it. So eventually the water will always and always and always be equal to the minimum boundary height. So till now we encountered 1 unit of water. Now from here we will shift to this particular position. So now we are on this block. Okay, how much water can we actually store on top of it? 0, right? Because there is nothing on the left that is going to hold it. Yes, there is a particular block that can help to hold it, but there is nothing on the left, so it will simply go down. So here also we have the 0 water, right? So we can shift to this particular block and we will see that we have some water on top of it right here. Okay, we have a 1 block of water, and the reason is that there is this particular block of height 2 that is holding this water in place, and then there is also this particular block that is actually helping to hold this particular block of water. How? Well, suppose that if this particular thing did not exist, this entire section did not exist, what do you think will happen? We will simply have this particular block and this would have been just shifted right here, correct? If this would have been shifted right here, then you can imagine how this particular block will actually help to hold this block of water, because this particular height will make sure that the water does not slip away somewhere. And so here the height is 3 and here the height is 2. And if this block did not exist, if this entire block was just empty, what do you think the height will be for the water? It will be 2 blocks, right? But right now it is not 2 block of water, it is just 1 block of water, because 1 block of water is actually blocked by this below land, right? So what you can say is that we are going to find the minimum of this, and we are going to subtract the height of the block that we are currently on. So 2 minus the height of this block is what? 1. So it means we are going to hold 1 block of water on this position. So now we have 1 more block of water. So now we will shift to this position and we will try to find out how much water can this particular position hold. So the height of this position is 0, right? So to figure out the amount of water that we can hold on top of this position, we will see that, okay, we have a block of height 2 right here, right? And then we have a block of height 3 right here, which is the maximum heights on left and right side. So what we can try to do is we can try to imagine that these blocks did not exist. Then what will happen? We would have a block right here, and then we would have a block right here. And since this block do not exist, what will happen is that these 2 blocks will actually come closer to each other. So this block will come closer to right here, and this block will come closer right here. And then we will see that we have these boundaries. So right now we have a boundary of 2 here, and we have a boundary of 3 here, and we have this particular block right in the middle. So it means the height of this particular block will depend on the height of this one and this one, right? So the minimum between 2 and 3 is 2, correct? It means the water cannot exceed the height of 2. So we will have 2 here, and now we have to subtract the height of the land or block that is present in this position. So the height is 0. So we will subtract 0. It means we will get 0. It means we can now add 2 into our sum of water. And now we can move on to this position. So here also we will try to assume that we only have 2 blocks of maximum height on left and right side. So we can shift this block right back to where it was, and this block will be shifted here. So we are basically isolating this block to find out the amount of water we can hold on top of it. So right now again we have a height of 2 here, we have a height of 3 here, and it means we will have to take the minimum. So 2, and then we have to subtract the height of this block, right? So the height of this block is 1. So 2 minus 1 is equal to 1. It means we have again a water amount of 1 here. So now let us move on to the next position. And here we can see that on this block, we want to find out how much water we can hold. So what is on the left side? Nothing. The maximum height block on the left side is right here, 2. But the height of this block is 3. So it is going to be above 2. So there will be nothing on the left side that is going to help hold the water on top of this 3 height block. Similarly, on the right side, we don't have any block that is going to hold the water for this particular block. So it means there will be 0 water on top of it. Now we move on to the next block, and here we see that we don't have any water here, because yes, there is a block of height 3 here to hold the water, but there is no block on this side that can actually hold the water, right? So there is no block of height greater than 1 that can hold the water on top of this block. So we move on to the next position, and here we see that we have a height of 1, and we have a boundary of these 2 blocks. The height is 2 here and the height is 2 here again. So we have this 1 block between 2 blocks. So we will have this 1 block of water. Why? Because left boundary is 2, right boundary is 2. So minimum between 2 and 2 is simply 2, and 2 minus the height of this particular block is, well, 1 is equals to 1. So 2 minus 1 is equals to 1. So we will now end up adding 1 right here. And I think I did not add this particular thing, so I will also add 1 right here. So now we will move on to this block, and here we will try to find out how much water we can store on top of it. So yeah, there is something on the right, this block, that can hold the water on this particular height, but there is nothing on the right. So it means all the water will simply go down. So we won't have any water on top of this block. Then we will move on to this particular block, and here you can see that we have something that we can use to hold the water on top of this block, but there is nothing on the left. So it will again go down. So water on top of it will also be 0. So it means we have this much water stored in the particular structure, which is equal to 6. And that should be the answer. So as you can see here, that 6 is the answer. And this is how we actually have to figure it out. So whenever we wanted to find the amount of water stored in a particular position like this, we would just take the maximum that is present on the left side, and we will take the maximum that is present on the right side of this particular position, and we will take the minimum of them, right? So 2 was here, 3 was here, I took the minimum, and then I just subtracted the height of the block of land that was on this position. So right now it is 0, so I will just simply do 2 minus 0 is equals to 2, which will give me the amount of water that is stored on top of this position, this much, right? So it is 2 blocks of water, and I got 2. Similarly, for this position also, the maximum height on the left is 2, the maximum height on the right is 3, and that's why we will take the minimum, that is 2, and 2 minus the height of this block is what? 2 minus 1 is equal to 1. And this one represents the height of the water block that is above it. So what it means is that in order to find the water at the ith position, we need to find out the maximum height of a block on the right side and the maximum height of the block on the left side, and then only we can figure it out. So it means we need to store these heights somewhere, right? So we can have two arrays, max left and max right, and in these arrays we will store the maximum left at a position I. So on this position here, what is the maximum height of a land in the left side, and that we can store right here, correct? And in the same way, we can store the maximum heights for a particular I on the right side. So in this way, we will have two arrays that are going to store the maximum in the right direction and in the left direction for a particular given I. So we will have a left max array, we will have a right max array, and we will optionally have a minimum array also. So you can calculate the minimum on the runtime if you want to. Otherwise, you can store the minimum values in the array also. So we will start with this position. What is the maximum on this side of the 0? 0. There is nothing, right? Then we will shift here. What is the maximum on the left side? Now left includes this particular position also. We are going to do this. We are going to include this particular position also. So we will have 1 right here. Then what is the maximum on here? It is still 1. Why? Because we have this one and this is 0. So maximum on the left side is still 1 for this particular position. Then we will go to the 2, and now the maximum is 2, right? Because 2 is greater than 1. Now we will go to the next position. We will have 1, and now the maximum is still 2 because 2 is greater than 1. Again, we will come here on 0. The maximum is still 2. Then for this also the maximum is 2. Then here we come and we get the maximum as 3 because 3 is now greater than 2. So now we will move on to the next position, 2 here. The maximum is still 3 here. Then for the next position we have 1. The maximum is still 3. For the next position is 2. The maximum is still 3. For 1, the maximum is still 3. And now in the same way, we are going to find out the maximum at right at each index I. So here, what is the maximum at right? Well, if we include this one also, the maximum on the right is 1. Then we will go here. The maximum is 2 now because 2 is greater than 1. So we will have 2 here. Then the maximum for this position is again 2. For this position is again 2. Then for this position, the maximum is 3. So we will have 3 here because we are including this position also to calculate the maximum. Then here we have 1, so we will again have 3 as the maximum. Then here we have 0, 3 will be the maximum. Then here we have 1, 3 will be the maximum. Here we have 2, 3 will be the maximum on the right. Here we have 0, 3 again. Here we have 1, 3 again is the maximum. And here we have 0, 3 again is the maximum on the right. And now we can calculate the minimum between these two values, the right max and the left max. So the minimum between 0 and 3 is 0. The minimum between 1 and 3 is 1. The minimum between 1 and 3 is again 1. Here it will be 2, 2, 2, 2, and then 2 again, then 2 again, then 2 again, and here we have 1. So now we have all the information that we need to solve this particular question. In order to find out the amount of water on the ith index, we can simply take the minimum of ith index and then subtract the height of the block, the height of the ith index block from it, and that will give us the amount of water that we can hold on the ith index, just like we were doing in the earlier dry run demonstration. But guys, as you can see that it is going to take order of n time complexity. Why? Because we are going to store n elements in this, n elements in this, and then n elements in this. So is there a better way to actually do this? Yes, and yes, you can remove all the three arrays and do this in order of one space complexity, which sounds crazy because you need all these numbers to calculate the minimum. But yes, you can actually do in order of one space complexity because there is a trick here. So till now we know that in order to find out the water on any given position, we need to find out the maximum on the left and the maximum on the right and find their minimum and subtract this particular height. That we understand very well. So what we can try to do is we can try to use two pointers here. Yes, it's a very tricky question to use two pointers, but that's the thing about it. This is a hard question. Here you need to be tricky. Okay, so we will have two pointers here, P and Q. Okay, now just think about it. The maximum on this left side is right now 0, correct? And the maximum on this right is what? 1, correct? And we also know that we cannot store any water on the end of the array because there is nothing on the right side to hold the water, and here there is nothing on the left side to hold the water. So it means the water storage will only happen in this particular section. So now we will again have a left max variable and a right max variable. These are going to store the maximum on the left side and the maximum on the right side. So first of all, we are going to start with 0 and 0. Then we will take these values right here, 0 and 1, and we will place them here. So left max will still be the 0, the right max will become 1. And now we need to move these pointers somehow, right? So which pointer are we going to move? P or Q? Well, whichever is the minimum. So right now the left max is minimum. So we are going to move the P here. So P will be on this element, on 1. Now for 1, the maximum left is 0 and the maximum right is 1. But we don't need the maximum right. Why? Because we know that this particular value, the left maximum, is actually smaller. And what it means is that even if there was something smaller than 1 here, suppose there was something 0, we would not care about it, right? Because we need the maximum on the right. And if there was something greater than 1, suppose that there was 3 here, actually, because we don't know whether there was 3 or there was some other element here. But even if there was something greater than 1 here, we will still not care. Why? Because this left max is the bottleneck. This will decide the maximum height that the water can take. Do you understand this thing? It is like this. We have two boundaries, okay? So it doesn't matter how big this particular boundary is. It can be 5, 10, 20. But the amount of water that we can hold here, it's going to depend on this particular minimum boundary, okay? So whichever is minimum between this and this, that is going to decide the amount of water that we can hold within these two boundaries. And that is why right now we have left max less than the right max. And that is why left max is going to decide what is going to be the amount of water that we can store on this particular position. So it is 0. It means we are going to store 0 minus 1. Okay, so it is going to give us -1. So -1 does not make sense. So whenever we will get negative values, we will simply make them 0. So right now we have 0 water stored on this position. Then we know that we have 1 here and 1 is greater than 0. So we will again update our max left and we will have 1. So now the left max is 1 and the right max is also 1. So which pointer should we move? Should we move Q or should we move P? Let us move Q. So now the Q is right here on this position, 2, right? So what is the amount of water that we can store on this position? Well, we are going to take the minimum between the left max and the right max. Since they are both the same, so we will end up taking 1 anyways. So 1 minus height at this particular position, that is 2. So 1 minus 2 is equals to -1, which will end up getting 0. Why? Because we are going to ignore negative values. Now since we have 2 here, so the maximum on the right side is going to be 2. Okay. Now we need to shift the P because the left max is actually less than the right max. So we will shift the P here. The P will come here. And now what? What is the amount of water we can store here? So here again, it will be depending on the minimum, right? So here the left max is the minimum. So we will simply take the left max and subtract the height of the current element. That is 0. So it is going to give 1. So right now in our sum, we got the first one. Okay. Then we will again shift the P because this 0 will not update the left maximum. Okay. So the left maximum will remain 1 and the right maximum will remain 2. So what is the amount of water that we can hold here? Well, the left maximum is 1. Okay. So we are going to do 1 minus 2, that is -1, which is equal to 0. So we cannot hold any water on this position. Now we know that we have 2 here. So the 1 will be updated to 2 here. And now we have both of these same, right? So we will just update the P again. So P will come here. Now what is the amount of water we can store here? We are going to do the same. Okay, we are going to take the 2 with the left max and we will subtract 1 here. So it will give us 1. So it means in the sum, we will again add 1. Now we will again shift the P because they are still the same. Okay, so I'm shifting P here. And now what is going to be the amount of water we can store here? It is going to be the 2 minus 0. So 2 minus 0 is equal to 2. So we will add 2 here. Now we can again shift P to here because these are same, the left max and right max. So now what is the amount of water we can store on this position? Well, we will again take the left max 2 minus the current height. of the block, that is 1, equals to 1. So we will add 1 right here. Now let us do something different. Let us shift Q here. Okay, so Q will be right here. Okay, what is the amount of water I can store here? Well, it is going to be the right maximum minus the height of the current element or the current block. So right maximum is 2. So 2 minus 1 is going to be 1, right? So we will get 1. Simple, right? So now we can again shift Q here. So Q will be here. Okay, now what is the amount of water we can store here? We are going to take the right maximum again. So the right maximum is still 2. So 2 minus 2 is going to be 0, right? So at this position, we can store 0 element. And now since we are getting 2 here and there is already 2 here, so I cannot update the right maximum still. Now I will take the Q here, I will shift it right here. So what is the amount of water I can store here? Well, I'm going to take the right maximum, that is 2, and I will subtract 3 from 2. So 2 minus 3 is equal to negative 1, which we will simply consider 0 because we are not going to deal with negative answer. So now we have 3 and 3 is greater than 2. So right maximum will become 3 here. Now we know that 2 is less than 3, right? So we will have to shift the P. So P will be shifted, okay, and P will come here. Now P and Q are at the same position. So it means that we will simply stop the loop. Now we don't need to run the loop. We have found the answer. We will sum all these numbers and we will get the answer. So 1 plus 1 plus 2 plus 1 plus 1 is equals to 6. And that is our answer. So now do you understand how we are able to actually remove all that extra array space and we are able to do the entire calculation in the order of one space complexity? That's a crazy trick, right? And I was not able to figure this out by myself when I was trying to solve this question. Like really, this trick is really hard and you might not be able to figure this out in an interview also because there is a time pressure of 45 minutes and to find out these kind of things, you will need to think about the problem for quite some time. So this is the kind of problem that if you have already seen it, you will be able to do it very quickly. Otherwise, it will take you a lot of time to figure out this kind of solution. So now let us look at the code. So left pointer is set to 0, the right pointer is set to the ending element of the given height array, and then we have the left max and the right max variable. So left max in the starting is going to be the height of the L pointer, the right max is going to be the height at the right pointer. Then we have water here is 0. Now here is the loop that we are going to run. So while left is less than R, so as long as the left is less than R, we are going to run this loop. So if the left maximum is less than right maximum, we know that we need to shift the left pointer. So I will take the left pointer and shift it to 1. Then I will calculate the left max. So it is possible that the current element at left after shifting is greater than the value stored at the left max. So I will just update the left max first with this particular line. And then here I will simply calculate the water. And because of these two lines, we will never get a negative value. How that will happen, I am just leaving it to you. You figure it out how this kind of thing actually make a difference. And then in the else block, we know that the left minimum is going to be greater than or equal to the right minimum. So we are going to take the right pointer, we are going to shift it by 1, and then we will update the right max right here, and then we will directly update the right max, and then we will calculate the water. These two lines make sure that we do not get negative values here also. And how that is going to happen, I'm going to leave that to you. Okay, now once that entire loop runs, okay, which means the left will become greater than or equal to R, we will know that we have gone through the entire array, and so we will simply return the water that we calculated till now. So now let us try to run this thing and see what happens. So our solution runs in 11 milliseconds and beats 71.05% solutions on LeetCode. It is also passing all the 324 test cases. So our solution is pretty efficient. Now let us look at the space and time complexity for this particular solution. So the space complexity is going to be order of 1 because we only have left max variable, right max variable, then we have left pointer, then we have right pointer. And all these variables are simply integers, right? The space that these variables are going to consume is going to be fixed regardless of the input size. So input can have 1 million elements in the array and these are going to consume the same space, and that means they are fixed, which is also means that they are constant, and that's why we are saying the space complexity is constant. The time complexity is order of n. Why? Because we will have a left pointer, we will have a right pointer. Okay, the left pointer will go in this direction, the right pointer will go in this direction. The left pointer can at max go through the n element that are present in the array. The right pointer also at max can only go through n elements that are present in the array. So it means together they will travel n plus n elements, which is 2n. So order of 2n elements is going to be order of n, right? Because we will simply remove the constant in big O notation. And that's why the time complexity is order of n. It is 2 pointer, guys. The 2 pointer is supposed to give you order of n time complexity. Hello everyone, today we are going to understand what is sliding window technique. It is one of the most important DSA question patterns for interview questions, which makes it essential to have it in your arsenal whenever you are trying to give a coding interview. The reason sliding window technique is asked a lot in coding interviews is because it actually makes this order of n square solution into an order of n. Isn't that amazing? You can take the order of n square time complexity solution and convert that into an order of n time complexity. It is a huge improvement in time complexity. And that is why the sliding window technique is asked so much in the interview question. Now, before we go ahead and understand sliding window, I am assuming that you know some basic stuff like for loops. You know about them. You know about big O notation. What is n square? What is order of n? This is like the basic stuff that you must know before we proceed to understand the sliding window technique. And if you do not know these things, then I highly suggest you that you understand them before you try to understand the sliding window technique. At least understand the for loops and the basics of the programming, because there is no point in trying to understand something like sliding window when you don't even have your own basics ready. So the first question is, what exactly is a sliding window technique? Sliding window is a technique in DSA that helps us to solve problems that involve contiguous ranges of elements, which means subarrays or substrings, and not just the individual pairs. So what this means is that we need to use a sliding window technique when we are dealing with contiguous range of elements. Contiguous means adjacent. So suppose that we have an array like this. We have elements like suppose 1, 2, 3, 4, 5. Okay. And we need to get some contiguous elements. So one set of contiguous elements is right here, 2 and 3, right? But another set is also right here, 3, 4, and 5. It is also a contiguous set because all of them are together. 3, 4, and 5 are adjacent to each other. 2 and 3 are also adjacent to each other. That's why they are contiguous. So it means it's a very specific situation. Sliding window will only work when we have contiguous elements that are adjacent to each other. And that is why we have this specific cases, subarrays and substrings. Right now, this 3, 4, and 5, this set is what? It is a sub-array, right? It's a sub-array. And that is why we can think of using sliding window on arrays. Similarly, we can have strings like A, B, C, D, E, right? And then here we have substrings. This is a substring, right? It is a substring. Then this B and C is also a substring. Why? Because all these elements are adjacent to each other. And so understand guys that this sliding window technique will not work on subsequence. It will simply not work. Why? Because the subsequence is like this. We have elements in the array and the subsequence is basically a range of element. But those elements does not have to be contiguous, right? So I can take 1 and 3 from here and this is a subsequence. So I can take from here 1 and 3 and this is a subsequence. It is not a subarray. It is not a contiguous sequence. Why? Because 2 is right between 1 and 3 and we did not take 2. So it is not a subarray, and the sliding window only works when we have contiguous elements. So it means if we have 1, 2, 3, then it will work. But when we only have discrete elements like 1, 3, it will not work because we need contiguous elements. Now, if you are getting the question in your head that why only contiguous elements? Why not just any subsequence? And the answer is very simple. Sliding window was designed for a particular purpose. It was not designed for subsequences. So subsequence were not a customer for this technique basically. It was only designed for a specific use case and so it does not have a way to deal with subsequences. And as the word itself says, it's a technique, it is not an algorithm, right? A technique is something that you use in specific situation to deal with the specific problems. And subsequence actually have a different problem than contiguous subarrays or substrings. Which means sliding window is actually solving a particular kind of problem for subarrays and substring which does not exist for the subsequence. And what this problem is, we are going to discuss in one of the next sections in this video. The next question is, where do you really use it? So you use it in linear data structures like arrays, strings, and linked lists, which means you do not use it on this kind of structure like a tree or a graph. You will usually do not use sliding window in this kind of structure. Why? Because it is hard to get access of contiguous elements without doing some calculation. So if you are in a graph on this node and you have access to this node somehow, then in order to get access to this node or this particular node or this particular node, you will have to do some calculations, right? You will have to go there, you will have to figure things out because it's not easy to get access of multiple elements in a graph in constant time. And that is why even if you try to use sliding window in these kind of graph problems or some other data structure problems, that will not be optimized. That will actually be an overhead. That's why we only use a sliding window in arrays, strings, and linked list. Why? Because we are dealing with a window of data that moves sequentially across structure, maintaining a contiguous block of elements. And since we are dealing with a contiguous block of elements, it becomes very important for us to get access to the elements in order of one time complexity. And this kind of access time complexity only exists for arrays, strings, or sometimes linked lists. So what it means is that if in your question you have to deal with the contiguous range of elements and you have been given an array, string, or linked list, then there is a high chance that you can actually go ahead and use sliding window, because sliding window works on these two things: the linear data structures like array, string, and linked list, and the contiguous range of elements. Now the next question is, why do you use it? There are mainly two reasons to use the sliding window technique. First of all, if you have a solution like order of n square or order of n multiplied by k, then it means you are using nested loop somehow, where you are repeatedly, note the word repeatedly, calculating the data over overlapping ranges. Do you understand? We will have overlapping ranges and we will be doing something with those ranges. And because of these overlapping ranges, we will have nested loops returning us order of n square or order of n into k complexities. And this is the kind of situation where we can use the sliding window to reduce the time complexity to order of n. How does this actually work? We are going to see in the next section in the video. Don't worry about it. Then the second point is that we want to avoid recalculating the middle part of a particular range. Okay. So middle part is important. It means we are just removing all the ending nodes or all the ending elements. So instead of recalculating the whole sum or count or anything that we were trying to do with the elements, when moving to the next position or next range, we can simply update the changes, simply add the new element, remove the old element. We will see how it works in the next section. Don't worry about it. So after understanding everything till now, we can make a few conclusions. We can use sliding window technique whenever we are dealing with continuous or contiguous range of elements. Then we will need linear data structures like arrays, strings, and linked lists. Then if we see that the brute force solution actually takes order of n squared, or it takes order of n multiplied by k, where k is a constant, or some other variable where k is another input, then we can think of using sliding window technique to optimize these time complexities to order of n. And so what this means is that in the question you will have to see if you're dealing with continuous ranges, if you have linear data structures, if you have this kind of time complexity in the brute force solution, then you can make a very good guess that okay, you can use sliding window technique. Because guys, sliding window technique is not a one solution that fits everything. It is a technique that is used in specific situations. And these points are basically the indication that you are in that situation where you need to use sliding window. So do not try to understand this point in isolation, because all these points are working together to make sure that the sliding window technique or the sliding window solution will actually work in that particular problem. So make sure to read the problem properly so that you will have all the points that you need to understand whether you should use sliding window in the problem or not. Now the next question is how? How do we have an order of n square solution and we can convert it into the order of n? Because it is one of the most important things to understand, because if you understand why this happens, you will be able to understand whether you can use sliding window in a particular solution or not. Understanding this is like the holy grail of sliding window. You will never have any issues with the sliding window ever in the future. So to understand why this happens, we need to understand what kind of problem we are trying to solve with the help of sliding window technique. So usually you will have an array or a string where you will have a few elements. Here we have 1, 2, 3, -1, -1, and 5. And then the question will ask us to do something with the sub-arrays or substrings. Since we have an array, so we are going to do something with the sub-arrays. Suppose that the question asks us to find a sub-array that have the maximum sum. We need to return its length. So what can we do to find the sub-array with the maximum sum in this given array? Well, we can try to use brute force to find all the sub-arrays and then calculate the sum of each and every subarray and then check which subarray had the maximum sum and then simply return the length of that subarray. And when we are doing that, we will be doing something like this. We will have a for loop that will run from I is equals to 0 to the end of the array. So right now we have indices 0, 1, 2, 3, 4, 5. The length of the array is 6. So it will run from 0 to 6. Then we will have another for loop that will run from j is equals to I till end, that is the 6, length of 6. Then we can have another for loop where we will run from I to j, and this is basically the subarray. This for loop, the I to j, is basically the subarray that we found, and then here we will calculate the sum. We will calculate the sum of all the elements from I to j, and then we can just check if it is the maximum sum or not. If it is not the maximum sum, we just keep on going. Okay, in this way we are going to find all the subarrays and then calculate the sum of the subarrays and then just return the length of the subarray that have the maximum sum. But as you can see that we have 3 loops right here. this particular for loop is actually used to calculate the sum of the array. So this for loop is not really a part of finding the subarray. It is just taking all the elements in the subarray from I to j and calculating the sum. That's why only these two for loops are actually part of finding the subarray, the starting and the ending index of the subarray. So I represent the starting index and j will represent the ending index of the subarray. And so this part is going to take order of n square time complexity. You can understand it in two ways. First of all, we have these two for loops that are nested within each other. So they will end up with the order of n square time complexity because they are going through the entire array, right? The other way to understand this time complexity is to understand that there are n square subarrays for any given array. And since we are going through each and every subarray, we will have to run the loop for n square time. And that's what is coming here. So that's how we get this order of n square time complexity. Now, how do we reduce it to order of n? That is the biggest question. Now, one thing to note is that we have I and j, we have two pointers that we are using to actually calculate the sum of the entire subarray. So what we can say is that we can use two pointers to represent a subarray, right? I can place a pointer p1 right here, and then I can place a pointer q right here, and then I can say that, okay, every element from p to q is part of a subarray, right? So I can simply use two pointers to represent any subarray that I want, right? Can I represent every subarray with these two pointers? Yes, I can. Can I go through all of them? Yes, I can. But if I go through all of them, then this n square time complexity will still be there. So we can try to remove the for loops with the help of pointers somehow. But how do we remove the n square time complexity, right? And the promising way to do that is by reducing the number of subarrays that we go through. So for any given array, we can have a lot of subarrays. We can have a single element subarray. We can have two element subarray like 1, 2. We can have three element subarrays like 1, 2, 3. We can have four element subarray 1, 2, 3, -1, right? We can have arrays like 2, 3, right? We can have arrays like 3, -1, right? We will have lots of subarrays for this particular array that I cannot even write them right here. And because there are so many subarrays, and if we try to go through all of them, we are reaching the order of n square time complexity. So if we somehow reduce the number of subarrays that we have to go through in the question, then we will be able to reduce it to order of n. Now the way we reduce the number of subarrays that we have to go through depends on the condition of the question. So the question will always have some condition that will help you to determine how to move these p and q pointer so that you will not have to go through each and every subarray that can be made with the given array. And we are going to use examples to see what those conditions can be. But understand that the reason we can go from order of n square to order of n is because the question itself will have some conditions that will help you to skip a lot of these subarrays, which are not going to give us answer in any way. For example, right now we are trying to get a subarray with the maximum sum, right? So I need to maximize the sum. It means if I try to add 3 and -1, it is going to give me 2, right? Which is less sum. So it means I need to have a way to skip 3 and -1, this particular subarray. And just like this, there will be many subarrays that will simply not help you to go to the answer anyways. There will be some subarrays that can have potential answers. So the conditions in the question will help you to go through those subarrays only, but all the other subarrays will simply be ignored automatically. You will not have to skip them manually. They will simply be skipped automatically if you use the conditions in the question smartly. And all this discussion is also valid for substring. So we can have string like A, B, C, D, E, right? The indices will be 0, 1, 2, 3, and 4. So the entire discussion that we had till now is also valid for strings and substrings. Now there are two types of sliding window technique. The first one is the fixed size window. The distance between the pointers is constant, and the other one is dynamic or variable size window, which basically means the window will expand and contract or shrink based on the conditions. Now these conditions will be given in the question itself. So in the first situation, you will have an array or a substring and you will have p and q at a certain length. So right now the length is 4 elements, right? This length will not change. It means if the q is shifted to here, the p will also be shifting to this side, maintaining the same distance again, which basically means that we have a fixed window or fixed number of elements between the p and q, and that's why it is called fixed size. This kind of thing happens when we are trying to do calculation on the subarray or substring of a fixed length. For example, you want to find out the substrings or subarrays of size 4 that have the maximum value. What this means is that we will go through the entire array with p and q at a distance of 4, and we will keep on shifting this p and q with the distance of 4, calculating the sum of elements between p and q. And whenever we find a maximum sum, we can simply store it and later on return it. Now in the dynamic type of sliding window technique, we have a few things to notice. First of all, these P and Q pointers does not need to maintain a fixed length between them. So if I decide to shift Q to here, I don't need to shift P. Okay, I can simply increase or decrease the length between P and Q. What this means is that we can effectively increase or decrease the size of the window of elements. But then again, guys, if we can increase and decrease the size of the window however we want, then how can we ever achieve a result? How can we ever decide that, okay, now I want to increase the P, right? So it means that the increase and the decrease in the size of this window is going to depend on something, okay? And that something is the conditions in the question. So the conditions in the question will help you to understand when to increase and decrease the P and Q pointers. Basically, you will have to figure out a valid window. Okay, not every window is going to be valid. So while the window is valid, you can keep on increasing the Q. Okay, and when the window is no longer valid, you can increase the P to make the window valid again. And now, what is the condition for a window to be valid? Those conditions will be provided in the question itself. So you will have to really look at the question, understand it very well to understand what exactly is a valid window. For example, a window can be valid if the sum of the elements in the window is positive. So if I write something like negative 500 here and the Q is not here, Q is right here, okay? So P is here, Q is here. The sum of the elements here is what? 4 plus 3, 7, 7, 8, 9, 10, right? It's a positive sum right now. But if I shift the Q to the next element that is negative 500, then the sum will be what? Well, negative 500 plus 10 will be negative 490, right? And now the sum is what? It is negative, right? So our condition was the sum should not be negative in the window. And now that we have the sum negative, we can start incrementing P, okay, till we reach Q. And if we reach Q, we will just end up incrementing Q and P again to the next index. So these kind of conditions will be present in the question that you will have to look for, and they will decide what is going to be conditions for a window to be valid. And while the window is valid, you can keep on increasing the size of the window. And when it is no longer valid, you can simply increase the P pointer and decrease the size of the window. So this is the really important. The condition that will make the particular window valid, you really have to look out for these conditions in the question and make sure you understand it very well. Suppose we have an array of integers and a number k. Find the maximum sum of any contiguous subarray of size k. Great. We have a linear data structure here, right? We have integers here. We have a number k that is input, and we have been explicitly told that we need a contiguous subarray of size k. Okay. So these are a lot of indication that tells us within the question itself that we can try to go ahead and use sliding window. And if we look at the brute force solution, the brute force solution of this problem will be what? It will be to find all the subarrays of a given array, and then out of them, the subarray of the size k, we have to take them and we have to calculate their sum, and then we have to return the greatest sum. And this is going to take at least order of n square. If you include the time for actually calculating the sum, then it will become order of n cubed. So the time complexities of the brute force solution also aligns and actually indicates us to go ahead and use sliding window technique. So suppose that this is the array that we have and the k is 3. It means we need to find out all the subarrays of size 3 and we have to calculate their sum and we have to return the maximum sum. So how can we do that? Well, we can start with having two pointers. We will have p here and q here, okay? And right now the size of the subarray is what? It is 1 because there is only one element in the p and q distance. So it means the maximum sum is simply 1 right now. Now what we can do is we can increase the q. So the q will go to the next element that is here. And now what is the maximum sum? Well, we can simply add 2 in the original max sum instead of taking 1 and 2 again and calculating their sum in a different loop, right? Because we already have a result from the previous subarray. So I can take 2 and add in the 1. So it will become 3, right? So it means the sum till here is 3. The size is not k. The size is what? The size is 2 elements right now. So it means it is not an answer. Now we will shift the q to the next element. And then we have what? We have 3 here. Now in order to find the sum of 3, 2 and 1, what we can do is we can simply add 3 here, right? Because we already have this 3, the sum of previous 2 elements. And so we can simply add the next element in the sum and we will get 6. It means the sum of this entire subarray is 6. Do you notice how we are using the previously calculated sum to calculate the sum for the next subarray in a constant time complexity? Just because we are taking the next element and adding it in the max element that we already have. And this reuse of the already calculated value is also one of the reasons to use sliding window technique. So now we have 6 here, okay? Now we have the length 3. So the P and Q are at a distance 3. 3 is basically what? It is equal to K, right? We must not go above K because we just need subarrays of length K, right? So this is a fixed sliding window technique. The reason we started with Q on the first place is just to make sure that we reach this length 3, and then we can just keep on shifting P and Q together. So now that I want to shift the Q again, I will take the Q from here, I will shift it here, Q will come here, then I will again take the P here and then shift it to the next index, right? And then P will be here. But now as you can see that I shifted the P from 1 to 2. It means in the current subarray. So current subarray is what? This 2, 3 and 4. What this means is that in the current subarray, we don't have 1, right? It means we should remove 1 from this maximum. So it will become 5, okay? And then since we are actually adding 4 in the subarray, we should also add 4 here to calculate the sum of this particular 2, 3 and 4 subarray. So 5 plus 4 is equal to 9. So it means the sum of this particular subarray is 9. Now do you understand how we are able to update the maximum sum just by shifting P to the next element and Q to the next element? If we shift the P to the next element, we remove the previous element from the max, and if we shift Q to the next element, we add this particular next element into the max. Simple, right? We don't have to take the entire subarray 2, 3 and 4 and use a loop to calculate their sum again. And so max till now is 9, right? Now if we try to move ahead, if we try to move the Q here, we cannot do that because we no longer have any more elements. So we cannot do that. We can simply end the loop and return the 9 as answer. Now one more thing that you should notice is that we never calculated for 1, 2, 3 and 4, this subarray, right? We never calculated the sum for this subarray. We skipped it. Do you understand it? We skipped this subarray. In the same way, we never calculated the sum for 3, 4 subarray. We skipped it, right? We never calculated the sum for 2, 3 subarray. We skipped it, right? All these arrays and many more arrays actually got skipped automatically just because we were following the rules of given in the question. So it means the conditions in the question will help us to skip all these unnecessary subarrays automatically. And here you can see that we only have P and Q pointers, and those pointers are going to reach each and every element only twice. So what this means is that Q at max can cover n distance and P at max can cover n distance, right? So it means P and Q together will cover n plus n distance, which is going to be 2n, which is simply going to be order of n. Why? Because we will simply remove the constant. We don't need constant in bigger time complexities. And what it means is that we went from the order of n square time complexity in the brute force to order of n in the sliding window approach. Now here is another example. We have been given a string and we have to find the length of the longest substring without repeating characters. So basically we have a linear data structure string. We have to find the length. That is something we have to find. And we have to do it for a longest substring. We have a substring here, right? And we have this condition without repeating characters. So we have a condition, right? From here to here. So all these are very good indication that we need to use sliding window technique. And the brute force solution for this problem can be finding all of the substrings that are possible from a given string and then separating out all the strings that do not have any repeating characters and then just returning the maximum length out of them. That can take around order of n cube time complexity, which is a very good indication that we should use sliding window technique. Now suppose that we have a string like this, and since we have to make sure that we do not have repeating characters, we need some kind of place where we can store whether we have actually encountered a particular character or not. So we can store that in a set. We will have a set like this, and inside of it we can store the character that we have encountered till now. And the set does not contain duplicates. It means if I add d 2 times, so I add d here and then I add d again here, I will only have a single d character in this set, which is a good thing for space optimization. So now we can try to go ahead and solve this question. We will have a P here and a Q here. Okay. Now since we are on the A here, I will take this A and I will first of all check, is this already present in the set? It is not in the set, right? So I will take the A and place it inside of the set here. And A itself is a substring right now and it does not have any repeating character, so it's a valid substring. So what I will do is I will simply take the Q and shift it to the next index, that is B. So what this means is that in this question, the conditions for making sure that a particular window is valid is to make sure that there are no repeating character in the window. So I have the Q here, okay. I will check if B is already present in the set. It is not present, right? So I will take the B, I will place it in the set. Then I will again move to the C So Q is here, it is no longer here. I will check if the C is present in the set. If it is not present in the set, I will add it in the set. Then I will shift the Q to the next character, that is D. Now I will check if D present in the set. It is not present in the set, so I will add D here. Then again I will shift here and I have a D again. So I will check, is D present in the set? It is present in the set. It means the window, this particular window from A to D is not valid, because what it means is that this particular window does not have unique characters. It have some repeating characters, and that's why it is not valid. And now what can we do to make this valid? Well, first of all, we only know that we have D, this character, somewhere in the string. Okay, we don't know whether it is right here or in the beginning. We don't know that, right? So what this means is that we will keep on shifting P until we make sure that D does not exist in the string. So what we can do is, we will take the character at P, that is A, and remove it from the set. It is no longer in the set. We will shift the P again. P will be here. We will check if the character at Q still exists in the set. It does. D still exists in the set. It means we need to take the P and we need to shift it again, right? So before we shift it, we will take the B and we will remove it from the set, because B is no longer in the window, right? So now we shift the P to the next one. Then we take the Q and we check, is D still present in the set? It is still present in the set. So we will shift the P again here and we will take the C, we will remove it from the set. Now we will check again. So is D present in the set? It is still present in the set, right? Then we will take the P and we will have to shift it again. So here it will be P, and before shifting, we will just take the D and remove it from the set. So now D does not exist in the set, right? And now when we take the Q and we will check if D exists in the set, it does not. So we will simply take this D and place it inside of this set. So D will be here. Simple as that, right? And then we will simply shift the Q to the next element, that is E. Is E present in the set? It does not exist. So we will simply add it. And if we try to shift it again, it cannot be done because there is no other element or there is no other character. So it means we can simply stop the loop. And now remember that we had to return the length of the longest substring, right? So we will have a result variable that will be equal to 0 in the starting. And as we kept on increasing the Q, while the window was valid, we will keep on incrementing the result variable also. So when P and Q were in the starting position, we will simply add 1 here. Then as Q shifted to next position, we will keep on adding 1. Okay. Then as it again shifted, we will keep on adding 1. Then it shifted to the D, we will keep on adding 1. Then it shifted to this D, right? Here. And this is where we actually started incrementing P, that is removing these elements from the set. So we will not increment right now. And as P reached this particular element after removing all these from the set, we will see that is the current length of the window greater than the result? Well, right now the result is what? 1 plus 1 plus 1 plus 1. It is equal to 4, right? So current length of window is 1. It is not greater than 4. So we will not really add anything. We will not update it, right? Then we will again shift the Q here. And we will see it is on here. The current length is what? 2. It is not greater than 4. We will not update it. We will only update this thing when the length of this particular window is going to be greater than the result. So the length of the window can be calculated like this. Q minus P plus 1. This is going to be the length of the window. And if it is greater than the res, we will simply say res or result is equals to Q minus P plus 1. This is going to be the condition that will update the result variable. And at the end of the day, whatever is going to be the maximum value in the result, we will simply return that as answer. And here also you should notice something, right? We never ended up going through the string B and C. This was also a substring, right? But we never really went for it. We checked for A, we checked for A, B, we checked for A, B, C, okay? We checked for A, B, C, D, but we never really checked for BC explicitly, right? What this means is that I ended up skipping this particular substring. In the same way, I skipped C, D also. I skipped this. I also skipped the string B, C, D, right? Because A, B, C, D is not same as B, C, D. So these are different substring. So I ended up skipping a lot of substring just by following the rules given in the question. And that's how I was able to go from order of n square to order of n. Why? Because these P and Q pointer are again going to go through the entire string, right? So if P is traversing the entire array, it can only traverse till n at max. If Q is traversing the entire array, it can also traverse only n elements at max. What this means is that time complexity is going to be n plus n, right? It is going to be 2n. So big O of time complexity of 2n is going to be order of n. Simple, right? And that's how we achieved this particular result. Now here is another example. Suppose we have an array of positive integers and a target number. we have to find the minimal length of a subarray whose sum is greater than or equal to the target number. So here we have a linear data structure array and we also have a subarray. Subarray represents the contiguous range of elements. So basically we have two things that are actually indicating that we can use sliding window technique. And then we also have this condition, sum is greater than or equal to the target. So this condition will help us to actually skip many of the subarrays. And also the brute force way to solve this question would be to find all of the subarrays, then find all the subarrays that actually have a sum greater than the target, and out of them we have to find a subarray that have the minimum length and we have to return that minimum length. And that is going to take order of n square time complexity just to find all of the subarrays. And so with all these indications, it is very clear that we are supposed to use sliding window technique in this question. So suppose that we have this particular array and then we have the target to be 10. So we need to find the subarray that have the sum equal to or greater than 10 and have the minimum length. So what we can do is we can start with the P and Q at the first element and we check, is this going to be greater than 10? It is not greater than 10, right? So it means I need to increase the Q to next element. So Q will be here. So what this means is that the conditions to make the window valid is that the sum of the elements in the window needs to be greater than or equal to 10. So with that in mind, now let us try to calculate the sum for this particular window. So we already had 2 here, right? So it means the current sum was already 2 earlier. I just forgot to update it. Now that we have 9 here, I will simply add 9 here, okay? So it gives us 11. It means we have a valid condition here. It is greater than 10. So I'm going to take the length of this particular window. The length is going to be Q minus P plus 1, okay? Which is going to be 1 minus 0 plus 1, which is going to be 2, right? So I will check which one is smaller. Is this smaller or the minimum length that we already stored is smaller? So this represents the infinity. There are different ways to represent infinity in different languages. So here it is very clear that this is greater than this, right? And I need the minimum. So I will take the 2 and I will replace infinity with 2. So till now the subarray that have the sum greater than or equal to 10 have a length of 2. And so now what should we do? Should we shift the Q or should we shift the P? We should shift the P. Why? Because we need to get the minimum length. If I try to shift the Q, I will reach here. It means I will have a length of 3, right? It will become greater than 2. But I need something less than 2, right? So what I should do is instead of increasing the Q, I should now increase the P. Why? Because we already have a valid window, right? So I need to figure out, is there a valid window smaller than current one? So I will increase the P, then the P will be here. And once I shift the P, I will take the 2 and I will remove it from the current sum. So it will become 9, right? And right now the current sum 9 is less than 10, which means it is not a valid window, okay? And at this point, I'm going to shift the Q again to get another valid window. So Q will be here, right? And as I shift the Q, I will take the 1 and add in the current max. So it will become 10. Now it is 10. So it is basically equal to 10, and that means this particular window is basically a valid window. So I will check what is the length of this window. It is 2, right? So I will not be able to replace 2 with 2 anyways. So I will again try to find a valid window of a lesser length. So I will again shift the P. So P will be here and I will remove 9 from this 10. So the current sum is 10 right now. I will remove 9. It will become 1. And 1 is not greater than or equal to 10. So it is not a valid window. So it means I will again shift the Q to the next element. We will have here. And right now we will simply add 3 in the current sum. It will give us 4. 4 is also not greater than or equal to 10. So I will simply take this Q. I will shift it again. I will reach 500. Then I will add 500 to 4. So it will make 504. So 504 is definitely greater than or equal to 10. So I know that I have found a valid window, right? So P is here and the Q is at the ending index. What is the size of it? It is 3, right? There are 3 elements, 1, 2, 3. So the size of the window is 3. But the minimum size that I already stored is 2. So 3 is greater than 2 and I need to store the minimum length. So I will not store 3 here. I will let it be 2. So now that I have a valid window here, I will try to find a valid window that is smaller than this. So I will keep on shifting P now. So P will come here, right? P is no longer here. So I will take the 1 and I will subtract from 504. It will become 503. It is still valid, right? And the new window is 3 and 500. That is the length of 2. So there is nothing to update because they are the same, right? Then I will again try to find another valid window by shifting P. So P will be here and right now the window is just 500. So basically as I shifted P, I will remove 3 and it will become 500 again. So 500 is definitely greater than or equal to 10. So I will try to calculate the length of the window. It is 1, which is less than 2, right? So it means I will end up replacing 2 with 1. So here will be 1 and 1 will actually become the answer because there is nowhere else to go after this. No element where we can shift P and Q. So 1 will be the answer and we will return that. So as you can see here that whether a particular window is valid or not depends heavily on the question itself. You really have to look at the question and understand it very well to understand how you are going to move P and Q and when you are going to move P and Q. That is a really important step. And here in this question also, you can see that we never went for 2913, this subarray, right? We never went for this. Why? Because we never needed to. We actually just skipped this, right? We never calculated anything for this. We never went for 2, 9 and 1 also, right? This subarray was also skipped. So in this way, many other subarrays were actually skipped automatically just because we were following the rule from the question. And that is why we were able to take the order of n square solution to order of n, because here also we have P and Q, right? So P can only move till n elements, Q can also move till n elements. So we will have n plus n, that is 2n. So P and Q together moved to n elements, and that means we will simply have order of 2n time complexity, which is basically equal to order of n time complexity. And that's how we are able to get this result. So today we have LeetCode 219, that is contains duplicate 2 problem. In this problem, we have been given a nums array and an integer k. Now, if there are two distinct indices in this nums array such that the values at those indexes are basically same and the absolute difference between these particular two indices is less than or equal to k, then we will simply return true as our answer. Otherwise, we can return false. So this is one of the examples from LeetCode test cases. Here we have 1, 2, 3 and 1 element in the array with the indices 0, 1, 2 and 3 respectively. We have to figure out if there are two different indexes on which the values are same and the absolute difference between those indices is 0. So let's take a few pointers, I and j. Right now we have I and j at 0 and 1 position. What is the difference between I and j? Well, absolute difference right now is I minus is equals to 0 minus 1 is equals to 1. So this is the absolute difference. We are not going to consider the negative sign. Clearly it is less than 3. It means one of the condition is fulfilling, but the values at these positions are not equal. So we cannot return true right now. Now the j will shift to this particular place. Now the j is 2. Well, I is still 0 and the j became 2. So it means it is 0 minus 2 and the absolute difference will be 2, which is still less than 3. It means one of the condition is still satisfying, but the element at index 2 is not equals to any other element in this particular window from 0 to 1. So we can definitely say that the other condition is not true. So right now we cannot return true. Now the j will shift to this particular index, that is 3. So now the absolute difference between the I and j is 0 minus 3, which is equals to 3, which is still less than or equal to 3. This is the condition that we have to follow. It needs to be less than or equal to k. So yes, one condition is fulfilling. And we can also see that the element at this particular index is actually equal to this particular index's element. So the other condition is also now true. So we can simply return true. Otherwise, we would need to return false. Here I have modified the example a little bit. Here I have replaced 1 with 2. Now let's see what will happen at this particular index. We know that from here till here, we won't get any true. So we will just ignore it for now and we will focus on these two indices 3 and 0. So the absolute difference between these two indices is still 3, which is still less than or equal to the given k. So one of the condition is fulfilling. But what about the other condition? Having these two elements same? Well, they are not same. So at first glance, we can see that the other condition is not true. That's what it feels like. But if we think about it, we will realize that, okay, we again have this particular element which have an index of 1. And the absolute difference between 3 and 1 is what? It is 2, which is still less than equals to k. So this particular index also actually fulfills one condition, but it also fulfills the other condition of having the same elements. So just think about it. If I have a pointer here and I keep incrementing this particular pointer, what I'm doing is that I'm always comparing between this particular pointer and this particular pointer only. And this is like a window. This is like having a window, right? So I basically have a window of length 3. If I try to go ahead and suppose that there was some other number here, I will go to this particular place. Now we know that this is index 4. Index 4 minus index 0, what? 4 minus 0 is equals to 4, which is not less than equal to k. So if it is not less than or equal to k, we know that we have to shift the I now. So it means that we are dealing with a sliding window problem where the window size is simply k. So here we can make two observations. First of all, every element that is present in this particular window will have this particular condition true. Because when j is at index 3, and I is at index 0, all the elements from 0 to 3 are actually going to have the absolute difference of 3. The second we shift pointer from here to here, and from 0 to first index, we know that all the indices from 1 to 4 have an absolute difference less than or equal to 3. So this particular condition will always be true for a given valid window. So it means that we can say all the indices that belongs to a particular window will follow this particular condition for sure. But we still have a problem. When we were at this particular element j and the I was at 0th element, we know that the 1 and 2 were not equal. What this means is that I need to figure out that is there some element from 0 to 2 index that is equal to this particular element, the current element. But I cannot figure out just with the help of 2 pointers. Otherwise, I will need to repeatedly traverse the entire window, which is not a good thing because it will make the time complexity as order of n into k. And because we are going to traverse the entire array once, and the k is because we are going to traverse the window k n times for each of these windows. That is not an optimal solution. So how do we solve this particular problem? We can use an extra space. We can have a hash map in which we will store all the elements that we have encountered till now. So what we will do is, first of all, we will have I. So I will store this element 1, and then I will store the value as how many times I have seen 1. So I will say, okay, I have seen it once only. J will start from this particular index. So I will store 2 here. How many times have I seen 2? Till now? Well, 1 time. How many times have I seen 3 now? Well, 1 time. Now, how many times have I seen 2? I come to this particular index and I need to check again, first of all, that have I seen this particular index earlier? In my hash map, I see an entry of 2, which actually have an occurrence of 1. So right here, I figured out that, okay, this particular condition is satisfying, having the same element at the indices. This particular condition, we know that it is going to satisfy for this given window anyway. So both the conditions are satisfying, we can simply return true. Now, in case if this was not 2, if it was something else, for example, 5. If it was 5 and I was forced to move forward, then what I will do is I will move forward the j, and since the window is not valid because the j is at 4, the I is at 0, which is basically 4, which is actually not less than equal to 3, it is making the window invalid. What I will do is I will also shift I from 0 to 1 index, and when I'm shifting the I will make sure that this particular one will actually be updated in the hash map. So now we are actually getting out of the window. We are leaving 1 here. So I will minus 1 here. So it will simply become 0. So now I am saying that there is no 1 in the current window. And this way we will traverse the entire subarray. And as long as we find these 2 conditions fulfilled, we will simply return true right then and there. Otherwise, at the end of the day, we can always return false. Now let us go through the code itself. First of all, I am declaring the hash map in which I will store the element and their occurrences or the number of times I have seen that element in this particular window. Then I'm initializing my I variable, and I'm also putting the element that was on ith index in my hash map first. I'm running a for loop from j is equals to 1 to the length of the nums, as we have already seen in our example, and I'm checking here that if the current window is not valid, then first I will go to my hash map and update that particular element's occurrence by 1. So I'm simply subtracting 1 here, and now I'm incrementing I by 1, and I know that it will always be valid at this point because we know that as soon as the size of the window becomes 1 more than k, we will be running this particular loop. So we just have to reduce it by 1. So we will simply say I is equals to I plus 1. After this, we will check does the element on the current jth index in nums actually exist in the hash map. If it exists, then we will also check how many occurrences are there for this particular element in the current window. If it is not 0, it means we know that we have encountered an element which is equals to nums of j in this particular window. So we can simply return true, else this particular line will execute. What I'm doing here is simple. I'm trying to get the element nums of j from my hash map. In case it is not present, I will simply use 0 as answer or the value, and then I will increment it by 1, and then I will store this particular value in this nums of j key in the hash map. So this line basically takes care of adding and updating the element. In case this entire for loop runs and we do not return true, we are very sure that there are no 2 distinct indices I and j where the value at those indices is equal and the difference between those 2 indices is less than or equal to k. So we can simply return false here. So now let's try to run it and see what happens. So yes, all the test cases are passing and our solution is correct. Now let's look at the time and space complexity for the solution. The time complexity is order of n because we are traversing the entire array with the help of sliding window technique only once. So that's why it is a simple linear time complexity of order of n. And in case of space complexity, what we are saying is simple. Whatever is minimum n or k, that will be the space complexity for this particular solution. And this is because if you look at the constraints of the problem, you will realize that n and k does not have to be equal or k does not have to be less than n. ever. The k can be a very big number and the n can be a very small number. N is the length of the entire array and k is the length of the window. So we are always going to store whatever is available in the window. But in case k is much larger than n, then we can only store whatever is available in the array. So minimum of k and n will be the space complexity. So what this line is saying is simple. The size of our hash map will always be equal to the minimum between k and n. But I also want to highlight that in our current solution, the space complexity is order of n. And that is because we are not actually removing the element from our hash map when those elements go out of the window. But if we remove the elements, this will be the time complexity. So let's remove them. So here I added the logic for that. Now in case the value at this particular key ever becomes 0 when we are shifting particular window, then we will simply delete that key from our hash map. And that will make sure that our space complexity is minimum of n and k. Now, of course, you can also use set in place of hash map, and that is probably a simpler solution for this problem. But I'm using a hash map because you can store the number of occurrences of a particular element in a window, and that will help you determine how many pairs like that actually exist in the array. In case somebody asks you, okay, I don't want to know whether they exist, I want to know how many of these kind of pair exist, you will definitely need to use hash map. So today we have LeetCode 424, that is longest repeating character replacement. In this question, you will have a string s and an integer k. Here you can choose any character of the string and change it to any other uppercase English characters. What this is saying is that we will only have uppercase English character in the string, and we can have multiple types of characters, and we can change any of those character into any other uppercase character. Now you can perform this operation at most k times. It means the replacement operation of taking a character and changing it into some other character can be done only k times. That's what this integer is for. Now we have to return the length of the longest substring that contains the same letter you can get after performing the above operations. Okay, so we have a string like A, B, A, B. Now we have to tell us the longest substring that can have the same characters after we perform the k replacement operations. Here we have two characters A and B. So the frequency for A is 2 and the frequency for B is also 2. And the k is 2. That means we can perform two replacement operations. So we can perform replacement operation on these A or on these B's. So I can replace all the A's with B's, that will give us B, B, B and B string, or I can replace all the B's with A's. So I will have 4 A's in the string. And these are going to be the longest strings that we can get after performing the k replacement operations. And the length is 4, so we will simply return 4. We do not really care about which character we have. We only care that all of them needs to be same in the substring. That's all. So how can we solve this question? One way is to just get all the substring for this particular string and then just simply check if you can actually make all the characters in that substring same or not with the help of given key operations. So suppose that we take this substring from B to B and the k is 2. So we can perform two replacement operation at max. So if I look here, then we have B, B and B. Now I can do replacement on C and X to make this entire string B. So if I replace C with B and X with B, then this entire string will have the same character and the length will be 5. In the same way, we can take other strings also and then check if we can actually make them same character or not. So there are n square possible substring for any given string, and then we will also use a loop to check if this particular string can be turned into a string of same characters. So that will take order of n. So that will take around order of n cube. So this will be the time complexity for brute force, which is not going to be very optimal. So how can we do better? Well, first of all, let us take this particular section and we will try to understand what exactly we are going to do. Now, since we are dealing with string and we have to deal with substring, that is finding the substring and checking if they are valid or not, we can use something like sliding window, right? But in order to use sliding window, we need to figure out what is the valid condition. How can you say whether a particular substring is valid or not? Now, the condition for a particular substring to be valid is that if that string can be converted into a string of same character, that means that string is valid. Here we can convert this particular string into the string of only B's by replacing these two, right? That's why we can say that this particular substring is a valid substring. So how we can check that thing? Well, first of all, notice that we are never going to replace B. Why? Because B occurs most number of times. The B occurs 3 times here, right? And C occurs only 1 time, X occurs only 1 time. So if we try to replace the B, it will never give us a string that will have same characters. It means we need to store the occurrence of a particular character in a substring. So we will have something like a hash map here. And here we can store that the B occurs 3 times, C occurs 1 time, and X occurs one time. Okay, great. Now this particular window will have some length, right? Let's just call it a window length. Now I can use this hash map to figure out the character that has the maximum frequency, right? So I see that the character with the maximum frequency is B. So I know that I cannot replace B. So it means I need to replace the elements other than B. So the number of elements other than B will be what? They will be window length minus count of B, right? If I can just remove the count of B from the window length, I will get how many characters there are that are not equal to the character that has the highest frequency. So here in this case, the window length is 1, 2, 3, 4, 5. 5 is the window length. If I remove the count of B, that is 3, I will get 2. So it means there are two characters that are not equal to the character with the highest frequency. It means if we can replace these two characters with the character of the highest frequency, we will have this particular window length valid, right? If I can just replace C by B and X by B, we will have a valid window. But how do we know that if we can actually replace them? And that is where this K will be helpful. So K will tell us if we can replace these characters. Since we only have two characters and the K is also 2, it means yes, we can perform two operations to replace two characters, right? So that means this 2 needs to be less than equal to K, because then only we can make this entire string a valid string. Otherwise, it will not be a valid string. So what this means is that this particular condition, window length minus the count of the maximum frequency element, should be less than equal to K. And if this is true, we know that the current window length or the current substring is a valid substring. And then what we can do is we can take the window length or the substring length and store it inside of a result variable. So we will have a result variable that is store the maximum substring length or window length. So it means each time we will find a valid substring, we will check if the current window length is greater than the length stored in the result variable. If it is greater than it, then we will simply store it here. We will update the result variable. Now getting the count of the character that has the maximum frequency will take order of 26 time complexity. Why? Because there are 26 alphabets in the English dictionary and we will have to check for each of them what is the value in the hash map. So it will take order of 26 and the entire algorithm will run in order of n time complexity. So it will take around order of 26 multiplied by n time complexity to go through the entire given string and find out the result. Now let's do a dry run and see how sliding window will help us solve this question. So first of all, both L and R pointer will be at the first index, that is 0, 1, 2, 3, 4, 5, 6. So both the pointers are on 0th index. Now we will check if the current substring, that is this particular A substring, is valid or not. So we will take the window length. So window length is right now 1 because there is only one character. So first of all, we will take this A and place it inside of the hash map. So A right now have a frequency of 1. Okay, and now we will take the window length of the current window, that is 1, because there is only one character in the window right now, and then we will minus or subtract the frequency of the element that have the highest count, which is currently only A. So 1 minus 1 equals to 0, and the key for us right now is suppose 3. Okay, so is 0 less than equal to 3? Yes, it is less than 3. So our current string A is valid. It means we will take the window length or the string length and we will compare it with the result. So currently result was 0 and now the window length is 1. So is 1 greater than 0? Well, yes, it is greater than 0. So we will replace 0 with 1 in the result. Now we will shift the R pointer to the next index, that is here. So R will be here. Now the window length is 2 because there are two characters and we have B again. So I will take the B and place it inside of this hash map. So B is occurring one time. Now we will take the current window length, that is 2, and subtract the highest frequency element from it. So the highest frequency is, well, just 1 in both the cases. So we will take the 1 and subtract it. And right now it will give us an answer of 1. What it is saying is that if we replace one element out of these A and B, we will have a string that will contain same element. So if I replace B with A, then I will have two A's in the string. Otherwise, if I replace A with B, then I will have two B's in the string. So now is 1 less than equal to K. So K is 3. So it means our current window is valid. We can turn every character same in this string. So now we will take the window length 2 and compare it with the result. Currently result is 1, which is less than the window length 2. So we will replace the 1 with 2. So result contains 2 now. So now we will take the right pointer and shift it again. So R will be here and the B is now increasing. So we will take the B and increase its frequency to 2 because there are 2 B's in the current string, this one. So now the window length is 3 and the maximum frequency of an element is 2 here, right? So we will subtract 2 from 3 and it will give us 1. Is 1 less than equal to K? It is, because K is 3. It means the current window or current substring is also valid. It means we will take the window length 3 and we will place it here in the result because 3 is greater than 2. So currently our answer is 3. Then we will take the R pointer, shift it again and we will be here. So we have a new C character. We will place it in the hash map the frequency is going to be 1. The current maximum count is still 2 for the B. So we will take the current window length 4 because there are A, B, B and C, and we will subtract the maximum count, that is 2. So it will give us 2. And is this less than equal to K? Well, it is, because K is 3. So right now this particular window length or this particular string is still valid. So we will take the 4 and we will just replace it here. So now our answer is 4. Now we will again shift the right pointer to the next element, that is X. So we have X, we will place it inside of the hash map right here. The frequency is going to be 1, and now the window length is 5, and the maximum count is still 2 for the B. So 5 minus 2 is equals to 3. Is this less than equal to 3? It is. It means we can take the 5 window length and place it here. We will cross the 4, and now the result is 5. Now we will again take the R, shift it to the next index, that is B. So the B will increase from 2 to 3 here. And now the maximum count is 3. And currently the window count is 6 because we have 6 characters in the window. So we will say 6 minus the maximum count 3 is equals to 3. Is this less than equal to K? It is, because K is 3. So it means this particular window length is also valid. It means we will take this 6 and place it right here in the result. Now we will move the R pointer again. We will be here. And this is the case where we might see some difference. So right now the window length is 7. Okay, we have a D character. The D will be placed here with the frequency of 1, and the maximum count is still 3. So 7 minus 3 is equals to 4. Is this less than equal to K? No, K is 3 and the current is 4. So it is not a valid string. It is not a valid string. And in this case, I will not place anything in the result. I will take this left pointer because R is no longer here. I will take the left pointer and I will shift it. So L will come here. And then we will take this A and remove its frequency from the hash map. So earlier it was 1, now it is going to be 0. We are updating it. Now the window length is again 6. So 6 minus 3 equals to 3, less than equal to K. And so the window length 6 currently is valid, but it is already here in the result variable. So we will not update anything. But now R cannot be shifted to any other element because it doesn't exist. It means L will keep on shifting to the next indexes. The window length will keep on reducing, and we will keep on updating the result variable as we were doing. So at the end, 6 will be the maximum substring length that we can have, and that will be the answer. Now the current time complexity is order of 26 multiplied by n. And this n is coming from the sliding window technique because sliding window takes order of n to complete entire solution. But this 26 is coming from this hash map. In each of this iteration, we have to take the hash map and we have to find the element and its count. So we can find the maximum count that we can subtract from the window length. And this is taking order of 26 time complexity because there are 26 alphabets in the English language. So is there a way to get the time complexity even lower? There is a way. We can get this entire thing done in order of n instead of 26. We can eliminate this order of 26 thing altogether. And we can do that by taking a variable maximum frequency and store the maximum frequency that we have encountered till now. So we will keep on updating this A, B, C and D. So each time we update it to a value that is greater than the maximum frequency that is currently stored, we will update the maximum frequency to this value. Okay, so this will represent the maximum frequency of a character in the current window. So it means in case in the future if B increments and it becomes 3, we will simply compare that to the maximum frequency and we will change from 2 to 3. And this is going to work fine because we are always going to get the access to the maximum frequency without actually going through this entire hash map. Each time we are just updating the hash map, we will also update the maximum frequency if we need to. Simple. But the place where it might break is when we are reducing the elements on the hash map. So suppose that the B is no longer in the window. So we will reduce it to 2. Now what do we do? Should we reduce the maximum frequency? I mean, logically, you should, right? I mean, if you are reducing the B to 2, you might think that you want to reduce the maximum frequency. But that is not really true. You don't need to reduce the maximum frequency. Because we have this particular condition that the window length minus maximum frequency should be less than equal to K. Now what we want to do is we want to get the maximum value possible for this particular expression. Basically we want to get K, to be honest. We want to make sure that we are able to utilize all of the K operation to get the maximum length substring. So how can we maximize this particular thing? Well, if we try to maximize the window length but reduce the maximum frequency, what will happen? We will easily surpass K. We will get a value greater than K, which will simply make the entire string invalid, right? It will make it invalid. But if we do the other way around, if we actually maximize this frequency and minimize this thing, what will happen? We will eventually get negative numbers, and negative numbers are not valid, right? Even though negative number is less than equal to K, But negative string doesn't exist, right? So what we need to do is we need to maximize both of these things. We somehow need to make sure that this is maximum and this is also maximum. So window length is going to get maximized automatically as we go through the sliding window. But this maximum frequency, this can increase and decrease based on what is happening in the hash map. But we know that we need to maximize the maximum frequency because the answer result will only change when our maximum frequency increases. So here you can see that as our maximum frequency in the hash map is increasing, the result is also actually increasing from 0 to 6. And as soon as we start decreasing the maximum frequency, the answer will again decrease to 5, 4, 3, 2, 1. So in order to get the maximum result, we need to make sure that frequency is going to be maximum. And so what this means is that we don't need to reduce the maximum frequency even after reducing the count from the hash map. Because if you reduce the count from hash map, you are going to get the older results, right? You are not going to get some new result. And the newest result is going to be the maximum result anyways, so we will anyways return that at the end of the day. So why not just use this particular maximum frequency throughout the entire execution? And if in the future some element actually surpasses the maximum frequency, we will simply update this maximum frequency and get a new result, right? And simply return that new maximum result. And in this particular solution, you will get the order of n time complexity. Why? Because you are not going through the entire hash map to find the maximum frequency. You are actually storing it right here in a variable. So that means this order of 26 will be eliminated and you will be only left with order of n. But getting to this particular order of n solution is kind of tricky and you might not be able to do it in an interview or in some kind of contest. And that's why this order of 26 multiplied by n is, to be honest, more intuitive to come in a pressure situation, because this is kind of a tricky thing. I was not able to figure this out order of n solution by myself. I had to look up online. So now let us look at the code for both of these solutions and then you can decide which one is your preference. So here is the order of 26 multiplied by n time complexity solution. Here we have the count hash map, then we have the result which is set to 0, then we have the left pointer set to 0, and now we are running a loop. Here we are using the r pointer as the right pointer. Now here we have the character at r index from the string s and we are trying to get its count. So if this character does not exist in the count, we will get a 0, otherwise we will get its count. And then we will increment its value and just store it in the count again. Now here's the condition for valid window. Now while this thing, the window length minus the maximum frequency is greater than k, while this thing is true, we are going to take the element at L index in the string, we will decrease its count from the hash map and we will increment the L pointer so that we will reach a valid window. And once we have found the valid window, we will simply update the result with the maximum of current window length and the originally stored value in the result. And once this entire loop runs, we will simply return the result. Now let us try to run this and see what happens. So yeah, it runs in 182 milliseconds and beats 23.27% solutions on LeetCode. Now let us look at the order of n time complexity solution. So in this solution, we have the count hash map, we have the result, we have the L pointer again, and we have the maximum frequency variable that will store the maximum frequency. We have encounter till far. Now here we again have the for loop, where we are using the r pointer as the right pointer, and here we are updating the count of the element at the r index in the string, and here we are updating the maximum frequency if it needs to be updated. So we are going to take the maximum between the maximum frequency current value and the count for the current character at index r. Once it is updated, we will use the while loop to make sure that the current window is valid, and then we will simply update the result here. And once this entire for loop runs, we will have the result right here and we will simply return it. So now let us try to run this and see what happens. So yeah, our code runs in 119 milliseconds and beats 60.80% solutions on LeetCode. So it's a pretty efficient solution. So the time complexity is something that we have already discussed. It is either 26 multiplied by n or simply n. But the space complexity is going to be order of 26. Why? Because we are using a hash map and this hash map will store A to Z characters, which are basically 26 characters. So it means the size of the hash map can be at most 26. That's why we have order of 26. You can also consider it as order of 1 because at the end of the day, it is kind of a constant thing, right? So today we have LeetCode 76, that is minimum window substring. In this problem, we have two strings, S and T, and we have to figure out the shortest substring of S that contains all the characters that are present in T. So for example, this is the shortest substring present in this given string, which contains all of the characters A, B, C inside of it. Now as you can see that A, B, C do not have to be in same order. Here we have B first, then we have A, and then we have C. It means the order does not matter as long as these characters exist in this string. Now remember that there are other strings also in which these three characters exist. For example, we have this string A, D, O, P, E, C. Inside of it also, we have all the three characters, but we are not actually taking this substring because it is not the shortest. So we have to figure out the shortest substring in which we have all the characters that are present in T. So one way to solve this question is to figure out all of the substrings of the given S string and then check if all the substrings contain this T string or not. So we can use two nested for loops to actually figure out all the substrings, and we will have one more for loop to compare the current substring with the T string characters. So it will be almost order of n to the power 3 time complexity, which is pretty damn bad. So what it means is that we need to do something better. We have to figure out a better solution. So whenever you have strings and we are talking about substrings, we have to go through all the substrings. What can we use? We can always use sliding window technique. So that is exactly what is going to be applicable in this case also. Because we have this linear data structure, we are talking about ranges of elements, that is from L to R, right? It's a range of element, which means it's a substring. So we are talking about substrings, we are talking about linear data structure, and both of these are very big hints for sliding window technique. So that is what we are going to use. So now look, in the question it is already told to us that we need to have each and every character that is present inside of the T inside of this substring S, right? What it means is that if I have A 2 times, it also means that I need to have A 2 times in my substring. Now understand that we are supposed to keep track of duplicates also in the T. So if I have something like A, B, C, what it means is that I need two A's inside of any substring that I'm going to select. If I don't have two A's, that substring is not valid. Okay, so that substring will not be an answer. What it means is that I need to keep track of what elements or what characters I have, plus how many times do these characters appear inside of the T. And then I will just keep comparing them here, right? So what it means is that I need a way to store the character and its frequency somehow. And the best data structure to do that is hash map. So I will have something like this. I will have a hash map of T, right? So in the T, I have right now three characters. So I have A, B, and C, and their frequency is just 1, 1, 1 because they are appearing only one time in the T. So I will write 1, 1, and 1. So basically, this is what we need. We need these elements these many number of times. So we basically have three conditions that A should be 1, B should be at least once, and C should appear at least once inside of the substring that we are going to choose from this string. So now we also need to keep track of the character that we have gone through in this string also, right? So we will have another hash map also that will keep track of the character that we have gone through in the as a string. So we will have a hash map like this. It will contain like just say a few rows. So right now I'm just creating only 3 rows because that will be an easier way to handle things. So this is the hash map for as a string. Right now A, B, and C all are 0 because we have not gone through any element in the S string. Now as we will start going through elements in the S string, we will keep on changing these. So assume that this box actually represents a sliding window. So I will have this box here and I will simply write L is equals to here, R will also be here. So right now we will start by increasing the window length. What it means is that I will have A inside of the window. So as soon as I place A in the window, I will increase or update the value of A in the hash map also. So right now I have 0. Now I will have 1 in the hash map. Now as soon as I update the hash map, I need to check if this hash map have all the values that are present inside of this also. So what basically I need to do is I need to go through entire hash map from A to C or to Z, and then I have to check is the value of A is equals to the value of A present in the need array. If the value of B is equals to the value of B present here, if the value of C is equal to value of C here, so that I need to check. And since there are 26 alphabets inside of the English language, it means that our inner loop of comparing these two arrays will be order of 26. So we will compare these two hash maps and we will find out that no, right now we have B is equals to 0, C is equals to 0, but we actually need B is equals to 1, C is equals to 1, right? So we will not do anything. We will simply take our window and we will simply increase our size. So R will actually shift from A to the next element. So R will go from here to the next element D, and our window size will also increase. So D is also now within the window. Now we will again compare these two hash maps. Are these two hash maps equal at this point? Well, since it is a D and D does not actually exist in the T, we don't really care, right? So on comparing the hash map, we will figure out that no, the hash maps are still not same. So we will take the R and we will shift it to the next element, right? So we have O right now. And if I try to take O inside of the substring also, so it will look something like this. Now our window length again has increased. We will again compare these two hash maps. Right now we have O, so we are not actually storing O inside of the hash map. We will end up comparing all these hash maps and we will find out that no, the hash maps are still not equal, right? The B is 0, the C is 0, but they need to be 1 and 1 at least, right? So then we will shift the R again and the R actually points to B now. And then we will simply take the window. So now we have B here and now we will take the count of B first. and we will increase it to 1. And then we will compare the entire hash map, all the elements in both the hash map again, and we will find out that, okay, fine, this condition is true, right? A is equals to 1 in both of these hash maps. Then B is also true, right? B is equals to 1 in both of the hash map. But C is equal to actually 0 in one hash map and it is 1 in another hash map. So this is not true right now. So that means we have still not found a subarray in S that contains all the characters present in the T, right? So we will keep on moving forward. So we will take the R, we will shift it to the next element, that is E, and we will actually increase the size of our window. So now we have E inside of the window also. Since E does not exist in the T, there is no point in adding it in the have array or have hash map and comparing it. But at the end of the day, that's how the code will be. So it will try to compare all these elements again. So the hash maps will be compared again, and we will find out that no, they are not equal. So we will again shift the R to the next one. Then we will get C. Our window size will increase and it will keep or accommodate C also. So now we can actually take the 0 out and we will place 1 here. And now if we compare both of the hash map in the code, we will find out that yes, all of these three conditions are actually true now. So this is also equals. And at this point, we know that we have found a substring that contains all of the characters that are present in T. As you can see that we have A, we have B, and we have C. So all the characters that are present in the T are also present in the particular substring right now. But we are still not sure if it is the shortest, so we still need to do something. First of all, we will take this length. So right now the length is 1, 2, 3, 4, 5, 6. It is 6. So current result is going to be 6. Rest is equals to 6, right? And now we are going to try and find out a substring that is going to have all the elements that are present in T inside of it, but it is going to be less than 6 in length. So to do that, I need to take the window and shrink it. So I will take the A first of all, and I will reduce its count in the hash map. So the 1 will be reduced to 0, and I will shrink the window. So the window will actually become something like this. We only have DOBEC in the window now. L will also shift. So L is no longer here. L will be on the D. So L has shifted, the window has decreased, and we have also decreased the count of A. And now we can check the entire hash map again, and we will find out that this condition, we have A is equals to 0 here, and we have A is equals to 1 here. So this condition is actually not true anymore. So it means we are not able to create a shorter string anymore. Now we need to take the window and increase its size to actually move forward for other substrings, right? We need to figure out what are the other substrings that we have. So we have increased the window size. The R will also shift to the next element, that is O, and then we will again check in both of these hash maps. And since O is not actually a part of this P, it will not make much of a difference for us. So both of these hash maps will still be the same. It means this condition is still untrue, and we will have to again increase the size of the window. So we will take the window, we will increase its size again, and we will have D inside of it. Similarly, D is also not part of the T, right? So on comparing the hash maps, we will again get the same state. The A is 0 here, the A is 1 here. So again, the condition is not met. So we will have to increase the window size. So we will take the window, we will increase it even more. We have E now. Similarly, E is also not present inside of the ABC, right? So it will also not make any difference. We will have to compare the hash maps again, but it won't make a difference. Then we will take the substring and we will increase its size again. Now as you can see that we have B here, and we also have B inside of the T, right? So we will take the B and we will increase its count in the have hash map. So right now it was 1, we will make it 2, and we will again compare the entire hash map, and we will check that it is still not okay, because the count of A in the current substring, that is this substring from D to B, is still 0. But we need a count of 1 at least in the substring. So what it means is that even now this condition is not true. It is still false, right? So we will have to again increase the window size. So we will take the window here and we will increase its size to accommodate the next character. And now we have A inside of the string, right? So we will take the R, we will shift it again. So R would actually be on the A at this point. I forgot to shift it here and here, but R will be at A, right? So we will take the A and we will update its frequency inside of the hash map. So right now we have 0 inside of the hash map, and we will simply make it 1 again. And now on comparing the hash map, you will see that we have all the conditions satisfied. We have A is equals to 1. So this condition is also satisfied, right? This is actually equal. And we have B is equals to 2. So this condition is also satisfied. Since it is 1 and we have 2, right? So it means that we have more than what we need. So we are basically fine, okay? And we also have 1 C in the substring, and here also the count of C is actually 1. So this condition is also fulfilling. It means all the 3 conditions are fine, which means we found a substring, okay? We found another substring that have all the elements or all the characters that are present in the T. Now the size of the substring is going to be what? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the size of the substring is 11, and 11 is actually greater than 6. So we will not actually update the result. 6 is less than 11, so we will keep the 6. Okay, this is the shortest substring that we could encounter till now. So we will not take 11, we will keep the 6. But now that we have a substring that contains all the elements that are present in the T, we need to find out, is there a smaller substring? So what we will do is we will start decreasing the length of the substring from left side. So we will take the L, we will decrease it, and the window size will become less. So window size will be here. So we remove the D and we will again check, are the hash maps fine? Well, they are still fine because the D was never present in the T, so we did not actually make any difference. Then we will try to again shorten this length. Now remember that as soon as we remove the D, the length will become actually 10. It is smaller than the 11, right? But it is still not smaller than 6, so we will not actually update the result. So we will keep on decreasing the length as much as we can. So we will have the window, we will decrease it again. Since O is also not present inside of the T, the hash maps will be fine. We will again compare both of the hash maps, they will be fine. It means the size actually increased from 10 to 9, right? So we will write 9 here. 9 is again greater than 6, so we will not update the result, but we will keep on decreasing the size of the window. So we have B here, and we will first of all decrease the count of B. So we have 2 here, we will decrease it by 1, and now we will have 1 here. So we have 1 count of B right now. We are going to remove the B from the window, and now we are going to check again the hash maps. Since we only decreased the count of B by 1, we still have a count of 1B inside of the substring, right? And that is also what we need, right? We need 1B and we still have 1B. So this is currently a valid string. This substring still contains all the characters that are present in the T. So it's a valid substring. So currently the length of the substring is 8, right? Because we decreased it by 1. So 8 is still greater than 6. Nothing can be done, right? Now we will take the window and we will decrease it again. So the E will be gone. And since E was not actually present in the T, it does not matter. The hash maps are going to be the same. The substring is still going to be valid. The only thing that will change is that this 8 will actually become 7. So we have a length of 7 now, and 7 is still greater than 6. So we cannot really update the result variable till now. So now we have C here, and we have C also in the hash map. So we will take the value in the hash map for C and we will reduce it by 1. So currently it is 1, right? We will reduce it by 1 and we will get 0. So right now this particular condition is not true, right? And it means that the current decreased substring or the current length of the substring is not valid, right? Because we do not have C in the substring. So it means I need to start increasing the length of the window again. So I will take the length of the window from here and I will increase it by 1. So the R will also increase by 1, right? R will be on N. And since N does not matter because it does not exist in the T, we will compare the hash maps and we will find out that this condition is still not true. C is 0 here, C is 1 here. So this particular substring is still not valid, right? And I forgot to actually place L here, right? So L will actually be right here on the O. L will also keep on, increasing. Now, since it is not a valid substring, we will take the length and we will increase it by 1. So now we have C also in the substring. We will update its count in the hash map. So we will take the 0 out and we will add 1 here. And now this condition is also again true, right? So it is true. We will compare the hash maps and we will find out that all the conditions are true. It means we again found a substring that contains all of the characters that are present in the T string also. So right now the length of this substring is actually 7, right? And 7 is greater than 6. So we cannot really update this result variable right now, but we can try to actually decrease the length of this window again. So we have this window and we will simply decrease the length of it. So right now we have O. We will try to remove the O from the hash map, but it does not exist, right? So we will not be able to do anything. We will simply take the window and decrease it by 1. The L will also change from here to here. And now we will actually check our hash map again. Since our hash maps are still fine, right? Nothing has decreased. It means that this current substring, the length is going to be 6. It is still valid. This is valid, right? Now we will try to make it even shorter. So we will take the window again. We will shorten it again. We will remove the D from the hash map. We will compare both of these hash maps again. And we will find out that all of the values in the hash maps are just fine. Which means right now the length is going to be 5. Okay, and 5 is not greater than 6. So we will update the variable result from 6 to 5. So result actually equals to 5 now. And now we will try to go even shorter. We will take the window length, okay, and we will make it even shorter. We remove the E. We again check the hash map. Since both of these hash maps are again equal, it means that this particular substring, B, A, and C, this is also valid, right? And the length of this substring is actually 4, right? And 4 is less than 5. So we will actually end up updating the result variable from 5 to 4. And now if I try to reduce the size of the window again, we see that we have removed a b. So the count of b will actually decrease in the hash map also, and we will have 0. And now if we try to compare both of these hash maps again, we get that, okay, this condition is not true. We will try to increase the size of the window, but we will not be able to increase it. Why? Because there are no more elements outside of it now. So it means that this is the time when our loop will actually end and we will get the result answer. So this 4 is the result. And now understand that we are actually storing the length of the result, right? But we actually need to store the starting and the ending position. Why? Because we need to return the substring itself, not just the length. So what it means is that we will have another variable also. So we will have something like res range, and it will actually be an array in which we will store the L pointer and the R pointer that we will be having whenever we will actually update this result variable. So whenever you update the result variable, take the values of this current L and current R and then just update this result R variable to make sure that you know the starting and the ending position of the string that you actually consider to be result. So in this solution, the time complexity will actually be order of n multiplied by 26. Okay. The reason we have 26 is because there are 26 alphabets inside of the English language, right? And at the worst case, this entire hash map can be as big as 26 characters, right? So basically, each time we compare these two hash maps, we will have to run a loop of length 26. So that's why we are multiplying 26 with n. The order of n comes from the sliding window technique. So sliding window technique solves everything in order of n. But since at each iteration we are also running this comparison, we end up getting this order of 26. But the question is, can you do better? Can you somehow remove this order of 26 from the time complexity? And the answer is yes. Yes, you can actually do that. Notice that we need to compare these two hash maps only to check these conditions. Is A is equals to 1 in this map and it is also equal to 1 in this map? Is B is equals to 1 in this map and it is also equal to 1 in this map? And is C is equals to 1 in this map and it is also equal to 1 in this map? So these are basically three conditions that we are checking, right? And in order to check these three conditions, we actually go through the entire hash maps again and again. But just think about it. Initially the A will be 0, right? And as soon as A becomes 1, we know that one condition has been fulfilled, right? So what I can do is I can just say that, okay, I have a variable have, and have will actually store the number of conditions that we have fulfilled. So I will simply increase have by 1. So right now have will have 1 as a value, right? What it means is that out of these three conditions, 1 has been fulfilled. Now as soon as the B actually becomes 1, instead of 0, it becomes 1, we can actually take the have and plus 1 is. So the value here will become 2. It means two conditions have been fulfilled or completed, right? In the same way, as soon as C becomes 1, or basically it becomes equal to this value, we can see that this third condition is also fulfilled. So we will add 1 also here and we will see, okay, the three conditions have been fulfilled, right? And these three conditions are basically equal to the length of this particular hash map. Is it not true? It is true, right? Because we take all the unique characters that are present in the T, we use them as keys, right? They are the keys and their frequency, the number of times they appear is simply the value, right? So basically, the number of unique characters are going to be the conditions. So you can have another variable that is need, and need will contain the total number of conditions that needs to be fulfilled. So here the need will be the length of this hash map, that is going to be 3. And we have to make sure that this have hash map actually fulfills 3 conditions for any substring to be a valid substring. So the benefit that we get from these two variables, have and need, is that as soon as we get any element, okay, we get A, okay, and it becomes equal to the element here, we just update the have variable. We don't have to go ahead and check the entire hash map again, because if after updating we see that the have value actually is equal to 3, which is equal to the same value as need, we know that we have found the valid substring and we can now start decreasing the window. We don't have to go through the entire hash map. We can just use this have variable and this need variable to determine that, and then we will keep on decreasing the window size until one of these elements, okay, one of these values actually become less than these values. So suppose that C becomes 0, right? And it became less than the proper value. What it means is that we will take the have, okay, and we will decrease it by 1. So it will actually become 2. And as soon as have becomes 2, okay, it became 2, we will stop decreasing the window. We will start increasing the window again. So what happened is that now you are just doing two operations. First of all, you are just checking, is this equal? Are these elements, the current element that we are updating, is its value same as here? If it is not, or if it is, we will just update the have, and then we will take the have variable, and then we will take the need variable, and then just make a comparison between these two. So basically, we replace the entire hash map comparison with just two operations, comparing these two variables and comparing these two. And this will actually remove the inner loop of 26. It means the time complexity will now be only order of n, which is a much better improvement. So now that we understand the theory, we can go ahead and look at the code. So here is the code. The first thing that we are checking is the condition on t. So if there is no t, okay, if t is empty or if it is null, then we will simply return empty string because we don't have any characters to compare to, right? Then here we are creating the count of t. We are taking the t string and we are using the counter function from the Python library to actually create a frequency map. It is just creating the same need map that we had in the drawing explanation. So this is the map for t string. Okay, then here is the window. This is the hash map for the s string. Okay, we are going to store the current substrings values inside of this window hash map. And then we have these two variables, have and need. Have is going to start from 0. Need is going to be the length of the count t. Then we have the result variable and we have result length variable. Result variable contains the starting and the ending position of the string. That's why we have this array here. This represents the starting position, this represents the ending position. And result length represents the length of the string. So we are storing this infinity inside of it because we need to minimize it, and in order to minimize something we first of all start from the maximum value that we can find. Then we have the left pointer to 0 and now we have the right pointer inside of this for loop. So now we are going from 0 to the end of the string with the help of this r pointer in this for loop. So first of all here we are taking access to the character c from the s string and then we are incrementing its value in the window hash map. Now what this line of code does is that if there is some value for this particular character in the window hash map, we will get that value, otherwise we will get 0, and whatever we get we will add 1 into it and we will store this entire value inside of the window c place. Now that we have updated the count of character c in window hash map, we will check if this character actually is present in the count t. What it means is that is this character c is actually part of the t string. If it is present, then we check is the value for the character c in window hash map is same as the value for character t in a count t hash. We can increase the have by 1. So that's what we are doing here. Okay, and then here we are checking while have is equal to the need. What this condition means is that we have found a valid substring that contains all the characters from t inside of it, right? So while we have a valid substring, that is while we have double is equal to need, we can try to decrease the size of the window. So that's what we are doing here. First of all, we are taking the length of the current substring. If it is less than the result length, we can update the result variable. Okay, so the new L and new R pointer will be stored for the result variable and the new result length will be stored here. Now here we will have the character at L pointer. We will have its value in the window hash map and we will decrement it, decrease it by 1. And then here we are checking if the character at L index is actually present in the count t. If it is present, then we check if the character at L index x value in the window hash map is less than x value in the count t hash map. Then we know that we are not fulfilling one of the conditions for a character. So we will simply decrement have by 1. And then we will simply increment L by 1. The reason we are incrementing L by 1 is to actually reduce the window size. So if you increment R by 1, it will increase the window size. If you increment L by 1, it will decrease the window size by 1. And once this entire for loop runs, we will have our result. So right here on line 34, we are taking the values from the result and we are setting as the new value for L pointer and R pointer here. And here in the return statement, we are simply returning the substring from L to R plus 1. R plus 1 simply because R plus 1 is not inclusive. So everything till R will be inclusive and R plus 1 will be left out. So that's why we have S from L to R plus 1. So this is the substring that we can return. And we will only return the substring if the result length is actually not infinity. Okay, if the result length has changed somehow, then only we will actually return this thing. Otherwise, we will return the empty string. Result length will stay infinity in case there is some character missing in the S string that is actually present in the T string, which means we will never actually get a string or substring in the S that will have all the characters present in the T, and in that case, the result length will never actually update and it will keep staying infinity forever. So now let us try to run this thing and see what happens. So yeah, our solution runs in 67 milliseconds, beats 70.75% solutions on LeetCode, and it passes all the 268 test cases. Our solution is pretty efficient. Now let us look at the time and space complexity for this particular solution. So the time complexity is very simple. It is going to be order of n, or it is going to be order of 26 multiplied by n in case you do not use that optimization for removing the comparison between hash maps. The space complexity is constant, but then you will say that Satyam, why is it constant? I mean, we are actually allocating 2 hash maps for these 2 strings s and t, right? Well, it is constant because those 2 hash maps can only be length 26. The maximum number of elements that you can store in any hash map is going to be 26 because there are only 26 characters inside of the English alphabets, right? There is no other character What it means that the string S and T are going to only have 26 unique characters. That's why we will only have 26 characters in both of these hash maps. So that's why it will actually become order of 52, right? And which is basically order of 1 because it is constant. Hello everyone, today we are going to learn about modified binary search. It is one of the most asked DFA question patterns in interviews, and that's why we are going to learn everything about binary search and what does this modified actually mean. So binary search is actually a way to eliminate half of the search space. So what this means is that you will have a search space and you will actually try to divide that search space and eliminate half of that search space. That is what binary search is. But then what is this search space? Search space is nothing more than elements that you are dealing with. Suppose you have an array. So you have 1, 3, 7, 8, and 10, like just say. So this is basically your search space. Search space is all the elements that you have at your disposal to actually use and figure out what you want to figure out. So here the search space is what? 1, 2, 3, 4, 5. We have 5 elements. So the search space is 5 elements. Simple as that. Now what the binary search aims to do is it tries to divide this search space in such a way that you can actually eliminate half of it, either this side or you can eliminate this side. That is what the main aim of binary search is. The main aim of binary search is not to find some element or find some value or do something. The main aim of binary search is to eliminate the half of the search space somehow. Because when you eliminate half of the search space, the remaining half of the search space is easier to search into, right? It's just less elements to deal with. And that is the only goal of binary search, eliminating half of the search space in some way. Now here we have used the elements of the array as a search space, but search space can be anything. It just needs to have element. You can simply have a set of 1, 5, 9, 8, 10, like these kind of elements. You can have a set and you just want to kind of divide that set into two parts and eliminate half of that set values so that your search space will reduce to the other half. So this search space is nothing more than a set of all the elements that we have in which we can search for the particular element or do the particular thing that we want to do. Let us try to understand the division of search space with the help of an example. Suppose that you have an array like this. We have one, and now we have a, like just say, target. Target is 10. Now we want to find out the 10 or whether the 10 exists in this particular array or not. We can go ahead and put a pointer here, p1. Then we can just check, is this 10? It is not 10, right? I can shift here. Here I will check here. Is this 10? It is not 10. Then again, I will shift here. I will check 8. Is this 10? No, it is not 10. Then I will go here and I will check here. Is this 10? Yes, it is 10. Then I will say, okay, return true. We do have 10 in the search space or in this particular array. But as you can see here that if 10 was not here, if 10 was at the end here, if this was some other element or something else, right? Then what I will end up doing is I will go to this place, then I will go to this place, then at the end I will find the 10 and then I will return true, which will take around order of n time complexity, right? It's a linear time complexity, but we would like to reduce it because what if the array contains around, I don't know, 1 trillion elements? I mean, you will have to just go through all 1 trillion elements to find the element that you need, right? And at that scale, it becomes really important for you to somehow divide the search space and eliminate the part of the search space where you will simply not find your answer. So now the question is, how do you divide the search space? Because if I randomly divide the search space from here, and then I say, okay, I'm going to eliminate the search space, how do I make sure that this particular 10 value is not going to be in this particular search space? That's the question that we are facing right now. And the answer to this question will be provided in the problem itself. So in the problem, you will have some kind of condition. It will be either a rule or a condition or some kind of situation that will help you to figure out whether this particular given 10 exists in half of the search space or not. So you will really have to read the question properly to figure out the rule, the condition or the situation that will help us to divide the search space in two parts and eliminate one of the parts. So here in this case, what is the rule? Well, the rule is very simple. We have a sorted array. And since it is sorted, we have this particular rule implicitly told to us that this particular element, the ith element, will be less than or equal to the I plus 1 element, right? The element at I index will be less than equal to the next element. Simple. And that is a rule that we can use now to divide the search space. So how can we use this rule? We will simply have two pointers, L and R here, and then we will try to find the middle point. So L plus R divided by 2 equals to the mid. And right now the indices of these elements are 0, 1, 2, 3, 4, and then 5. So L is at 0, R is at 5. So 5 plus 0 divided by 2 is equals to 2, the integer division. It means here will be our midpoint. right? And we will check what is the element at mid. So we have 8, and then we can try to compare it with the 10, right? That is what we are doing. We are trying to compare this with the 10. We will see that 8 is less than 10, and now we will try to figure out whether we can use this condition or not. So right now we know that the 10 is greater than the current mid element 8. So it means the 10 will be on which side? On the right side, on this side, right? If 10 exists, it will have to be on the right side of the 8, because we know that the 10 is greater than 8, and if something is greater than 8, it will have to be I plus 1 index. And so what this also means is that this side, this entire side, will not have 10 at all. And this is how we are able to use this rule to divide the search space and eliminate this particular part. Okay, and now all we have this much. This is the part that we are going to search. So we will set the L to this 3 index, and then we will again find the midpoint. So right now the left is 3 and the right is 5. So 3 plus 5 is what? 8. So 8 divided by 2 is what? 4. Now the mid is here. So this here represents our mid. Right now the value at mid is 12. We will try to compare it with 10. We see that the 10 is smaller than the 12. It means 10 cannot be on the I plus 1 side. It means it cannot be on the right side, which means we use this particular rule to figure out that the 10 cannot be on the right side. It cannot be, which means it will have to be on the left side if it exists in the array. So based on this conclusion, we can take the R pointer and we can shift it to the mid minus 1. And now the R will be here. And now we can try to find out the mid again. So L plus R is what? Well, 3 plus 3 divided by 2. That is 6 divided by 2 is equals to 3, right? We found the mid element to be 3. So the mid element will also be here now, and we will cross it. Now we will check, is the current mid element equal to the 10? It is. Since it is equal to the 10, we will simply go ahead and return the index of this 10, that is 3. This will be the answer. Simple as that, right? So now do you understand how we are using these particular conditions or situations like sorted condition to actually eliminate the part of the search space in which we will not be able to find the current element, basically our answer. And in the same way, you will have some kind of rule, some kind of condition, or some kind of situation in each and every question that will actually help you to figure out which side of the search space can you remove and in which side you need to search. So you will really have to be on the lookout of this rule, condition, or situation present in the question. And based on this rule, situation, and condition, you will have to modify your binary search algorithm also. So here is the standard implementation of binary search. We have the left pointer at 0, right pointer at the last index of the array or of the search space, and we have the while loop which is going to run while L is less than or equal to R. Then we are here calculating the mid. Then this condition, actually L plus R minus L divided by 2, it is used for basically making sure that you do not go overflow. So it is possible that in language like C or C++, you will end up hitting the overflow issues. So in that case, this particular condition will make sure that you find the mid element without going overflow. But in languages like Python, you can simply do L plus R divided by 2. That's what you can do in Python. Now, once we find out the mid, we will have this if condition where we are checking if the element at a mid index is basically our target. If it is target, we will simply return the index m. If it is not our target, we will check if the element at m is less than the target, then we will use the rule that we got from the sorting condition. Since it is less than the target, we know that the target has to be on the right side of it. So we will update the left pointer to mid plus 1. We are not going to update to mid. We are going to update to mid plus 1 because we know that mid is not the target. So we don't need to update till mid. Otherwise, at the end, we are sure that the current element, the nums m, is greater than the target. So we are saying that R is going to be m minus 1 or mid minus 1. And then this while loop run until we find the element on this condition and we will return the element. Otherwise, at the end of the day, we don't find the element, we will simply return minus 1 or minus 2, whatever the question asks you to return. Now the question is, how will you modify this particular algorithm for different questions? And before we answer that, we need to understand where we can actually modify it. I mean, it's a very simple algorithm, it's a very small algorithm. So what are the points where we can actually try to modify it? Well, one of the points is this one. This is the condition. You can have L less than equal to R, or you can have L less than R. So we can have these two conditions inside of this while loop here. So we can modify based on this. Then the next place that we can modify are these conditions, these if and elif conditions, where we are trying to find the target. These conditions are right now written on the basis of the sorted list or the sorted array rule. But if you have some kind of other rule, these are the conditions that will change. Now let us try to understand how these conditions and these conditions will change based on other questions. So here we have a question. You are given an integer mountains array, it's an array, okay, of length n. So we have n elements in the array. where the values increase to a peak element and then decrease. Okay, so the values are increasing and then simply decreasing. Okay, that's clear. Now we have to return the index of the peak element. Got it. So it means we will have something like this. So this is the visual representation of the data we will get. Suppose we have 1, then 2, then 3, then I don't know, 5, then 4 here, then simply, I don't know, like just a 2 here again, and then 0. So this is what is going to happen in the question. We will have an array like this: 1, 2, 3, 5, and then we have 4, 2, 0. So the question is very simple. It is saying that the elements in the array will increase till a particular position, and then after that they will decrease from that position. Now we have to figure out the peak element. So peak element here is what? 5. Peak element simply means max element, maximum element, right? So that is what we have to figure out. Where does this happen? Now currently I have 5 as the peak element in the middle, but it does not have to be in the middle. It can be at the end. It can be in the starting. How are we going to figure out which element is the peak element and return the index of that peak element? In the current example, we will end up returning 3 as an answer. And now this is where you will have to read the question properly, understand the situation, and you have to see what are the rules that you can use to eliminate half of the search space. Yes, you can go through each and every element and then find the maximum element. That is, yes, one situation. But in this kind of question, it will be told to you that you have to find out something that is not linear time complexity. You have to find out something like a order of log and complexity, which can only be achieved by binary search. So you are kind of forced to use the binary search in this kind of situations. So how will you be able to do this? You will have to read the question properly and see what is going on in the question. Here we are saying that the elements will increase till a particular element and then they will decrease. So what can we figure out about this particular element from this condition? We will be able to figure out that, okay, the left and the right element of this particular element will be less than it. So as you can see here that the 4 is less than 5 and 3 is less than 5. So it is one of the condition. The target element will be greater than left element and it will be greater than right element. Now what else can we figure out in the question? Well, if we look at the 2, we will realize that if the left node is less than it and the right element is actually greater than it, we know that the 2 is not the target, but the target needs to be in this direction, in the increasing direction. Why? Because the element before 2 is less than 2. It means we are on an increasing slope, on this slope. It means the maximum element has to be on the upper direction or the right direction of the array. So the other condition is that the element, if it is greater than x left and if the element is less than x right, then we know that the target needs to be greater than the element. Do you understand this thing? We have been able to figure out two conditions. Now the third condition is on this side. If we have 2 on this side and we look at the right is what? Less than 2 and the left is what? Greater than 2. So it means in the third condition we can say if element is greater than the right and element is less than the left, we know that the target is going to be less than the element, which means on this side. Because the third condition is signifying that we are on a downhill slope on this side of the array. And since we are on a downhill, it means the maximum element should be on this side. So now that we have these three conditions, we can go ahead and create our binary search algorithm. So now this is the new modified binary search algorithm because we modified the condition. We still have L is equals to 0, R is equals to the last index, and we have while loop as it is. We are still using the same L less than equal to R condition to run the while loop. We are still calculating the mid element just like we were doing it before, but here the conditions are changed. Right now, here we are checking if the element at mid index is greater than the element at left index, and if the element at mid index is greater than element at right index, that means we have found the peak element based on our first condition, and so we will simply return M here. Otherwise, if the element at mid index is greater than element at left index, and element at mid index is less than element at right index, we know that we are on a upslope. It means the peak should be somewhere here, right? That's why we will increment the L to mid plus 1. And in every other situation, we know that we will be on a downhill slope. So we will simply decrement the R to mid minus 1. And at the end, we are returning negative 1 just in case the input is invalid. But whenever the input is valid, this particular condition will end up returning the answer. So now I hope you understand how we can get the conditions from the question and use those conditions to modify our binary search algorithm. And that is literally all modified binary search is. Just a little bit of modified conditions and modified return statement. That's all. Now here is another example that will help us to understand modified binary search even better. So here we have a non-negative integer x and we have to return the square root of x rounded down to the nearest integer. Nearest means nearest on the left side. So if the answer is something like 2.89, we will end up returning 2. Then the integer that we are going to return should be non-negative as well, and which is a valid point because if I have something like 4, then we have two numbers, negative 2 and 2 as its square roots. So we are only supposed to return the 2 instead of negative 2. So the first thing that comes to mind is what is the search space in this question? Well, the search space is all the elements from 0 to x. Yes, we have not been given an array from 0 to x like 0, 1, 2, 3 till x, but this entire search space has been given to us implicitly in the question because we have to find out the square root of x. And square root of x can be anything from 0 till x. If the x is 1, the square root of x is also 1. It means the search space is going to be from 0 till x. Or you can remove the 0 and just say it is going to be from 1 to x. So all the elements from 1 to x are going to be in the search space. So think of this search space as an array that is starting from 1, then 2, then 3 and ending at x. That's what the search space is. Now since we don't have an array, we have to calculate these kind of elements mathematically in the answer. So now let us try to get some conditions from the question. First of all, we have to get the square root of x. It means square root of x cannot be bigger than x itself. So we can have a condition like this. The square root of x cannot be greater than x. So the other condition that we can figure out is if we take an element from the search space and we square that element, it should not be greater than x if it is a correct element. If the square of the element is greater than x, okay, it means that element and every other element after that, well, they will simply not be square root of it. So it means we can remove all the elements after this element. So this is an important condition that we can use. In the same way, the third condition is that if the element's square is less than x, it means the square root of x needs to be on this right direction. So we will safely ignore all the elements on the left side of the elements. So left side will be eliminated and right side will be taken. So now that we have these three conditions, we can try to create a binary search algorithm. So here is the modified binary search algorithm. The L is at 1, the R is at x, that is the ending element. Then we have the while loop, which is running while L is less than equal to R. Then we are calculating the mid. Then here are the conditions that we got from the question. So if the square of m, the square of mid, is basically equal to x, we know that the mid is actually square root. So we will simply return mid. Then if the square of m is less than x, we know that we need to go higher. It means we will simply update the left pointer to mid plus 1. And then in every other condition, we will simply reduce the r to mid minus 1 because we know that the m square will be more than x. And then at the end here, we are returning minus 1 in case the input is invalid. And that is it. This is the modified binary search algorithm. We are simply taking conditions from the question and using it here to modify our binary search to get the correct answer. That's it. So people face a lot of problem between deciding whether they should use this condition, left less than equal to right, or should they use this condition, left less than right. And the answer totally depends on what you are doing in the algorithm. If you are using left less than equal to right, you need to make sure that anywhere in your algorithm you are not setting left equals to mid or right equals to mid. If you are doing this, do not use this particular condition. Do not use, okay? Because if you're doing this, then you will end up having either left equals to mid or right equals to mid at some point of the execution. And from there, if you try to calculate mid again, it will give you the same pointers again, like the previous pointer, and that will cause an infinite loop. And that is not what you want. So if you're doing something like this, if you're setting L equals to mid or R equals to mid somehow in the code, do not use this thing. Do not use this thing, okay? This particular condition should only be used when you are using this particular while loop condition so that you will not have any issues with the infinite loop. So it means you can use left less than equal to R only when you are doing left equals to mid plus 1 and right equals to mid minus 1. If you're using conditions like left less than R, then you can do left equals to mid or right equals to mid. The point of this condition is to make sure that you have some kind of ending point. And if you do not use them properly, you will end up in an infinite loop. That is like the other side of the blade. So today we have LeetCode 278, that is first bad version. So this problem has been phrased like a real world scenario in which you are a product manager and you are trying to lead a team. The team is basically working on a product. Now, unfortunately, the latest version of the product actually fails the quality check. And since each version is dependent on the previous version, if any version like V1 or V7 actually fails, all the other version or all the next versions will also fail. So if we had version 1, version 2, version 3, version 4, and in case the version 3 fails the quality check, the version 4 will also fail the quality check. And now the question is saying we have n versions which are numbered from 1 to n, and we have to find out the first version that was a bad one, which caused all the following ones to be bad also. Now we have been given an API that is called isBadVersion, which returns whether the given version is bad or not. And now we have to implement a function that will find the first bad version. And also we should minimize the number of calls to the API. So what the question is really saying is that we will have a bunch of version v1, v2, v3, v4. Let's just say v5 also is there, v6 is also there, v7. And now suppose v7 is the latest version which is failing the quality check. Now since v7 is failing the quality check, we have two possibilities. One is that v7 is the first bad version. Another one is that one of the versions from here, v1 to v6, was a bad version and that caused all the other versions after it to be bad also. So we have to figure out which version is the first version that caused all the versions after it to be bad one. If version 7 is the first bad one, then we will simply return 7 and we are done. Otherwise, we have to figure out which one is actually the first bad version from v1 to v7. Because it can be any version, right? If v5 is bad version, then v6 will also become bad, v7 will also become bad. Similarly, v3 is bad version, v4 will also become bad, v5 will also become bad, v6 will also become bad, and v7 will also become bad. So we have to return the v3 because this will be the first version that was bad. So we will simply return 3 in this case. And now we have also been given this isBadVersion API. Now API here simply means a function, that's all, okay? We have been given this function just to determine whether the given version is bad or not, because they have not provided any information about the criteria for a bad version. So they are just providing us API and they are saying that, hey, just put the version in this function and we will tell you whether it is bad or good. Now we have a couple of ways to solve this question. We can actually go through and run a loop on 1 to n for all the versions. So we will have 1 to n and we can run this particular API, isBadVersion. So for each version, we will be checking if it is bad version or not. And the first time we find a version to be bad, we will simply return that version. We will not go any further. We will return the first bad version, simple. And now since in this solution, we are going from 1 to n, and checking all of these versions with the help of this version API, we may end up going through all the versions in the worst case. Because if the latest version is the only bad version, it will be the first bad version. And so all these will be fine, right? And then we will end up going through all the versions just to reach the end version. So in that case, the time complexity will be order of n, which is a linear time complexity. But hey, we can actually do better. We can do much better than this. Suppose that we have versions 1 to 6. And now we also suppose that the first bad version is 4. So if we actually try to create an array of whether a particular version is bad or good, then we will see something like this. 1 is not bad, so we will simply say false. 2 is not bad, we will simply say false. 3 is not bad, we will simply say false. Now 4th is the bad one. So we know that it is bad one. So the function or the given API will return true. It is a bad one. Then for this one also we will get true. For this one also we will get true because all of these are coming after 4th. So this question turns out to be something like this. Okay, we have to find out the first place where we get true. That's pretty much what we have to do, right? So how do we figure out the first place in an array like this where we find that true? Well, we can use binary search in this case. So I have written the indices of the elements here. Now let us have L and R. So initially L will be 0 and R will be 5. Now let us try to find the midpoint in this array. So we will have L plus R divided by 2, which is equals to 5 divided by 2, which is equal to 2. The integer division will be 2, not 2.5. So it means we will get this particular position, right? So mid will be here. And now we will need some conditions to figure out whether we should increment L or decrement R, or we should return this particular index to itself. So just think about it. We are supposed to find the first place where we see the true, right? So just before the first place, we must have a false. So we will check if the current index is true, then we will check if the previous index is false. In this case, we don't have that, right? Current index itself is not true. So we know that the true will come after this F. So we will end up incrementing L. L will come here. Then we will check again M. So M will be L plus R divided by 2. So we have 5 plus 3 divided by 2, which is 8 by 2, which is 4. So mid is here. And now we can check, is the current element true? Well, yes, the mid element is actually true. Then what about the previous one? Well, the previous one is also true. That means we cannot really tell if this true, the previous one is the first one or not, because maybe there is another true right before it. So we don't actually have security, right? So what we can do is we can shift the R to mid minus one, and the R will be here now. So as you can see that L is basically equals to R at this point. So it means we can stop our binary search. We have found the place where we will find the first true value. And in this case, we will simply return L, or you can also return R, but we will simply return L. So we basically have three situations that can happen. We can actually get the mid element as true and the previous element will be false. In this case, we know that this is the first true. So we will simply return the mid index. Mid will be returned. Now there is another situation also. What if we are at this place? We have the false here. Okay. Now what about the previous one? Well, we don't have to check the previous one, because if we are at the false, we know that we have to go ahead, right? The L pointer needs to be shifted ahead because the true will be somewhere in this direction. So we can simply shift the L to mid plus one. So L will be mid plus one. And now we also have a condition like this. Suppose that we get this position, and in this position we are actually getting true. Now we will check which one is the previous position. And the previous position is also true. But we cannot definitely say that this is the first true, because we may actually have another true here. And just how many times are we going to check? How many levels deep will we go, right? So we cannot just simply keep going and keep checking which one is the true. Otherwise, that will simply become order of n complexity again. So we will make a decision based on this particular information only. If the current one is true, the previous one is also true, we know that the first true needs to be in this direction. So we will take the R and we will shift it to mid. This is the mid, so we will shift it to mid. Here we are shifting L to mid plus 1, and here we are shifting R to mid. Simple. And in this way, two things will happen. Either first we will find this M, the particular M, where we actually have the first true, and we will simply return the mid element, or we will end up completing the entire binary search, and we will have L double is equals to R. The L and R will be same, and we can simply return L at the end. And so based on these conditions, we will create a binary search algorithm. So now let us go through the code also. We have L equal to 0, R is equal to N. Then we are starting our binary search. And then in the binary search, we are running this only when L is less than R. So as soon as L becomes equal to R, we will end it and we will return L at the end. But in the while loop, we are first of all calculating the mid. So L plus R divided by 2, we are getting the mid. Then this is the place, okay, where most people might confuse. So this function has been provided by the question itself. So this function will be defined in the online judge anyways. So we can directly use it here. We don't have to create this function here. So what I'm doing here is I'm using this function and I'm passing the mid here to check whether the current mid is good one or bad one. It will return true or false. So if this returns true, that means the current mid element is actually the bad version. Then we will check the previous one. We will check if the previous one is bad or not. And if it turns out that the previous one was actually not bad, it means the previous one was actually false, then we will simply return mid here, as we already discussed in the drawing explanation. And then here we are checking the second condition. If the current version is bad and the previous version is also bad, it means we have the situation where we found two truths. So we are supposed to just shift the R pointer to mid. Otherwise, in every other case, we can simply shift the L pointer to mid plus 1. And these are the three conditions that we discussed in the drawing explanation. And so if we ever find the first true during the binary search, we will return it. Otherwise, at the end, we will return the L, because L and R will reach the first true after the complete binary search anyways. So now let us try to run it and see what happens. So yeah, it runs in 38 milliseconds and beats 48.74% solutions on LeetCode. So it's a pretty efficient solution. Now we can discuss the time and space complexity for this particular solution. So clearly the time complexity will be order of log n, because we are using binary search. Time complexity for binary search is simply order of log n. Now the space complexity will be order of 1, that is constant, because we are only initializing the L and R and the mid variable. And all these three variables will consume a constant or a fixed amount of memory, no matter how much the input size is. So n can be in millions, but this L, R, and M will only keep consuming the same amount of memory. And so the memory consumption is basically fixed or constant, and that's why we are saying it is order of 1. So today we have LEET 433, that is search in a rotated sorted array. This problem can greatly help you to understand what is modified binary search algorithm. So in this problem, we have been given a nums array that is going to be rotated in some way, and then we have to find the given target in that nums array. So a normal sorted array will look like this. We have the minimum number here, the maximum number here. But here we will get a rotated array at an unknown index. Okay. So suppose that I want to rotate this array at this particular index. So I want to rotate this array on the index 2 somehow. So how can we do this, right? Well, we can take this entire part and place it first here. Okay. 4 and then 5. And then we can take this entire part and place it after this. So we will have 1, 2, and 3. That's what a rotated sorted array is. We have rotated this array at the index 2. And then we will have a target from the question that we need to find in this rotated sorted array. What this means is that if target equals to 1, then I need to find out where 1 is in this particular sorted array, and then I will have to return the index. Now understand that indices have also been reset now. What this means is that earlier 4 was actually at third index, right? But in this new sorted array, we are going to consider indices like this: 0, 1, 2, 3, and 4. Indices are still in the same order as they were. Only elements have changed their order, that's all. So suppose that we have an array like this. Here we have elements from 0 to 7, and we have rotated this particular array after the third element. That's why we have 4, 5, 6, and 7 here, and then we have 0, 1, 2, and 3. Now let us try to visualize this particular array or this particular situation with the help of a graph. So usually the graph of a sorted array will look like this. We will start from the minimum element 0 and we will reach the maximum element 7. But in case of our rotated sorted array, it will look something like this. So we will have the same graph again, but this time we have to rotate the entire graph after the element 3. So here in this original graph, the 3 element was here, right? This is the third point, and now we have to rotate around this. So it means that we have to take this entire part, and we have to place it first, and then only we can place this entire part. What this means is that we will have something like this. We will have a third point here, and then the entire rest of the graph will look like this. It will be here. So we are starting from 3 to 7, okay? And then we will have a break because now we are going to go for the another part of the sorted array that is going to start from the 0th position to the third position. And this is how you can visualize this situation. You have two parts. You have two properly sorted parts. One sorted part is this, another sorted part is this. So we need to figure out some way with the help of this visualization to create the binary search algorithm that will help us to find out any element inside of this array. The reason we are using binary search algorithm is because it is strictly told in the question to use order of log n solution. And mostly when you're talking about log n solutions, you can only use in most of the questions binary search. So now that we are using a binary search, we know that we will have to modify it also. So let us try to figure out a few rules that we can use to actually create a modified binary search algorithm. So let us try to figure out a few rules. First of all, we know that there are two parts of this sorted array, right? We have this part, first sorted array part, and then we have second part. Now when we are trying to run the algorithm, we will have a mid pointer. Okay, we will calculate mid pointer, we will have left pointer here, we will have right pointer here, and then we will try to calculate a mid pointer in the binary search, right? Now suppose that the mid pointer actually is here. Now how do I know whether this mid pointer is in this part of the array or in this part of the array? How do I know this? In which part are we present currently? Because that is one of the first things that we should know, in which part of the array we are present. So if we notice properly, we will see that we are on 7th element in the array. Now, in order to find out in which part we are, we can try to compare this 7th element with the element at L index, okay, left index. So right now the element at left index is 4. Since this particular element 7 is greater than the 4, that is the smallest element on the left side, we know that we are on the left side of the sorted array. But in case if our mid pointer was actually on this place, that is the first element, and we will try to compare the 1 with this particular element L, we will see that the 1 is smaller than this one. It means we are on the second sorted array. So we have our first rule right here. If the element at mid index is greater than or equal to the element at the left index, this index, then we are on the left side of the rotated sorted array. Otherwise, else we are on the right side of the rotated sorted array. Simple, right? Now suppose that our mid pointer is right here on the 7th index, that is on the first sorted array, and now we want to find out our target. So in case the target is less than 7, the current mid element, then the target can be 4, 5, 6 or 1, 2, 3, because all these elements are less than 7. Now how do we know whether we need to search in this part or in this part? That's a big question, right? So what we can do is, after comparing our target with the element at mid, that is 7, we can compare it with this element, the element at L index, and if our target is smaller than this element, we know that it will have to be in this side of the array. So in this case, we will know that none of these elements 4, 5, 6, 7 are going to be our target, and we will shift our left pointer to this place, mid plus 1. So this gives us our second condition. So if our target is greater than or equal to the element at left index, but it is less than the element at mid index, then we can say that we need to shift the r pointer from here to this place. Why? Because our element will be somewhere here. It is greater than the 4 and less than the 7. But in any other case, we know that it will be on this side of the array, and that's why we are taking the L pointer and shifting it right here. And so in the else, we have L is equals to m plus 1. Now suppose that the mid pointer is right here in the second sorted array. Now how can we find out our target? Well, if the target element is less than 1, we know that it has to be in this direction. Why? Because it is a sorted array, right? If it is less than 1, it needs to be in this direction only, because every element in this direction is going to be greater than 1 for sure, because we are in the second sorted array. So if the element is less than 1, it is very simple. We will take the r and we will place it right here in this index, and the L will stay at the same place. But if it is not less than 1, then we have 2, 3, 4, 5, 6 and 7 as potential answers, right? It means our answer can be in this part or in this part, right? How do we know in which part we need to search? Because we cannot go in both the ways in binary search. So to figure that out, after we have compared the target with 1, we will compare it with the 3. 3 is the element where r will be present, and it is the maximum element on this side. So if the target is greater than this 3 also, then we know that we have to come back here 4, 5, 6 or 7. It means we will have to search in this part of the array. But if it is not greater than 3, if it is less than 3, we know that we have to search right here in this part only. So with this observation, we have another condition that we can use in our binary search algorithm. So the third condition is very simple. If the target is greater than the nums of mid index and it is less than or equal to the right index, we know that the target is somewhere between mid index and the right index. So we will simply take the L and make it mid plus 1. But in any other condition, we know that the target is going to be in the left side of our array. So we will simply take the right pointer and we will shift it to mid minus 1. Now we have three conditions, right? Well, there is one more thing to notice. This particular condition is only valid when we are on the left part of the rotated sorted array, and this is only valid when we are on the right part. So that means we have to use these conditions 2 and 3 based on the first condition, whether we are on left part or we are on right part. So now we have all the three conditions. We need to create a modified binary search algorithm. So now let's go ahead and look at the code. Now let us look at the code. First of all, we are initializing the left pointer with 0. Then we are initializing the right pointer with the ending index of the nums array. And now here we have our binary search loop. So we are going to run the while loop on the left less than r condition. In case the left ever becomes greater than the r index, that means we can stop the loop because we have gone through the entire array. Now here we are calculating the mid index. Then we are checking if the element at mid index is actually the target. If it is target, then we immediately return the m because m will be the answer. Then in this condition, we are checking if the element at the left index is less than equal to the element at the mid index. If that is the case, then we are in the first part of the rotated sorted array, and we are going to use the second condition that we discussed to figure out the target. And here we are checking if the target is greater than equal to the element at left index, but it is less than the element at mid index. Then we are going to shift the r to mid minus 1. Otherwise, L will be shifted to mid plus 1. Else, we know that we are on the second part of the rotated sorted array, and so we are going to use a third condition to find the target. So here, if the target is greater than the element at mid index, but it is less than equal to the element at right index, we can simply shift L to mid plus 1. Otherwise, R will be shifted to mid minus 1. And once this entire loop is done and we have not returned the answer using this condition, it means we need to check the element at L index. So if the element at L index after this entire loop is done is equal to target, then we will simply return the L index. Otherwise, we will return the negative 1. And this will happen when the L and R become same, or the R will cross the L right before we find the element. So in that case, L will be at the correct element, and we have to check if the element at L is basically equal to the target. If it is, then return the L index, otherwise return negative 1. So now let us run it and see what happens. So yeah, our solution runs in 0 milliseconds, it passes 196 test cases and beats 100% solutions on LeetCode. This number is questionable, don't trust it, but yeah, it's a pretty efficient solution because we are using binary search. So now let us try to look at the space and time complexity for this particular solution. So the space complexity is going to be constant because all we are doing is having L and R and mid pointer, and these are going to take the constant amount of space no matter what is the size of our array. So the input array can contain 1 million elements, but the space taken by L, R and M is going to be constant no matter what the size of the array is, and that's why it is going to be fixed, and that's why we have order of 1 space complexity. The time complexity is order of log n because we are using binary search to divide the search space by 2 each time. And that is why we will have log n time complexity. So today we have LeetCode 410, that is split array largest sum. Now this problem is actually a hard problem, but I would call it crazy hard problem because yes, there is an intuitive solution to it that you can actually code up, and it sometimes passes on the LeetCode, but the solution that we are going to discuss right now is something that is like the optimal solution, and that solution is very tricky to come up with. Coding that solution is not hard, coding is very easy, but to be able to come up with that kind of solution is very non-intuitive for beginners. At least the best I can say is that if you have solved a lot of problems like this, then you will be able to have the intuition to actually go ahead in that direction and discover that solution. So basically in this problem you will be having an integer array nums and you will have an integer k. Now we have to split the nums in a k different subarrays. Remember that we are dealing with subarrays, not subsequences. So the elements needs to be contiguous, that is adjacent to each other. Now we need to divide this nums array in k subarrays in such a way that the largest sum of any subarray is actually the minimum sum possible. So what does this mean? Suppose that we have this particular array and now we have to divide it with 2 parts. Now what we can do is we can try to divide it in 2 parts like this. I can have 8 here. 8 will be another subarray, and this 7, 2, 5, 10 will be another subarray. 7, 2, and 5, and 10. So this is another subarray. We have 2 subarrays, and the sum of this subarray is 8. The sum of this subarray is 24. So the largest sum is 24. Now we have to figure out, is there a way to divide this particular array in such a way that this largest sum will actually be less than 24, right? And yes, there is a way. So we can divide the array like this from here. Then we will have 7 to 5 here in one subarray, and we will have 10 and 8 in another subarray. So the sum here is 18 and the sum here is around 14. So as you can see that the maximum sum actually got reduced to 18 from 24 to 18. And if you try to actually divide it in any other way, then suppose that you want to divide it from here, this sum will actually become greater than 18, right? Yes, this sum will reduce, but it will become greater than 18. So the minimum sum that you can figure out is 18. So that will be the answer that you need to return. Remember, you are not supposed to return an array because it is very clearly told to us that we have to return the minimized largest sum. So 18 is the minimized largest sum, and that's what we are returning here. And here we are only saying that a subarray is a contiguous part of the array. So it means that I cannot take a 7, then 10 and 8. 7, 10 and 8 is actually a subsequence. It is not a subarray, okay? Now yes, there is an intuitive way to solve this question. What you can have is you can have a recursive decision tree. So we will have a few choices. Why are we going to have few choices? Well, first of all, we are going to create 2 subarrays right here, okay? We have to create 2 subarrays. So I can take this first of all in one subarray, and then the rest of the thing will be in another subarray, right? Subarray 2. Or I can do something like this. I can take these 2 in one subarray and the rest of them will be another subarray, right? Or I can do something like this. I can take these 3 in a one subarray and these 2 will be another subarray, right? Then I can simply take these 4 in one subarray and this 8 is going to be in another subarray, right? And then can I take this whole thing inside of a subarray and then let the other array be empty? No, I cannot do that. I need to have something in every array. Why? Because we are supposed to split. We are supposed to split this given array. So that's why this is not valid. We need to have something in every array. So it means till now it is valid. We can have this as one subarray, this as another subarray. So what we have is we have a few decisions. So what will happen if I take 7 as first subarray? We have this, right? What will happen if I take 7 and 2 as a first subarray? And then what will happen if I take 7 to 5 as the first subarray? Then what will happen if I take 7 to 5 and 10 as a subarray? And here by taking 7 as the first subarray, all the other elements are going to be part of the other subarray, right? And here if I take 7 and 2 as first subarray, then all of these are going to be part of other subarray automatically. Yes, we will have to calculate their sum and everything, but that we can do easily in the code. But this is the intuitive way that you can actually solve this question. So you will have 7 here, then you will have a big subarray. You can divide this subarray in the other branches. You can have more branches everywhere, right? So you can divide it more. And yeah, that's kind of an intuitive way to do this. But this solution does not really pass on the LeetCode because this solution will actually become a dynamic programming solution. You will have the I and you will have the K. So K is going to be the input parameter that you have to divide it into. So you will have to memorize this thing, or you can use true dynamic programming. But at the end of the day, you can have a time complexity like and square k. Okay, and we are not going to go through this solution because it is an intuitive solution and it does not really pass on LeetCode. Yes, there are some optimization that you can make to make it pass, but we have a better solution. Actually, we have a much better solution, but that better solution is going to crack your head open. Now what we are going to do in this better solution is we are going to use binary search. It is a little bit non-intuitive, but it is definitely like the best way to solve this question. So how are we going to use binary search on this question? Well, we need to figure out what we were doing in the intuitive solution. What we were doing is that we were taking all the possible set of subarrays. So we had possible set of subarrays, right? We can have 7 as a single subarray, and we can have 2, 5, 10, and 8 as a subarray, right? Then we can have something like 7 and 2 as subarrays, right? And then we can have all the other elements like 5, 10, 8 as another subarray, right? We are dividing this in 2 subarrays because the k is 2. If k was 3, we would be trying to divide this in 3 subarrays, okay? Then we can have another subarray like this, 7, 2, 5, and then we can have 10 and 8 in another subarray, right? So this is another set of subarray, right? Then we can have something like 7, 2, 5, and 10. This is going to make one subarray, okay? And then we can have other subarray like 8, single 8. And now what we were doing is that we had a particular set of subarray, right? We had 7 and this one. What we will do is we will take the largest sum. So this will be the largest sum somehow, right? So it will come out to be like 25, right? The sum is going to be 25. Then once you have this sum, you can, yes, store it somewhere. So you will be having a minimum sum of 25 as the largest sum that you have figured out till now. Then you will go to the next subarray set. Okay, then you will calculate the largest sum here, and then it may be something else, right? And then you will go to next subarray, then you will go through next subarray, and you will keep on calculating the largest sum. And at the end of the day, after comparing all of these sets, okay, you will compare all of these sets and you will get an answer like 18. And this 18 is actually coming from this particular set, okay? So what is basically happening is that you are going through sets of subarrays. You have 1 set, 2 set, 3 set, 4 set, okay? You are going through all the 4 sets of subarrays and you are figuring out the maximum sum for all of those sets, and then you are actually just getting the answer by comparing all those maximum sums. You are returning the minimum sum that you can find. And this is the insight where you can actually use binary search. And this is where you need to think or understand that yes, we have multiple sets of subarrays, but not all of them are going to be answers, right? But we have to check each and every set. Why? Because we don't have a way to decide whether this particular set is going to be an answer or not. That is the only reason we are going through each and every set. Each and every set needs to be checked just to get the proper answer. So what it means is that if you try to go from subarray sets to sum, you will have to check each and every set of subarray, right? But what about the other way around? What if we try to go from sum to subarray? Now suppose that I take a random sum. The sum right now I'm taking is 20. Now I need to figure out, is there a way to split this entire array in such a way that the maximum or the largest sum for any subarray is going to be 20 or less than 20? Well, we can try to figure that out. So let us put a pointer I on 7. So we will have 7 here. So is 7 less than equal to 20? Well, yes, it is less than equal to 20. So we can make this subarray bigger, right? So I take more elements in the subarray. Now I will take 2. 7 plus 2 is what? 7 plus 2 is 9. Is 9 less than equal to 20? Yes, it is less than equal to 20. So I will go for another one. I will take 5. Okay. So 7 plus 2 plus 5 equals to 14. So is 14 less than equal to 20? Yes, I can take another element in this subarray. Now 14 plus 10. Now 14 plus 10 is 24. Okay. And 24 is not less than equal to 20. This is not true, right? What it means is that this particular subarray till 10 is not valid for this sum. The largest sum of this subarray is actually more than 20. But this subarray is valid, right? 7 to 5. The sum of the 7 to 5 was 14, which was less than equal to 20. So we will have one subarray like this, okay? Then we will take 10 in another subarray. So we will have another subarray and then we will have 10. So 10, is 10 less than equal to 20? Yes, it is. So we will again shift the I pointer to the next one and then we will add 8. Then is 18 less than equal to 20? Yes, it is less than equal to 20. So it means this is also valid. Now if I try to go any further, I don't have any elements, right? I don't have any more elements. What this means is that I can simply stop the loop and we have two subarrays like this. We have 7 to 5 and we have 10, 18. What this means is that we were able to split this array in two parts in such a way that the maximum sum or the largest sum of any of these two arrays is going to be less than or equal to 20. So what can we figure out from this? We know that we need to find out the minimum largest sum. We need to find out the minimum limit of the largest sum, right? So what we know is that since it is actually working for 20, we can try to go for lower numbers. I can go for 19. I can try to split this array into subarrays in such a way that the maximum sum will be less than or equal to 19. I can try to do that, right? Then in the same way, I can go to the 18, right? I can try to do that. If this also works, if there is actually a way to split this array in such a way that the maximum sum of any subarray is going to be 18 or less than 18, we can try to go for even lower values like 17 or 16, right? But where do we stop? That is the question. Where do we really stop? And the stopping point will have to be the largest element, not the sum, the largest element present in the array. Why? Because if we go any lower than 10, suppose I go to 9, then I will not be able to accommodate this 10 anyways, right? In any of the subarrays. But I need to be able to accommodate 10 also in one of the subarrays. So if I go to 9, if I go to 8, if I go to 7, I may be able to accommodate other elements, but I will not be able to accommodate 10 anywhere in any of the subarrays. So that's why 10 is going to be the cap. We cannot go any lower than 10. So we know what is going to be the minimum number that we need to check. But here we started with 20. And 20 was a random value that I took, right? How do I figure out what is going to be the maximum value or the largest value we can take and we can start from there? Well, we know that the k is equal to 2, right? Which means we need to divide this array into two subarrays. So what we can do is we can take the array and divide it into two parts. First is 7, the other one is this, right? Then I can divide it into this part, then I can divide it into this way, then I can divide it into this way, and then I just take the maximum that is present, the maximum largest number I could find out, and I can take that as the upper limit, okay? But this way is not really very good. At the end of the day, we just want to find out the upper limit. That upper limit does not have to be true, right? It just needs to be the upper limit, the place where we can start from. So the best way to do this is actually to just take all the elements and sum them up, okay? So if I take all the elements and sum them up, we will get 32. So 32 is the largest sum that we can get from this array, okay? So I can take 32 as the upper limit. So what this means is that the answer is going to be somewhere between 10 to 32, right? So we will have an answer between 10 to 32. And we know that for this particular array, the answer is going to be 18. So yes, 18 exists between 10 and 32. So we also have this way, right? I can take a sum and I can try to figure out if I can split this particular array into two subarrays such that the largest sum of any subarray is going to be less than or equal to 32. If it is less than or equal to 32, I can try to find out the lower numbers. I can try to check for lower numbers. If it is not less than equal to 32, I know that I need to go up. I need to figure out a bigger number. So here you can see that we have a condition and we can go either this side or this side. Right? Do you understand? I can check for lower numbers or I can check for upper numbers based on a condition here. And that's why we can use binary search. Remember that yes, we can go ahead from 32 till 10 and search for all of the values. Just figure these things out for all of the sum. But if we try to do this, we will end up going through each and every set of subarrays again, right? We don't want to do that. We don't want to go from 32 to 31 to 30 to 29 and all the way to 10 checking everything, right? Because it will not help us in any way. It will just make us go through the entire set of subarrays again and again and again. So what we need to do is we need to observe that, look, we are not supposed to check for each and every value, okay? We have a particular answer that we need to search, okay? We need to find out the minimum possible answer, right? So basically we have a set of these numbers and we need to search for a particular number based on a condition. So I can simply put binary search on it, right? Instead of going through every element or every number or every sum, I can just divide and then check for the condition and then simply eliminate half of the search space each time, right? And that will help us a lot and speed up our searching very quickly. So that is why we are going to use the binary search on the possible sum, right? The possible sum for this particular situation is just 10 to 32. Okay, for other array it can be different. All you have to do is just take the largest element from the array and then just take the sum of the entire array. That will give you the range in which you need to perform binary search. Now there is one more thing I want to clarify here. So here we have k is equals to 2, right? But what if it was not true? It was actually 3. And then here we were able to just take the two arrays. Okay, we were able to split in two arrays and the sum of each array was less than equal to 20. So will it be a problem if I just split it in two arrays, okay, and not three arrays? Well, no, it is not going to be a problem. Why? Because if we have the largest sum in any of these arrays less than 20, then we can simply take that largest array and break it in two parts, right? So I can have 5 and 10, and I can have 7 and 2, and the sum of these individual arrays is also going to be less than 20, right? So that's it. I don't have to exactly make 3 subarrays. If I can make 3 or less than 3 subarrays and make sure that for all of the subarrays, this particular condition is true, largest sum of any of those subarrays is less than 20, I know that this particular number is fine. Okay, we can look for lower numbers, we can look for 19, 18 or some other number. But if I end up figuring out that no, I actually had to create more than 3 subarrays, I had to create 4 subarrays to actually make sure that the sum is going to be less than 20 for each and every subarray, then I know that I cannot have 20 as the answer. I need to increase the sum to reduce the subarrays. Okay, so then I will start checking for 21, 22, 23 or other numbers. So this is the condition that is going to help us figure out a binary search solution. So here is the binary search solution. We have the left pointer, we have the right pointer. Left pointer actually points to the largest element that is present in the nums array, and the right pointer is basically the sum of all the elements in the nums array. So we have a range in which we need to check for our solution. Now we will always calculate a mid in the loop. So we will have the mid and we will check if we can split the nums array in such a way that the largest sum of any of the subarrays is actually less than or equal to mid, that is this particular element, then we know that we have found a possible solution. So we will set the result is equals to mid, and we will make sure that the right pointer is decremented to mid -1. Why? Because we need to find out the lower values now. Okay, so we need to find out the mid -1, mid -2, right? All those values. But if that is not the case, if we cannot split it in such a way, then we know that we have to find out a bigger value for the sum. So we will take the L pointer and we will shift to mid +1. Simple as that. This is going to be the entire binary search solution. And this can split will actually be a method that will help us to figure out if we can actually split the array in such a way or not. And this can split is actually the easy part. It is nothing more than a simple greedy algorithm. You will see it in the code. So here is the code with all the proper comments. I will provide this in the description also. So first of all, we have the can split function. That is probably what you guys need to know, right? So in the can split function, we are taking a sum, okay, the largest sum that we are currently dealing with, and we will try to create subarrays. Since we always will be actually having at least one subarrays, we are going to start with subarrays needed with 1, okay, and the current sum is going to be 0 right now. Then we will take the nums, okay, each number in the num array, and then we will start checking things. So if the current number is actually greater than the largest sum, we know that it is bigger than the limit itself. So it is not possible to keep this number inside of any array, right? Because it is larger than the largest sum. So here we can directly return false that, okay, look, we cannot split this array in any way such that the maximum sum will be less than or equal to the largest sum. Then here we have the condition which is actually calculating the sum. Now if the current sum plus the current number is actually less than or equal to the largest sum, we will simply update the current sum, okay, and then we will move on to the top of the loop again and we will go for another number. But if it is not less than the largest sum, okay, if the current sum plus number is not less than the largest sum, it means we need to create another subarray to actually accommodate the number. So in the else block, we will simply increase the number of subarrays that we need, and then we will take the current sum and we will set it to num. Why are we setting it to num, not 0? Well, that is because we need to take the current number into the next subarray, right? And the next subarray is going to start with the current number, not the first element. So suppose that we have an array like this and we were able to sum everything till this point, okay? So we have a subarray of this one, and I'm trying to add 10 into the sum of the subarrays so that I can take 10 also inside of this current subarray. But the situation is that the current sum of this subarray, that is 14, plus the next number 10, is actually greater than the largest number, right? So it is greater than the largest sum, and the largest sum, suppose it is like, just say, I don't know, like 14 itself. I'm supposing that it is going to be 14, okay? So if this is actually larger than the largest sum possible or allowed, then we know that we cannot add 10 inside of this subarray anymore, right? So it means I need to create another subarray. So the another subarray will be starting from here, okay? And that's why I'm taking the current sum variable and actually setting it to n or num basically, because 10 will be the current num. So it is going to start with the 10. The first value itself will be 10, and then we can just keep on increasing and just add 8 in the next iteration and so on. And once we have gone through the entire for loop, we will know how many subarrays we need to actually make sure that the sum of each subarray is actually less than or equal to the largest sum. And then we will check if the subarrays needed is actually less than or equal to k. Okay, so k is the allowed number of subarrays that we can make, and the subarrays needed is actually the proper number of subarrays that we need. So if the subarrays needed is less than or equal to k, that means it's fine. We can simply return true. Okay. Otherwise, if we need more than k subarrays, we can simply return false. So we will get true or false from this condition. And now here we are going to start our binary search. So we have the left and right pointer, and then we have res is equals to right. So we are going to make sure that we are taking the worst case as the answer. So we will take result is equals to right. Okay, that is sum of all the elements. And then we have the while loop. So while left is less than equal to right, we will figure out the middle element. So this particular expression will help you figure out the middle element. This expression, make sure that you do not actually deal with any overflow condition. So try to use this expression whenever you are trying to find out mid. And then here we are using the can split method on the mid. Now if the result is going to be true, then we will go for this. We will set the result to mid, and then we will set the right to mid -1. Otherwise, we will set the left to mid +1, just like we discussed earlier. And once this entire loop is done, we will get the result. We will simply return the result, and that will be the answer. So now let us run it and see what happens. So yeah, our solution runs in 4 milliseconds and beats 31.76% solutions on LeetCode. We are passing all the 34 test cases. It's a pretty efficient solution. Now let us discuss the time and space complexity for this particular solution. The time complexity is order of log of s multiplied by n. S simply means the sum of all the elements. So suppose that you have an array like this. You have 1, 1, 1, okay, 1 and 1. So here every element is just 1, okay, right? So the minimum number or the minimum sum you can have is 1, right? Because each and every element is just 1. So the maximum out of each and every element is also going to be 1. And then the largest element or the upper limit of solution that you need to check for is going to be sum of all these elements, that is going to be 5, right? So as you can see that the range between the left pointer and the right pointer is what? It is 5, right? The range is simply 5. And since we are going to run the binary search on this range, we will actually end up going for log of this range. So the range is basically what? In the worst case scenario, range is basically sum of all the elements. That's why the r will be replaced by s. So log is log of s. So time complexity will be log of s. That's why we have this log of s here. And then we are multiplying this with n. The reason we are doing it is because instead of this binary search loop or while loop, we have another function can split, okay? And this function runs in order of n time complexity because we will have to go through each and every element of the array in this can split function. So that's why this function will be run each time the while loop is running, and that's why we have multiplication sign here. So you can also write it something like n log s. It looks more better, I would say, but this expression actually shows what is really happening. We have a binary search, and inside of this binary search we are running an order of n function. So this represents the workflow a little better, but at the end of the day you can also write it like this: n log s. The space complexity is going to be order of 1 because we are using binary search and we are just using a few variables in the can split. We are not actually allocating new space for hash maps or for arrays or any other thing. So that's why the variables that we are using or we are allocating in binary search and in the can split function are going to take the same amount of space no matter what is the size of the nums array. So the memory that we are using in the functions does not depend on the size of the array, right? Does not depend on the input size. And that means the memory consumption is going to be fixed for all the functions, and that's why we are saying that it is going to be constant space complexity. And everyone, today we are not solving any lead code problem. Today we have graphs and BFS, and we are going to go in depth about these two topics. We are going to understand what exactly is a graph. Is it just a node, edges, and all that? Or is it something even more deeper? And then we are going to understand what is a BFS and how we can apply BFS to crazy situation like a simple array, which does not even feel like a graph at first look. So before we go ahead, I am assuming that you have some basic knowledge of graph. You at least know that there are nodes and those nodes are connected to other nodes. We can have multiple edges between multiple nodes. And I'm also assuming that you at least know the concept of adjacency list and adjacency matrix. If you don't understand that properly, that is fine. But you must have some basic understanding of these two things and graph. Because in this video, we are going to go in depth in these graphs, and we are going to understand what a graph really is. We are going to see how we can turn something crazy like a simple array into a graph. We don't even need something like the adjacency list to actually, kind of create a graph. We are going to go in depth of these concepts. Suppose that we have this adjacency list. This is 0 index, this is 1 index, this is 2 index, and this is 3 index. And we are saying that at 0th index, in this list, we have stored another list. And this another list contains 1 and 3. So basically, we have this array, and inside of this array, at each index or at each position, we are basically storing an entire list. So it is basically an array of list. So now if I want to create a graph using this adjacency list, how can I do this? One thing I know is that these indices are actually representing nodes, right? So I can say that I have a node 0. So I can simply create a node 0. That is great. And now at this 0th index, we have this list that is 1 and 3. So what this list is saying is that if I'm at node 0, I am allowed to go to node 1 and node 3. Okay, so let's just go to node 1 and node 3. So I will simply say 1 and then I will simply say 3. So with the help of this much information, I was able to create this graph, right? Now let's move on to this node, that is one node. So we have already created the one node here. Now the one node actually contains this list. This list is saying that from one node, you can go to 0 node and you can go to the node 2. So here I have already created this edge from 1 to 0. So I am able to go to 1 to 0 already. Now I am also able to go to the node 2 from 1. So okay, let us go to the node 2 from 1. Great. Now let's move on to the next node, that is 2. So the 2 contains this list. We have 1 and 3. We are saying that from 2 we can reach 1 node and we can reach 3 node. So here we already have this connection from 2 to 1. So this condition is solved. But we also need to have a connection from 2 to 3. It means I can just create an edge here. That is great, right? So from this much information, I am able to create the graph till now. Now we have this last node that is 3. So here in the array at 3 index, I am storing this particular list. And this list is saying that from 3 node, I can go to 0th node or I can go to 2 node. Okay, so I already have this 3 node here, correct? I can go to 0th node. So yes, I already have this edge. And I can also go to 2 node. So I already have this edge. So I don't really need to change anything in my graph. And with that, all of our adjacency list is done. And we are able to create this graph. Now I want you to notice something. We were able to create this graph because we were following a rule, correct? And the rule was saying that for every node, I am providing you a list of nodes that you can reach. So you must only go to these provided nodes from that node. And that is why we were able to create these edges from 0 to 1 and 0 to 3, correct? Because of that rule, we were able to figure out that 0 can only go to 1 and it can only go to 3. It cannot go to 2. Why? Because we don't have 2 in this list, right? So the rule restricts, or the rule says that you cannot go from 0 to 2. And similar case for all these other nodes also. So from this discussion, we can get this insight that this edge, what is this edge? This edge is nothing more than a representation of the fact that the rule is actually allowing us to go from this node to this node. If the rule was not allowing us to go from 1 to 2, we will not actually have this edge. But since we have this edge, it means that we are allowed to go from 1 to 2 because of that rule. It means that the edges of any graph is just a representation of some kind of rule. Now, what that rule is, that will be actually given in the question itself. But that rule can change, can be twisted, can be done anything with that rule. But the fact is that these edges, they always represents whether you can go from one node to another node only based on the rule. So from this, we can conclude a very important thing. We can conclude that a graph must have a rule. Graphs must have a rule because edges can only be created according to this given rule, correct? So rule is really important. But there is one more thing which is important. These edges do not mean a thing if we do not have these nodes, right? So what is a node? Well, a node is basically a situation or a place or a configuration or a state. In the current example, we can say it's a place. Why? Because 0 here represents an index. It's a position. So we can say it's a place, right? So you are at the 0th place, then you are at the first place, that you are at the second place, then you are at the third place. And the rule, this rule is actually telling you that you can go from 0 to first and third position only. So if you're standing on this place, you are only allowed to go to third place or the first place. That's what the rule is saying. So a node can be place, state, configuration, or situation. State does not mean the MP or Uttar Pradesh or something like that. State simply means the conditions of a particular thing at the present time. So for example, if you are a person standing on the 0th position, your state is that you are at a 0 position. Now you go to this position based on the rule, right? So your state is now is that you are at first position. So your state changed from 0 to 1, right? So that's why I'm representing this node as a state also. Now this node can be a configuration because suppose you have a Rubik's cube. In the Rubik's cube, you have many colors, you have many configuration, right? So you can go from one configuration to another configuration by rotating some of its sides. So it means each configuration of the Rubik's Cube can be considered as a node, and when you rotate one of the sides, you are going to another configuration of the Rubik's Cube, right? The earlier configuration was C1, then you rotate a side, and then you reach to new configuration C2 of the Rubik's Cube. So each configuration can be considered as a node, and rotation itself is a rule, so that rotation will lead you to another state. So that's why I'm saying configuration can also be a node. In the same way, any situation can also be a node. If you go from one situation to another situation, that is a node. That particular situation itself is a node. So we can say that a graph is anything that contains a node, that is a place, state, configuration of some kind or a situation. And we have a rule which actually gives us a way to go from one node to another node. So it means we are not restricted to these kind of graphs where we have these kind of nodes, right? We don't need these kind of graphs where we have a class and we have to create nodes and we have to just go through them like that. We can have a simple array as a graph also. So now let us try to understand how a simple array can also be a graph. Suppose you have an array of integers, okay, a simple array, and from any index in that, you can only go to 2i plus 1 index or 2i plus 2 index. Great. So we have this array of integers and we have this rule that actually only allows us to go to 2i plus 1 or 2i plus 2 indices. So let's try to create an array. I will have 1, 3, 2, 9, 8, and like just say 10. Okay. And the indices for these will be 0, 1, 2, 3, 4, and 5. Great. So now we can consider these as places, right? So 1 is at 0th place, 3 is at 7th place, 2 is at 2nd place, then 9 is at 3rd place, then 8 is at 4th place, and 10th is at actually at 5th place, right? So these are like places. And since these are like places, we can consider them as nodes. So the 0th node contains a value of 1. Do you understand this thing? So let's try to draw this thing also. So I will first of all try to draw the 0th node. So I will have a node and in that the value will be 1. Why? Because the 0th node contains the value 1. Then from this 0th node, this index, I can go to 2i plus 1 or 2i plus 2. So here I is what? I is 0, right? The index is 0. So 2i plus 1 is what? 2 into 0 plus 1, 1. And then 2 into 0 plus 2 is simply 2. So it means we have a rule that is saying that we can go from this place to this place only. So I will have an edge that is going to this particular node. That is a node at one position and this node contains a value of 3. So I will write it like this. Similarly, I will have an edge from one to another node that will contain a value of 2. So we have gone through these two nodes, right? Now I will shift and we can say I is now at first position. So now where can we go from first position? We can go to 2i plus 1 and 2i plus 2 again. So 2 multiplied by 1 plus 1 is 3. So from first position I can go to third position, right? So I will simply say, okay, from this node I can go to a node whose value, the value here is 9. So I created the third position node here with the value 9. Similarly, we can go to another node which is 2i plus 2. So 2 multiplied by 1 plus 2 is 4th. So we can reach this 4th node also, right? And the value of the 4th node is 8. So it means from this node I can reach another node whose value is 8. Great, right? And now we have reached all the nodes that we could reach from this particular node. Now we can shift the I to this position and we have I equal to 2. So what is now 2i plus 1? So 2i plus 1 means 2 multiplied by 2 plus 1. It means 4 plus 1, that is 5. It means you can reach the fifth index from the second index. So I will create another edge from this node to a node whose value is 10 because the value of fifth node is actually 10, right? Similarly, we will have 2i plus 2. So 2 multiplied by 2 is 4. 4 plus 2 is 6. Now we don't have a 6 here. So it means we only have one edge from 2 to 10 here. So now we can also shift I again here on this particular position. And now we have I is equals to 3. 2 multiplied by 3 is 6. 6 plus 1, 7. But we don't actually have 7. It means this node does not exist. Then we can go to 2i plus 2, which is 2 multiplied by 3 plus 2, 6 plus 2, 8. So we don't have 8th node also, right? In the similar way, if you increment I to 4th position or 5th position, we will not have any more nodes that we can connect. So it means we were able to create this particular graph with the help of the rule that was provided to us and the nodes that were provided to us with the help of this integer array. So here also a graph is nothing more than a node, which is basically a place or position in this case. And then we have this rule that allows us to go from one node or one place to another position or place. So are you able to get an idea how anything can actually be considered as a graph as long as there is a node and there is a rule? Because we were able to create this entire graph with a simple array. Let us take another example. Here we are saying that we have an array of integers and the ith integer tells the maximum possible jump we can make from that index. Okay, so we will basically have an array like 1, 3, 7, 9, 10, right? Something like this. And we are saying that this number 1 is telling us how big of a jump we can take from this index to the next index. Since it is 1, so we can only take a jump of length 1, which means we will only land on 3. But here we see that we have a 3 index, right? So we can take a jump from 3 to 7. We can take a jump from 3 to 9, or we can take a jump from 3 to 10 because the maximum length of the jump can be 3. Similarly, from 7 we can jump to 9. We can also jump to 10. But we cannot jump anymore because we are getting out of the array. So it means we can only access this and this using 7. Similarly, from 9 you can only go to 10. So let us try to put the indices also 0, 1, 2, 3, 4. And here we don't actually have much use of the indices because we are actually dealing with these elements themselves. So if I try to create a graph, I will have a node with 1, and the number 1 means that the maximum jump we can take is from this position to next position. So it means that 1 will have an edge from itself to another node, which is 3. Now let us look at this 3. So the 3 allows us the maximum jump length of 3. So I can go to 7, 9 and 10, which means I will have 3 edges from 3. So I will have an edge from 3 to 7 because I can reach 7 from 3. Then I will have a 3 to 9 because I can also reach 9 from 3. And then I can have an edge from 3 to 10 because I can also reach from 3 to 10. Then we will have this 7. So where can we go from 7? 7 allows us to have a maximum length of 7 indices. It means I can go from 7 to 9 and I can go from 7 to 10. It means I will have 2 edges from 7. First of all, I will have an edge from 7 to 9, which is this one, and then I will have another edge from 7 to 10, which is this one. I hope you are able to see the graph taking shape. Now let us go to this. So 9 have a maximum jump length of 9 places, which means we can go to 10 from 9. Of course, we can no longer go to any other place because everything else is out of bounds. These things do not exist, right? So we can only go to 10th. So it means we will have an edge from 9 to 10. So I will simply create it like this. Now understand one thing. I can only go from 1 to 3, right, in this direction. It means I have a directed edge. We are not allowed to go back. We are only allowed to jump forward, right? So I have a directed edge from 1 to 3. I can go from 1 to 3, but I cannot go back from 3 to 1. Similarly, we can go from 3 to 7, but I cannot go back from 7 to 3 because we can only jump forward. In the same way, I can go from 3 to 9 and 3 to 10. In the same way, I will be going from 7 to 9 and 9 to 10. This is basically an example of creating a directed graph using simple array and a rule. So the node here can be considered as a state. You are going from one state to another, and the rule here is jump length. So jump length is actually the rule that allows us to go from one state to another. And note that even though this rule is allowing us from going from 1 to 3, it is also restricting us to go from 3 to 1. We are not supposed to go to 3 to 1. In this earlier example also, we are only supposed to go forward. It means these are also directed edges. They are not two-way edges. And from the graph, you can also notice that it is a simple tree. So a tree is actually represented by this condition, 2i plus 1 and 2i plus 2. So a tree is actually represented inside of an array with the help of these conditions, the 2i plus 1 and 2i plus 2 conditions. Now here is another very important example, that is two-dimensional grid. So we are saying that we have a 2D grid with the dimensions m multiplied by n, and we can only go up, left, right and down from any cell in the grid. Now suppose that we have this particular grid and we want to start from this particular cell. So how are we going to represent this cell? Well, we can use the row number and column number to represent it. So it is at row 1 and column 1, right? Now I can only go up, left, right and down. So it means let's just try to create a node here. 1 comma 1. This represents this particular cell. Now I can go up, right? So if I want to go up, I will simply subtract 1 from the row number to go up, right? So it means that I will have an edge from 1 comma 1 to 0 comma 1 also. Why? Because 0, comma 1 represents this particular cell. Great, right? Now, if I want to go to the right direction, what is the coordinate? Well, in order to go to the right, you need to add 1 to the column number, right? So I will simply add 1 to the column number. So I will have the row number same and the column number will simply become 2. So that's how we will be able to reach this particular cell. And so if I want to go to this cell, I will have to subtract 1 from column number. So it will become 1, comma 0. So I will have another edge from 1, comma 1 to 1, comma 0. Now if I want to go down, how will I do that? If you want to go down, you will have to add 1 to the row number. It means I will have another edge from 1, comma 1 to 2, comma 1. So the row number is 2 and the column number is 1, which is this one. In a similar way, we can go to 0, comma 0 from here. So I will have an edge from 0, comma 1 to 0, comma 0, correct? And I can go to 0, comma 2. So I will have another edge from here to 0, comma 2. Now here's one thing. I have 0, comma 0, right? And from 0, comma 0, I can go to this 1, comma 0 also. Why? Because 1, comma 0 in the downward direction. So I will have an edge from 0, comma 0 to 1, comma 1. And in the same way, we can keep on creating this graph. So in the similar way, I tried to create the entire graph. So as you can see here, that we were able to convert this two-dimensional matrix into a graph because we had two things. We had nodes, and nodes in this case represent these particular states, or you can say positions, or you can say place. So these are represented by nodes. And then we have a rule. The rule is saying that we can only go up, left, right, and down from any cell. That is why we have this particular graph. If we also allow the diagonals, so it means I can go to the diagonal directions also, this graph will become very, very big and very complex. But even then, we will be able to represent this grid with the help of a graph. So I hope that you are actually getting a sense that anything can be a graph as long as you have nodes and you have rules that govern how you can go from one node to another node. So now let us talk about breadth first search, or BFS. BFS is a way for us to go through each and every node in a graph. Suppose I have a graph like this. Now it may look like a tree because trees are also nothing more than special versions of graphs. But here you can start from any node. In trees, you will actually have a node like this, head node, and you will start from there. But in graph, you can start from this node, you can start from this node, you can start from this node also. So that's why we are calling it a graph. So you can use BFS to start from any node and go through each and every node in this particular graph. So how does BFS work, right? Well, BFS requires some initial configuration. First of all, we will need a queue. So we will have a queue like this in which we will store nodes. Queue is a data structure that follows first in, first out principle. We have a FIFO principle. So whatever you place inside of it first, that will be the element that will get out of it the first as we pop it. So whatever goes inside of this queue first will also come back first. So let us number these nodes as 1, 2, 3, 4, 5, 6, and 7. So I'm starting from this node. I will take this node and I will put it here. This is the initial configuration what we are doing, okay? We will have a queue. We will first take the starting node, we will put it into the queue, and then we are going to start the BFS. Now in the BFS, what you do is you take out the node from the queue. Now you can do whatever you want to do with the node. You can actually just console log it, you can perform some operations, or whatever you want to do. After you have done whatever you wanted to do with the node, you will use the rule that is given in the question to figure out what are the neighbors or what are the other nodes connected to this first node. And then you will find those nodes and you will place them inside of this queue. So here I can see that 1 is connected to the node 2 and node 3. Now I have already popped 1. So queue does not have this node 1. But after doing these operations, I will be putting 2 and 3 inside of this queue. So 2 will come here and then 3 will come here. Now I will again pop a node from the queue. This time the 2 will be popped because we entered the 2 first. So 2 will be popped. Then we will also again do operations. And then we will find the neighbors based on the rules provided. And then we will place them inside of the queue. So 2 has the neighbor 4 and 5. So I pop the 2, I perform the operations, and then I will place 4 and 5 inside of this queue. Now 2 has been done, right? It's already popped out, so it will no longer be in the queue. Now I pop again. This time 3 will be popped because it was placed before 4 and 5. So 3 popped. We perform some operations on this 3. Then we again use the rules provided in the question to find the neighbors. And then we place those neighbors, that is 6 and 7, inside of this queue. So 6 will be here and then we will have 7 here. And now the 3 is popped. So 3 no longer exists in the queue. Now we have 4. So we will take out 4, we perform operations, and we try to find the neighbors for the 4 based on the rules given in the question. We see that we don't really have any neighbors anymore, so we do nothing. We just pop this one and we are just done with the 4 now. We will have 5. 5 will be popped, same. 5 don't have any neighbors. So whatever you want to do with this node, you do it, and that's it. 5 is done. Similarly, 6 will be done, and then 7 will be done because they also don't have any neighboring nodes. So this is how the logical workflow of BFS works. Let me show you the code. So here is the BFS function that will go through each and every node inside of a graph. So we have the start node, and from this node, we are going to start our BFS traversal. So first of all, we have this queue, and inside of this queue, we are placing the start node. This is part of the initial configuration. And then we have something called visited set. Now the reason we use visited set is because one node can be connected to multiple nodes. So suppose that this fifth node was actually connected to the first node also. So when we were actually taking out fifth node, we were performing operations and we were trying to find the neighbors. We will find this first node as a neighbor, but are we going to add this one node again into the queue? Are we going to do that? No, we are not going to do that. Why? Because we have already traversed the one node. If we add it again, we will end up traversing the entire graph from one to the last node again. It will be an infinite loop. That's why we have something called visited set. So in the visited set, you will store the nodes that you have already visited. For example, I placed one in the queue, right? So when I place one in the queue, I will also place one in this set so that I will know I have visited the one node, and if any other node have one as its children, I will not add this one node again into the queue. So that's why we have this visited set, and we are putting the start node inside of this set so that we will not end up actually adding this start node again in the queue. Now here the BFS actually starts working in this while loop. So what we are doing is we are checking if the queue is empty or not. So we are going to run the BFS while the queue is not empty. First of all, we will pop the node. Okay, so we have the current node. We will take the queue and pop the node. So initially we had one in the queue, right? So one will be popped and we no longer have one in the queue because popping the element simply removes it from the queue. We pop the one we store in this particular variable current node, and then here we can do whatever we want. Currently we are just printing the current node, but we can do whatever we want with the node. Now after this step is done, we are checking for all of its neighbors. So here the graph is basically the adjacency list. From this adjacency list, we are taking out all the neighbor node for this particular node, and we are checking if that neighbor is already visited. If it is not visited, we will add it into the visited set, and then we will add it into the queue also, so that next time we will be popping this particular neighbor. This is the step where we actually add 2 and 3. Now once this is done, we will again go back to this while queue. We will check if queue have some element or not. Well, yes, it does have these 2 and 3. So we will again go inside of it. We will pop the node. This time 2 will be popped. So 2 is no longer in the queue. We have popped it, and now we are printing the 2 and then taking all the children of 2 and putting it inside of this queue again. And in the same way, we can go through entire graph. Now, one thing to notice is that in the BFS, part from here to here will be basically the same. Okay, it's not really going to change all that much. But this part, the place where you are actually taking the children and placing it inside of the queue, that can change. The main logic will actually not change. You will place the neighbors inside of this queue, but how you are going to do that can change. Because currently we have this graph adjacency list, and that's why we are doing this particular thing. But adjacency lists have a rule, right? Because of which we are able to find the nodes connected to a particular node. What if the rule changes? What if we don't have the adjacency list? What if we are given an array and we have a rule that from any index you can go to 2i plus 1 and 2i plus 2? The same example that we saw earlier. What will happen in this situation? Now let us try to see how we can actually use BFS inside of this array, which represents this graph based on these rules. So we will again do the same thing. We will have a queue, and inside of it, we will place the starting node. Suppose we start with 1. Okay, so we place 1 here. The queue contains 1. And we will also have visited. So visited will contain the 1 at this point, and then we will have this while loop where we are checking whether queue is empty or not. So if queue is not empty, we will go inside and we will take the current node. So we have popped the queue, right? So it means current node right now is 1. We have the current node, and this 1 is actually no longer present in the queue. We have popped it. Okay, and here I can do whatever I want with the node. I will simply print it here for simplicity's sake. So I have printed the node, and now it is time to actually take the children of this node and place them inside of the queue. So how will I do this in this case? Because I don't have an adjacency list here. I simply have these conditions, right? So in these kind of situation, you will actually have to calculate the neighbor nodes yourself. Why? Because you don't have a list of neighbor nodes. You just have a condition that will tell you which are the neighbor nodes. So you will use these conditions to calculate it. Okay. So I will use this condition to calculate the neighbor one. Now neighbor one will be equal to 2 into I plus 1. Correct? Neighbor 2 is equal to 2 multiplied by I plus 2. Right? Now, one thing is that we don't have I right now, correct? What this means is that in the node, storing 1 is not enough. We need to store its index also. So a node will look like this. We will have index 0 and we will have the value that is present at the index. So a node will be like this. So when we are popping it, the current node will actually have two things. Okay, it will have 0 and it will have 1, right? So we can take this 0 into a variable called I. So I will be equal to and then 0. I can store this current node as 0 comma 1 inside of a node, right? I can store it as a list also. So that's why I'm using the index 0 to represent that I want this particular part of this stored list. Now I have I, and then I will simply calculate. So n1 currently is going to be 2 multiplied by 0 plus 1. So 2 multiplied by 0 plus 1 is what? Simply 1, right? So I will get this particular index 1 and I will store the value. And I will actually have to store these two things inside of the queue. Similarly for n2, we will have 2 multiplied by I, which means 2 multiplied by 0 plus 2, which is basically the second index. So I will have this stored in the queue. How will I do this? I will simply say queue dot append. Then I can append a list inside of the queue. I will say I want to append n1, which is basically the index of the element that we want to append. And then I can say nums of n1. So what we are doing is that we are taking the index and the value present at that index in the given nums array, and we are storing this inside of the queue here. So the queue will contain 0 comma 1 also. Similarly, we can do the same for n2. Queue dot append n2 and then nums or the element at n2. And this will also be stored inside of this queue. So the queue will now contain one more element, that is 1 comma 2. And the queue is basically this big right now. And in the next iteration, we will end up popping 0 comma 1 in this current pop, and then we will just repeat the same entire process again to store the new neighbors. Now understand that here you will actually have to check if this particular n2 is actually present in the visited or not. If it is not present in the visited, then only you append. So it means the condition will be like this. So if n1 is not visited, then only you append it. So if n2 is not visited, then only we append the n2 element inside of the queue. So I hope now it is getting clear to you that if we don't have adjacency list in the question and we only have these conditions or these rules, then we are supposed to use these rules to calculate the neighbors and then store them in the queue. So now let us try to understand how we can actually implement BFS on jump game example. So in the jump game example, we had this kind of array, and due to this array, we were able to create this kind of graph. In the jump game, what we are simply doing is that we will take this value and we will know how many jump we can do, the length of the jump. Since it is 1, it means we can only go to 3 because the length of the jump is 1. But if we are at 3, we know that the maximum jump length that we can have is 3. So we can go to 7, or we can go to 9, or we can go to 10. Why? Because we have maximum jump length of 3. That's why in the graph 3 have edges to 7, 9 and 10. So jump length is the rule for figuring out the neighbors here. So here I'm doing the same thing as we did in the earlier example. We have the queue here, we have the visited here, and we are starting the while loop. Now I am popping the node here. So it means 0 comma 1 has been popped. It is no longer in the queue. Now here I'm printing this value 1 by accessing it from the node. And then I'm accessing this index 0 with the help of this I variable from the node, because I is going to be used to figure out the next neighbors. So we know that the maximum jump we can make is the value of the element itself, right? What we can do is we can actually start a for loop that will run from 0 to the jump length, and the jump length is simply node 1, right? Because in this index we are storing the jump length, the element, right? So we will simply have this for loop, and the 0 is going to be k equal to 0 because we are going to use k variable inside of the for loop. So what we will do in the for loop is we will calculate the neighbors of the current node. So I will have a variable neighbor is equals to the index I, which we calculated here, and then we will add k. In the starting, the k will be 0, it will return us I, which means the k should not start at 0, it should start at 1, so that we will not get the I back. Now the index at the starting was 0 because this is the element that we actually popped out. 0 plus 1 is what? 1, right? So what we will do is we will simply say q dot append an index and the value at this index. So this is how we are going to add this thing. This is basically a list. So we are going to add this thing inside of this queue, which means we just ended up adding 1 and 3 inside of this queue. So we will have 1, 3 here. Now in the next iteration, the k will become 2. But this thing is basically 1, right? So we are only supposed to run the loop till the maximum limit of 1. So it means as soon as the k becomes 2, this loop will end and we will go back to this while loop. We will check if the queue is empty or not. Since it is not empty, we will again go here. We will pop the 1 comma 3 here. Now we have 1 comma 3 in the node. We will print the 3. The element 3 will be printed, and then we will have this I. The I in this case will be what? 1, right? So the I will be 1, and then again we are going to start the for loop from 1 to this 3. So in the for loop, we will have I is equals to 1 and the k will be 1. So 1 plus 1, 2, right? So we will have this particular element 2 comma 7. We will store it inside of this queue. Then the next iteration will happen. In the next iteration, the k will be what? K will be 2, right? So 1 plus 2 is equals to what? 3. So we will have 3 comma 9 inside of this queue. So in the next iteration, we will have k is equals to 3. 3 plus 1 is equals to 4, right? It means we will end up storing this particular index or this particular node inside of the queue. So we will have 4 comma 10. And now this loop has been run 3 times. So this for loop will end. And now after ending, we will go back to this while loop. We will pop the 2 comma 7. We will calculate its neighbor. We will put them in the queue. The same process will repeat for all these nodes. So in this way, we are using the given condition of jump length to calculate the neighbors of a given node. Now, of course, there are a few checks that I've skipped. So before appending something into the queue, you need to check if it is already existing in the visited or not. So you will have a if condition checking if n is already in visited or not. If it is not in the visited, then only you append it. That is a very small thing that you can figure out on your own. Now we will try to perform the BFS on 2D grid and see how we can calculate its neighbors. So first of all, we are going to start from this particular cell, the middle cell. That's why I have placed the 1 comma 1 inside of this queue. Now we have the visited set. So visited will also have 1 comma 1 in the earlier stage. And now we are starting the while loop. So while the queue is not empty, we are going to pop the node. So node will be popped and then we are getting row and column. So this node has been popped. It is no longer in the queue. The row will be 1 and the column will also be 1 at this point. So it will be equal to 1 and 1. So row is 1, column is 1. Now we have to find out the neighbors of this particular node, particular state or this particular place. Then what we can do is we can use the given condition. In the original example that we discussed earlier, we could only move up, left, right, and down. These were the only 4 directions in which we could move from a given cell. So it means at maximum we can have 4 edges from each node. So we will calculate the node at up direction. So I have row and column. If I want to go up, then I need to subtract 1 from the row. Then I will say the up is row minus 1, comma, original column. So column will not change. Similarly, right will be equal to, well, in case of right, I need to go from 1 to 2. It means I will need to increase the column number, right? So I will simply have row as the same and C, the column number will be increased by 1. Similarly, if I want to go to left, the column number will decrease. The row number will be same, the column number will become C minus 1. Why? Because going from 1 to 0, I need to decrease 1. In the same way, I can also calculate the down direction also. So for the down, I will simply increase the row by 1 and I will keep the column as same. So these are the 4 nodes that I will have available to me to place in the queue. Now, of course, I will check whether these nodes are actually existing in the visited or not. But if they do not exist in the visited, we will simply take them and place them inside of this queue. Simple, right? We are using the given condition inside of the question to actually calculate the possible neighbors. So all these nodes will be placed inside of the queue, and then you can simply use q dot append up, q dot append right, q dot append left, q dot append down. That function will change from language to language. I'm using Python, so I can use append function. But you see the function that is present in your language for you. Now here is one topic that you need to understand about BFS. In BFS, we are going from level to level. First, we will take all the nodes on this level, the level 0. Then we will take all the nodes on this level, the level 1. And then we will take all the nodes on this level, level 2. But right now we don't have any way to figure out whether the node that we popped from the queue is actually at level 1 or at level 2. So how can we figure that out, right? So here we have our normal BFS. We are starting from this node. So we will store 1 here already. Then we will have 1 here already before starting the while loop. And if you notice, the length of the queue currently is what? 1, right? Currently, there is only one element inside of the queue, so the length is 1. And we will be always sure about it because we are going to start with a single node always. So it means the 0th level will always have one node. So to track the level that we are currently on, we can have a variable like level and we will initialize it with -1. Okay. Now, as soon as we get inside of the queue, we will simply increment the level by 1. So level will be level plus equals 1. So level at this place right now is 0 because earlier it was -1, right now it is 0. And now here is the main thing. Right now we are taking just one element from the current level and we are doing it, right? Which is fine because there is only one element right now. So we take one and we just take all the children of the one and we append them here. Okay. So 2 and 3. But if I try to run this loop now, we will have 2 at this point, correct? So this loop will only run for 2 and then we will again go back to while loop. And once we go back to the while loop, we will take the 3 out and at this point, we will again increment the level by 1. So level actually will become at this point 2. But we are still traversing the elements of level 1 only. So what do we need to do? We need to actually take all the elements present in the queue and we need to run the for loop together for all the elements. Then only we will come back to while loop. So to do that, we will have another variable current length of queue. Okay, so in this current length of queue, we will calculate the length of queue that we currently have. So it will be equal to len queue and then we will use this variable to place everything here into a for loop. So we will run from 0 to current length of queue so that all this logic will run for every single element that is currently present in the queue. And once we have covered all the elements, then only we will go back to the while loop and then only we will actually increment the level. So level will not be incremented here. It will be incremented before this for loop here in the while loop. So level will be incremented here after the while loop and before this for loop. So level will be level plus 1. And now the level will be properly updated each time. So first we will get to this node. We will run this for loop for this particular length, that is one length. It will run, we will increment the level by 1, so it will become 0. And then we will have 2 and 3 inside of the queue. We will get back into the while loop. We will be inside of the for loop and we will run this for loop for both of these elements. So it means we are going through all the elements of the current level before going back to the while loop. And that is how you are going to track the level that you are currently on in a BFS. I know it may be a little messy, but you will have to practice on your own to understand these kind of things. DFS and call stack hurts my brain. We can easily solve this problem with the help of BFS iterative solutions. Hello everyone, let's solve some LeetCode today. So today we have LeetCode 104, that is maximum depth of binary tree. In this problem, we have been given the root of a binary tree and we have to return its maximum depth. A binary tree's maximum depth is the number of nodes along the longest path from root node down to the farthest leaf. It simply means that if we start from the root node, which of these leaf node is actually the farthest node from the root? We can see we have this node and this node which are farthest from the root nodes. So either this length or you can consider this length to be the depth of the tree because both of them are actually at the same level. So the most common way to solve this particular problem is simple DFS, that is depth first search. What you do is simply go to each and every branch once and go through those branches and then just count how many nodes you encountered, and from all these particular paths you can say which one is the longest path and you simply return the length of that path. But it requires you to understand recursion and call stack concepts, and these concepts really hurt the brain of beginners. So we can easily solve this problem by another method, that is BFS. This is an iterative solution. It does not have any call stack or recursion. BFS algorithm actually travels the entire tree level by level. This is first level, then we have this second level, and we have this third level. So you can see that the depth of the tree is simply the number of levels that we have in the tree. So we will go through all the levels and we will simply at the end of the day return how many levels we traveled through BFS, and that will be our answer. So let us understand concept wise how the BFS really works. First of all, we will have a queue in which we will put the nodes. First, we are going to traverse through the first level. So I will simply in the starting take this node and put it here. Now we will have a while loop in which we are checking whether the queue is empty or not. If it is not empty, we will continue this while loop. So in the while loop, first of all, I will take the length of the queue because this length will tell me how many nodes are actually present on the current level that I'm trying to traverse. So I'm trying to traverse this particular first level and I have placed this node in the queue. So first I need to take the length. So here we are storing the number of nodes on the current level by taking the length of the queue at this particular instance of time. So we have only this particular node, so we get a length of 1. Now I will iterate over these current level nodes with the help of a for loop. So we are iterating over the current level nodes and then I will start popping the elements from the queue from starting. So once we have popped the element, we know that the tree is gone from this queue. We can cross it. Now the queue is empty. So it means we have traversed this particular level completely. Now we do have to traverse the next level. So we will have to place these nodes in the queue somehow. So we can simply append these nodes in the queue. So here I'm adding the left child and then the right child in the queue. So this queue will now become 9, then 20. Now this particular for loop is now done because this particular thing was equal to 1. So we will exit this for loop from here. Then we will come back here. We will check if the queue is empty or not. It is still not empty. So we will continue. Then we will take the current length. Then we know that the length is now 2. So this thing will simply become 2 now. Then we will start from 0 to 2. First we will pop this particular element 9. Then the children of 9 will be placed inside of it. So right now there is none, no children here. So we can put a check that will only append the elements in the queue if they are not none. Now since they are both none, we are not going to append anything and we will continue. The for loop will go to the next iteration, that is on this element. Now the 20 will be popped in this particular variable and we will have 20 here. Now we will add these elements in the queue on these lines. So we will have now 15 and 7. Now after that we will exit from the for loop. We will come back here. Then we will check if the queue is empty or not. It is not empty. We will again get the number of nodes on the current level. It will still be 2 because there are only 2 nodes in the queue now. And then we will again continue with this for loop. Now in this case they have only none nodes here. It means that nothing will be added in the queue and the queue will become empty after this iteration. So this loop will also exit after that and we have done our BFS traversal. How do we know how many levels we have traversed? So if you notice, this for loop is what helps us traverse the level. So after this for loop, we know that we have traversed one single level and we have appended the elements for the next level. So we can have a res variable here, that is our result variable, and it will be equal to 0. And after this for loop completes, we will simply say res is equals to res plus 1. We will simply update this variable by 1 once this entire for loop runs. And then at the end of the day, we will simply return res as answer. So the res variable will tell us how many levels we have traversed with the help of BFS, and the number of levels is basically the depth of the tree. Now let us go through the code also. Here we have res is equals to 0. It will be the answer that we are going to return. Here we have the queue initialized as empty queue. Now if we are checking if the root is none, it means that the input that we have is itself none. We can return 0 because there is no depth in a null tree. This is where we are setting up our BFS. We will add root into the queue and then we will start the while loop. While the queue is not empty, we will take the number of nodes on the current level and then we will iterate over each of these nodes. We will pop the element from the queue and then we will add its left and right child if they exist. Now once this for loop is done, we know that we have traversed through one level. So we will simply update this res variable here. Now after this entire while loop completes, we know that we have traversed all the levels. So we can simply return our res variable. Now let us run it and see what happens. So yes, everything is passing and it's a pretty efficient solution. Now let's talk about the time complexities of this particular solution. The time complexity for this solution is order of n. Even though we have nested loops, it is still order of n. Why? Because we are only going to traverse each and every node once. That's it. What this means is that the for loop and the while loop together will run at most n times only. So that's why it is order of n time complexity. In terms of space complexity, this solution is order of n too, because we are using a queue to store the node that we want to traverse later on. So the queue might actually store n nodes depending on the configuration of the graph. So today we have LeetCode 994, that is rotting oranges. In this problem, we have been given an m by n grid, and in this grid we will have 0, 1 or 2 number at any given cell. 0 represents an empty cell, there is nothing there. 1 represents that there is a fresh orange there, and 2 represents that there is a rotten orange there. And every minute, any fresh orange that is 4 directionally adjacent to a rotten orange becomes rotten. So the fresh oranges are actually becoming rotten if they are adjacent to the rotten oranges. And then we have to return the minimum number of minutes after which no cell has a fresh orange. If this is impossible, return -1. So it means there can be cases where we actually get a fresh orange which does not become rotten in any case. So LeetCode has also given us an example. We have a rotten orange here and all of these oranges are fresh. So at minute 0, there is only one rotten orange given by the question itself. After minute 1, the adjacent oranges, the 4 directionally adjacent oranges, actually become rotten too, right? Remember that it is not working diagonally. So diagonal oranges are safe. It means the 4 direction simply means up, left, right and down. There is no diagonal edges. Now at minute 1, we have these bad oranges. At minute 2, the oranges adjacent to these bad oranges also become bad. So this and this orange is now rotten. On minute 3,
this orange is also now becoming bad because it was actually adjacent to this one, right? So this is now bad. And on a minute 4, all the oranges are now bad. This one become bad because it was adjacent to this one. So at minute 4, all of these oranges are bad or rotten. So we will simply return answer as 4. So suppose that we have this 3 by 3 grid with the oranges. Now this problem can actually be solved as a graph problem. Well, it's a grid, right? It's a 3 by 3 grid, and each of these cells actually represent a state or a place or a position. So we have a state, place or position, right? And in the question we have found a rule that is saying you can go in 4 directions from any given cell, which means we have a node and we have a rule that actually allows us to go from one node to another node. So let us try to draw this graph. Suppose we start from the middle cell. This middle cell is what? This is 1 comma 1, right? The coordinates of this cell is 1 comma 1. So we will have a node like this, 1 comma 1, representing the middle cell. Then this middle cell can actually reach this place or this place, right? So we can say we have an edge from 1 comma 1 to 1 comma 0, and we have an edge from 1 comma 1 to 1 comma 2. Similarly, we can go here also and here also, right? So we have an edge from 1 comma 1 to 0 comma 1, and we have an edge from 1 comma 1 to 2 comma 1. In the same way, from 0 comma 1 you can go here or here. So you will have an edge from 0 comma 1 to 0 comma 0, and you will have an edge from 0 comma 1 to 0 comma 2. In the same way, from 2 comma 1 you can go in this direction or in this direction. So you will have an edge from 2 comma 1 to 2 comma 0, and you will have an edge from 2 comma 1 to 2 comma 2. And then from 0 comma 0 you can go in this direction and reach this place, right? So you will have an edge from 0 comma 0 to 1 comma 0. Similarly, from 1 comma 0 you can reach 2 comma 0. Similarly, from 0 comma 2 you can reach 1 comma 2, and from 1 comma 2 you can reach 2 comma 2. So this is how the graph will actually look like for this particular grid. If you have any issues in understanding how we are able to create a graph out of a grid, please watch my video in which I am explaining everything about graphs, how you can convert anything into a graph. I will provide link in the description, or you can see a card popping somewhere here in the video. So now that we know we can solve it as a graph, let us try to solve it. Suppose we have a bad orange here. So this orange is a bad one. Now we can use two things. We can use either DFS or we can use BFS. If I try to use DFS, and I go in the depth, then I can reach here. So on minute 1, I will be making this orange bad, right? On minute 2, I will reach here. I will make this orange bad. On minute 3, I will reach here. I will make this orange bad. On minute 4, these oranges will also become bad, which works fine. Our answer right now is 4. But the DFS solution will break as soon as we have more than one bad oranges. Suppose I make this orange bad also. Now I run the DFS on this side. So I will go here. This will become bad. Then I will go here. This will become bad on minute 3, right? On minute 2, sorry. Then I will go back and then this will become bad. But this is where the issue is. Why is this becoming bad at this point? I had to go from here to here on minute 1, then here to here on minute 2, then here to here on minute 3. So this orange is actually becoming bad on minute 3. But we already have a bad orange here, right? This is a bad orange. It means this bad orange must have made this orange bad on minute 1. And this is where the DFS is breaking. This is exactly the reason why we cannot use DFS, because we can have multiple bad oranges resulting in multi-source DFS, and that multi-source DFS is not actually giving us right answer. There are places where you can use the multi-source DFS, but not in this condition, because you need minimum time to make all the oranges bad. And whenever you have something like minimum, the best approach is to use BFS. Why? Because BFS goes from one node in all of its children node and make them bad at the same time. Then it goes to all of their children nodes and make them bad at the same time. It is going level by level. That means it will reach all the nodes in the minimum time. So how are we going to solve this question with the help of BFS, right? We will first of all have a queue, and inside of this queue, we will place all the bad nodes or all the bad apples or all the bad oranges in the starting. So we have this orange bad and this orange bad. These are basically 0, 0 and 0, 2, right? So we will have 0, 0 and 0, 2 in the starting in this queue. Usually we start with only a single node, but since we are starting from both of these nodes, we will have both of these in the queue in the starting itself. Then we will run a while loop. In this while loop, what we will do is we will find out the length of the queue currently. So length of the queue is basically len queue. So currently the length of the queue will become 2, right? So we will have currently 2. Then we will also have a time variable. So we will have time. Suppose I'm setting it to 0 initially. And now here I will simply make the time plus 1. So I'm incrementing the time here. I have these bad oranges and I'm starting to increment time. Basically I'm going to their children, right? And right now we have to process these two nodes, these two bad oranges at the same time, and then only we can actually have all of their children in the queue here. So we will have a for loop, and this for loop will run from 0 to the length. This is the length of q, right? So we will run this for loop for all of these nodes, and now we will start popping oranges. We will pop the first orange. We will simply say orange is equals to q dot pop, or whatever function you need in your language. Then we will get this particular orange, right? So we will have like 0 comma 0 here. And now I'm not writing code because it will become very long. So here I'm saying now add all of x children in queue. So you pop the orange, you will take all of x children and place it in the queue. So we will have all the children here. And when we are placing the children, we can have a visited set. We can either store the children in the visited set also, so that next time if some other orange is connected to other orange, we will not visit that orange again. This is a simple thing in BFS. If you understand how BFS works, you will know the visited. And so we also mark them as visited. So we place them in queue, we mark them as visited. And also one thing that we need to do is we need to reduce the number of fresh oranges that we have. So somewhere in our code, we need to maintain a variable fresh oranges. In this variable, we will contain all the fresh oranges that is present in the 0 time. So when we are starting out, we have 1, 2, 3, 4. 4 fresh oranges. So in the starting, we will have 4 here. And here we will keep on decrementing the oranges as we keep on popping the bad orange and make its adjacent sides or make its children bad. We will keep on decrementing this fresh orange count. And since we are using BFS, guys, I will end up placing this node in the queue. This will be in the queue, and since this is also a bad node and I'm actually making sure that I'm running a multi-source BFS, I will take this node also and place it in the queue, which means I have 2 nodes which are actually becoming bad at time 1. And now once I have gone through these 2 oranges in my this for loop, I will go back again in the while loop. I will take the length of the queue again, because these 2 will be gone. These 2 will be popped out. We will only have children of these 2, right? We will take the length again and we will increment the time. So it means the time at this point is 2, which is correct, right? On time 1, these 2 became bad, and then on time 2, these 2 will become bad, which is correct, right? So this is how the BFS will work. Now, one thing you might be thinking is, why do we have this count of fresh oranges? The reason we have it is because we want to make sure that after running all the BFS, if we are left with any orange, any fresh orange, we will return -1, because that is written in the question. If there is any fresh orange, we will have to return -1. Otherwise, we will return the time. So that is why we are keeping track of the fresh oranges and decrementing them as we go in the BFS. Here is an example where we can end up with a single fresh orange. So here we have 2 bad oranges, this one and this one, right? This bad orange will actually turn this orange bad, right? But after this, even if we go in any direction, here or here or here or here, we will not get any more bad oranges, right? Because there is no orange there. And it means that this orange, which is completely isolated, will stay fresh. And it means the count of fresh oranges will be 1 at the end, which means we still have a fresh orange. So we will end up returning -1. It is impossible to make every orange bad or rotten in this example. Now you might be thinking about how we are going to do this. How are we going to find out all of the children and mark them as visited? Well, we are going to use this graph, this particular graph, to find out which coordinates are basically the children, and we will just place them in the queue, and that's it. If you don't understand how this works, please watch my video on BFS and graphs, where I have explained completely how you do these kind of things. Graphs are super simple if you understand what they really are. So now I believe this much explanation is enough, and we are going to go in the code. So here is the code. First of all, we are starting with the queue as empty. Then we have a visited set in which we will keep all the nodes or all the oranges that we have already visited. Then we have this fresh oranges variable that will keep track of how many oranges are fresh. And here we are going through each and every cell of this grid. We need to find out 2 things. First of all, which nodes or which cell actually have bad oranges. 2 means bad oranges, and which cell have good oranges, the fresh oranges. So what we are doing here is we are figuring out the bad oranges or the rotten oranges, and we are placing them inside the queue, and we are making them visited already. And if we get a good orange or a fresh orange, we are increasing the number of fresh orange count in this variable. So we are basically setting up this initial configuration to start running BFS. Now here is a productivity check. If you find that there are no fresh oranges in the starting itself, every orange is a bad orange, or there is no orange in the grid itself, you can simply return 0. There's nothing to do, right? No need to run a BFS in this case, right? But if we do have fresh oranges, we will start running the BFS. So here I'm starting with the time equal to 0, and then I'm saying while the queue have some elements, first of all I'm increasing the time. So on time 1 this is going to happen. First of all, I'm going to take the length of the queue at this current time. So at this current time, the length will represent the number of elements in the queue. Then for this length, I will run this for loop. Now in this for loop, I'm popping the element from the queue So I'm using the pop 0 because I'm simply using a list in the Python. So in order to pop from the start, you need to use this 0. So I will have the row and the column. I'm simply representing them as I and j. Then I know I can go in 4 directions from this particular cell. So I can go in up, left, right, and down. So that is what I'm calculating here. In order to go up, I will simply subtract 1 from the row. In order to go left, I will simply subtract 1 from the column. In order to go right, I will simply add 1 to the column. And in order to go down, I will simply add 1 to the row. This is basic grid operations that you should know. And once we have figured out all these places where we need to go, we can actually start adding them inside of the queue. And now that we have all these edges, we can figure out whether we can add them in the queue or not. Now that we have all these cells, we can go to, now we will try to add them in the queue. We can only add these cells based on a certain condition. First of all, these cells should not be out of bounds. If they are out of bounds, we cannot add them, right? Then second condition is that if they are already in the visited set, we cannot add them. We have already visited them. And the third condition is that there should be a fresh orange on these cells. If there is no orange, why do we add them, right? So that is exactly what we are checking. In case of up, we need to make sure that this first element, the I-1 that we are changing, is greater than or equal to 0 because we are going up, right? So in the up condition, we might actually become negative. So that is why we are making sure it is within the bounds of the grid. Then we are checking if there is a fresh orange in this particular up cell or not. And then we are checking that if up is not invisited, then only we go ahead and reduce the count of fresh oranges by 1. We append the up in the queue and we append the up in the visited set. The same thing we do for left, right, and down. So for left, we are making sure that the column is greater than or equal to 0. And these two conditions are same. Then for right, we are making sure that the column is less than the end of the grid, that is maximum length of the grid. And then these two conditions are basically the same. And then for the down, we are making sure that the row is less than the length of the grid. So these conditions are making sure that the given cells are within the bounds of the grid. Otherwise, we will go out of bound and that is not what we want, right? And these conditions are basically the same. And here we are reducing the fresh oranges by 1. We are appending or adding the current cell in the queue and we are adding it in the visited set also. And now once we have gone through all the current elements in the queue with the help of this for loop, we will go back in the while loop with the new children elements already added in the queue. And after this, we will again increment the time. So these new children elements will be actually getting processed at the same time, and then the BFS will simply repeat for them also. And now after this entire BFS is done, here we are checking if there are any fresh oranges remaining, we will simply return -1. Otherwise, we will return time -1. The reason we are subtracting this 1 from time is because this BFS will actually run for the last node also, right? For the last set of nodes which are already bad. So it means it will run one more time basically. So that's why we are subtracting 1 from here. Now we will try to run this thing and see what happens. So yeah, our solution runs in 0 milliseconds, beats 100% solutions on the LeetCode. I'm really not very sure of this number because nothing can run in 0 milliseconds. And good thing is that all of the 307 test cases are passing. So our solution is working. Now let us look at the time and space complexity for this solution. So the time complexity is order of m multiplied by n, and the space complexity is also order of m multiplied by n. So m multiplied by n simply means all the elements in the grid. M is the number of rows and n is the number of columns. So that's why we are saying order of m by n, because in the worst case scenario, every cell in the grid might actually have oranges, right? In that case, we have to go to each and every cell of this grid, and it means we will have to go through m by n elements. Same is for space complexity. Since we are using a queue to store all the elements, we might end up storing m by n element in some worst cases. So we are saying order of m by n for space complexity also. Now there are ways to make space a little bit more efficient, like we may not need to use visited set. We can just mark these 1 cells as 2 after we have gone through them. In that case, we will not need to use visited set, but then again, space complexity will still be the m by n because we will have to use queue.
So today we have LeetCode 127, that is word ladder. In this problem, we have been given a begin word, that is the starting word. Then we have an ending word, and we have to reach from starting word to ending word. So we will have a word hit and we have to somehow reach the word cog. And we can do this based on these two rules. Every adjacent pair of words differs by a single character. What it means is that I can take the hit word and I can replace a single character inside of it. So suppose that I decide to replace I. So it will give me hot. So this is the word that I was able to reach from hit by replacing I with O, correct? And the second rule simply says that this newly created word must be part of this word list. If it is not inside of the word list, this is invalid. It means we are not allowed to go from hit to hot. But since hot is inside of the word list right here, it means we are allowed to do this transformation. We are allowed to actually replace the I with O and get the word hot. But if we try to do something like this, we have hit and we try to just change the H, okay, to D. So now we have DIT, dit. Now this is an invalid word. Why? Because it is not actually present inside of this word list. We have hot, dot, dog, lot, log, and cog. So only these 6 words are present in the word list, and dit is not one of them. So we are not allowed to go from hit to dit. Okay, this is not allowed. So basically what the question is asking us is that if we have some starting word like hit, then how can we reach an ending word like cog? So we can start with hit, then we can go to another word by replacing I with O. So we will have hot. Okay, that is present in the word list, so it is valid. We can go here, and then we can replace the H with a D, and it will give us dot. Okay, which is also present inside the word list, so it is also valid. And then from here we can replace T with G, so it will give us dog word. Okay, do you understand it? And dog is also inside of the word list, so it is valid. And from D we can simply go ahead and replace this T with C, and we will get cog word, and that is also present in the word list. So do you understand how we are able to go from hit to cog by going through all these words by making a transformation of one character each time? We are not allowed to change multiple characters at the same time. If that was allowed, then I could have just taken the hit word and then replaced all the characters at the same time. Replace H with C, I with O, and T with G. And then I will simply get cog word in one single swoop. Like this would have been an order of one time complexity, and that's why they have just disallowed it to do this. We can only replace one single character at each operation. So that is why first of all I'm replacing I with O, getting hot, then I'm replacing H with D, getting dot, then I'm replacing T with G, getting the dog word, and then I'm replacing the D with the C, getting the cog word. Now how many steps it took me to start from the hit word and then reach the ending word cog? Well, it took me 1, 2, 3, and 4 operations. It means it took me 4 steps. And this is the minimum number of steps that I need to take to go from hit to cog in this particular example. And that is exactly what we need to find out. We need to find out the minimum number of steps we need to take from starting word to reach the ending word. Here in this case, it is 4. So 4 is the answer. But in some another example, it can be 10, 12, or maybe 1. Who knows, right? So that is exactly what we need to find out, the minimum number of steps, which we are basically calling the shortest transformation sequence in the question, but it is simply minimum number of steps. So how do we solve this question? Well, before trying to solve this question, let us try to understand what the question really is. What does it truly represent? So we will have a starting word like hit, and we have to reach an ending word like cog. So in order to do that, we have to go through a few words. Like from hit, we have to go to hot by replacing I with O. And here is the magic. Here is something that we really need to understand. So right now we have something called a word here. Okay, this is a word. Now let's not call it a word. Let's just assume that it is something. Okay, we don't have to call it a word. We just say that it is something. Now we have a rule here. The rule does something and then we reach some other place or some other thing. So what is happening is that we have a particular thing. Let's just call it a state. And we have a rule that helps us to go from state 1 to state 2. And we know that any state, place, condition, or configuration can be called as a node. If you don't understand how graphs work, I have already created a video on graphs that will explain everything that you need to know about graphs ever. Like you will never have to deal with any confusion regarding graphs ever again. So basically here we have a state that is simply a word, and that word is going to be a node. And then we have a rule here that is going to help us to go from one word to another word, right? So what it means is that we have a node and we have rules for movement between the nodes, right? What it simply means is that we have a graph. In graphs, we will have node and we will have rules that will help us to go from one node to another node. Let us try to create a graph of this particular example. We will have the starting node as hit, okay? Then we can go to some other node. So where can we go? Well, I can replace I with O and I can reach hot. So this is one of the words that I can reach from it. Can we reach some other word from hit? Well, there is no other word that we can directly reach from it in one single operation. So we will have to now move on to the next level. So I can take hot and simply replace H with a D and I can go to DOT dot. Okay, this is the next word that I can reach. Or I can replace H with L and I will simply go to lot. LOT. This is the another word that we can reach from hot. And now here you can see if we replace D with L, I can simply go from dot to lot. So it means I will have an edge from dot to lot also. And then if we replace T with G, I will be able to reach from dot to dog. So I will have an edge like this from dot to dog. So this is another node that we can reach. And then if I replace D in the dog with L, then I will simply go to log. So I will have another node here, log. And then if I try to replace D with C, I will be able to go to cog, that is our ending word. So basically we are able to create this particular graph starting from the starting word, and we have this ending word right here. And now the problem simply reduces down to finding the shortest node from starting hit node to this particular cog node. So I can go from hit to hot to dot, then I can go to dog, and then I can go to cog. So if I take this path, I will have 1, 2, 3, and 4 steps to reach the ending word from the starting hit word. And now that we understand that we are only dealing with a simple graph, we can use something like DFS, or we can use BFS to go through the graph and find out the shortest path. But since we are trying to find out the shortest path, BFS is always the preferred way to do this, because if you try to use DFS, we will have to go through each and every path. We will end up going through here, then here, then here also, then like we will have to go through crazy paths, okay, just to figure out which one is the shortest. We might end up going through each and every path to figure out which one is the shortest. So DFS is not really preferred here, okay. So DFS is not something that we use for finding the shortest path. BFS is much better for that. So how do we apply BFS in this particular question? Well, one way is to create an adjacency list, and then you apply the BFS on this adjacency list. Now, if you want this kind of solution, you should go ahead and watch the LeetCode's video where he is actually explaining you how to create that adjacency list. But creating this adjacency list actually makes the problem a little bit harder to understand for people. So we are going to skip this thing. We are going to skip the whole adjacency list creation part, and we will directly figure out the solution. So how can we skip this adjacency list, right? Well, understand that the reason we have adjacency list is to make sure that we understand which node is connecting to which other nodes. Okay, that's the only reason to have an adjacency list. So how can we figure out this thing in some other way? How can I figure out that this particular hit node is actually connected to hot node or some other node? It is simple, guys. I will have the hit node, and then I will simply take the h, that is the starting position, that is the 0th position, and then I will replace the h with all the possible 26 characters in the alphabets of English language. What it means is that I will have 26 words after replacing h, and for these 26 words I will check which one of them are actually present in the word list, and I will only consider them as valid, which means only they will be connected to the hit. Then I can take the I word, and then I will simply keep h same, and then I will take the I, and I will keep the t same, and then I will replace this position I with the 26 characters from the alphabet, so it will give us another set of 26 words, and then we will check which of these words are actually present in the word list, given word list here, and we will only consider them as a valid word, and then we will take them as children. In the same way, I will just keep the I here, and I will just replace the T, and that will give us another set of 26 words. And then I will again check which one of these 26 words actually exist in this particular list, and only those words will be valid. So in this way, we can take a word like hit, we can replace each character with 26, and we can generate all the words that we need, and then we can just figure out how many of those words actually exist inside of this list, and only those words will be taken and placed inside of the queue. Okay, only those valid words we will take and place inside of the queue. Word 1, word 2, word 3. Okay, and rest of the words will be ignored because they are not valid. So in this way, we can find out the words connected to the hit, and then we will take those words, place them in the queue so that we can go through those words in the next iteration of BFS. Do you understand this thing now? We have everything to run BFS. We have the starting node hit, then we know how to figure out the connected node with the hit, and then we can take those nodes, we can place them in the queue, and then in the next iteration we can take out the W1 and then find out its neighbors, okay, and then place those neighbors back into the queue, okay, and then just keep repeating. And in this way we will be able to perform BFS in this particular question. Now remember, guys, that the starting word and all the words inside of this particular list will have the same length. It means it will be possible for me to go from this word to some other word in the list. That is not an issue. Okay. So in the starting, we will have a queue, simple queue, and inside of it, we will have this hit word, which is the starting word. So this represents the starting node that we are going to start the BFS from. And right now the length or the level is basically 1. So I will take out the hit and I will try to find out its neighbors. Now I can replace I with O. It will give me hot. Okay. Now if I try to find out some other neighbor, I can try to replace I with A. So I will have hat, right? Is hat a neighbor? It is not. Why? Because it is not present inside of this list. That's why hat is invalid. Then I can try to replace H with D. So is DIT a neighbor? No, it is not a neighbor because it is not present inside of this list. It means DID is also invalid, and in the same way, many other words will be invalid, and that will leave us with only this word that is going to be valid. So we will take the hot word and place it inside of the queue. So hot is now here, and since we actually removed the hit, so it is no longer in the queue. Now remember that we are going to run this whole thing inside of a loop, and the loop will depend on the length of the queue. Okay, so we will find out the length of the queue. Okay, and then we are going to run a loop on this length. Suppose this is L, and then we will simply say for I is equals to 0 to L, the length of the queue, we are going to run this whole thing. This is going to come here. Why? Because we need to calculate the levels. Okay, so what it means is that I need to process everything on the current level together. Okay, so that's why in the starting when I had only hit, okay, I'm going to run this loop only one time because the length of the queue at that time is going to be 1. And that means I will take the hit, I will take all of his children nodes and I will place them inside here. Okay, and then this for loop will end. This for loop will end, and once it is ended, I will take the L and I will update it to L plus 1. This is the level that I'm talking about. Okay, then we will go back again to the top of the loop, that is here on the while loop, where we are checking the condition for queue, and we will find that okay, there is still something in the queue. So I will take the length again, I will again get the one length here. So this is going to be one length here again because we only have hot here. Okay, and what it means is that this particular thing represents the second level. Now we are going through the second level of our graph. So earlier we started with the 1, here we updated it to the 2, the level is 2, and now we are going through all the nodes inside of the level 2 in this for loop. And once we go through this for loop, we will have dot and lot inside of this queue, and we will not have hot. So it means we will have 2 new elements and we will update the level here again. So we will have 2 plus 1, that is 3. So on the third level, we will have 2 elements. We will go back to the while loop again, we will take the length, it will be 2 now, and then we will run this for loop for 2 nodes. Then we will take their neighbors, we will place them here inside of the queue, and we will update the level again. And while the loop will be running, we will find the ending word cog, and then we will simply return the level, because this level is going to be the minimum or the shortest path we need to take from the starting word hit to the ending word cog. Since we are going to generate a lot of words from each node, we need to have a way to find out whether those words exist in the word list or not in order of one time complexity. So that's why we are first of all creating a word set with this word list elements. This set will help us to find out whether the generated word is present in the word list or not in order of one time complexity. Then first of all, we are checking if the ending word is not in the word set. Then we are going to simply return 0, because if it is not in the word set, we will never be able to reach that word ever. So in this case, it will be impossible to reach the ending word, and that's why we are returning 0. Now here we are creating the queue and we are placing the begin word inside of the queue. And the current length or the current level is 1. And then here we have the alphabet string. From this string, we are going to take the characters and we are going to create new words by replacing them. And now our BFS starts. So first of all, we are capturing the level size because that's what we are going to run the for loop on. So we are taking the length of the queue and then we are going to run a for loop on this length. So we are going to process all the elements or all the nodes that are currently present in the current level. Then we will simply pop the word from the queue. We will take the word. If it is equal to the end word, we will simply return the current length or the current level. If it is not equal to the end word, we are going to try and get its neighbors. So here we are running a for loop on each character of the word. We are storing the original character that we are currently on. And then here in the nested for loop, we are taking each character from the alphabet string. And then we are just creating a new character or the new word here with this replace alphabet character. Now this new word we are going to check if it is present in the word set or not. If it is present in the word set, we will take this new word, we will place it inside of the queue so that we can go through this word in the next iteration of the BFS. And as we append this in the queue, we are going to remove this word from the word set because we don't want to append this word again in the queue in case some other node is connected to it. This is our way of marking this visited. We are not using a visited array, so we are just removing the word from the word set itself. Now here this condition checks if this particular character from the alphabet string is basically equal to the original character. If it is equal, that means we actually got the same word again. So we are simply going to continue in that case. And once this outer loop is done, we have gone through all the words in the current level. So we will go back to the while loop above. And here we will again check the level size. But before going to the while loop, here at the end, we are updating the length or the level. So it means after the first level ends, we will update it to the 2 and so on. And in this way, the entire BFS will keep on running. And at the end, we will simply return the length. So if we ever find the end word, this condition will be responsible for returning the length. Otherwise, in the worst case scenario, we will end up returning 0 because it will not be possible to reach to that end word. And it is possible to never reach the end word if that end word is actually an isolated node. So if the graph is divided into components, then it is possible that the ending node is actually part of a component that you cannot reach ever from the starting node. So in that case, the entire BFS will run without ever reaching the ending node, and we will come here in this line, ending line, and then we will simply return 0. That hey, we can never reach the ending word with the given starting word. So now let us try to run this and see what happens. So our solution runs in 315 milliseconds, speed 38.30% solutions on LeetCode, and passes all the 51 test cases. So now let us look at the space and time complexity for this particular solution. The time complexity is going to be order of n multiplied by m multiplied by 26 because we have n nodes, and for each of these nodes we are going to go through each of the characters of the word. So the word length can be m, and for each of those characters we are going to replace them with 26 characters of the English alphabets. So that's why we have 26 here. So we have n multiplied by m multiplied by 26 as the time complexity. Then for the space complexity, we are going to have order of n, because in the worst case scenario, the queue will contain all the nodes given in the word list. And also we are using the word set to check if the given or the current word is actually present in the word list or not. So that also consumes order of n space complexity. In code also you can see we have the while loop that is going through all the nodes. Then inside of this while loop we have this particular for loop that is going through each and every character of the word. So the word length can be m, and then for each of these characters we have this for loop going on inside, that is 26 character for loop, because we are going to take all the 26 characters from the English alphabet and we are going to create new words with those characters for the current word. So basically the while loop is going to run for n times, the for loop inside of it is going to run for m times, and this entire nested for loop is going to run for 26 times, which is giving us m multiplied by n multiplied by 26 time complexity. And here in the starting we have the word set and the queue, which are going to give us the space complexity of order of n.
Today we are going to understand what is DFS or depth first search. This is basically an algorithm that helps you to go through the entire nodes of a graph. Suppose you have a graph like this one. You are on this one node and you want to go through all the other nodes in this graph somehow. Well, you can use a technique like DFS that helps you do that. There is one more thing like BFS, but that I have already discussed in a different video. So if you want to understand BFS and how the graph works, please check out my other video of graphs and BFS. That video contains everything you will ever need to know about graphs and BFS, and I have provided the link in the description, and you will also see a card somewhere here. Now let us get back to the DFS. So D stands for depth. You can also consider as a path. Depth sometimes confuses people, so you can also consider it as a path. So you can think of it as a path first search. Basically what we do in this kind of algorithm is we will be on any given node, and then from that node we will try to go to other nodes. So suppose I try to go to this node. Then once I'm here on the 2 node, I have choices. I can either go this direction or I can go this direction. So suppose I choose this direction and then I will be on this node. From here I will even go deeper or further in this path. Then I will reach 8, and from here I have a choice to go to 7. So I will go to 7. I will go deeper and deeper in this path. I am traversing a path first. So I'm on 7, and from 7 I can go to 6. So I will go to 6. From here, I will go to 4, and from here, I will go to 3. And from 3, I have choices. I can go to 2 or I can go to 1. But here is the thing. I have already gone through 1 and I have already gone through 2. It means I cannot go anywhere from this 3. That means I have gone through one complete path in the graph till the end of its depth. And that's why we will now try to go back. So I'm on 3, I will go back. I will be on 4 now. Then from 4, I will go back to 6. Then from 6, I will go back to 7. Then from 7, I will go back to 8. Then from 8, I will go back to 5. Then from 5, I will go back to 2. And here on 2, we had a choice, right? We could go in this direction, but we chose to actually go to this direction, and that's why we actually ended up completing this particular path, right? But we did have choice to go to this side, right? So when we are coming back to 2, we will try to go to other nodes that are connected to 2. So if I try to go to this node, the 3 node, I will see that 3 has already been visited. So it means I cannot go to 3 anymore. It will be like doing the same work again. So I will simply say I cannot go to 3, and I will simply return to 1. Once I come back to the starting node, I will again try to see if this starting node has some other children. Starting node does have a children. It have 3, right? But I cannot go to 3. Why? Because 3 has already been visited. That's why I cannot go to it. So it means 1 does not have any other neighboring nodes that I can go to, and it means I will simply go back from 1 also, and this means the DFS will end at this point. However, if for some reason you actually had a node connected to 1, suppose you had something like this, 10 node is there, then 20 is there, right? Then 11 is there, something like this. Then what will happen is that you will come back from 2. You will see that 3 has already been visited, right? So what you will do is you will go to the 10th node. Then on the 10th node, you will again have a choice in which path you want to go. You can go this path or you can go this path. Suppose you go to this path, so you will reach 20. Now from here, you don't have any choices, right? It means there is no neighboring node to 20. So from here, you will have to return. You will go back from 20 to 10. And then you will try to traverse the other possibility. So other possibility was 11, right? So I will go to the 11 now. But from here also, I don't have any other nodes to go to. So I will simply go back to 10, right? And now on 10, I have no other nodes that are connected to it. Yes, 10 is connected to one node also, but it is the parent, right? It is where it came from. So it will not go back to the parent itself. It will go back to the parent node when everything on this 10th node is done. So here on the 10th node, everything is done. 20 is done, right? 11 is done. So the only option is to go back to the first node and tell that yes, I am done. 10 is done. We are not trying to traverse the first node through 10. We are simply saying that okay, 10th is done. We are closing the DFS for 10 and we are going back to the original node from where we started the DFS for 10. That's all. So here, if you look at it properly, what happened is that we picked a node 1 and then we just started going through depth. We took a path and on that path, we just kept on going until that path was completely finished here, right? Then once it was finished, we actually came back. We actually came back till here too. We tried to go to the other direction, but we could not because it was already visited. So we go back to 1 again. Then we try to go through other path, right? On 10th, we had two choices to go through. So we chose to go to the path of 21st. We reached the depth of the 20th path and then we came back. Once we came back, then only we decided to go to the other path, right? That's what a DFS really is. What we are doing in a DFS is that we have a node and then we will have paths, right? So we will take a path and we will go in the depth of that path, complete depth, and then only we will return on that node and then we will take the other path. We will go to the depth of that path, then we will return and then we will go to the depth of the other path. That's what we are doing. And if you really notice it properly, this way of going to a node, going to a path, then returning, then again going to some other path, then returning, there is one algorithm that does this thing very well, which is recursion. So it means that DFS is done mostly based on recursion. If you do not use recursion, the DFS or the graph topic itself will be a nightmare for you. Seriously, guys, it will be truly a nightmare. You will have to deal with a lot of things like maintaining a stack and all that stuff becomes an extra overhead when you are trying to solve very complicated graph problems. So it becomes very important for us to know and understand recursion very well. Suppose we have this graph and this adjacency list. Now in this adjacency list, I have 0 also, but I don't have any 0 node because this is actually a 1 based graph, right? So we have 1 to 7, but we may need to create an array to store the adjacency list. So in the adjacency list, we will actually have the 0 index, but that 0 index will not actually matter to us because it will not have any neighbors to it. And also none of the other indexes will have 0 as its neighbor also because it does not exist in the graph also. So let us try to see how the DFS will work in this case. We will be on 1. We can be on any other node. We can be on 6 also. But suppose for simplicity's sake, we are on 1. So when we are on 1, we will check its neighbors. We have 2, 4 and 3. So we will start going from left to right in this list because we will be using a loop. So first of all, we will go to 2. And when we are on the 2, I will be on this index. I will use this index to get the adjacency list for this particular 2 node. So the 2 node have 1 in its adjacency list, right? So if I want to go anywhere from 2, I will end up going to 1 because that is the only thing present in the adjacency list here. But we cannot go to 1 from 2 because it has already been visited, right? 1 is where we started from. It means we will need to store it somewhere. So we will have a visited set, and in this set we will store the thing that we have already visited. So I have already visited 1, so I will store it here. And here on the 2, when I'm trying to go through the adjacency list here for 2, I will check if this particular node has already been visited or not. So I will check that in this visited set, and if I found that yes, it has already been visited, I will skip that node. I will not go through that node. But since in the case of 2, there is only 1 here, and I ended up skipping 1, there is nothing else, it means I will simply have to go back. So it means the DFS call for 2 will end on the recursion stack, and I will end up going back to 1. Now when I'm on 1 and I have already gone through 2, I will have 4 next on the list. So I will try to go to 4. Now when I'm on 4, I will be able to use this fourth index to access this particular list. So from the fourth also, I will go to the depth. I will keep on going to the depth and depth only. So in the fourth, the first thing we get is 1, right? But we check it in the visited and we find that in the visited we already have 1. We also need to have 2 in the visited because we also visited 2. So 2 will also be there. So since 1 has already been visited, we will skip this thing. We will not call DFS on this. We will go to 5. Is 5 visited? No, it is not visited. So that means we can directly go to the 5th node. I will come here. Then I will use this 5th index to get this latest adjacency list. And when I went from 4 to 5, I will also need to store 4 in my visited. And now at 5, I will try to go through its neighbors. So I see 4 here and I see that 4 is also in the visited. So it means I will skip the 4. Then I will go to 7. 7 is not in the visited. It means I can go to the 7th. Now I am at 7th. It means I can use this index to get the hold of this list. And also when I went from 5 to 7, I will end up storing 5 in my visited set because I have already visited it. So now from the list available for 7, I will see that first thing is 5, but 5 is already visited, so I will not go back to the 5, right? So I will not try to traverse 5 from 7. I will skip it and I will call DFS on the next element, that is 6, because 6 is not visited. So it means I will go from 7 to 6, and now I am at the 6th node. And when I'm going from 7 to 6, I will add 7 in my visited set also. So now I am at 6, right? And I will use this particular list to get a hold of the neighbors connected to this particular node. So I will see that 4 is the first element that is connected to it, right? But I see that 4 has already been visited. It means I will not try to traverse the 4th from 6. I will not call the DFS recursive function on 4 from 6. So I will skip the 4 and I will go to the 7. 7 I see it has already been visited. It means I will not call DFS recursive function on 7 also. So I will skip this one also. And once I skip it, there are no more neighbors. It means we have reached the depth. We have gone through all the elements or all the nodes on a particular path till its entire depth. It means from this point onwards, I will start returning. So the DFS call for 6 will end on the recursion stack, and I will end up going back to 7 automatically. Here also on 7, I have no more nodes to actually go to. I will go out of bound in this list. So it means the DFS on 7 will also finish, and I will go back to 5th automatically from the call stack. Then again from 5, I will go back to 4 because there is no more stuff to go through on 5th node. Then from 4, I will try to go to 6, but I will see that the 6 is already in the visited. I believe I forgot to add 6, so I will add it now. So 6 is in the visited. I will not be able to go here. It means I will directly go back from 4 to 1. So I'm going back from 4 to 1, and then I will be back on this particular list. So I will see that on this list we still have a 3, right? And 3 is also not visited. So I will go from 1 to 3 at this point. And now on the 3 node, I will have access to this list. And in this list, I only have 1, and 1 is already visited. It means I will not call DFS on the first node again. So then I will do whatever I want to do with the 3 node itself, and the DFS will end on the call stack, and I will end up going back to the 1. And once I go back to 1, I will again have this list, right? And in this list, if I try to go any further, I will go out of bound. It means we have gone through all the elements of the first node. So at this point, the DFS will end, simply end. And the code will look like this. First of all, we will have a recursive DFS function that we will create ourselves. That DFS function will have node and will have a visited set. We will need node to actually start traversing, and we will need visited set to make sure that we are not trying to traverse a node that has already been visited earlier. So in this function, the first thing we do is add the node to the visited so that we will not try to call DFS on this particular node ever again in the future. Now, once we have done this, we will simply start doing our work with the current node. So we must have some kind of work with the current node, right? We can either print it, we can calculate something based on the current node. We can do whatever we want with the current node in this section. So right now I'm just printing it. That's what my work is with the current node. Then once I've done my work, I will start going through the next nodes. I will start going through the neighbors of this node. So I will use a for loop to take all the neighbors in the adjacency list of this node. And for all of these neighbors, if they are not in visited, I will actually call DFS on them. I will call DFS on those neighbors. And from this line, a new DFS call will start on the recursion call stack. So we have call stack like this in the computer. Suppose I start from the first node, I will have DFS of 1. Then I go to the node 2 that is connected to the node 1. Then for that also I will have a DFS of 2. Then again I will have a DFS of 3 in the call stack. And suppose that the node 3 is not connected to any other node, it is only connected to 2 node, but we will not call the DFS of 2 from 3 because this line will actually stop us from doing that. It means this for loop will run completely without ever calling DFS on any other thing. So it means after here, this particular DFS call will automatically finish on its own, and hence this instance of DFS function call will be destroyed by the operating system itself, and we will end up going back to this instance, the DFS of 2. And on the DFS of 2, we will again continue with the next neighbor that is present in the adjacency list for node 2. And if there is some other node like 4 connected to 2, then we will have another DFS call stack for 4. In the same way, we will have more call stack. We will keep on deleting call stack and call stack and call stack until we reach back to the DFS of 1. If we have some other nodes, great, we will go for them also. We will create call stack there. Otherwise, this will also be deleted and we will go back to outside. It means the DFS function will end at that point. Now, this call stack is not something that we have to maintain. It is maintained by the operating system, the computer itself, because we are using recursion. If you were using something like iterative solution, yes, you will need to maintain a stack yourself. And that's why the entire graph topic and the entire DFS relies heavily on the already provided call stack from the operating system. And that is one of the reasons why we are using recursion so heavily in graph topic. If you don't use recursion, the graph topic will be a nightmare for you, really. Now, one thing I want to point out here is that this part, pretty much this entire part will be common for all kinds of DFS algorithms. But this part, this particular part actually will change. It will change based on what kind of graph you have, okay? So right now we do have an adjacency list for this particular graph. It means the question is providing us an adjacency list, but it is not guaranteed that you will always have an adjacency list or you will be able to create an adjacency list. Because remember that graph does not mean adjacency list. Graph is a completely different thing. And if you don't understand what a graph is, I will ask you to go through my video of graphs and BFS that I have already made. In that video, I have explained in very detail how you can turn anything like a simple array into a graph or a two-dimensional array like a matrix into a graph. So we do have questions on matrices also. So here is an example where we will not have an adjacency list. We will have to calculate the neighbors of a particular node. So here we have an array of integers. It's a simple array, and the ith integer tells the maximum possible jump length we can take from that index. Now, if you do not know how we can generate a graph out of this particular question, you need to watch that video, the graph and BFS video. There you will learn all these kind of things. But I will create it here so that you will understand. So we will have a particular array like 1, 3, 1, 2, 9, 5. And here we have indices like 0, 1, 2, 3, 4, and 5, right? So here this particular number tells you how big of a jump you can make from this position, the 0 position, to any other position. The next positions, actually, you cannot go back in this question. So you will have to consider the forward positions only. So 1 means I can make a jump of length 1. So it means at max I can go to 3 here. When I'm on 3, the maximum jump I can make is 3 steps. It means I can either go to 1, I can either go to 2, or I can go to 9, because all of them are within the range of my jump length. Then if I am on 1, I can only make a jump to 2. If I am on 2, I will be able to make a jump on 9, and I will be able to make a jump on 5 also. If I am on 9, I will only be able to make a jump on 5, and if I am on 5, there is nothing else, right? Nothing else to make a jump to. So if I try to create a graph out of it, so I will have a node 1. So 1 will be here, and from 1 I can only go to 3. So I will have an edge from 1 to 3. From 3 I can go to 1, 2, or 9. So I will have 3 edges. That is 1, 2, or 9. Correct? Because there are 3 places that I can go to. And then from this one, I can only go to this 2, right? So I will have an edge from 1 to 2. And then from this 2, I can only go to 9 and 5. So I will have an edge from 2 to 9. And I will have an edge from 2 to 5. Now I believe you can guess what will happen next. We are at 9. So from 9, I can go to 5. So I will have an edge from 9 to 5, right? And from 5, I cannot go anywhere else. So it means I will not have any other edge. Now understand that these edges are actually one way because we are saying that we can only jump in the forward direction. So it means we will have an edge from 1 to 3 like this, then like this from 3 to 1, then this way, then again this, then this, and here also, and yeah. So what we are saying is that I can go from 9 to 5, but I cannot go from 5 to 9 in the backward direction. Now here is the DFS function that we created earlier. Here also this particular part will actually be the same. You will have a node and you will just keep on adding it in the visited, and you will actually print or basically do whatever work you want to do with the node. But the part that will change is going through the neighbors, because here you do not have an adjacency list, right? ADJ list is not existing here. So it means you will have to calculate what is the next neighbor based on the current node. So you will simply use this jump length rule to calculate the next neighbors. So the way we can use this is we can create a for loop here from 0 to this particular jump length. And jump length is basically what? Jump length is simply this particular node. I'm running a for loop from 0 to this particular node. The node value is like 1, 3, 1, 2, 9. This is going to be the value of node. And in this for loop, what I will do is very simple. I will simply calculate the next neighbor. So neighbor will be node value, okay, plus whatever is the current index. So I will have something like I is equal to 0, right? So I will add I, and that will tell me the next neighbor that I can go to from this particular node. And then I will simply check if NE, that is neighbor, not in visited, then we can run DFS function on this neighbor. And this is how you will be going through the neighbors of this particular graph. So you will have to use the rule provided in the question to figure out what are going to be the neighbors. Now here is another example of two-dimensional grid where you will have to calculate the neighbors again. So we have a 2D grid with m by n dimensions. It means m is the number of rows and n is the number of columns. We can only go up, left, right, and down. So there are only 4 places or 4 directions in which we can go to. Now we have to traverse this entire graph from any node or any cell with the help of DFS. So how can we convert this particular situation into a graph? So we will have a grid like this. Here we have all the coordinates already written in each cell. So it means the middle cell is actually represented as 1 and 1. So we will have a node that will be like a set of coordinates 1 comma 1. It represents the middle cell. Now in order to create a graph from this, suppose we start from this particular node 1 comma 1. So I will have a node 1 comma 1 here, and then I will try to figure out how we can create a graph. So in this problem, we can actually go to these 4 directions: up, left, right, and down, right? So if I try to go up, I will reach 0 comma 1, right? So it means I have an edge from 1 comma 1 to 0 comma 1 because I can reach 0 comma 1 from 1 comma 1. If I try to go down, I will reach 2 comma 1 from 1 comma 1 because it is already allowed. So I will have an edge from 1 comma 1 to 2 comma 1. In a similar way, if I try to go this side, then I will have 1 comma 2. So I have 1 comma 2 also as a node here connected to 1 comma 1. On this side, I will have 1 comma 0. Similarly, here from 0 comma 1, I will have 0 comma 0. On this side, I will have 0 comma 2 because we can go from here to here, right? Then from 0 comma 2, I will again be able to go to 1 comma 2. So I will have an edge from 0 comma 2 to 1 comma 2. Then from 2 comma 1, I will have an edge from 2 comma 2. So okay, I will go from here to here 2 comma 2. Then from 2 comma 2, I can go to 1 comma 2. So I will have an edge between these two nodes. In a similar way, we have 2 comma 0. So 2 comma 0 will be here. I will have a node here. I will have an edge from 2 comma 0 to 2 comma 1 because I can go from here to here or from here to here. And then I will have an edge from 1 comma 0 to 2 comma 2 because I can go here or here. And similarly, we will have an edge from 0 comma 0 to 1 comma 0. So it means we are able to create a graph out of this grid. And now we can take any node and try to run DFS on this. While applying DFS to this grid, this particular part will be the same. The only thing that will change is adding the neighbors. So how do you add the neighbors? Well, suppose you are on 1 comma 1. If you want to go to up, what you will have to do is you will have to subtract 1 from this row number, right? So you subtract, it will become 0. If you want to go in this direction, you will have to add 1 to this column number. That's why it became 2. If you have to go to down, you will have to add 1 to the row number. Similarly, you will have to subtract 1 from the column number to go to the left. So it means to go in 4 direction, you will have something like this. You will have to add negative 1 comma 0 to the current node to go up. You will have to add 1 comma 0 to the current node to go down. You will have to add 0 comma 1 to go to the right direction, and you will have to add 0 comma negative 1 to go to the left direction. So these things will help us to go in different direction from a current node. It means I can store these in a particular set or in a particular map or in a particular array, and I can go through it on a for loop. So I will have a for loop that will go for each direction in directions. So I'm taking one direction from these 4 directions in the direction array, and I'm trying to figure out the neighbor. So neighbor will be equal to node plus dir. Now, how you are going to do this node plus dir? Well, that will depend on the particular implementation of your language. You might actually have to take these indices one by one and add them manually, or you might be able to do this with the help of a built-in function, but that's not our consideration here. We are just going to say that yes, we are going to add them just to get the next neighbor. Now, once you have the neighbor, you will have to check a few conditions. First of all, you need to make sure that you are not going out of bound. If you are on 2, 0 and you try to go this side, there is nothing, right? So you need to make sure that you are not going out of bounds from any node. And for that, we actually have a very long condition. So I will just paste it here. So here's the condition. In this if block, what we are checking is that if the node, the neighbor node is out of bound, or if it is already present in the visited, we will not go through it again. We will simply continue the loop from here. We will not go any further. We will just skip this iteration and we will continue back from for loop. Otherwise, if it is not out of bound, if it is a valid node like 0, 1, and if it is not invisited, then we will go ahead and here we will simply call DFS for this particular neighbor. And here instead of node, we will have neighbor in visited. So if the neighbor in visited, we will simply continue. Otherwise, we will actually go through the DFS. It is a little counterintuitive to check that the neighbor is inside of the visited, because till now we have been checking that it is not in visited. But in this case, it actually makes everything simpler to write in terms of code, because here we are making sure that if the neighbor is actually out of bound or it is already visited, we do not run this thing. We will not run DFS. We will simply continue. Continue means we will directly go for the for loop again. We will skip any of this stuff. So yeah, this is how you will be able to run DFS inside of a grid. So I have coded everything that I know about DFS in this video.
So today we have this binary tree in order traversal problem. And this problem is very easy because it's just a simple implementation of DFS algorithm. So if you know DFS, this problem will be a breeze for you. So basically in this problem, we have been given a root of a binary tree. Note, it's a binary tree, not a binary search tree. Okay. So a binary tree have two nodes, one is left and one is right, but there is no requirement on what values needs to be on the left and on the right node. So what we have to do is we have to return the in order traversal of these nodes. Simple. Okay, so now let us try to understand how to solve this particular problem. So basically we kind of have to apply DFS, that is depth first search, and we have to provide an in order traversal. So depth first search, we understand what it is, right? Basically we will start from a particular node and then we will go in the depth of this node, right? So we can decide whether we want to go in the depth of left nodes first, or we can decide whether we want to go in the right node, right? So that's how basically DFS works. But in the in order traversal, there are some requirements or some rules. So first of all, it is said that you have to go to the left of the tree as deep as you can, and then you have to first print the left node. Okay, so you can print 4, and then you have to print the root, that is 2, and then you have to print the next right node, that is 5 or something. So for example, if I try to traverse in the DFS, first I will be on the 1, then I will go to the 2, okay, but I will not print 2. I will go in the even more depth, that is to the 4 in the left side, right? Now when I'm in the 4, this is null, this is null. Okay, so basically I have two null nodes at 4, but I'm at fourth node, right? So I will go to the null node. So I went to this null node, I see that it's a null, I return to the 4, and then I print the 4. So I will then print the 4. So I'll just write here 4. Okay, then I will go to the right. So null. Okay, so right is also null for 4, so nothing will be printed. Then I will come back to the 4, then I will go to the 2. Correct, I will go to the 2, and then I will have to print or basically write 2, right? Because I have already went through all the left nodes of the 2. So I will have to write 2 here. And then we can actually go to the right subtree of 2. So I went to the right subtree of 2, I found 5, but I cannot print 5 yet. I have to go in the even more depth, right? So I will go to the left node because left is present and the left is where we go first whenever we are at any node. So I will go to the left node. I found 7. Then again the same situation, null and then null. Both left and right nodes are null. So I will end up going to the left node. Once null, I will see, okay, it's a null node. I will return without printing anything. I will come back here. Then I will simply print the node. So that means I will write 7 here. And then I will basically go to the right node. It is also null, so I will come back without printing it, and then I will go back because I have already printed the 7, correct? I will go back to the 5. Now once I go back to the 5 from the left subtree, I will simply print the 5. So 5 will come here, right? And then I will go to the right subtree of the 5. So it is null currently. Right subtree is null, so nothing will happen. I will go back to the 5, correct? Nothing will be printed. And then I will go back to the 2, right? Now we have already printed 2 earlier, so we will not be printing it again. And now I will go to the 1, correct? Now for this particular one, we have already covered all of its children nodes, correct? So it means its entire left subtree we have already printed here. So now what we will do is we will print 1 here, right? So 1 will be written here, or 1 will be appended to our list. Now we will go to the right subtree of 1. So now once we go to the right subtree, we encounter 3. Now on this node, again, we will first have to go to the left of this node, and then only we can go to the right. So on 3, I will go to the left without printing 3. I'm not printing right now. I will go to the depth of it to the left, and I see 6. Again, we have null left and null right nodes. So I will go to the null first, left, right, and then I will come back. I will print the 6 now. So 6 is here. Then I will simply go to the right of the 6. I see null. I will simply come back without printing anything. And then all the subtrees that is left and right are gone or have been processed for 6. I will go to the 3 now. Now since I have processed the left subtree of 3, I will now simply print the 3. Correct? So the next will be 3. 3 will be printed, and then I can actually go to the right subtree of 3 here, and this is currently null, so we cannot print the null. So I will go back here. Okay, we have printed the 3, and then I will go back here. We have already printed 1 here, so I don't need to print anything. We have printed all the things, so basically our answer has been done, right? Our answer is complete at this point. So this is the in order traversal. First what we did is we went to the left, correct? We went to the left like this, from 1 to left 2, correct? But we did not print anything. Then from 2 to 4, this is where we went. Now once we reached the 4, we realized that there are no left or right subtrees for 4. They are both null, correct? So we cannot print null. So we simply printed 4 here first, correct? Then we went back to 2, and then we printed the 2. Okay, so we will first print the left. Okay, then we will print the current root, okay, and then we will print the right subtree nodes, correct? So we first went to the left, so we printed 4, then we went to the root again 2, and then we printed the 2, then we went to the right subtree, right? And we encountered 5 here, but we did not print it here, right? Because we have to go to the depth of it. So from 5, first we went to the left subtree, okay? So from each node, first we have to go to the left subtree, okay? And similarly here, 7 have no left or right subtrees. Both of them are null. So I simply printed 7. So 7 is now here, correct? And now we can actually go back to the 5. Now we went to the 5. We have already completely printed or processed the left subtree of 5. So we can print 5 now. And that's what we did here. We have printed 5. We tried to go to the right subtree, but it's null. It is null. So we cannot print anything, correct? So we went back to the 5. And from 5, we went back to the 2, correct? From 2. And then from 2, because we have already printed the true, right? We have already processed the root node 2. We went to the 1 now. So we have processed the left subtree of 1. Now we can actually print or process the root node 1. So I printed it here in the list, right? Now I can go to the right subtree. I will go to this subtree. Okay, for 1, I went to 3, but we cannot print 3 right now because 3 is not the last node for this subtree. So I will go to the next node for 3, that is the left node of 3, correct? So I see the 6, I will print the 6 because 6 also have just null node for right and left trees. So 6 will be printed here. Okay, once the 6 is done, I will go back to the 3, I will print this current root node 3. So 3 will be printed, right? Then I will go to the right subtree. It is null. So since it is null, I cannot print anything. I will simply go back to the 3, and then from 3 I will go back to the 1 because 3 is already printed, right? We have already processed the root node here, correct? Now I went to the 1, I realized that the right subtree is also done. So now our in-order traversal is complete. Now the problem that people face is basically in recursion, okay? So usually the function is written something like this. We will have a DFS, right? It's a DFS function. We will pass a node, or maybe just node, I would say, and then that's it. Usually this is basically the way to do this in Python, okay? So then you will see a base condition. If node double is equals to null or none, basically. In Python, null and none are basically kind of the same. So you can think of them analogically, and then I will simply return, right, without printing anything. Now understand that this condition will only be true after reaching the leaf nodes, okay? So basically, once I reach the leaf nodes, okay, if I try to go to the left node and pass the left node to this function, okay, so left is null or none basically, okay, it's a, they doesn't exist, right? So this is where at this point, this particular condition will be true. So we will simply return because we cannot print the none, right? So we will return here at this point. Now, after this if condition, basically, you will have this, okay, you will again call the DFS in the recursion, and you will pass a node dot left. After this, you will write here something like this, list dot append current nodes value. So node dot val, okay, so current nodes value you have appended, and then again you will write something like DFS node dot left. Sorry, not left, it is right, because now we are dealing with right subtree, okay? So how does particular function works, right? So basically what will happen is that you will call this on the root node, okay? So first this will be a root node, right? So first the node will be 1, because at this point the root node is 1 for us, right? Now the node is 1 and node is not null. So this condition will be false for 1. Okay, so then we will again go into the depth of 1. So node dot left means the left node of 1, that is 2. So we are first of all basically trying to process all the left nodes of 1, right? So we will pass 2 here on this position. Okay, simple. We will pass 2 here. Now node dot left is 2, and remember at this point there will be a call stack, okay? So once this line hits, okay, a new stack, basically this call will be placed on an internal stack by operating system. So this will be placed on a operating system, okay? Suppose DFS 2. So this was the DFS 1, okay? Then now this is on DFS 2, on node number 2, okay? Similarly for 2 also, we will first go inside of this function. On the if statement we will check, okay, 2 is not none, so we will now again go back here on the DFS. So we will place the left node of 2. So currently the left node for 2 is 4. So now this will again hit this DFS node dot left, and we will again have a new call stack for this DFS, right, for 4, for root node 4, okay? So now we have 4 here. Now currently we have 4, that is leaf node. Now again the same logic will happen, okay? So we will check if the 4 is none or not, okay? And it is not none, so we will now place or basically put node dot left, okay? So the left node of 4 is none or null or none, okay? In Python it is none, so this Python is none, okay? So now this is none, correct? And it means, first of all, there will be a call stack for this. So DFS none. So none will be passed in the DFS, and then in this particular call stack, okay, in the topmost call stack, call, okay, this condition will be true, correct? This condition will be true. So what will happen is that we will return. So once we return from here, okay, this particular call will be cancelled, or basically this particular call will be returned. So this topmost call is now does not exist in the call stack. It just finished, correct? Now we are back on the DFS core. So once we are back on the DFS4, so in this particular call, we were on this particular line, correct? Now this is done. This line is done. The function call for this was done, we have seen. And now we will go to this line particularly. Now the value 4 will be appended to our list. At this point, the 4 will be appended to our list, okay? And then we will now go to the right subtree of 4. Now we see that the right subtree of 4 is also none. Basically, for the right subtree, there will be another DFS call here, okay? So the DFS will be something like this, DFS again none, okay? And the same thing will happen. We will hit this particular line, okay, this particular condition, and then we will cancel the call, not cancel, actually return the call. So this will also be gone, and then we have processed both left and right subtree for 4, correct? For 4 we have processed it. Now what will happen is that after this line, this particular call, okay, this particular call will return automatically. It will return automatically. So DFS of 4 is now returning. Now we are reaching the DFS of 2 on at this point, okay? So on DFS of 2, what will happen is that even on DFS of 2, we will again be stuck on this particular line, but this is now completed. So now we will go to the next line, this particular line, correct, on appending the nodes value. And now we will append 2 here, simple. And then we will go to this line and we will actually try to explore the right subtree of 2, right? So now we will go to the right subtree of 2, that is DFS of 5. So now the call stack will again have another call, that is DFS of 5, something like DFS of 5, okay? Now for the 5 also, we will again go for the 7, that is, we will again hit this line, this particular line, correct? So this line will be hit, and then we will again have the 7th, or basically the DFS of 7, okay? DFS of 7, then 7 again have a null nodes, okay? So first we will try to go for DFS of none for left node, DFS of none for left node. We will see that it will simply return, so it will be cancelled or basically returned early, right, because of this particular condition, because of this one, okay? Now once that happens, the DFS of 7 again resumes or continues from this particular line, and then we will go to this line, correct, and then we will simply append 7, and then we will go to the right subtree of 7, right? So right subtree of 7 is also none, correct, because there is nothing there. So we will simply again have a DFS of none, DFS of none on the call stack, correct? And then it will also return, it will simply return, it will return, okay, and it will come back to the 7, right? It will come back to the 7 at this position, it will come back. And then after this, there are no code, so it will simply return. So the DFS of 7 will also simply return because it has been processed, okay? Now we are back on the DFS call of 5. So the DFS call of 5 here, okay, in this DFS call, we are still stuck on this particular line. So we will move and we will go to the append line. We will append the 5, and then we to go to the DFS of right node. So the right node of 5 is again null. So I will not make a new call, but understand that there will be a new DFS of none, which will simply return early, okay, in the call stack. And then we will go to the 2, and in the similar way we will reach back to the 1, okay, because for 2 we have been stuck here, so once the right node or right subtree of 2 is done, so the DFS of 2 will also be cancelled or basically returned, and then we will go back to the DFS of 1. So the entire left subtree for DFS of 1 is now done, correct? Now we will move to this one particularly, and then we will simply add 1 here, okay, in our list. And similarly, we will then again proceed to process all the right subtree of 1, okay? And in the same way, we will have DFS of calls, okay, for 3, for 6, for all the levels basically. And then eventually we will have our in-order traversal like this. So this will eventually become our in-order traversal 4, 2, 7, 5, 1, 6, and 3. Simple as that. That's how in-order traversal really works. Now here the Python code for this. It's a very simple code. So I have a global variable res. It will basically store our result. Then I have defined a function in the in order traversal function itself. So in the DFS, I am basically taking a node. Okay, I'm not saying that I'm taking root. I'm taking any node. It's an easy way to understand the DFS or basically call stack. So I'm taking any node and then I'm checking if that node is none or null. So for Python, it is going to be none. There is no null in Python. So we will return if it is none, and then we will check. Okay, if it's not none, then first we will check it's in left subtree, then we will append the value of this particular node to the rest, correct, as we have seen, and then we will check its right subtree, correct. Now the function ends here, and now we are simply calling this function here with the root. So we are passing this root here in the DFS, and this root will simply run and then populate the rest, and then we will simply go ahead and return this res. Now all we have to do is run this thing and see what happens. So as you can see that it's, just good enough, I would say. I mean, you cannot really trust the LeetCode thing because it says 0 millisecond. I mean, there is nothing that can work in 0 millisecond. That's kind of crazy, but I would say it's a good enough solution. There is no extra space. There is nothing, I would say, just a call stack of extra space. And in terms of time complexity, if we analyze it, I would say space complexity is order of n because we are using the space for call stack, and the time complexity is going to be order of n because we will actually be traversing through all the nodes. So yeah, both are order of n right now. And even if you try to create an iterative solution for this, that will again need a stack. It is just that you will have to maintain that stack by yourself manually. Currently, the recursion is handling that stack for us, but if you use iterative, you will have to maintain it by yourself. So today we have LeetCode 200, which is number of islands. In this problem, we will be having an m by n 2D binary grid, and in this grid, we will be having ones and zeros as a string. They are not numbers. Here 1 represents the part of land and 0 represent the part of water, and we have to return the number of islands that we can have in the grid. An island is surrounded by water and is formed by connecting adjacent lands horizontally or vertically. It means we have two directions, horizontally and vertically. We don't have a diagonal direction, only two, horizontal and vertical. And we can assume that the edges of the grid are all surrounded by water. It means anything outside of this grid is simply considered as water. We cannot go there. So what this question is saying is that we will have a grid like this. In this grid, we will have some ones and some zeros. Zeros is representing water, one is land. We need to find out how many islands we have. So we have, for example, here one single island like this. So this is an island, right? Basically, we have to find out the number of groups of ones in the given grid. Now suppose that we have a grid like this. Here we have ones and zeros. Now we need to find out the number of islands that are present in the grid. An island is nothing more than land connected horizontally and vertically. So basically we have to find out the group of lands connected vertically and horizontally. So one is representing land. So we have a group like this. So this represents an island because they are connected horizontally and vertically. In the same way, we have a group like this also. This is also an island. It's a smaller island, but it is an island. It is connected horizontally. This itself is an island, even though it is simply a single land, but it is really, really small island. And this here is another island. Understand that this island is not part of this one, okay? Because we are not considering diagonals. So this is a completely different island. So that's why this is a completely different island. It means we have how many islands here? We have one, we have two, we have three islands, and we have four islands. It means the answer will be 4. Now the question is how to solve it. Well, we can use graphs because we do have cell here, which is basically a node. So this node can contain 1 or 0, and then we have a rule. We can either go horizontally or we can go vertically. We cannot go diagonally. So it means we have a node and we have rules that actually tells us how we can go from one node to another node. It means we can construct a graph with the help of these two things. If you do not know how this works, please watch my video on graphs and BFS. In that video, I have told you everything about graph that I know. I have poured all of my knowledge in there. So I will have a link in the description, and you might also see a card somewhere here linking to that particular video. So what we will do is we will consider these ones as nodes and we will start traversing them with the help of DFS. We will use DFS. You can also use BFS if you want, but DFS implementation is simpler, so we will use DFS. But as you can see here that we can have multiple islands inside of our grid. It means we will actually need to perform DFS multiple times. And how can we do this? Well, it's simple. we will actually go through each and every cell of this grid with the help of a for loop, just like we normally traverse a simple grid. And each time we find a 1, we will say run a DFS from this node. And in that DFS, we will end up going through each and every one connected to that particular node. And so suppose if I start from this particular one, I will end up going through this one, this one, this one, and this one. This entire land will be covered, and all of these nodes or all of these cells will be actually placed inside of a visited set. Inside of this, we will have all these nodes collected, and it means once the DFS completes for this particular island, we will not go through DFS again for any of these ones. We will just skip it. Then we will go to this particular node. We will see it's a 0, it's a water. So we will not actually place DFS here also. Then we will eventually come to this node, right? We will place the DFS on this one, and then the DFS will end on this node itself because it's a single node. So it means we have run DFS 2 times till now. Then we will reach these nodes, and here we will start running DFS from this one. We will cover both of these nodes, and then we will come back. It means the DFS has been run 3 times till now, and then we will move forward. We will find 0 here, we want to run DFS. We will find again a 0 here, we won't run DFS. We will find 0 here, 0 here, we will not run DFS. And then we will find a 1 here. We will again run DFS for this one to find out all of the ones connected with this. And that means we have used DFS 4 times till now in the grid. And 4 is exactly the answer. And then we will move on, we will find 0, we will not run DFS. And then if we move on, we will not have any element to traverse. It means this particular number 4 is basically the answer. The number of times we run DFS is basically equal to the number of islands that are present inside of the grid. So now that we have understood this thing theoretically, it is time to look at the code. So here's the code. First of all, we have this direction array that will actually help us to go up, down, left, and right from a given cell. And here I'm writing the DFS function. So in the DFS function, I'm taking the row, that is I, then I'm taking the column j, then I'm taking the visited set in which we will have all the cells that we have already visited, and then we will have grid. And here I'm saying I'm going to use a variable direction, which is basically non-local. It means that this variable exists outside of this DFS function, that is here. Then here the DFS starts. The first thing I'm doing is that I'm taking I and j and I'm adding them inside of this visited set. I am creating a tuple of I and j and I'm adding it in the set. And then I'm going through all the neighboring nodes or all the connected lands to this land. So for each direction, in the directions, I am calculating the row and column for that particular neighbor. So here I'm checking a few things. First of all, if the row is less than 0 or the row is greater than the length of the grid, or the column is less than 0 or column is greater than the length of the grid's columns, then we can say that we are out of bounds. We are outside of the grid, and it means we will not be running any DFS because these row and column are invalid. They are outside the grid. But if they are inside the grid, then here we are checking if these row and columns have already been visited or not. If they are visited, if they are inside of this visited set, we will not be running DFS because we have gone through this particular column and row anyways, right? But if they are also not in the visited, then the last thing that we are checking is what is present on this particular cell, on this particular row and column cell. If it is 0, that means if it is water, then also we are not going to run DFS. So if any of these conditions become true, then we are saying that we are not going to run DFS. We will simply continue the loop from here itself. So we will not be running this particular line. But if this condition turns out to be false, we will run the DFS on this particular row and column, and we will go through all the neighboring nodes also and mark them visited. So this marks the end of our DFS function. And now we are going to try and calculate the islands. So first of all, I have this island variable that is set to 0. Then I have my visited set that is basically empty at this point. And now I'm going through each and every element of this particular grid, just like we normally go through each and every element of a grid, right? So I have an I loop, I have a j loop, and then I'm checking if this particular I and j are not in visited, and the element at this I and j in the grid is actually one, that is a land. Then we actually run DFS on this particular I and j on this particular cell. And once we have run the DFS on this particular I and j or on this particular node, we would have gone through all the connected land or all the connected nodes, and we would have already marked them visited inside of our DFS function. So it means after this DFS function completes, we have found an island. So we will simply increment the island. We have ran the DFS function 1 time till now, and then we will keep going through all the elements inside of the grid, and we will keep on running DFS until we find all of the islands. And once this is done, we will have all the islands and we will simply return the islands. So now let us try to run this and see what happens. So yeah, our code is running and it is passing all of the test cases. Now there is a way to better optimize the space, and that is by not using a visited set. So here the reason that we are using visited set is to make sure that we do not go through the same cell again. So to do that, we can simply remove the visited set, and when we are going through the cell, here in this case, we simply mark this particular INJ cell as 0. So I can simply say grid I and j equals to 0. If I do this, I will not need a visited set, because here we have a check that we only run the DFS for I and j cell if and only if it contains 1. It means if I actually set I and j, this cell, to 0 during the DFS, it is basically making sure that I never run DFS on this particular cell again in this loop. So it is basically going to simulate this visited set. And here also in this particular condition, we are checking if a particular row and column contains 0, we will simply continue from here. We will not try to run DFS on this particular row and column. So it means going through the neighbors is handled, then calculating the DFS function cost is handled. So it means we don't really need the visited set actually. I just added it here to make sure that you understand these kind of concepts easily. But yeah, here if you do this, it will help you to optimize the space also. So now let us analyze space and time complexity. So the space and time complexity is same. It is order of m multiplied by n. You might be thinking that, hey, Satyam, we are using graph traversal, that is DFS. It should be order of v plus e, right? The number of nodes plus the number of edges. And yes, it should be this, but the reality is that we are also going through entire grid, right? And going through all the elements of the grid actually costs us m multiplied by n time complexity. And this is much, much, much bigger than this thing. And that's why in big O notation, we are basically taking this particular bigger term as a time complexity. So yes, DFS does take this much time, O of v plus e, but we are also going through each and every element of the grid in the for loops. So that's why we have this time complexity. Now the same is true for the space complexity, because we are using visited set, right? And in this visited set, we will end up storing all of the elements that are present inside of the grid. It means this m multiplied by n number of elements will be present inside of this visited set eventually. But even if you remove the visited set, what will happen is that in the worst case scenario where the entire grid is actually a simple land, there is no 0 in the grid, you will end up creating a call stack of DFS, m by n DFS calls, because you will be running DFS on each and every element, right? So that call stack, which is an implicit call stack, it is done by operating system, will take order of m multiplied by n space complexity. So you will get m multiplied by n space complexity in both of these cases. But yes, if you remove the visited set, you will be saving space in terms of absolute amount. So today we have LeetCode 329, that is longest increasing path in a matrix. In this matrix, we will have a few numbers and we have to find out the longest increasing path. For example, here we have 1, 2, 6 and 9. So this is the longest increasing path in this matrix. If you try to go some other path, for example, you can start with 9 and you try to go in this direction, you will have a lesser number. If you try to go in this direction, you have the same number. In this direction, you have a smaller number. So you cannot go in any direction and find a greater number. It means the length of the longest path from 9 is simply 1. Similarly, if you start from 4, you can go in this direction and you will find 8. Now 8 is greater than 4, that's why we are here. If you try to go somewhere else from 8, suppose I want to go here, then I will find 6. It is not greater than 8, so I cannot go here. If I try to go down, it is not greater than 8, it is 1, right? So I cannot go down also. It means I can go 1 and then 2. So the length of the longest path starting from 4 is 1 and 2. This is the length. Similarly, we will have many paths starting from each of these cells and we have to compute which one is the longest path out of all of them. Now, before we try to find out the maximum path, let us try to make some observations. First of all, let us take this particular path. We are starting from 1, then we are going to 2, then we are going to 6, and then we are going to 9, resulting in a length of 4, correct? It means the length of the longest path starting from this position is 4. Now, what about this position, the 2 position? What is the length of the longest path from here? Well, it will be 2, then 6, and then 9. Basically, the length is 3. So I can say the length from this position is 3 and the length from this position is 4, right? Now suppose that this number was not 9, it was 10. What would be the length now? If I start from 2, I will have this, and then finally this 10. It means that we will have 1, 2, 3 and 4 numbers. So now this particular position will have 4, correct? And now if I want to calculate the longest path starting from this particular position, I can simply do this. I can take the longest path starting from this next position, that is 2. So it will be 4, and I can simply add 1 for this particular cell. That will give me 5, right? Which is correct. If I start from 1, I will get 1, then I will go to 2, then I will go to 3, then I will go to 9, and then I will go to 10, which is equal to 5 steps. So it is correct. So this observation tells us that it is worth it to store the longest path from different cells or different positions, because we can use those stored numbers to calculate the path from other cells, which means we will not have to go through the entire path for each and every cell. Now the other concern is that what if there are some loops? If I can just go into this particular loop, then maybe I will just keep on going in the loop infinitely, right? So is it possible to have loops in this problem? Well, no. If you really look at it, if I'm going from 1 to 2, then 2 to 6, then 6 to 9, then the next number that I would like to go to is going to be greater than 9. So if I try to go to any number other than greater than 9, if I go to 9 again, it will not work, right? Because it is equal to the 9. If I try to go any smaller number also, it will not work because I want to go to a greater number. So it means we will not have any loop in this problem. So now let us try to figure out the most brute force way to solve this particular question. Now since we know that we have a matrix and we have to go through each and every path, we are going to use DFS, and this is a very standard algorithm. If you understand graphs, you will have to know this particular algorithm, otherwise you will clearly not be able to deal with these hard kind of problems, because it's kind of a mandatory for hard problems. So in the most brute force way, what we can do is we can take the DFS algorithm and run the DFS algorithm on each of these cells. So we can run out 9, 6, 8 and all of these cells, and what it means is that I will end up running DFS on all of these cells for m multiplied by n times, where m is the number of rows and n is the number of columns. M represents this length and n represents this length. And the time complexity of DFS itself is order of V plus E, right? So V is the number of vertices or nodes and E is the number of edges. So the total time complexity will be M multiplied by N whole multiplied by V plus E, right? So what is V? Well, V is the number of vertices, and how many vertices do we have? We have these many vertices. Each and every cell represents a vertex here. So we will have M multiplied by N vertices plus how many edges do we have? Well, in the question it is already told to us that we can go to left, right, up and down. So we have 4 edges because we are able to go to 4 direction, right, from any given node or any given vertex. So we have 4 edges. Now this 4 is per vertex. It means for each vertex we have 4 edges. So how many edges are we going to have for each and every vertex? We will simply do this. 4 multiplied by M multiplied by N. Simple as that, right? Now you may be saying that Satyam, no, this is not correct. You can go here and this is out of bound and this also is out of bound, and we have multiple nodes like this. These are all out of bound, right? So these edges do not exist. And I will say, yes, they don't exist. But right now you are looking at a 3 by 3 grid. What if it was actually a million multiplied by 1 million grid? At that time, the vertices at the edges are going to be very less compatible to the vertices in the middle or anything in between. So in those insanely large data sets, this number is going to be very, very, very close to the exact number. And that's why we are going to take this number as the time complexity. So we will have here M multiplied by N multiplied by M multiplied by N plus 4 into M multiplied by N, which is going to be equal to M square N square plus 4 into M square N square, right? Which is going to be equal to 5m square n square, which is going to be m square n square in big O notation, because we can remove the constant. So the brute force solution of taking the DFS algorithm and running it on each and every node and trying to go through all of the paths from each and every node in the matrix, you will get this time complexity, order of m square n square, or you can also call it order of m multiplied by n whole square. So now the question is, can we do better? And the answer is yes. Yes, we can do better. And we can do better by actually using the first observation that we found. So in the first observation, we know that we can find the longest increasing path from this cell if I just add 1 to the longest increasing path of the next cell, right? So I can just take the longest increasing path from the 2 here, and I can simply say LIP of 2, and I can simply add 1 into it, and that will give me the longest increasing path from 1. If I go in this direction, then only this is going to be the longest increasing path for 1. And so what it means is that I can simply go in up, left, right and down direction and get 4 different longest increasing paths. And then I can simply select the maximum between those 4 different longest increasing paths. I will get a longest increasing path from right direction, then for up direction, then for left direction, and then for down direction. Just select the maximum of these, right? But how do we start this? How do we start storing all this stuff? Now, since we have a matrix and we have to store the values for each of these cells, we will also need to have a matrix of our own. So we will have a matrix like this. It will also be same dimension, that is 3 multiplied by 3 here. And now we can start storing inside of it. So what we can do is we can start with the 9 and we will try to find out the maximum path. If I go in this direction, I will get the same number, so I cannot go in this direction, right? If I go down here, I will get a lesser number or smaller number, so I cannot go here because I want the maximum increasing path. I cannot go up because it is out of bound. I cannot go left because it is also out of bound. So what it means is that I can only stay at 9 if I start from here. So the length is going to be 1, right? So here I can store 1. So the longest increasing path starting from 9 is 1. Then I will be here. So what is going to be the longest increasing path from here? Well, if I try to go here, I will not be able to do that because it is the same number. If I try to go here, it is a smaller number, so I cannot go here. If I try to go down here, it is also a smaller number, so I cannot go here. And if I try to go up, it is out of bound. So it means I will need to stay at 9 all the time, which means here also the length is going to be 1. Then I will reach here. Now where can I go from 4? I can go to this path, right? I can go from 4 to 9, and when I'm going from 4 to 9, I do not need to go from 9 to any other path. Why? Because I already have the maximum longest path starting from 9 stored. So what I can do is I can take the 4, okay, and then I can just take the path from the 9. So the longest increasing path on the 9 is 1, and I can simply add 1 into it, so I will get 2. And that is correct, right? Because the longest increasing path in this direction is going to be 2. So in the left direction, we have the longest increasing path as 2. Now we will have to go through other direction. If I try to go up, I will not be able to do anything. It is out of bound. So right now the maximum increasing path is going to be 1, right? So in the up direction, it is going to be 1. In the right direction, it is going to be again 1. Why? Because it is also out of bound. So right also contains 1. If I try to go down here, I will see 8. Now here for 8, we do not have anything stored. So what we will have to do is we will have to run the DFS on 8 and we will try to go here. This is the recursive DFS right now. So if I try to go to 6, I cannot go here. Why? Because 6 is smaller than 8. I need the greater number. If I try to go down, I will not be able to go down because it is also smaller. If I try to go here, I cannot go on the right side because it is out of bound. If I try to go up, since our algorithm is going to be written in a way that we will allow to go up, will I be able to go up from 8 to 4? Well, I cannot. Why? Because 4 is smaller, so I don't need to handle this particular case, right? Because 4 is smaller, so I will not be able to go to 4 again from 8. So this is going to be handled automatically. So from 8, I was not able to go anywhere else, so it means the length from 8 is going to be 1. So it means the longest increasing path from 8 is going to be 1. So I can simply store that 1 here. And now I will go back to the 4 and I will add 1 to whatever path I got from 8. So it will become 1 plus 1, 2. So in the down direction, I will have a candidate of 2. Now here I just need to select the maximum of these. So the maximum is going to be the value 2. So I can simply store 2 here. Now as you can see here that we have been able to store 1 here also, right? We also had the same candidates for 8 also. I just did not write them down. The candidates were simply 1, 1, 1 and 1. Okay, that's why I did not write them down because I did not need to write them down. That's why we actually selected 1 and placed that here. So now we have 6 here. If I try to go this side, I cannot go, right? Because it is the same number. So I will get a 1 here. Then if I try to go to left, I will again get 1 because it is out of bound. If I try to go down, I cannot go here because it is less than 6. So I cannot go here. So it is going to give me 1 again. Then if I try to go up, I can go because 9 is greater than 6. So the up is 1, right? So I can add 1 plus 1 is equal to 2. So I can store 2 here. And this is going to be 1 because we already calculated it right here for 8. Now this 6 is done. We will go to the next one. So for this 6, we cannot go in this direction because it is same. So we will get a length of 1 here. If we try to go down, we cannot go down because it is less. So we will get a length of 1 here again. If we try to go up, we will get a length of 2. Why? Because the up actually contains a length of 1. So 1 plus 1 is equals to 2, right? If we try to go to the right, then I will get a length of 2 again. Why? Because 8 have a length of 1. The maximum increasing or the longest increasing path from 8 is 1. So I will again add 1 to this path and I will get a path from 6. So this is 2, this is 2. Okay, so the maximum is simply 2. So I can simply write 2 here. And now this 8 has already been calculated right here. So we don't have to go through it again, right? Now we can go to the next cell, that is the 2. If I try to go right, I cannot do that because it is less than 2. So I will get a length of 1 back, right? If I try to go left, it is out of bounds. So I will get a length of 1 here again. If I try to go down here, I cannot do that because it is also out of bounds. So I will get a length of 1 from the down also. If I try to go up, I will see that 6 is greater than 2. I will check the matrix. So there is something stored in the matrix. So I will take the matrix value 2 and I will simply add 1 to it and I will get my path. So the maximum path from 2 is going to be 3. Now we will reach this one. If I try to go to left, I will get this 3. So I will take 3 plus 1, that is 4. So the left candidate is 4. If I try to go up, I will get this 2 here, right? So the up candidate is going to be 2 plus 1 is equal to 3. If I try to go down, I will not have anything. It is out of bound, right? So I will get 1 back. So the down candidate is going to be length 1. Now if I try to go right, it is same, so I cannot do that. So I will go back to the 1 with a length of 1. So the right candidate is also the length 1. So it means the maximum here is 4. So I will end up storing 4 right here. Now the only remaining element is this one. So if I try to go up, I will see that there is something stored in the matrix, that is 1. I will take 1 plus 1 is equals to 2, right? If I try to go left here, I cannot do that. Why? Because this is basically the same. So I cannot go to left here. So this will return a length of 1 here. So the left candidate is going to be 1. If I try to go down, I cannot do that because that is out of bounds. So I will return back with a length of 1. If I try to go right, it is also out of bound. 1 length again. So it means the up candidate is 2, the left is 1, the right is 1, the down is also 1. So the maximum is 2. So I will store 2 here. And this cell was filled with 4. I erased it by mistake. So I will just add 4 again here. And now our matrix is complete, right? Now we will take the maximum value in the matrix and that is going to be answer. So we can simply take 4 and answer is going to be 4. So this is how it's going to work. And so you can already see that we were able to reduce many recursive DFS calls by using the already stored values in this matrix. And that reduces the time complexity by a huge amount. But before that, let us look at the code. So this is the code. First of all, I'm taking the rows and the columns from the given matrix. This makes it easier to do calculations later on. I don't have to keep writing length matrix and the length matrix 0. And here is the DP hash map. You can also create a 2D array if you want, because that's what we discussed in the drawing explanation. But using a hash map feels more simple to me. Then we have this particular variable Max-Heap. It is going to keep track of the maximum value that we have encountered till far in the execution. Then here is the DFS function. We are taking the row, the column and the previous value because we need the previous value to compare if we should run the DFS on the current value or not. If the current value is same or less than the previous value, we should not go ahead, right? So that's why we have previous value here. Then we have the non-local Maxi. What we are saying is that we are going to access a non-local variable Maxi outside of this function. And here are the base cases. So if the row or column is out of bound, we are going to return 0. Similarly, if the current value of the matrix is basically less than or equal to previous value, we are again going to return a 0 because we are trying to find the maximum increasing path. And the final base condition is that if we have already calculated the longest increasing path for the given row and column and we have already stored it inside of the DP hash map, then we can simply return that value. Then here we are running the DFS call on 4 different directions. This is going to run the DFS call on the lower direction or the down direction. It is going to run it on up direction. This is going to run it on the right direction and this is going to run it from the left direction. And each time we are adding 1 to the result that we got from the DFS call for that direction to get the maximum increasing path starting from the current node in that direction. And then we are checking if this particular length is actually greater than the current result. If it is greater than the current result, we will take that length and we will store it in the result variable. And then we will take the new result variable and then we will go in the next directions. Okay, and then we will again make the comparison for this new result variable to the longest increasing paths present in the other directions. And then eventually we will have the longest increasing path stored in the res variable for this current node or this current row and column value. And then we will simply store this res inside of this DP so that we will be able to access this value later on in the code execution. And here we are making sure that if the current result is actually the maximum result that we have found so far, then we will actually update the Maxi variable also, because this is going to contain the answer because it is actually tracking the maximum that we have seen so far. And here we are simply returning the result, ending the DFS call. And now here I'm running a loop on rows and the columns of the matrix to go through all the elements that are present in the matrix, and I'm trying to run a DFS on all of them. The reason this works is because if we have already gone through this particular row or column and we have already stored the value in the DP, this first base condition will hit the second we start the DFS and we will return immediately. We will not go to this particular section ever. So that's why this works. And now at the end, we are returning the Maxi because we actually kept track of the maximum length that we got so far. So Maxi is the answer and we will return that. So now let us run it and see what happens. So our solution runs in 194 milliseconds and beats 27.58% solutions on LeetCode, and that's pretty much as efficient you can get about it. And also you cannot really trust these numbers all that much because they change each time you submit the code. So now let's look at the space and time complexity for this particular solution. So the space complexity is order of m multiplied by n because we are actually creating another matrix or hash map that will have the same size as the given array, because we will have to store values for each of the cells in the given array. So this will contain m multiplied by n elements, hence we get the space complexity to be m multiplied by n. But the main thing is time complexity, and right now it is m multiplied by n. Earlier it was actually square of m multiplied by n, but right now it is simple m multiplied by n. So how did it reduce so much? Well, before making this video, I saw one of the LeetCode's video on this particular problem, and there he is actually explaining one of the best intuitive ways to understand it. He is simply taking two cases. In one case, every element is going to be the same, right? It is going to be 9, 9, then here also 9. So here we have 9 in each place. It means we will have to run DFS for each of these values, and we will get 1 as the length for each of these values. So in that case, we will end up running DFS. Okay, DFS will be run for each of these values. And how many values do we have? We have m multiplied by n values. So DFS is going to run m multiplied by n. And there will be no recursive DFS inside of any DFS call because all of them are same, right? So I cannot go in this direction or in this direction or in down direction or in up direction. So it means I will always be on the same cell. Why? Because all of them are same and I need a greater element, not the same element. So in this case, the DFS is running m multiplied by n times. Now the other edge case is that all of them are actually increasing 1, 2, 3, 4, 5, 6, 7, 8, and 9. So it means I can start from the 1 here, okay, and I will run the DFS. I will have a recursive DFS from the 1 then. So I will go to 2, I will run a DFS here. I will go to 3, I will run a DFS on this one. I will go to 4, run a DFS here. Go to 5, run a DFS here. Go to 6, here also I will run a DFS recursively. Go to 7, DFS. Then 8 also will be actually called. Then 9 also will be done. So it means after starting DFS from 1, I will end up going through each and every cell inside of this grid, right? So it means this particular first DFS call actually costed m multiplied by n recursive DFS, right? This is the recursive DFS count. But the thing is that now you don't have to run the DFS for any of these other cells. Why? Because they have already been calculated and stored inside of this grid somehow. So it means the DFS calls for each of these cells is going to take order of 1 time complexity now. And in the smaller example, this might not be very accurate, but when you are going for 1 million by 1 million cells, right, or 3 million by 3 million cells, well, at that time, this is going to overtake this order of 1 time complexity by a huge margin. So at that time, we can directly say that it is order of m multiplied by n time complexity. So this is an intuitive way to figure this out. If you try to go for mathematical way, that can actually get very complicated. So yeah, that's why I'm not going into the mathematical proof, but you can of course go ahead and learn it online. I mean, there is ChatGPT and Gemini available at your fingertips all the time now. And so that is why the time complexity is order of m by n. Hello everyone, today we are going to learn topological sort because it is one of the most important topics in DFA interview questions. So what is a topological sort? Well, it is a linear ordering, or you can also call it a sequence of nodes, and in this ordering the node u will be written before the node v if there is an edge between u and v like this. So it simply means that we will have a graph and we have to write the nodes of this graph in a sequence where the node u and node v, if there is an edge between u and v like this, we will have to write u before v in that sequence or in that ordering. So suppose that we have this particular graph and now we have to find out the topological sort for this graph. There are a few topological sort or topological ordering available for this, and all of those orderings are valid. You can use any of them. All you need is one. So by definition, we notice that if there is an edge between u and v like this, we have to write u before v. It also means that we can write v after u, right? So if I start from the ending node, the leaf node 6, then I can write it like this. So I have 6 here. Then there is an edge from 5 to 6. So I want to write 5 before 6. It means I can simply write 5 here. Then I also have 7. So we have an edge from 5 to 7 like this, right? It means we have to write 7 after 5. So it means I have to write 7 somewhere after 5. Where should I write it? Should I write it after 6 or should I write it before 6? Well, both of them are fine. Both of them are valid ordering. Why? Because 7 and 6, they do not have an edge. So you do not need to worry about in which order you want to write 7 and 6. You can write 7 and 6. You can write 6 and 7. So I write 6 and 7 here. So I have 5, 6 and 7 at this point.
And now that we have written 5, it means that we have gone through this entire part of the graph, right? It means I need to figure out the 4th. So what are the other nodes that have an edge to 5? Well, we only have 4, right? So we have to write this node before 5 because we have an edge like this. So we can simply write 4. Similarly, we can write 3 here, then we can write 2 here, then we can write 1 here. So this particular ordering is a topological ordering or a topological sort. We also have another topological sorting for this graph. 1, 2, 3, 4, 5, 7, 6. So in these two sorting, the only difference is the order of 7 and 6. Here we have 7 and 6. Here we have 6 and 7. The reason we could interchange these two numbers is because there is no edge between 6 and 7 directly. This edge does not exist. So it doesn't matter in which order we write them. So here we started from the ending node, the leaf nodes. But if I start from the first node, what will happen? Well, I will simply write 1. Then I will see if there is an edge like this between 1 and any other node. Yes, we have 2. So we will simply write 2 after it because the node u needs to be before v. So here the u is 1 and then the edge is like this and then the v is 2. So we are on the right track, 1 and 2. Then from here the u is 2 and the v is 3. So we are going to write 3 here. Similarly, we will write 4 here. Similarly, we will write 5 here. And then we have 5 as the u and we have 2 v's. One is this and one is this. So we can write 6 here and then 7, or we can write 7 and then 6. It is completely our choice. So this is also a way for you to figure out the topological sorting. Of course, currently we are using our eyes to figure out these sortings, and we cannot do that in very complicated graphs, and so we will have some algorithm for them. But this is a very rudimentary way for you to figure out, okay, this is going to be the topological sorting for this particular graph. One thing to keep in mind is that topological sortings exist only for DAGs, which means directed acyclic graphs. So why does it not exist for normal graph? If I have a graph like 1, 2, then 3, then why can I not figure out the topological ordering for this particular graph? It is an undirected graph. We do not have these kind of arrows, right? So why can I not figure out the topological sorting for an undirected graph? And the reason is because any edge here does not represent a one-way connection. For example, here we have an edge from 1 to 2, right? But what this really means is that we have an edge like this, 1 to 2, and we have another edge like this, 2 to 1. We are simply representing these two edges with the help of a single edge, and we are removing arrows to say that, okay, we have a two-way connection. We can go from 1 to 2 and 2 to 1. But here's the issue, right? If I can go from 1 to 2 and 2 to 1, how can I write an ordering for these two nodes? Suppose that we don't even have the third node. What about these two nodes? Can I write topological sorting for these two? I cannot, right? Because if I say that this is u and this is v and we only look at this particular edge, we will end up writing 1 before 2, right? But there is also this edge, right? It means we need to consider this edge also. So because of this particular edge, we will have to say 2 needs to come before 1. Because for this particular edge, 2 will become u and 1 will become v, right? And this is the issue that we are facing. We are not able to figure out whether we should write 1 before 2 or we should write 2 before 1, because we actually have two edges here, right? It's not a single edge. And that is why we are not able to write topological sorting for undirected graphs. But why the acyclic graphs? Suppose that we have this graph. We have an edge from 1 to 2 and then we have an edge from 2 to 3. So if I try to write a topological sort for this particular graph, it will look like this: 1, 2, 3, because we have u, then v, and then we have this particular edge, right? So u is appearing before v, and then for this particular node, this is the u, this is the v. So here also the u is appearing before the v. So it is okay, it's a perfectly valid topological sorting. What if I have an edge from 3 to 1 like this? Then what will happen? Well, if I start from the 1, then till reaching 3, we will get this particular topological sorting. Till now, everything is fine. But as soon as I reach 3, and I say that 3 is the u now, and 1 is going to be the v again, and this will be the edge, now I have a problem, right? The u, that means the 3, should actually exist or written before 1. But if I try to do this, then it will become like this. Then we have this particular 1 duplicated, but we don't have two nodes as 1. We only have a single node. So how can we write this particular sequence? Because I end up creating a duplicate here. And this is not a valid ordering, right? Because we only have 3 nodes. We don't have 4 nodes, right? And so it means here also we are facing the same issue. Whether we should write 1 before 3 based on this implicit edge. So whether we should use this and write 1 before 3 like we have here. We have 1 here and 3 here. Or we should use this edge and write 3 before 1.
And so we end up in the same situation again, not able to decide whether we should write 1 before 3 or 3 before 1. And that is the reason why we do not have any topological sorting for cyclic graphs also. And that is why we are saying that the topological sorting exists only on DAG, directed acyclic graphs, the graph that have nodes and then edges like these directed, and they do not have any cycles. Only for them we can figure out any topological sorting. Otherwise, in every other case, we will have this particular situation repeat again and again somehow, and we will not be able to create a topological sorting for those other cases. Now, here is a big question. Since the topological sorting is very important, what exactly is the use of it? Why are we even trying to create a topological sorting for a graph? Well, it is really useful, guys. Suppose you are actually working in a big company. Okay, in that company, you are having a big project, and that project is divided into components. Component A, right? Component B, then we have component C, then we have component D like this. Okay, then we suppose have a component E. Now all of these components are basically created by different teams. So different teams are working on this component, but that does not matter here. Okay, so you have the components. Now suppose that D is actually the base component. This is the component that is actually going to provide facilities or functions or libraries to other components, so that other components will not have to create their own functions. They can simply use the common functions from the D component. What this means is that there will be an edge from D to C, then D to B. And let us make an edge from D to E also. So it means that these three components E, B, and C are using functions or libraries created in the D. And then we have the A. So A is taking some stuff from E, then A is taking some stuff from C, then A is also taking some things from B, and then eventually we get a product that something user can use. So we have been able to create this particular graph. It is called the dependency graph for components because C depends on D and then A depends on C, right? So when you will try to place your application on production, you will have to build this particular application. Building simply means taking all the code that is present in these components and converting all that code into platform specific code or machine code like 001 or something like that. You might end up creating something like byte code in case of Java, but that doesn't matter. Eventually, you will have to take all these components and build them into some kind of file. So when you are trying to build these components, then it will become very important for you to figure out which component to build first, right? Because you cannot build C until you build D. Because C uses functions from the D, it means if you try to build C before D, you will get an error that the function from the D does not exist. So it means the first thing you need to build is D. Then only you can build E, C, and B. And then only you can go ahead and build A. If you try to build A first, you will get the error that E does not exist, C does not exist, or B does not exist. And so what this means that there is a particular ordering or a particular sequence in which the component needs to be built. First, we need to build the D. Then we can go ahead and build E, C, and B in any ordering that we want to build them. And then only we can go ahead and build A at the last. And this particular ordering or sequence is basically the topological sorting. So it means these are the kind of places where we actually use topological sorting. We will have to first build D. So D will come first here. Then we can build ECB or BCE or CBE in any order. So I will say ECB is my choice. And then only I can go ahead and build A. So this is one of the linear orderings that is a topological sort. There can be other ordering also. If I try to build D first and then I can build C, B, or E, and then in the end I build A. This is also a valid ordering. So this is the place where we actually use topological sorting. And there are hundreds of other use cases where you can use topological sorting. Now, one more thing is that suppose I have a dependency from E to D. And this is the kind of cyclic dependency that we do not want in production code ever, because it makes it impossible to build this production application. We will have to figure out some workaround through this particular dependency. So since we are dealing with graphs, there will be two ways to figure out the topological sorting. One is DFS and then we have BFS. We are going to look at the DFS here first. So suppose that we have a graph like this. Now we want to figure out the topological sorting for it. The first thing that we can do is we can take all of the leaf nodes in the graph and take them and place them in the sorting order. We have 4 here. Then we can go backwards. So from 4 we can reach 3. And so I will simply write 3. Then I have two options. I can go 1 or I can go 2. It means I can simply write anything like 1 or 2 or 1. It's my choice. And then from here we have this particular node, right? 0. So 0 needs to come before both 1 and 2. So 0 will be here. So in this approach, we actually took the last node, the last leaf nodes, and then started from there, just backtracking from there, right? And so that is exactly what we can do with the help of DFS also. So here is the DFS algorithm that we can use to find out the topological sorting for any graph that we want. So in the DFS, first of all, we are taking the node and we have a visited array. If you do not understand how DFS works, please watch my other video in which I am explaining DFS. That is a prerequisite for this video. This visited set contains all the nodes that we have already gone through. Now inside of the function, first of all, we are marking this particular node as visited so that we will not go to this particular node through any other particular node and edge ever again. And once we have marked it true, we will use a for loop to go through all the neighbors for this particular node in the adjacency list. So we will take all the neighbors for this node in the adjacency list and we will check if that particular neighbor has not visited. If it is not visited, then we will run the DFS on this particular neighbor also. But if it is visited, we will simply skip it. And at the end, after the entire for loop completes, we will simply take the current node, this one, and place it inside of a stack. So it means we will have a stack like this. Now, if I try to use this particular function on this graph, what will happen? Well, I will start from 0. Suppose I will be on DFS of 0. So D of 0, we have started here. Now I will mark it true in the visited set, and then I will go through all of its neighbor nodes. So neighbor is 1 and 2. Then I will just take any direction. Suppose I take the direction of 1. So I will go here and I will have DFS of 1. Now I will mark this 1 true and then I will go to the next node. The neighbor of 1 is 3, right? Then I will go in this direction. I will have a DFS of 3 and then I will mark this also as true in the DFS function. And then we will go to the next neighbor, that is 4. Then I will have this DFS of 4 and here I will mark it true. Then I will use the for loop to go through all of its neighbors, but I will realize that it does not have any neighbors, right? There is no outgoing edge from 4 to any other node. It does not exist. It means it is a leaf node. So this for loop will simply exit because this adjacency of nodes will be empty. And once it is exited, we will use this particular line stack.append and we will append the node 4 inside of the stack. So we will have 4 here. Then we will end up going back from D of 4 to D of 3, right? And now we will try to see if there is any other node connected to 3. Well, we do not have any outgoing edges. We do have an incoming edge from 2 to 3, but that is not an outgoing edge. We do not consider that. We only consider the outgoing edges. There are no other outgoing edges, so it means that this for loop that was running in the call of DFS3 will also end and we will reach this particular line, the stack.append node, and we will append 3 also in the stack. Then we will go back to the 1. We will come back here on DFS of 1 and here we see that there are no outgoing edges anymore. That means the for loop for 1 will also end at this point and we will reach this stack line. We will end up adding 1 in the stack. Then we will go back to the 0 and we will try to see if there is any other outgoing edge. We have an edge from 0 to 2. So we will go for DFS of 2 now. Now here also, first of all, we will mark it visited inside of this visited array. Then we will see the for loop. We will try to go through all the neighbor nodes for this 2 node. We will see that there is one neighbor, that is 3. But we will check if the visited of 3 is true or not. If it is true, we cannot go inside of it, right? It will be true here. Visited of 3 will be true. We cannot go inside of it. And that means we will try to go to some other neighboring node. But 2 does not have any other outgoing edges, right? 3 was the only one. So it means the for loop will end at this point and we will reach the stack line. We will append this particular node 2 in the stack again. So we will have this particular node 2 here. And then we will go back from 2 to 0, right? And then here on DFS of 0, we will try to see if there is any other neighboring node available for 0. There is no neighboring node available now. So the for loop will end for 0 also. And then we will reach this stack line for 0 also. We will append the 0 in the stack. So it means we have 0, 2, 1, 3 and 4 in the stack. And now I can just start taking them out. I will take out first of all 0, then I will take out 2, then I will take out 1, then I will take out 3, then I will take out 4. And this is the perfect topological ordering for this graph. It is actually one of the topological ordering because you can interchange these 2 and 1. So you can have 0, 2, 1 or you can have 0, 1, 2. That is up to you. Why? Because we got 2 inside of our topological sorting because we decided to go from 0 to 1 first and then we went from 0 to 2 afterwards. Otherwise, we would have got this thing 0, 1, 2, 3, 4. So what we are doing in the DFS algorithm is very simple. We are going through the node, we are marking it visited, we are going through all of its neighbors and then running DFS on them if possible. And at the end of the day, we are taking the current node and appending it into the stack. That's it. There are only 3 steps. Mark it visited, go through the neighbors and append it into the stack. That's it. And the intuition behind this algorithm is something that we have already discussed. In our earlier discussion, when we were discussing about what is the topological sorting, we tried to find the topological sorting from the leaf nodes, right? We just started from the leaf nodes and then we went backwards, right? We wrote the 6. Then we see that there is an edge from 5 to 6. So we will use this as U, use this as V. We will write U before V. So we will have 5 here. Then we also see that we have 7 here. So 7 and 6 does not have an edge. So I can write
6, 7 here or 7, 6 here. Depends on where I started from. If I would have started from 7, I would have wrote 7, 6. But now here we are on 5. It means this entire graph is done. Now we have u as 4, right? And 5 as v. So u must come before v, right? So we will write 4 here. Similarly, this will become v, this will become u. We will have 3 here. Similarly, this will become v, this will become u. We will have 2 here. Then this will be v, this will be u, we will have 1 here. So the same intuition is exactly what we are using in the above DFS function. We are going for the leaf nodes and we are starting from there. We are going till the leaf nodes and then we are appending the leaf node in the stack, and then only we go back and append other nodes. That's why we have first of all 4, then 3, then 1, then 2, then 0. And when we take them out, we actually get this particular topological sorting. Here is the more formal code in Python. We have the DFS for topological sorting function here. It is taking graph, then it is taking the start node, it is taking the visited set or visited array, and it is also taking the stack. You can use them as global variables also, but I'm just placing them inside of the function so that it will be easier to access them. Then the first thing that we are doing is marking the start node or this particular node visited. Then we are going through all of its neighbors with the help of this graph adjacency list. So for neighbor in the neighbor of this particular node start, we go through the neighbor, we try to run DFS on them if they are not in visited. If they are in visited, we do not run the DFS, we simply move on to the next neighbor. And once we have gone through all of the neighbors, we will simply append this node into the stack. Simple, right? The same 3 steps that we already discussed. Now you can use this function for the connected graph, where every node is connected to other node in some way. But there can be graph where nodes are actually isolated. There can be groups of connected nodes. We call them connected component. What will you do in that case? Well, here is what you will do. So in the execution part of the code, we are creating the visited set, we are initializing it, then we have the stack, we are initializing the stack also. And here in this part, we are going through each and every node of the graph. So if the graph has like 5 nodes, we are going through 5 nodes. If the graph has 100 nodes, we are going through 100 nodes. If the graph has n nodes, we are going through n nodes. And here we are trying to see if the node is already visited or not. If it is not in the visited, we will run the DFS topological sorting algorithm on that node also. This particular code will help you go through all of the connected components inside of a graph. It means you will always have the perfect linear ordering or the perfect topological sorting for any kind of directed acyclic graph. Whether it is connected or not connected does not matter. And here in the end line, we are simply printing the topological sorting. Here you can do whatever you want to do with the sorting. Now let us look at another way to find topological sort, and that is Kahn's algorithm or BFS. Kahn's algorithm is not exactly BFS, it is a modified version of BFS. But before we understand the Kahn's algorithm, we need to understand the concept of in degree. In degree simply means the number of incoming edges to a particular node. For example, here in the 0th node, we don't have any incoming edges. We only have outgoing edges, right? That's why the in degree of 0 is 0. But in case of one node, we have one incoming edge from 0 to 1. It means the in degree for 1 is 1. And we have one incoming edge from 0 to 2 also. So the in degree for 2 is also 1. And then for 3, we have two incoming edges. One is coming from 1 to 3 and then another is coming from 2 to 3. So the in degree for 3 is going to be 2. And for 4, we only have one incoming edge. That means we have 1 as in degree for 4. And we are going to use the concept of in degree to our advantage to find the topological sort. So here's the adjacency list for this particular graph. The 0 is connected to 1 and 2. The 1 is connected to only 3. The 2 is connected to 3. 3 is connected to 4 and 4 is not connected to any other node. And here we have the array that contains the in degree for each of these nodes. Now we can start finding the topological sort. So first of all, we will create the topo list. In this, we will store all the topological sort. And then we will also need a queue because it is a BFS. So of course, we are going to need a queue. Now in the queue, we are going to store all of the nodes that have the in degree of 0. So currently the only node with 0 in degree is the 0 node itself. So we will store 0 here as the node. And now we can start the BFS. So first of all, what we will do is we will take out this 0 and then we will store it inside of this topo sort. And then we will go to all of the nodes connected to the 0, node 1 and node 2, and we will reduce their in degree by 1. So currently the in degree for 1 is 1. It will be reduced to 0. And the in degree for 2 is also 1, it will also be reduced to 0. What we are essentially doing is that we are starting from the nodes that have in degree 0. That means no other node is actually depending on them. They are the one who is depending on other nodes. So we will take these nodes and we will basically cut off these links, these edges. That's kind of what we are doing. And that is why we are placing the nodes with 0 in degree in the queue first, and then we are taking out the nodes and then placing them in the topological sort. Now that we have reduced the in degrees of the nodes connected to the 0th node and their in degree has become 0, we will put these node 1 and node 2 inside of the queue. So we will have 1 and then we will have 2 here.
and this node has already been taken out, so it will not be there anymore in the queue. Now in the next iteration, we will take the one node out and we will place it inside of the topological sort. So we have one here, and we will see what other nodes have the one connected to it. So one is going inside of the 3 node. We have an edge from 1 to 3. It means we will go to the 3 node and we will reduce its in degree by 1. So it was 2, now it is going to be 1. And since the in degree for 3 is still not 0, we will not place 3 inside of the queue. Then we will move on to the next element in the queue, that is 2. We will take out the 2 from the queue, we will place it inside of the topological sort here, and then we will go to the nodes connected to the 2. So the 2 was going inside of the 3, right? And so it means we will go to the 3 and we will reduce its in degree by 1 again. So this was 1, now it will be 0. And now that in degree of 3 has become 0, we will take the 3 and we will place it inside of the queue. And 1 and 2 has already been taken out, so they will not be in the queue anymore. Now we have 3 in the queue. So we will take the 3 and we will place it inside of the topological sort now. This is happening in the next iteration. And now that we have taken out the 3 from the queue, we will cross it because it is no longer in the queue. We will go to the node that actually have an incoming edge from 3. So there is only one node, fourth node, that have an incoming edge from 3 to 4. So we will go to the fourth node and we will reduce its incoming edge or in degree by 1. So after reducing it by 1, it will become 0. And since it is 0, we will take this fourth node and we will place it inside of the queue here. And in the next iteration, we are going to take the fourth out, we will place it here, and now we have this 4 here, and now we will go to the nodes that have 4 as an incoming edge. We see that 4 does not have any incoming edge to any of the other nodes. It doesn't exist, right? And so it means we are done. We have gone through all of the nodes in the graph and we have figured out our topological sort, that is 0, 1, 2, 3, and 4. And we can try to cross verify it also. So in a topological sort, if there are two nodes u and v, and we have an edge between u and v, the u must always come before v, right? So let us start with a 0. So we have 0 and then we have an edge from 0 to 1. So it means the 0 should come before 1. Here we have 0 before 1. We also have an edge from 0 to 2. So it means 0 should come before 2. And that's exactly what we have here. Then we go to the 1. So 1 have an edge from 1 to 3, right? It means 1 should come before 3. Then we see that yes, 1 is before 3 in the topological sort. Then again we have 2 here. 2 is also having an edge from 2 to 3. It means 2 should come before 3 node. That is exactly what we have here. 2 is before 3 node. And then we are in the 3 node, right? So on the 3 node, we see that we have an edge from 3 to 4. So it means 3 should come before 4. And that is exactly what we have here. 3 is before 4. So it means that our topological sort is valid. The intuition behind this approach is very simple. So earlier we discussed that we can start finding the topological sort from 2 points. We can either start from this point and then go in this direction, or we can start from the leaf nodes. These are the leaf nodes in the graph, and from the leaf nodes we can go in this direction. So in case of using the DFS as algorithm to find the topological sort, we were using these leaf nodes to actually go backwards. We were going backwards in the graph from the leaf nodes, and so that was the approach that we were using for the DFS algorithm. But in the Kahn's algorithm, we are using the other approach. We are using the approach where we actually take the node which is depending on other node, and we take this node and process this node first. That's what we are doing in the Kahn's algorithm. In the case of DFS, we were taking the nodes that were not depending on any other node, and then we were actually starting in the opposite direction. We are taking a node that depends on the other node, and we are actually processing it first, because we know that if there are nodes u and v, and we have an edge like this, u depends on v, then we are going to simply take the u and place it before v in the topological sort. And that's why we have this 1, and then we have 2, and then we have 3, and then we have 4, and then we have 5 or 6 or 6 or 5, because 6 and 5 do not depend on each other, so we can write them in any order. But then Satam, you might ask that what if I start with a 3? And my answer to that is we are not going to start with the 3 ever. Why? Because the in degree of 3 is what? 1. There is one incoming edge from 2 to 3. That's why the in degree for 3 is 1. And we have already seen that in case of Kahn's algorithm, we always take the nodes that have 0 in degree. So as you can see here that the first node, this particular node, have 0 in degree. There is no incoming edge coming to this node, and that's why we are starting from the first node, because it has 0 in degree. So that's why it is working, guys. So that is the role of in degree. We are making sure that we take the node that have 0 in degree or that have no dependencies, and then we process that first, because that is going to be the first node in the topological sort. And then to find out the next node, what we are doing is that we are taking out this particular node 1, and we are reducing the in degree of other nodes that were connected to 1 by 1, right? So the in degree of 2 was 1. We took out the first node, we basically severed this connection, and we reduced the in degree of 2 by 1, and that will result in 0. And then when we see 0 as the in degree for 2, we take this 2 and put it inside the queue so that we can take this queue in the next BFS iteration. So it means after 1, we will take out the queue and we will place it here in the topological sort, and that means we have severed this connection. We have severed the connection of 2 from nodes, because we will take off the 2 and we will reduce the in degree of nodes that are connected to 2. So we have 3 connected to 2. It means we will reduce the in degree of 3 also. It will become 0. And then we will take 3 into the queue. We will run BFS on 3 and then so on. So I hope you understand why Kahn's algorithm works and why do we need in degree. We need in degree to make sure that we are not starting somewhere random in the graph. We do not want to start from 4, right? Because there is an incoming edge from 3 to 4. So if we try to start from 4, we will not be able to do anything. We will not be able to create a proper topological sort. We need to start from a node that have 0 incoming edge, because we are cutting off this node from the graph, right? If I try to start from 4 without dealing with in degrees and I cut off these connections, it means all these nodes will also be cut off, right? And that's why it becomes important that I do not start from any random place in the graph. I must start from the nodes that have 0 in degree, just like this one. So now let us see the code and understand the concrete implementation behind this algorithm. So here is the code. First of all, we have the adjacency list that I'm calling graph here. So 0 is connected to 1 and 2, 1 is connected to 3, 2 is connected to 3, 3 is connected to 4, and then 4 is connected to nothing. There is no outgoing edge. So 4 have 0 adjacency list. Then we have this function, Kahn's topological sort. Here we are calculating the topological sort from the given graph. So first of all, we are calculating the in degrees. So you can use an array or a map like I'm using here for creating the in degree. What we are doing here is we are going through the nodes in the graph, and for those nodes, we are going through their adjacency list. For example, if my node is 0, I am going through this 1 and 2, this list, and in that list, I'm taking the 1 here and I'm increasing its in degree by 1 and I'm just storing it here. Simple as that. Then I'm taking the 2 here, I'm increasing its in degree by 1 and storing it in the in degree array. Simple as that. Here, of course, I'm using a hash map or dictionary, but you can also use array. So step 1 is done, then the step 2 is to initialize the queue with 0 in degree nodes. So basically, we go through the entire in degree and we find all the nodes that have 0 in degree. If they are 0 in degree, we basically add them inside of our queue. And then we have this topo order, basically a result list. Inside of this, we will store the topological sort. And now we are going to start our BFS loop. So while there is something inside of this queue, which there will always be at least a single node which will have in degree 0, because it is not a cyclic graph. So in directed acyclic graphs, there will always be a single node at least that will have in degree 0. So we will always have something inside of the queue. So first of all, we will take out the node from the queue. We will add this into our topological order, and then we will simply go through each and every connected node from this U node, and then we are reducing their in degree by 1. And then we are checking if the in degree of this particular node is actually 0 now. If it becomes 0 after reduction, we will simply take this V node and we will append this into the queue so that we will have something for the next iteration. And once we have done this for all of the nodes, we have found our topological sort. Then here is a simple check for cycle detection. So in case the length of the topological sort is not the length of the graph, it means the length of the topological sort or the number of elements in the topological sort is not equal to the number of elements or nodes in the graph, you know that you have detected a cycle, because only in case of the cyclic graph, the topological sort will have less number of elements in it. Otherwise, we know that it's not a cyclic graph. We have found a topological order with the help of Kahn's algorithm. So that's what we are printing here. And on this line here, I'm simply calling the function to execute everything. So yeah, this was the Kahn's algorithm for finding the topological sort. We are using a modified version of BFS here. So today we have LeetCode 210, that is course schedule 2. This problem is very similar to course schedule 1. In the first problem, we were supposed to detect a cycle in the directed graph. If there was a cycle, we know that we cannot schedule or take all the courses, and we return false. If there was no cycle, we simply return true. But in this question, we are supposed to give the ordering itself. So we have a number of courses that we would like to take that are labeled from 0 to n minus 1 or num courses minus 1. Then we have a prerequisites array. This array actually tells us which course depends on which other course. For example, here, the A course depends on the B course. First, you have to complete the B course. Then only you can complete the A course. It means we have a dependency from A to B course. Now, this relationship tells us that it's a graph problem because we can have some other course that depends on A. We can have some other course that also depends on A. So it becomes a graph where each course is actually a node in the graph. For example, here we have 0 and 1. First, I need to take the 1 course and then only I can take 0. So the order should be I take first 1 course and then I go to the 0 course. So it means the order will be 1 comma 0. So this should be answered, right? Now, here the question officially asks us to give the ordering of the courses in which we need to take those courses to finish all the courses. It means there are cases where we might not be able to take all the courses. Let's take this example again. I have a zeroth course that depends on one course to be completed. So it means I need to complete the one course first and then easily I can complete the zeroth course, completing both the courses easily. What if there was also a dependency like this? 1 depends on 0 to be completed. That means I need to complete 0 before I complete 1. So now what? Which one do I complete first? And the answer is I cannot complete any of them because there is a cycle. So it means in the cases where there is a cycle in the graph, we know that we cannot complete all the courses. Yes, sure, we might be able to complete some parts of the graph where there is no cycle. But if you are talking about all the courses, complete graph, then if there is even a single cycle in the graph, we cannot take all the courses. Simple. Here is another test case in which we have to complete the zeroth course first and then only we can complete the one course. It means the order in which we should complete the courses is 0, comma 1. This should be our answer and that is exactly the output. The main goal of this problem is to teach you how to find topological sort. Topological sort is simply an ordering in which if there is an edge between two nodes from U to V, in that ordering the V must always come before U like this. So what we are saying is that if there is a graph and U depends on V, then in the ordering of topological sort, write V before U, telling that you need to complete V, then only you can complete U. This helps a lot in build system. In big companies, you have many components, component 1, component 2, component 3, component 4, and they can have interdependencies. One depend on other depend on one, this one might again depend on this one. So we can have a lot of dependencies in the system. And there we need to find a topological sort to understand which component needs to be built first so that other component can be built. That's where the topological sort is usually used. Now there are two ways to find the topological sort. One is DFS and the other one is BFS. BFS means Kahn's algorithm. BFS or Kahn's algorithm is what we discussed in the course schedule 1 problem. So we can go for DFS in this problem. Now, yes, we are going to perform DFS on this graph, but understand that we also need to detect cycle in the graph. If there is a cycle, we are simply supposed to return empty array. That's it. As we already discussed that if there is a cycle in the graph, then we know there is no valid topological sorting. We cannot create any topological sorting for that. So we need a mechanism through which we can detect if there is a cycle or not. And that's where you need the knowledge of how to detect the cycles in directed graphs. So in directed graphs, we have two concepts, that is cycle array and visited array. In visited array, you store all the nodes that have been visited, just like in a normal DFS algorithm. In cycle, you actually store the nodes that are currently visited on the path of DFS that we are taking. Let's start the DFS now and we will understand on the go. So first I'm starting from the 1. So 1 is going to be in the cycle because 1 is on the current path of DFS. Now I go to the 2. 2 now is on the current path of the DFS, so I will simply add 2 here. Now I have a choice. I can go to 3 or I can go to 6. Suppose I go to 3. Now I have 3 on the current path, so I will simply add it on cycle. Now I will simply go to 4, so I will add 4 also in my cycle. Now I have a choice. I can go to 6 or I can go to 5. Suppose I go to 5. Now I will simply add 5 in my cycle. Simple. Now from 5, there are no outgoing edges. It means that 5 does not really depend on any other course. 5 is like an independent course that you can take by itself. So I will have an output array that will define the topological sort. So once we found a course that does not have any outgoing edges, or we have already traversed through all the outgoing edges of that node, we will simply put it in the topological sort array. So at this point, 5 is the course that we can take by itself. Now we will simply return. And when we are returning, what we are going to do is we will remove it from the cycle because now 5 is not on the path of DFS traversal. We have already done it. And since we are returning, we have already gone through the 5 also, right? So 5 is what we will put in the visited set. So at this point, we are starting to fill up our visited. Now we are on the 4 and there is still one edge from 4 to 6 that we can take. So we will go from 4 to 6. We will simply add 6 in our cycle. And here in the 6, we can see that there is no outgoing edge. There are two incoming, but there are no outgoing edge. It means that we can take 6 by itself. So we are going to put 6 in our topological sort. And with that, the 6th node is also done. Now we will go back. And while we are going back, we will simply remove 6 from our cycle and we will put 6 in our visited array. It means that we have visited the 6 and we are not supposed to visit it ever again during any DFS traversal. Now we are on the fourth, and we can see on the fourth that we have gone through both the outgoing edges of this four. It means we have completed all the courses that we require to complete before completing fourth. It means we can actually complete the fourth course now. So we will simply put it in our topological sort array. And now we can go back from fourth to three. Now, while we are going back, we will cross it or we will remove it from the cycle set because 4 is no longer on the path of DFS traversal that we are going to take. And since we have completed the fourth course, we will put it in the visited set and we will not go through it ever again. So here we are on 3 and 3 does not have any more outgoing edges. It had only one that goes to 4 and we have completed all the courses till 4. It means we have completed all the dependencies of 3. It means now we can also take the third course. So I will put it in my topological sort and we can now go back from 3 to 2. And while we are going back, we will simply remove it from the cycle because it is no longer on the path and we will put it in the visited set. Now here on the 2, we still have an edge from 2 to 6. That means we still have a dependency from 2 to 6. It means that 6 needs to be completed before 2. So I try to go from 2 to 6 and we see that 6 is already visited. So we don't have to visit it again. It means we have already completed the dependency. It means we don't really need to go here. So we can simply place the 2 in our topological sort because we know we have completed all the dependencies of 2. So we can complete the 2 course now. Now we can go back from 2 to 1 and while we are going back, we will remove 2 from the cycle and we will add it in the visited. And now on the 1, we again don't have any more dependencies or any more outgoing edges. So we will simply add it in the topological sort here. And if we go back now, we are simply terminating our DFS call. So we will simply remove 1 from the cycle and we will put it in the visited. Now here you have your answer, the topo sort. This is what you can return at this point. This is going to be the answer. Now this was the happy path where we did not have any cycle in the graph. So we could easily figure out a topological sorting and we can return it. But what if? What if there was actually a cycle? So suppose I remove this particular edge and I actually create a cycle from 6 to 2. Let's completely have a new cycle and we will understand how the cycle and visited array will behave now. Now let us understand how the code flow will work. We will be on the first node starting from here. Then we will put it in the cycle. We will go to 2. Then we will put that into the cycle. Then we will go to the 3. That will be in the cycle. We will go to the 4th. That will be in the cycle. Now here we have a choice. We can go to the 5 or we can go to the 6. We will go to the 5. We will put that in the cycle. Now 5 does not have any outgoing edges. So it means that it is actually a part of topological sort. So we will have an array here. We will put 5 as a topological sort. Now we will go back from 5 to 4, removing 5 from the cycle and we will put this in the visited. We will not visit 5 ever again. Now we are on the 4th node and we still have an edge to 6. So we will go to 6 from 4th now and we will put the 6 in the cycle. And 6 itself have a dependency on other cores. There is an outgoing edge from 6 to 2. So 6 will try to go to 2 and we see that okay, 2 already exists in the cycle. It means that we found a cycle that we cannot really create any valid or correct topological sort for this graph. And if we cannot create any correct topological sort for this graph, we know that we can only return an empty array. This is going to be the answer, an empty array. Simple as that. It's really, really, really simple. Now let us go through the code also. First of all, we are creating an adjacency list here as we usually do in the normal DFS traversal for graphs. Here on the basis of prerequisites, we are filling the adjacency list. Here we are deciding which node connects to which other nodes. Here we have the cycle and visited set declared, and this is the output array in which we will store the topological sort. And here is our DFS function. We will start from a particular source node. You can also call it course if you want, but source node is what I understand better. So we will start from a source node or a course, and if that node actually exists in this cycle array, then we know that it is actually a cycle and we have to return false. We cannot create topological sort for this particular graph. We will simply return false. But if it is not in the cycle and it is in the visited, now remember that we never remove nodes from the visited. Once they are visited and in the visited array, we don't remove them because we know that we are not going to ever go through those nodes again. So we need to remember that we have visited them. The cycle array is just for a path. You will be adding and removing elements in the cycle array based on the path you are going to take. So here, in case we have already visited the node, we will simply return true. If both of these base cases are not hit, we know that we have found a course or a node that is new. So we will add it in the cycle set, and then we will go through all the nodes that connect to this particular source node. So for all the nodes that connect to this particular source node, we will perform DFS on those nodes. If the DFS return false, we know that we found a cycle and we simply have to return false. We cannot create a topological sort. Otherwise, don't do anything. Take the next node and perform DFS on the next node. Here at the end, I'm removing the source node from the cycle because I know that it does not need to be in the cycle because I'm going back. And while I'm going back, I'm adding this into the visitor so that I do not go through this node again. And also here, I'm appending this source node or this course into the output array because we know that by now we have completed all the dependencies of this node. So we can complete this node also. Now here is the tricky part. As we know that in a graph, we don't have to have all the nodes connected with each other. We can have isolated nodes also, isolated components themselves also. So for that reason, I'm basically making sure that I'm placing DFS call on every component that I can find. So I'm taking a course from the known courses, I'm applying the DFS on that course, and I'm going through that component. Now, in case after going through the component, if there is some isolated node that have not been visited, we will then be able to apply DFS on that also because of this loop. Now, if at a point we found a component in the graph that actually does have a cycle, we know that we cannot create a topological sort for the entire graph, so we will simply return empty array. Otherwise, if this entire thing passes, we know that our output array now contains a topological sort, so we will simply return that. Now let us run it and see what happens. So here we can see it takes 3 milliseconds and beats 77% of the solutions on LeetCode. This is a pretty efficient solution. Now let us talk about the time complexities and space complexities for this solution. The time complexity for this solution is order of V plus E. This is the number of courses and this is the number of prerequisites. And it is because we know that we have to traverse through all the nodes or all the courses, and we may do it based on the number of edges. We can have multiple edges from one node to many other nodes or many other nodes to one node. So E also becomes a component here. In the same way, we have space complexity as order of V plus E because we will have an adjacency list to store the graph. Now this adjacency list will take all the number of nodes and it will also store the relationship between them, so edges. So we will have order of V plus E space complexity for this adjacency list. We are not talking about the output array because it will take less space than this space. So we are going to take the upper bound. So today we are going to solve LeetCode 269, that is Alien Dictionary. I'm using the problem statement from LeetCode's website because I don't have LeetCode Premium, so I cannot show you the description from the LeetCode, but this is actually the same problem on LeetCode's website. Basically, in this problem, we have a foreign language, or you can say alien language, which actually uses the same alphabets that we use, the A, B, C till Z, and they are pretty much the same. The only thing that is different is the ordering among those letters. For example, in our normal language, we have ordering like this. We have A, then we have B, then we have C, then so on till Z, right? This is the normal ordering that we have. We always say that A comes before B, B comes before C, C comes before D, and so on. But here in this language, the alien language or the foreign language, this does not have to be true. The ordering can change. They can have B, D, M, N, K till Z, right? They can have that kind of ordering, or they can have something like A, N, D, K, M, Z till the end of the 26 letters. So they can have any other ordering that they want. That is completely up to them. We have no control over it. Just like we decided that our ordering is going to be A, B, C, D, they decided that their ordering can be something else. Now we have a non-empty string of words from this dictionary, the alien or the foreign language dictionary, and in this dictionary, the words are sorted lexicographically based on the rules of the new language. Basically, based on the ordering of elements in the new language, we have a lexicographically sorted list of words. Okay. So first of all, what is lexicographically sorted? It simply means that we have words in a sorted array. That's all. Just like we can have a normal dictionary from Oxford that will have all the sorted words, in the same way, there is some dictionary in the alien world also that have all the sorted words. And we just took some words from that dictionary and placed them in the sorted order. Now, what is lexicographically sorted? Well, in the normal dictionary, the one that we humans use, we can have two words like ape and we can have another word apple. Okay. Now, I want to sort these words. How will I do this? Well, I will take the first character and compare it. They are same. Then I will take the another character and I will compare it. They are also the same P and P. Then I will take the third character and compare them. Now as you can see that E is basically not same as P, right? And E comes before P in our ordering. This is the human ordering that we follow, right? So E will come after D, but it will come before P, right? So it means this word ape will be first in the ordering and then apple will come. Okay, this is going to be the order. First we will have ape, then we will have apple. Now understand that after this first change, okay, after this first different word or first different letter, these letters they can be in any order in both of the words. The only thing that matters is the first character that is different. Based on the first different character, we will decide the order of these two words in a list. And this is how the humans do it. The same thing is applying for alien dictionary. They are also sorting their words based on this rule. It's just that their ordering is different, that's all. So if in their case the P is actually before E, if that's what they decided that they want P before E, then in that case we will have apple before ape in their dictionary. So this will be the ordering for them, probably. So that is what the lexicographically sorted means. It simply means that they have words in their dictionary and they have sorted those words based on their ordering, which is different from the human normal ordering, and those words are placed in the words array. Now we have to derive the order of letters in this new language or the alien language. If the order is invalid, return an empty string. If there are multiple valid orders, well, return any of them. So this is a good thing. If there are multiple valid orders, we can return any of them, right? But it also hints at the possibility that we can have an invalid case where we will need to return empty string. So what does it even mean for us to have an invalid case? We will have to look into it, right? So basically, we will have a lexicographically sorted list of words and we have to find out the ordering that aliens are using. Just like we have this ordering A, B, C, D, E, they can be using some other ordering and that's what we need to find out. Okay. Now we do not need to find out all the characters of the 26 alphabets in their language. We just need to find the ordering of the letters that are present in this words array. So the words array will have multiple words and those words will be made up of letters. And whatever letters we found there, we need to consider only those letters to return the ordering. Now here we have a few rules. This rule is basically something that we have already discussed. This rule defines which word should come before the other word based on the first different character that we already saw here. This rule, the next one, is actually a little bit more important. So if the word A is the prefix of word B, A dot length should be less than B dot length. This rule is saying that if there are two words A and B and A is actually a prefix of B and A's length is less than the B's length, it means the word A should always appear before B in the given word list. For example, suppose in the normal language I have two words, app and I have apple. Okay. Now here you can see that this word, A word, is actually a prefix. Okay. It is a prefix of this another word, which also means that the length of this word, that is 3, is going to be less than the length of this apple word, right? Because the length of apple word is 5 and the length of app word is 3. So if these two conditions are true, if a word is actually prefix of the another word and the length of this word is less than the length of the other word, this word with the less length should always and always appear before the word with the greater length in the lexicographically sorted list of words. So it means if inside of this words array, we ever find something like apple, and then we are finding app, this is an invalid order. Why? Because this is actually a prefix of this and length of this word is less than the length of this word, so it should be before this word. That is what this rule is talking about. And this is one of the cases where you will need to return an empty string because this whole thing actually makes the word list invalid, so you can simply return an empty list. So how do we solve this question? Well, here we have an example. Okay, here we have a few letters like H, R, N, then we have F, then we have E, then we have just N and F again. So basically we have a few letters, that is H, R, N, then we have E, and we have F. So these are the 5 letters that we have based on the given list of the words. So we don't need to find out the ordering between all the 26 characters. We just need to find the ordering between these 5 characters. So try to think about it. How can we do this? What are the hints or what are the situations that the question is giving us? The question is saying that this list is going to be sorted, right? It means this is going to be before this somehow, right? And we know that it is also lexicographically sorted. So it means that these two words are actually sorted based on the first different letter. So what is the first different letter? Well, H and H, same, right? R and R, same. N and F are not same. So these are the first different letters. What this means is that N is going to come before F. Okay, so you will have something like this. We have a pair N and F where we know that N is going to be before F, because in lexicographically sorted order, the word with the letter that comes first in the ordering is actually kept first, and then we have the other word. Just like we discussed in the case of ape and apple. Since E comes before P in our normal human ordering, that's why we have ape first and then we write apple in the dictionaries. So we could at least find out this much. And always comes before F. So now let's look at the other two words. We have HRF and ER. What is the first different character? We have H here and E here. So we will take the H and E and we can deduce that H must come before E. In the same way, we can go to the next two words and we see that E is same, right? But R and N are different. So this implies that R must come before N. So R will be before N, right? Then we can go to these two words and we can try to figure out which one is different. So we have E here and we have R here. These are the first letters that are different. So we can also deduce that E must come before R. Now what do we do with these pairs? We have four pairs and we have a few letters. Well, we can try to connect them. So we know that N connects to F, right? H connects to E. R connects to N. And E also connects to R. Now I know that E connects to R, right? So E is here and E is also here. So instead of having this, I can simply say that E connects to R, right? And also we can see that we have a one N here and one N here. So it means that this particular N is basically the same. So if I try to make it better, it will look something like this. We have H here. I'm starting from here, okay? So we have H, then we have E, then we have R, because we have E, then we have R, then we have N, so it will come to N, so we will have N here, and after N we have F, so I can just write it like this, we have F. So the relationship between characters actually looks like this. This is basically what we are able to connect. Now here you can see that we have something. It is basically a letter, but let's just call it something. It can be anything. A configuration, state, situation, place, right? So it is something. And then we have this rule. There is a rule that is allowing us to connect from H to E somehow. So what it means that we have something and we have a rule that is allowing us to go from one thing to the other thing, right? So I can simply call it a node, right? That something is nothing more than a node, and that rule is nothing more than an edge. So I can just convert this whole thing into a graph, right? Because that's the rule of graph. If you have something and this thing can be anything, like a normal configuration, it can be state, place, position, whatever, it could be anything, and you have a rule that is allowing you to go from one thing to the other thing somehow, okay, then these two observations simply mean that you actually have a graph, and that is exactly what we have. We have a graph here. Now this arrow actually represents the rule, that's why I'm just removing it, but we do have a graph like this that is starting from H and ending at F. It is a directed acyclic graph because we are allowed to go from H to E, but we are not allowed to go from E to H. Why? Because these edges are actually based on the rule of sorting, lexicographical sorting, the ordering between the letters, and that's why we don't have any edge from E to H again. So what this means is that all the letters that are present in the list are nothing more than nodes, and the property of sorting the letters actually helps us to go from one node to other node. And now a lot of you guys will be able to do this problem because it is a simple graph. That's all it is. Now you guys must be thinking one more thing, that hey Satyam, you are actually comparing this word to the next word. Why can't I compare HRN with this ER? And the answer is yes, you can. You can compare the first word with the third word and it will give you H to E. So there will be a relation from H to E also, right? And we already have this relationship right here. So let's take another example. We can have HRF and I can try to compare it with RFNN. So here I can see that H and R are different letters. So it means that there is an edge between H and R. So it should look like this, right? There is an edge from H to R. So you can do that. You can have an edge from H to R, but this new edge is actually not needed. Why? Because these edges are actually implicitly trying to tell you that, hey, you can go from H to R. H will always come before R. That's what these edges are representing. And that is why we did not need to take an element and then compare it with all the other words in the list. We can take the two adjacent words and just compare them, because if you try to compare each word with each other word, you will have edges, like many edges, and most of them are simply redundant, like this one, right? We don't really need this edge because these two edges are implicitly conveying that we can go from H to R. So even if you have this other edge, it will not really change the answer anyways. Yes, it will make the calculation a little bit more messy, but it will not really change the answer. It will not have any effect in the logic. So this is the graph that you are able to create based on the given example. And this is a very simple graph, right? You can actually just look at this graph and you can figure out that, okay, this is the ordering, okay? So you have the H, E, R, and F. This is the ordering, or you can simply call it, this is the answer. This is something that you can return and that will pass the test case. But let me tell you guys that not all of the graphs that you can generate are going to be this simple. You can have crazy graphs. Right now, this is a simple linear graph, but you can always have graphs like H, E, then E will be connected to, like, just say F, right? Then H can be connected to here R. So this can also be a graph that you will find in the questions. And now it is not very clear which ordering you should take, right? Because you have two orderings. You can go from H to E, then you can go from E to F, and you also have this ordering that you can go from H to R. So you can write H, R, E, F, or you can write H, E, R, F. The only thing that matters is that H must come before E and H must come before R. Okay, so H is before E here and H is before E here. H is also before R here and H is also before R here. Now, what is going to be the order between R and E? Well, that does not matter. Why? Because there is no edge between E and R. So we cannot say what is going to be the order between E and R. It can be anything. So both of these orders are actually valid. And the reason that we have F at the last is because we know that F must always come before E. And that is why if E is here, F needs to be here. Even if E is here, F will be here. Now here in this case, you can change the F. You can make it H, E, F, R. So this is also a valid ordering. Why? Because we have E after H. Okay, so E is after H. We have F after H. So F is also after H. And we have R after H here. So R is also after H. So that is why we have three ordering here. 1, 2, 3. So which one are we going to take? And yes, the question is saying that we can return any ordering, which is very good. But how can we even figure out these ordering? What is the way to figure out these kind of ordering? And so here is something that you should observe. So if you have two nodes, H and E, and there is an edge between H and E like this, that means H is going from H to E, then H should always appear before E in the given ordering. What kind of condition is this? This is the condition for topological sort. In topological sort only, if we have two nodes, U and V, and we have an edge from U to V, the U will always come before V in that ordering. So this whole alien dictionary question simply reduces down to topological sort of the graph. That's all you have to do. You will have a graph like this or like this one, and you just need to figure out the topological sort for that graph, and that will be your answer. Isn't that intuitive, guys? Now you can find the topological sort with the help of BFS, or you can find it with the help of DFS. Now DFS is definitely preferred way. Why? Because BFS is actually very cumbersome way. You need to keep track of multiple things. That's why usually people do not use BFS and they simply use DFS. Even though it is a recursive solution, it is a lot more simpler to implement, and that means you will have less errors when you are doing interviews. Now if you do not know what is topological sort or how to find topological sort with the help of BFS and DFS, I have already created a video completely explaining what topological sort is and how to use BFS and DFS to find the topological sort. So you can go ahead and watch those videos, but here I will simply give you a very quick short overview of it. So topological sort is nothing more than post-order traversal. If you know what is a post-order traversal of a graph, you know topological sort. So to find out topological sort with the help of DFS, you can simply do a post-order traversal. You can start from the node and you will simply go to the depth of the nodes. And once you have reached a node that is a leaf node, you will simply take that leaf node and you will put it in a stack. Okay, so suppose that I have a stack here. I will put that node inside of the stack R, and then I will go back. Why? Because this is a leaf node, so I need to go back. I will come back here on the edge, and then I will go to the other branch. So I will go to the E, but I will not do anything right now. I will try to go to this left side, but it does not exist, so I cannot do anything, right? So I will simply come back easily and I will go to the right side. I will find a leaf node F, right? So now I cannot go here and I cannot go here because they don't exist. So I will take the node value, that is F, and I will place it in the stack. Okay, and then I will go back. I will go back to E, and I see that there are no more children or no more neighbors that I need to deal with for E. So it means the E is completely done. I will take the E, I will place it inside of this list, and then I can simply go back to H. Now H is also done. We have gone through the left neighbors and we have gone through the right neighbors. So H is done, and I will simply place it inside of this stack. And now we can simply keep on popping. We will have a string S, and we can pop the element H, and then we will pop the element E, we will pop the element F, and then we will pop the element R, and this will be the string. This will be the answer that we can return. Simple as that, guys. All you need to do is get the post order traversal of your graph. That's all. That is literally all you need to do to find the topological sort for a given graph with the help of DFS. Now, yes, there are some edge cases like cycle detection. So suppose that we had a graph like this. We had only E and we had only R. Okay, so we only had two words in the given dictionary and we could only find two letters from those words. So we have E and R. So E will be placed before R in an ordering. But what if there was an edge from R to E? Okay, so we have a cycle here. We can go from E to R and R to E again, right? It's a cycle. Now this is an invalid case. Why? Because what does this even mean, right? If you say that we have E before R and then you are saying that we have R before E, so what does this thing mean, right? What does it mean? It does not mean anything because in an alphabetical ordering, you cannot have the same alphabet come twice. So it means it is an invalid case. And if you ever see a cycle like this in the graph, you are supposed to return an empty string as answer. This is going to be the answer in this case. And so detection of the cycle in graph is very important. And you should go ahead and watch my video on topological sort to figure out how we actually decide whether there is a cycle in the graph or not. How do we detect the cycle in the graph? With both DFS and BFS. So both of them have been explained. You will find the links in the description or the card somewhere here. So now that we understand what we need to do, we can go ahead and look at the code. So here we have the code and we have this function foreign dictionary. So the LeetCode function name might be different, but the logic is going to be the same. So we will first of all have a set nodes. In this set, we will store all of the letters that we can find from the words dictionary or the words list. So right now we have empty set for nodes, and then we are taking each word from the words list and we are figuring out all the character in that word and we are adding those character inside of this set. Now even if we try to add the same character multiple times in the set will only keep one value for that character. It will not keep multiple copies of that character. So that's why we are able to add characters easily. Now here is the part where we are actually building an adjacency list. So we have this adjacency list variable here and it is basically a hash map. So what we are doing is we are initializing the hash map like this. So for each node in the nodes set, we are creating a list in this dictionary. So what it means is that each letter that is present in the nodes now will be present in the dictionary also as a key, and its value will be an empty list right now. And in the empty list, we will simply store the other character that we are connected to. So here we are figuring out the length of the words list, and now here we are simply figuring out the edges between the character. So we are taking two adjacent words here, word 1 and word 2, that are present at I index and I plus 1. And then we are figuring out the minimum length of the word between them because we need to check for the invalid condition where a word is a prefix of the other word and the length of this prefix word is less than the length of the other word, but this smaller word is actually coming after the larger word. So that is the case that we are checking here. If that is the case, then we can simply return an empty string. Why? Because it is an invalid case. This should never happen. This is an invalid case. Now if this case is fine, we can move on. And now here we have a loop. So we are comparing the character between word 1 and word 2. So if the character at jth index at word 1 and word 2 is different, it is not equal, then we are going to say that the character in word 1 have an edge to the character in the word 2. Just like we did in that drawing explanation. We can have two words, HR and H and K, and we can find the first different letters. So it is R and N, and then we are saying that R have an H to N. What it means is that in the list, in the adjacency list, we will have something like this. The key will be R, and it will have a list, and in the list we will store N. So it represents that we have an edge from R to N, and that is exactly what we are doing here. And once we find this character, we are going to break, and then we will come back here and we will go for the next set of words. Now after we have built our adjacency list, we have these sets. So these visited set, past visited set, they are actually part of DFS and topological sort, and those things are actually prerequisite mandatory things. You must know them before trying to solve hard question because they are kind of just like they are the ABCs for hard question. You need to know them beforehand. So we have visited, we have past visited, and we have stack. Stack will store the topological sort. Visited set will store the node that we have already visited, and path visited actually stores the nodes that are on the current path that we are traversing. This is used to actually detect the cycles. Okay, and now here we have the DFS function. So we are taking a node or a character and we are checking if it is already in the path visited, we are going to return the true, which means we have a cycle. Okay, we have detected a cycle. It should not be in the path visited already. Now, if we see that node is actually in the visited, we will return false. What this means is that we have already gone through this node in some other path, and now we don't need to go through this node again. Now, if node is not in path visited or node is not in visited, then you will simply take the node and put it in the path visited, representing that now we are going through this node. And now you will go through all the neighbors of this node. And if at any point the DFS of neighbor actually returns you true, then you know that you have detected the cycle in the inner parts of the graph, so you can also return true from here. That is saying cycle detected in the child. Otherwise, you have gone through all the neighbors, and now you can actually come back here. You will simply remove this node from the path visited. You will add this node in the visited, and you will add this node in the stack. Because it is a post-order traversal, that's why you will add this node in the stack after you have gone through all the neighbors. Okay, all the neighbors should be processed first. Then only this node will be appended in the stack. And then at the end, we are returning false. False means that we have not detected the cycle in the graph. And now here we are actually using the DFS function to calculate the answer. So for all the nodes that are present in the nodes, we are going to run the DFS. So if the node or the letter is actually not present in the visited set, that means we have not gone through it yet. We can simply take that node or that letter and run the DFS algorithm on it. And if the DFS algorithm actually returns true, it means we have detected cycle somehow. So we will simply return the empty string here. Now, if this entire thing actually runs before returning the empty string, we know that now our stack actually contains the topological sort. So we will simply take all the values from the stack. We will create a string here and we will simply return that as the answer. So now let us try to submit it and see what happens. So yes, our code is accepted and we have passed all the 24 test cases. So now let us look at the space and time complexity for this particular solution. So the time complexity is order of n plus v plus e, where n is basically the sum of all characters that are present in the words list. So we can have multiple words like HR, then we can have RN, then we can have NN, okay, then we can have KP, then we can have PPK, right? So sum of all these characters. So how many characters do we have? Not the unique, the sum of all. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11 characters total present in the list. So that is what the n represents. And we have this n here because we are running a loop in the starting to figure out all the unique characters from all these words, because those unique characters will actually be the nodes, right? The vertices or the nodes. So to run that loop, we are going to go through all the characters in this particular list, right? So basically we will run that loop n times, where n is the total number of characters in the given word list. Then after that, we build the graph or the adjacency list, and then we are running the DFS on that graph. That is V plus E. The time complexity for running a DFS on any graph is V plus E, the number of vertices or nodes plus the number of edges between those nodes. Here V is nothing more than the letter that we have in the nodes set, and E is nothing more than the relationship or the edges between those nodes. So this is the time complexity, and the space complexity is actually order of V plus E because we are actually building an adjacency list. And the adjacency list stores the information about all the vertices and all the edges between those vertices. So it is going to consume order of V plus E space complexity. Today we are going to understand what are priority queues and what are heaps, because they are related to each other, but they are not the same. And priority queue is one of the most asked patterns in DS interview questions. So it becomes a really important topic for you to understand. So let us start by understanding what is a priority queue. A priority queue is nothing more than an abstract data type. It is a simple ADT, abstract data type. What this means is that a priority queue is not really a data structure, like there is no implementation for priority queue as such, but it is basically a set of rules. That's what this abstract data type means. It is a set of rules that actually defines the behaviors that we want. And the rules are very simple. To be honest, there is just one rule that you need to understand, and that is the top element in this priority queue, or the first element in this priority queue, should be of highest priority. What this means is that the highest priority element should be easily obtainable. We should be able to get this element in the lowest time complexity. But here the question arises, what is exactly a priority? Well, a priority is just a number. Okay, it's going to be 1, 2, 3, 4, 7, 9, whatever it is. It is going to be a number that actually denotes the priority of the item. For example, we can have data like this, 1, Raj. We can have these kind of items inside of this priority queue. Now this number 1, this number 2, and this number 3 is going to be treated as the priority. They are going to indicate what is the priority for this particular data, Simran. What is the priority for this particular data Raj? What is the priority for this particular data Juice, right? And then it will be up to us to decide whether the 1 will represent the highest priority or will it represent the lowest priority. Will 3 represent the highest priority or will it represent the lowest priority? And that will be on our part. Do we want to say that 1 have a higher priority than 3, or do we want to say that 3 have a higher priority than 1? That is our decision. And based on these two decisions, we will end up having two types of heap that we are going to understand shortly. And this is pretty much it. This is the priority queue. It is an abstract data type, which simply means it is a set of rules. And one of the most important rule is that the top element or the first element in the priority queue should have the highest priority. Now, whether a lower number have a higher priority than a larger number, that is depending on our choice. We can set that, we can decide that in the priority queue. But the top element or the first element must have the highest priority so that we can get this number or get this element as quickly as possible. Now understand that priority queue is just an abstract data type. It is a set of rules, right? It does not really have an implementation. It is like me telling you that, hey, I want something that have four circular things, okay, that can move from one place to another place, that can basically make a sound if I want someone to get out of my way, that can actually help me play music, that can actually connect to the internet also, that can do something like accelerate and decelerate. These are my requirements, right? I'm telling you that, hey, I want something with these kind of specific behaviors or specific properties. And it turns out that a car actually implements all of these rules that I talked about, right? You can go from one point to another point, you can accelerate, you can decelerate, you can play music, right? You have these four wheels, the four round circular things, right? You have all these rules satisfied with the help of a car. But just think about it, right? It's going to be a real car with a real engine, okay? But you can also implement the same functionality with a toy car, right? A toy remote control car also implements all of these functionalities. So the way you implement these functionalities can differ. Okay, these are basically the implementation, the toy car, the real car, their implementation of the rules or the behavior or the properties that I just specified, going from one place to another place, right? Then playing music, then being able to honk on other people, right? So all of these are basically just rules, and these two implement these rules. They can implement them. But let's be honest, when we are talking about these rules, we are not really talking about the toy car, we are just talking about the real car mostly, right? It's like an implicit thing. And I believe you can guess now, the heaps are basically the implementation for priority queues. So priority queue is basically a set of rules or set of requirements, and heap satisfies those requirements. Heap is basically a data structure, a real implementation of priority queue. Now heaps are not the only implementation. We can implement priority queue with the help of an array also, or a list also. So suppose that we have a list like this, L is equals to like this, okay? Then we have a, let's just say, and now in terms of priority, let's just say the smaller element have more priority than the higher element. It means the first or the one actually have the highest priority. So this particular thing, this particular array also satisfies the priority queue right now, right? Because we can take this element fastest. It is going to be order of one time complexity, right? But understand that this array is right now sorted. It doesn't need to be sorted, right? What if we had a 6 here instead of 1? In that case, we would actually have to go through each and every element here on this list, and then we will have to find out the element with the maximum priority. In this case, it is 1, then we will return the 1, correct? But this going through entire list, then taking out the element, it is going to take order of n time complexity. Do you understand this thing? So it is having an order of n time complexity to get the element we want. And now if I want to insert an element like 7, I want to insert 7, I can simply take this element and place it at the back, right? So after 5, I will have 7 here. So basically, the time complexity for insertion is order of 1, and time complexity for extraction or finding the element is order of n, correct? And that is in the case of unsorted array. Now, what if this is sorted? What if we have an array like this, or a list like this? We have 1, 2, 3, 4, 5. Okay, we have this sorted array or sorted list. So it is going to be sorted always, right? Here you can get the element with the highest priority first easily, because it will always be the first thing in the list, right? So you can easily get this out, and getting it out will be order of one time complexity. But inserting something, if you want to insert, like let's say, I don't know, like let's say 3.5, then you will have to take this thing, place it here, right? And if you want to place it here, you will have to take all these elements and shift them by 1, and that will take order of n time complexity. So it means the insertion is order of n at this point. Here the extraction was order of n and the insertion was order of 1, and here the insertion is order of 1 and extraction is order of n. So it basically just flipped. It doesn't really give us anything useful, right? And yes, even though you can implement the priority queue with the help of these array or these kind of solutions, they are definitely not optimal. We have order of n time complexity. We can do much better. And we can use heaps to do much better. And that's why we are going to use heaps to implement the priority queues. So now let us understand the heaps. We basically have two types of heap, Min-Heap and Max-Heap. But before we go to them, let us try to understand what exactly is a heap. So a heap is a simply binary tree or BT. That's it. It's just a binary tree. But this binary tree actually implements a specific property. But before we understand that, what exactly is a binary tree? A binary tree is basically a tree in which we have a node and we have two children of that node. Okay, we have one children, we have another children. This is the left children, this is the right children, and this is the parent node. That is a simple binary tree. So we can have a tree like this. One node here, one node here, then one node here, then one node here, then one node here, right? So we can have a tree like this. Here, this node actually have these two children, and this particular node actually have these two children, right? Similarly, this node have these two children. So each node actually have two children, and two means binary, and that's why we actually call it a binary tree. Now, this binary tree is basically like a base tree, a raw material that we can use to generate many different kind of things. We have a binary search tree. We call it BST, and that binary search tree is basically a binary tree. It just implements a property that, hey, this parent node will have a value greater than the left node. So it will be like this, and this parent value is going to be less than or equal to the value in the right node. So suppose that we have a 3 here. So it means it is important that we have a value less than 3 in the left node. So I can write 2 here or I can write 1 here, right? So suppose I write 1 here. And then on the other hand, in the right child, it is important that I will have a value greater than or equal to 3. So I can write 3 here or I can write 4 here or I can write 10 here. But I cannot write 2 here because 2 is not greater than or equal to 3. So that's why I need to write something like 4 or 3 here. And now this has become a BST or binary search tree because it is implementing a particular property or particular rule inside of it. And this is exactly what we are going to do to construct our heap also. So heap also have a property that we are going to implement inside of this binary tree. A binary tree is like a white paper. It's like a canvas in which you can actually draw whatever you want to. So now let us look at the Min-Heap first. The Max-Heap is basically the opposite of the Min-Heap, so it will not be hard for you to understand what that is. So for Min-Heap, we have this particular property or a rule. Each node must be less than or equal to both the child nodes. What this means is that we can have a binary tree like this. We will have, like just say 5 here, okay? And then in both of these child nodes, the value should be greater than or equal to the parent node. For example, I can write here 6, I can write here 10. This is a condition for min-heap. The each node, that means this one node, the 5th node, must be less than or equal to both child nodes. So for 5th node, we have this 6 as child node, 10 as child node. So 5 is less than this child node and this child node. So it is actually satisfying the min-heap property. But then how do you actually construct a tree like this? Well, for that you need to understand one thing, how we represent a tree inside of an array. We have a list like this, okay? And here we can have like just say 5, 7, 9, 8, like just say 12, okay? So these are the nodes that we have. Now in an array, we can represent a tree like this. We have a parent node, okay? And the index of the parent node is I. Then the index of the left child node, LC, is going to be 2 multiplied by I plus 1. And the index of the right child node is going to be 2 multiplied by I plus 2. So if I try to make a tree with this data, it will be something like this. We will have indices like 0, 1, 2, 3, 4, and now we can start making it. So first of all, the I will be 0, right? So I will take the 5th node like this. And now we want to figure out the left child node and the right child node of this 5th node. So the left child node is what? 2 multiplied by I, that is index, plus 1. So 2 multiplied by 0 plus 1 is 1, right? So it means the index 1 represents the left child node. It means the 7 is going to be the left child node. So we will draw it like this. In the same way, to find the right child node, we will do this. 2 multiplied by I plus 2. So 2 multiplied by 0 plus 2 is what? 2, right? So the index 2 represents the right child node. It means the right child will have 9 here. Okay. In the same way, if I want to figure out the child node for 7, so the index for 7 is what? 1. So the left child node for 7 is going to be 2 multiplied by 1 plus 1. So the third index is going to represent the left child node for this particular 7th node. So we will have like this. We will have 8 here because 8 exists on the third index. In the same way, I can figure out the right child node also. So 2 multiplied by 1 is going to be 2 plus 2. So the fourth index is going to represent the right child node for this particular node. Now if I try to find out the left child for 9, I will multiply 2 by 2. So 2 multiplied by 2 is equal to 4 plus 1 is equal to 5. But we don't have a fifth index, right? We don't really have it. It means that ninth does not have any left child. And if I try to find the right child, I will have to multiply 2 by I. So 2 multiplied by 2, 4 plus 2 is going to be 6. We also don't have 6. That means we don't have any right child for 9 also. And in a similar way, we don't have any left child for 8 or right child for 8. We don't have any left child for 12 and right child for 12. So I hope you can understand how we are able to represent a simple binary tree. It is not a heap right now or a BST right now. It is a simple binary tree with the help of a list like this. And now we have all the information we need to create a heap. So now suppose that we have a list like this. We have 9, 10, 1, 3 and 2. And we want to create a heap from this list. So what we can do is we can take the first node, okay, and we will just write it like this. We will have it in the heap like this. We will just store it. So we will actually have this heap a list here. Inside of it, we will keep on storing the nodes, but I'm not showing it here like this explicitly. I'm just showing everything visually. So we will have the 9 here, and now we will get the 10. Okay, so the next thing is 10. 10 is what? 10 is greater than 9, right? So the first instinct will be to actually create the left child node for the 9. Since 10 is greater than 9, we will simply create a left child node for the 9. What this simply means is that we will have a 9 here and then we will directly add 10 here. Simple as that. Okay, that's what it will mean. Now we will actually get this 1. And now here the things get tricky because 1 is less than 9. So I cannot just go ahead and place it like this here. It will be wrong, right? But that is exactly what I'm going to do. I'm going to take the 1 and I'm going to place it here. Okay. And then I'm going to use a function like shift up. Okay. We will create this function in the code. Don't worry. But we will use this function on this node. Okay, and we use this function to make sure that this particular one is going to be on the correct position. So what this shift function actually do is that it will take the current node, that is 1, and it will check the parent. Now how do you find the parent of a node in this particular heap list, right? Well, you will have the index of this one node. Okay, now to find out the parent, you will simply do this. Parent is equals to I minus 1 divided by 2 floor function. Floor function simply means that if the result of I minus 1 divided by 2 is something like 2.5, you will round it off to only 2. That means the parent is going to be 2 if the answer is 2.5 here. That's all the floor function means. And do not worry, you do not have to implement this floor function yourself. In each language, you will have a mathematical library that will have it for you already. So now in the shift up, what we will do is we will take the index of the 1. Okay, so basically we will be placing 1 here immediately after the 10th. And then we have the I is equals to what? 2. So I right now is 2. Now to find out the parent is 2 minus 1 divided by 2 is equals to what? 1 divided by 2 is equals to what? 0.5. And then the floor function of 0.5 is what? 0. It means the parent is going to be on the 0th index, which is 9, right? So 9 is the parent. And now we will check just one thing. Is this current one node less than 9 or not? If it is less than 9 or basically less than the parent, we will swap. We will take this one node and we will take this 9th node and we will swap their position. Okay, so we will also have to create a swap function that will take two things, two value 1, value 2, and it will simply swap them. And do not worry, we will see this swap function implemented in the code. So here I will just take the 1 and 9 and I will simply swap their positions. So 9 is gone from here, 1 is gone from here, and then we will write it like this. 1 will be here, 9 will be here. So we have swapped the elements. Now 1 is less than 10 and 1 is less than 9. So it means we are again satisfying the min-heap property that each node in the tree will have less value or equal to value than the child nodes, not more than them. Now we will take the next element, that is 3, and we will insert it inside of the heap. So we will simply add it at the end. So 3 will come here And now we will check, is it actually making sense? So what is this 3? Where will it be? Well, the index of 3 is what? 3, right? So what is going to be its parents? Well, 3 minus 1 divided by 2. 2 divided by 2, that is 1. It means the element at index 1 is going to be the parent. So the element at index 1 is what? 10. It means 10 is going to be the parent and it is going to be the left child node of 10. That is 3 will be here. Now we see that the 10 is more than 3 and 10 is the parent here. It should not be the case. It is breaking the min-heap property that each node is going to be less than or equal to its children. So we are going to use shift up again on this third node. So we will take this 3 node, we will calculate its parent and we will swap it. So after swapping, we have 3 here, we have 10 here, just like we have in the heap array. Remember, I'm using the drawing of this tree for visualization. Okay, in the memory, in the computer, this list is going to be stored in the computer. Now we reach the next element, that is 2. So we will try to place the 2 here. We will expand this list and we have 2 here. Now where will it be? Well, the index of the 2 is what? It is going to be 4, right? And so the parent is going to be 4 minus 1 divided by 2 floor function, which means 3 divided by 2 floor function, which means 1.5 floor function, which means 1. So 1, that means this particular node, the 3 node, is going to be the parent of this 2 node. It is going to be the right child of 3 right now. So we will have 2 here. But you can see that it is breaking the heap property. So 2 is less than 3. But it should be the other way around because it is a min heap. It is a min heap. That's why we need 3 to be the child of 2, not the other way around. So we will again use the shift up function and we will simply swap these two elements. Now after swapping, the tree will look like this and we don't have any other elements anymore in the given list. And our heap looks like this: 1, 2, 9, 10 and 3. And this is how we are able to build a min heap. So now we are going to use the same heap that we created above and try to extract the element from it. So we know that the top element is going to have the minimum value, and here we are saying that 1 is greater than 5 in terms of priority. That's why it is a min heap. So it means 1 have the highest priority, so it is at the top. So what we are trying to do is we are trying to take this element out 1 and then reheapify, or basically recreate this entire thing in as less time complexity as possible. So what we will simply do is we will say element that we want to get is lm. Lm is equals to what? Heap 0, because we know the highest priority element is always going to be at the 0th index. So we have the element now and we just have to remove this from this particular place. So how do we do this? Well, if I just go ahead and do this, I just try to remove this from here, I will have to take all this element and shift them this side, right? And it is going to take what time complexity? Order of n. That will be order of n time complexity, but we don't want that. If we wanted that, we would have used the sorted or unsorted array anyways, right? So what do we do now? It is very simple, guys. We will take the last element and we will override 1 with 3. And to remove the last element is very simple. We will simply remove it. We will use function like pop, or basically we will just override it with 0. Okay, removing the last element is basically order of 1 time complexity in any language. But now that we have placed the 3 here, we need to make sure that the heap actually satisfies the property properly. So right now we have 3 here and we have removed this last element from the heap. So as you can see here that this 3 is basically greater than this child element. But that should not be the case for min heap. For min heap, each node should have greater child than itself. So it means we are not satisfying the min heap property. So now we have to use something like shift down. Okay, shift down is actually a function that will help us make sure that this tree is again a heap. So we will run the shift down on this particular node and we will need two things. First is left child, which is going to be what? 2i plus 1. And then we need right child. It is going to be 2i plus 2, right? Now we know that the index of this particular node is what? 0. So what is going to be the left child? Well, 2 multiplied by 0 plus 1, 1. In the similar way, 2 multiplied by 0 plus 2, it is going to be 2. So left child is going to be at index 1 and right child is going to be at index 2. Okay. So after finding out the left and right child, we will take the minimum of these three. We will take this element, we will take this element, and we will take this element, and we will make sure that we actually get the minimum of these three elements in this top position. So first we will check, is the element at index 0 greater than the element at index 1, that is 2. If it is greater than, we will simply say that the min element is at index 1. Okay, this particular index. And now that we have the min index 1, we know that the value at min index is 2, right? This particular 2. And then we will actually make a comparison between this 2 and this 9. Okay, we are not going to make a comparison between 3 and 9 because we know that 3 is basically greater than this element. So we need to make sure that this element, the 2 element, is also less than this particular right child element. So if I make a comparison, then I realize that yes, 2 is less than 9. So the minimum index will stay 1. If in case this was not actually 9, suppose if this was actually 1, if this was 1, we will see that 2 is greater than 1 and we will have to change the minimum index or update the minimum index to basically 2, the index 2, because this particular node will be at index 2 in the heap list. But currently it is not 1, so we will not do that. And now we have the index at which we have the minimum element. So what we will do is we will take the element at this index and we will swap it with this particular 3. So the index is 1, that means 2. So we will take the 2 and we will swap it with 3. And now after swapping, we have 2 here and 3 here. And now we will run the shift down function on this node because we want to make sure that this particular subtree is also a min heap. Okay, so that's how we are going to do. And here I can see that the 3 is greater than 10 and this particular thing does not exist. So it is already a min heap. So we don't have to do anything. We can stop right here. But if it was something like 2, we will actually have to do the same process again. Get the left child, get the right child, find the minimum index, and then we will swap them again. And so we will keep on calling this shift around function until we make sure that we have the entire subtree as a heap again. Now we can go ahead and see the operation versus time complexity. So for insertion, we actually have a time complexity of log n. And this is because we have a tree like this. We have node here, then again node here, then again some node here. Okay. And we are actually inserting something at the last index here. And then we just bubble it out, top and then top. We are not dealing with every other element here. We are going to be running the shift up function from this node to the root node, and that is going to take log of n because we are not going through every element here. Similarly, to remove an element from the top, we will use the shift down function, and the shift down function will also just go on a particular path only, and that will also take order of log n because we are not going through each and every path. If we were going through each and every path, we would have gone through n elements and nodes, but we are not going through each and every path. We are going to specific path. Now here is the tricky part. If you have an array like 1, 9, 7, 8, okay, and you want to build a heap out of it, in our current implementation, it will take order of n log n because you will keep on inserting the elements in the heap and you are inserting n elements and each element will take order of log n time complexity. So it will take order of n log n time complexity to build a heap from a given array. But in languages, okay, you have a much better, more optimized solution. So there you will actually just take order of n time complexity to build a heap from a given array or a list. So in our current implementation, it is order of n log n, but the implementation that you will be using from your languages, it is going to be n. And the proof of this order of n time complexity is actually quite mathematical. So I will not be going in that proof, but you can search online if you want to dig deeper in this concept. Now the max heap is identical to the min heap. It is basically the same. The only difference is the property. So here each node value is greater than or equal to the child nodes. Basically in min heap, parent was actually less than or equal to child nodes, but in Max-Heap, parent is greater than or equal to child node. And that means the only thing that will differ is this particular sign. In the Max-Heap, we will use the greater than equal to sign, and in the min-heap, we are using this less than or equal to sign to actually implement the shift down and shift up. Everything else will be same. All the implementation, all the logic, all the time complexities are going to be the same. They will not change. And you will see that very clearly in the implementation that I'm going to show you for Max-Heap and min-heap. Believe me guys, they are the same even in implementation. The only thing that will change is this particular sign from less than to greater than. So here is the implementation of min-heap in Python just to make sure that we understand everything easily. First of all, we are creating this heap array or heap list in which we will store the heap. And we are doing this in the constructor so that each time we create an object of min-heap, this particular array or this particular list will already be initialized. It will not be null or none. And then here we have a few functions. This function tells you the parent of the given node I. So we will have the index of the node, we will pass it in the function and we will get the index of the parent. Okay, here we are using the I minus 1 divided by 2. This particular sign says integer division. So it means if the answer of this expression is actually 2.5, we will actually get 2 here. Basically the floor function that we talked about. And then here we have the function to get the left child node. As you can see here, 2 multiplied by I plus 1. We are returning that index. Here we have the function to get the right child node. 2 multiplied by I plus 2. So here is the swap function. It's a very simple function. We will have the I, we will have the j, and then we will simply swap the elements at I and j with j and I. It is a simple swapping function, and yes, in Python you can do this. Okay, this line is only valid in Python, but if you are using something like C# or Java, you will have to use the temp variable to store one of these elements and then just make the swap that way. Now here's the function that inserts a particular element inside of the heap. So we will take the element or the key that we want to insert in the heap, and then we will take the heap, and then here in the heap array, we are appending or we are adding this thing at the end. So append function will take this particular given input, the key or the element, and append it at the end of the heap, just like we were doing in the drawing explanation. Now once we have the key at the end of the heap, we will use the heapify up or shift up. So this is basically the shift function that we talked about. It is heapify up or shift up. You can call it whatever you want. But this function is going to do the same thing that we discussed. Here we are giving it the index at which we appended the key, which basically means that we are giving it the last index that is currently existing in the heap, and then we are running this particular heapify function. So what does this heapify function do? Here it is. It is going to just run the while loop just like we were doing. So what it will do is it will make sure that the index is greater than 0. It is not basically less than 0. If it is negative, we have reached the top and we have gone out of the bounds. So at that point, we will simply stop the while loop. But here is the main condition. Here we are checking if in the heap, the parent of this particular given node I, if it is greater than the current node's value, the value at the current index I, then we will simply swap, because we want to make sure that the parent is less than, but it is currently greater than this particular ith node. So we will simply swap the ith node with its parent, and then we will set the I to its parent's index, and then just keep on using the while loop until we make the entire tree a heap again. Now here's the function that will remove the node with the highest priority. Here also what we are doing is simple. We have a few checks in the starting. First of all, if the self.heap is none, it means it doesn't exist. Simply return none. Okay. Then we are checking if the length of this particular heap is 1, that means there is only one element. We will simply pop that element. It means the heap at this point is empty. Simple, right? And we will just return it. But in any other case, we know that we will have to re-heapify or basically reconstruct the tree somehow. So first of all, we will get the root element or the element with the highest priority in the root variable, just like we did in our drawing explanation. And then we will take the last element in the heap, we will pop it, and then we will take that element and we will override the top element or override the top position in the heap. That's what we are doing. And now we are simply using the shift down function or heapify down function to make the tree a heap again. And in the heapify down function or the shift down function, we are doing exactly the same thing that we discussed in the drawing explanation. We are getting the min index, we are setting it to I right now, because that's what we know, that I is the minimum right now for us. Then we are taking the left child, we are taking the right child, we are taking the length of the heap so that we will not go out of bound. And here we have the checks. So if the left index is less than n, that means we are within the bounds of the array or the list, and the value at the left index is less than the value at the current minimum index, we will change the minimum index to left. Simple. And then we will check again if the right index is less than n, which means we are within the bounds of the list. And then we will check if the element at right index is less than the element at the current minimum index. That means even after updating the minimum index here, we are again checking it with the right element. So it means the element at the right index is still less than the element at the minimum index. Then we will simply update the minimum index again, and then we will check if the minimum index is not basically the same as I. Then we will simply swap I with minimum index, and we will just again call the heapify down function on this new minimum index. We are calling the heapify down function on this new minimum index. It's a recursive call. If it is not true, that means we have made sure that the current heap is a min heap again, and we will simply exit this function. And then here we have a simple example usage. So we will simply create the object of this min heap class, and we will have some elements like this, and we will just keep on inserting these elements inside of the min heap easily. And once we have the min heap, we are just printing something, and that's all. You can use this as an example code to test things out on your end. And here is the example for Max-Heap. It is literally the same as min-heap. We have the constructor here. We are again initializing an empty heap here. We have the functions for calculating parents, for calculating left child, for calculating right child, and then we have this function for swapping also. Then we have this function for insert also. It is basically the same as earlier function. And then we also have this function for extracting or removing the element. It is also basically same as the earlier function. The only difference is this heapify up and heapify down function. So in case of min-heap, the only difference was that this particular sign was actually like this. Okay, and we just flipped the sign to this. So right now what we're saying is that the parent element, if it is less than the current element at index I, we are going to swap. We are just doing the opposite of what we did in the min heap, and the rest of the function is basically the same. Same for the heapify down. Here we are checking this particular thing. We are checking if the element at left index is greater than the element at max index. If it is greater, we update the max index, and then we are checking if the element at right index is greater than the current max index. If it is greater, then we will again change the max index, and here we are checking if the max index changed, then we are simply swapping, and then we are again calling the heapify down on the max index recursively. It is basically the same thing. The only thing that we are changing are these signs. That's all. And here's the code for example usage here. So you can create a max heap object, then you will have some list of elements, right? And then you can simply insert all of those elements with the help of max heap.insert function. Then you can try to print everything down if you want to. You can use this example code to test out your max heap implementation also. Now, one tip that I want to give you is that you will use the heaps or priority queue for these kind of questions. The top k elements or the top k greatest elements. Basically, you will have a condition and you will have to find the top k or the most useful or the most important k elements from the given elements for that particular condition. And there you will use the priority queue or minimum or maximum heap depending on the question. I have already created the videos in which I am solving these kind of questions with the help of priority queues. So you please watch them if you want to get a greater understanding of it. So today we have LeetCode 1046, that is last stone weight. In this problem, we have been given a stones array, and in that array we have been given the weight of the stones. And now we are playing a game with those stones. So in each turn, we have to choose the heaviest two stones from the given stones, and we have to smash them together. Okay. Now suppose the heaviest two stones have the weights x and y, where we are assuming that x is going to be less than or equal to y. The result of the smash will be if x equal to y, then both the stones will be destroyed. Nothing will be remaining. If x is not equal to y, the stone of weight x will be destroyed, and the stone of weight y will have a new weight. Okay, and here the question is saying at the end of the game we will have at most one stone left, and we have to return the weight of the last remaining stone. If there are no stones left, we simply return 0. So basically we have a lot of stone A, B, C, D, X and Y in an array, and we are playing a game with these stones. Now in the game, at each turn we are supposed to take two stones out of this array. So we are going to take the two heaviest stone. So we suppose that X and Y are the heaviest stone till now in the array. So we take X and we take Y. And now we are saying that if X equals to Y, then both the stones are smashed together and both of them gets destroyed. And if they gets destroyed, we don't really have to do anything, correct? We just can go to the array and get next two heaviest elements, suppose C and D, and we play the game with C and D in the next turn. Simple. If X is not equals to Y, we are saying that X will be destroyed. So X will not be there anymore. And the Y will actually become Y minus X. Now Y minus X will always be positive. Why? Because here we are saying that X is going to be less than equal to y. But then again, this condition has been stated in the question itself. While we are coding, we can simply use absolute function to get the positive difference between y and x, so that we will know that okay, it's always positive. And now this thing, the y minus x, will give another stone, right? So new stone will be this one. And since we have a new stone here with a new weight y minus x, we can actually put that again back into this array so that we can play with this stone also in the next turn. So that's what we are supposed to do in this question. So based on the discussion that we have done till now, let us try to understand how we can actually solve this question. So we are supposed to get two heaviest elements from this array in each turn. So suppose that we want S1 and S2 at each turn. Now nowhere in the question it is mentioned that the array is sorted. It means we can have any random order of the elements. So how do we get the two most heaviest elements from the array? Well, one way is to actually sort it. You can go ahead and sort the stones array and get the two heaviest elements from the end or from the starting based on how you are sorting. So yeah, you can actually sort it. Suppose we sort it in the descending order, so it will become 8, 7, 4, 2, 1 and 1, and then we can just get the element from the starting of the array each time and then smash them and then put them back into the array, sort it again if we want to. So yeah, we can do it, but this is going to take at least order of n log n. So this is actually coming from the sorting part. That's why the overall time complexity for this thing will actually become n log n. But as I already said that we can actually do better, so let's look at that solution. Now let us try to understand what exactly do we need to do in each turn. So in each turn we are supposed to get two heaviest elements. Right now the heaviest elements are 8 and 7. Great. So how do we get these in the minimum time? So if we really notice, we will know that the condition is that each time we take out something from this array, it needs to be the maximum element in the array. We are not really worried about the order of the other elements. The order of the other elements can be anything. But each time we are taking an element out of the stones, it needs to be maximum. And this kind of property where we are saying that we need the maximum element from the given elements each time I'm taking out the element, this kind of property actually exists for the heap, specifically Max-Heap. So Max-Heap will give you the maximum element from the array each time you are taking out the element from it. And the order of the other elements does not really matter, because each time I take out an element from the Max-Heap, the Max-Heap will readjust itself in log n time to get the next maximum element at the top, and then we can just get the 7. And so that is pretty efficient. And so it means the time complexity for taking out an element is log of n. Similarly, insertion is also log of n. So these are the properties of Max-Heap. You should learn about Max-Heap if you don't know about it. So we will have a Max-Heap here, and we will just put all these elements into the Max-Heap. Now I am going to put them in the sorted order just for the ease of explanation. But understand that they don't have to be sorted order. Each time you create a heap from the given elements, they can be in any order. The only thing is that the maximum element will be at the top, always. So let us try to create the heap. So we have our condition fulfilled. We have the 8 that is maximum at the top, and rest of the elements are below it. Now it looks like a stack, but it is not a stack. Okay, it's not stack. Not stack. It just looks like it because I'm just trying to explain you how the min heap works by taking out the element at the top, which is maximum. So first we will take out the two elements that are maximum. I will take the first 8. 8 has been taken out. The heap will readjust itself to make sure the 7 is at the top. So 7 will be next taken out, and now the heap will readjust itself to have 4 at the top. Great. And now we play the game with S1 and S2. So this is S2. So 8 and 7 are not equal. It means they both will not get destroyed by each other if I smash them together. So they are not equal. So all I need to do is get the difference between 8 and 7. So 8 and 7 difference will be 1. So the weight of the new stone equals to 1. And now that we have 1, we are supposed to put it back into the heap. So if I put it back into the heap, I will have another element here. Now here I'm adding it at the end, but it doesn't have to be at the end. It can be in the middle of these two ones or at the top of the ones. It depends on the heapify function that we are going to use. So as I said, the order of the elements does not matter. The only thing matters is that the top element in a heap is always the maximum element or the minimum element, depending on which heap you are using, max heap or min heap. So basically 8 and 7 are gone. So I will now take out 4 and then I will take out 2. So I will have now 4 and 2 in the next iteration. Now 4 and 2, they are also not equal, right? They are different. So what I will do is I will have a new stone that is 4 minus 2, that is 2, and then I will again put this 2 into this heap. So the 2 will come somewhere here. So as we know that we actually removed the 4 and 2, but we are again putting the 2 back into, so the 2 can come here. So we again have 2 in the heap. And now we have 2 and 1 as the next maximum elements. So we will just use them, 2 and 1. Now they are again not equal. So we will simply say new stone is equals to 2 minus 1 is equals to 1. And now we will put 1 into the heap. And earlier we removed this 2 and this 1, right? So the heap function can place the 1 here again. So we have 1, 1 and 1. 3 ones in the heap. So I will take the next two maximum elements 1 and 1. Then we will have 1 here and then 1 here. And these are both same. So they will be destroyed, right? So we don't have to put anything back into the heap. And then this is gone, this is gone. So the only element that remains is 1. So the only element that remains is 1, and we don't have any other element. So we cannot continue the game with a single stone. So we end the game and we just return the weight of this particular stone, whatever it is. So this will be returned. And that's it. This will be the answer. Now, in case we have nothing in the heap, everything gets destroyed, we can simply return 0. That is, we have no stones left anymore. Now let us go through the code. Now let me tell you that I'm using Python, and in the Python we don't have the concept of Max-Heap till yet. We can only create min-heap, and that's why there is a clever way to actually get a Max-Heap from a min-heap. So yes, here I am creating a min-heap, but what I'm doing is that I'm setting the value of the stones as negative. So here I'm running a for loop for the stones, and I'm just setting the negative value of the stones in the stones array. Basically, I'm taking all the values in the stones and just turning them into negative. And then I'm using the heap_heapify function from Python to turn this stones array into a heap. And now since stones array actually contains everything as negative of its original value, the min heap created by this line will actually act as a max heap for us. Let me show you how. So here we have a while loop that is actually representing the game that we are playing. We are just running this while loop till the length of the stones array is greater than 1. So if we ever reach a point where the length of the stones array is 1 or 0, we end the game because we know that we have found the answer. And now at each iteration, we are taking S1 and S2. So here you can see that I'm using the negative sign. Why? Because everything in the stones was already negative. So in order to get the original value, I will take out the stones value and I will make a negative of it. So as you can see here that S1 will be positive. So I'm popping the element from the stones heap and I'm turning it into negative just to get the original value back. And once this line runs, the stones heap will actually readjust itself to get the next maximum element at the top. And once that happens, in the S2, we will actually get the next maximum element at the top. And here also the heap will readjust itself to get the next one at the top. Now here we are checking if S1 double is equals to S2, we do nothing. Everything is destroyed. We just take out the stones and just throw them away. So we will simply say, okay, continue. Let's move on to the next iteration or next turn. Otherwise, if they are not equal, we know that after smashing them, we will have a new stone and we are supposed to put that new stone into the stones heap. We are calculating the new stone S1 minus S2, the absolute value, and then we are storing the negative of this absolute value of S1 minus S2, that is the new stone value, into the stones heap. Remember that this step we are doing only for Python. In other languages or in other places, you don't really need to use it because there is a concept of Max-Heap there. But for Python, we have to use this clever way of using negative sign to actually just, create a Max-Heap out of a Min-Heap. So now once we have pushed it, the heap will again readjust itself to get the maximum element at the top. And once this while loop is actually done, we will have either one element into the heap or we will have nothing. So that's what we are doing here. If there is any element into the stones heap, we will return that element. And of course, we are actually adding the negative sign to return the original value that was actually present. Otherwise, if the length of the stones is not greater than 0, we know that nothing is there, everything is destroyed, so we will simply return 0. This is a short way to do this in Python. In other languages, you might actually have to use if-else statement properly. So yeah, let's try to run this code and see what happens. So yeah, our solution runs and passes all 74 test cases. It runs in 0 milliseconds and beats 100% of the solutions on LeetCode. Although this number is very questionable, I mean, how can you run 74 test cases in 0 milliseconds? Maybe you are using nanoseconds or something, but yeah, you can understand that it's a pretty efficient solution. Now let us look at the time and space complexity for this solution. Now here the space complexity is order of n, and I'm pretty sure that people know why it is. We are using heap, and in a heap, we can actually end up storing n elements in the worst case. So that is why we are saying order of n for space complexity. The interesting thing is order of n log n for time complexity. As I have already told you that sorting is not a good way to solve this question because it will take order of n log n at least. And so you might be thinking that why am I using heap then? If it is the same time complexity, why the heap? Well, let me tell you that it's not the same complexity. So by using sorting, you can actually solve this question in two ways. Either you sort the stones array one time in the starting and then just use that array, or you can sort the stones array each time into the while loop. So in case one, when you're sorting the stones array earlier without the while loop, what will happen is that in the while loop, you may actually get a new stone and you will put it into the stones array. And now you don't want to sort it again. So what you will be doing is, in order to put it into the stones array, you will run a for loop inside of this while loop to check where should I place this new stone value. And once you find the new stone value that, okay, this is where you can place it, you will have to shift the already existing elements towards right side just to accommodate the new stone on this place, right? And then yes, there will be some elements in this side also, but you will definitely have to shift the elements, and that can take like order of n in the worst time complexity. So finding the place in the stones array where the new stone should be and then adding the new stone into that place by shifting the rest of the stones to the right, this entire thing will actually take order of n time. Why? Because first of all, you're going through the elements that are not supposed to be shifted, then you find the place where you can actually put the new stones, and so you put it there and you shift the rest of the elements to the right side. So in this entire operation, you actually traversed each and every element in the array only once. So that's why order of n. But then what will happen? Since we are using a for loop inside of a while loop, and that for loop can actually run for order of n, the time complexity for this will actually become order of n square. And which is just not good, which is worse than order of n log n. Now in case you just said, okay, I don't want this thing, I will just remove it, I will sort the array each time inside of the while loop, your code will look something like this. You will have a while loop, you will play the game, then you will get a new stone, you will put it into the stones array, and then you will sort it. Now in the first iteration, the sorting will take like n log n. Now in the second iteration, we will have like one less element into the stones array. Why? Because one of the elements were got destroyed, correct? We took out 2, we just put 1 into it. So one element or one stone must have been destroyed. So in the second array, when we are sorting, we will have n minus 1 elements and then log of n minus 1. Similarly, in the third iteration, we will have, and once you have add up all of these, you will get a time complexity of order of n square log n, which is definitely worse than order of n log n. So that's why we did not use the sorting algorithms. We simply used the heap algorithm. So now I believe you can appreciate the heap algorithm far better. So today we have LeetCode 347, that is top k frequent elements. In this problem, we have been given a nums integer array and an integer k. And now we have to return the k most frequent elements from this nums array. And we can return these elements in any order, which means we don't need to use sorting. Here is a simple example. We have 1, 2 and 3 in the array. The 1 occurs 3 times, the 2 occurs 2 times, and 3 occurs only 1 time. So 1 occurs 3 times, 2 occurs 2 times, and 3 occurs only one single time. Now we have this k integer and it is equal to 2. It means we need to send back or return two most frequent elements, which means we need to return two elements that have the greatest frequency or greatest count in the array. And that is why we are returning 1 and 2, because 1 has the count of 3 and 2 have the count of 2. However, if the k was equal to 3, we would need to return 3 elements that have the most frequency in the array. And right now, it would have been 1, 2 and 3 all. So our answer would have been 1, 2 and 3. This would be the answer. Now there are a few ways to solve this problem. One of the ways is to just sort the array. You sort the array and then you will have something like 1, 1, 1, 2, 2 and 3. Now in the sorted array, you can just take a pointer like p1 and you just store these elements. So you will have a result variable and then we will just store it like this. So first p1 is at this value. So we will store the 1 here and then p1 will come here and we will check, is this value same as the previous value? If it is same as the previous value, we will simply shift to next one. And here also this one is same as the previous one. So we will simply shift to the next element. So the p1 will be here now. And now we check, is it same as the previous element? No, it is not. So it means we found a new element. So we will simply place it here. And now you can see that the length of the result is basically 2, which is equals to the k. It means we do not need any more elements to store in this result list. So it means we can simply stop this particular loop and just return the result from here. But here is the thing. The sorting takes order of n log n time complexity, which makes it not very optimized. So is there any other way to solve this particular question? Well, there is. So we have two optimal ways in which we can solve this question. We can use the heaps or we can use the bucket sort. Now bucket sort is a little bit tricky to implement and a little bit tricky to understand. So we are not going to understand it in this video. But if you use bucket sort, you can get up to order of n time complexity and order of n space complexity. But it's a little bit tricky for people to understand. So we will see the bucket sort some other time. But right now the main thing is heaps. This solution is also very optimal and it is very acceptable solution. Suppose we have a list like this. Here we have 1, 2, 3 and all these elements are actually randomized. They are not in sorted order. So how are we going to solve this question with the help of heaps? The first thing we need to do is make sure that we know the occurrence of each element. So 1 is occurring 1, 2 and 3 times. 2 is occurring how many times? 2 times. So we will have something like this. Then 3 is occurring how many times? 3 times. Now what does this thing look like? This thing looks like a hash map. It is actually a hash map. So we are going to create a hash map where we will store the frequency of each element. And now once we have this hash map, we can now try to use priority queue or heaps. So in this case, we are going to use a Max-Heap. So Max-Heap is basically a data structure that will give you the element with the highest priority or maximum priority first. But what is going to be the priority here? The priority is going to be this frequency, because this frequency is what we are using to judge whether we want to actually return 1 or not. And we are only returning the elements with the maximum frequency. So it means we are going to use frequency as the priority. So we will have a heap and we will place all of these elements inside of this heap. Now after placing all of these elements inside of the heap, we will have something like this. And I'm representing heap like a stack only for visualization. Okay, this is just a visual understanding. A heap is actually a tree structure. It is not some stack structure. Okay, it's a tree. But just for the sake of simplicity, we are using this kind of visualization here. Now this is a max heap, which means the element with the highest priority is going to be at the top. And that's why we have 1, 3 at the top, because the priority is here 3. Then we have 2, 2. Then we have 3, 2. Now these 2, 2 and 3, 2 actually they are having the same priority. So it is possible that the 3, 2 can be above 2, 2 or 2, 2 can be below 3, 2. Like that's possible because heap only cares about the topmost element. This element, the top element, should be of the highest priority. All these elements, well, their order can slightly change each time you run the heapify function to generate a heap. But since their priorities are same, right, x2, it does not matter whether we return 3 or 2 in the list. They are both fine. We can return whatever we want. And here I've made a slight change. The thing is that when we are storing things in the heap, this priority is going to be the first element inside of this tuple. So that's why I'm storing this count or the priority here. And this is the number or the element that we are supposed to return. So here 2 is priority and here 2 is the number that we can return. Here 2 is priority and here 3 is basically the element or the number that we can return. So now we can create a result list, and inside of this list we can start adding elements. So the first thing we will do is we will pop the first element from the heap and we will get 3, 1. Now we don't need to check what is the priority, we just need this number, right? So we will take this number and we will place it inside of this result array. Then this thing is gone. This has been popped, right? It is no longer in the heap. Now this thing, the 2, 2 will be popped. Then we will get 2, 2 here like this. And then we will simply take this number 2 and we will place it inside of our result array. And in the same way, we can pop out the 2, 3 also. So we will have priority 2 for the number 3. And then we will just take this number, we will take it and place it inside of the result array. And then we can return it. However, if the k was 2, if we are saying that we only want 2 elements in the result, then this 3 would not be here. But if the k was 3, then this thing would be here. But if the k was 4, what do you think will happen? Well, we will still give the 3 back, and since we don't have any more elements, so the result will only store 1, 2 and 3 in case the k was 4. And that is how, my friends, you can use heaps to solve this particular question. Now let's go through the code. First of all, we are creating this count hash map in which we will store the number and its occurrence. Then here in this for loop, we are actually calculating the occurrence for a given number and storing it inside of the count hash map. Then here we are creating a simple list and calling it a heap. Right now this is not a heap, it's a simple list. Then here we are simply going through our count hash map, taking the number and the count for that number, and then we are appending the negative of c, that is negative of count, and the number here. So this is the tuple that we are appending inside the heap. The reason we are using this negative sign is because in order to create a Max-Heap inside of the Python, you actually have to basically just append the negative sign for the priority. And that is a neat trick to create a Max-Heap inside the Python, because Python does not support Max-Heap. It only supports Min-Heap. Now, of course, whenever you are popping the element and you need this priority, you will again have to multiply it by -1 to get the original priority, because in the heap it will be stored as a negative number. Now, once we have placed all of the pairs for priority and the number inside of the heap list, we can just heapify our list. So I'm using the heapq module, and then I'm using the heapify function, which is present in the Python built-in libraries, and then simply heapifying this particular list. So this line will simply convert this particular simple list in a heap. So it means this particular heap is simply a max heap now. Now we are creating the result list, and here we are running the while loop. In the while loop, we are running it only while k is greater than 0, so that we will not go out of bounds, and only if the heap contains something inside of it. If heap itself is empty, there is no point in running the while loop. We will simply return this empty list. Now in the while loop, first of all, we are taking the element by popping the element from the heap, and then we are appending the number from this particular element, because the element is going to be a tuple, right? It will have -c and n, right? So we are going to take the number that is present at the 1 position in the element, and then we will append it into the result array, and then we will simply decrement the k by 1. And once this entire while loop is done, we will have the result inside of the result variable, and then we can simply return it. So now let us try to run this thing and see what happens. So our solution runs in 3 milliseconds and beats 90.44% solutions on LeetCode. It's a pretty efficient solution. Now let us look at the space and time complexity for this particular solution. The time complexity here is k log n. Why? Because we are running the while loop at the end for k times, and each time we are popping the element from the heap, the pop element will take log of n time. And since we are calling the pop function inside of the while loop, it means the pop function for heap will run k times, k multiplied by log of n. And that's why we have this time complexity here. Note that the heapify function that we use to generate the heap from the given list actually take order of n time. So you can also say that this time complexity is order of n if n is very large. Now let us look at the space complexity. And the space complexity is also order of n. The reason is very simple. We have a hash map inside of which we are storing the frequency for each number, right? So this can take order of n time complexity in the worst case scenario, where each number in the given input is actually a unique number. So you will store all these numbers here. And also we have a heap, right? So heap also contains pairs of these same numbers, right? And heap can also be order of n in the worst case, when every element in the given input is actually unique. You will end up storing all of these things inside of the heap. So that is why space complexity is also order of n. Now I know that there is bucket sort also that we can use to solve this particular question, and that will give us order of n time complexity. But that is a little tricky solution, so we will see it later on. So today we have LeetCode 295, that is find the median from data stream. Basically, in this problem, we have to create a data structure that can handle a stream of data. So the stream is simply adding numbers. So first I add 4, then I add 3, then I add 2, then I add 1. That's the simple stream. And this data structure should also be able to give us the median of the entire data that is currently present in the stream. The median is the middle value in an ordered integer list. What it means is that we can have a list like 1, 2, 3, and it is sorted, right? It is from smallest to the greatest, and then here the middle element is going to be the median. So this is the median. But if the size of the list is even, there is no middle value. The median is the mean of the two middle value. What it means is that if we have a list like 1, 2, 3, and 4, the size is even, right? And here we don't have any middle value. We have two values in the middle. So we will take them 2 and 3. We will add them and then we will just divide them by 2. So it is basically equal to 5 divided by 2, that is 2.5. That is the median. One thing to notice is that we can find median in a sorted list, okay? But the stream will have random values. First you can get 3, then you can get 2, then you can get 1. So the sorted order is not guaranteed by the stream. The stream can give you any random number. So how can we solve this thing? Well, first of all, let us try to find out the median. So the median only needs the middle values, right? And finding the middle values is very easy in case of list. So even if you increase the size of the list, we can always find the middle value just by taking the length of this entire array and dividing it by 2. So that will simply give us the middle element or middle two elements, whatever we want. So that is going to give us an order of 1 time complexity, which is pretty good. Like this is exactly what we want to find the median. The tricky part is actually inserting the elements in the list. So suppose that in the data stream we get 3 first. So okay, we will add 3 here. Then we get 2. Now what do we do here? Well, we can simply add 2 here, then actually run a sorting algorithm on this list. Okay, so this will actually sort this to 2 and 3, and then our insertion will complete. Then we will get 4 here, then we can simply add it at the 4 here, right? Then we can get 1 here, right? And as soon as we get 1 here, 1 will be placed here, and we will end up sorting this entire list again. So now we will run a sorting loop here. So we will get 1, 2, 3, and 4. So one way is to just add the element in the list and run a sorting algorithm in the list. So that is one way to do this. And this will make the time complexity of our insertion function to be order of n log n. Why? Because sorting takes order of n log n. That's why it will become order of n log n. But you can do better. There is more efficient ways. So if I get 3 first, I will place it here. Then if I get 2 here, then I will not place it here. I will not do this, right? I will simply take the 2 and I will go through this entire list. I will see where is the first element that is greater than 2. So I will find 3 and I will take the 3 from this position. I will shift it to this side. And then in the position of 3, I will insert 2. And this thing we can always do. Now if we get 4 here, then we can simply come here. We will go through the entire list and we will place the 4 at the last, right? But if we get 1 here, we will come here. We will see that 2 is greater than 1. So we will take the 2, we will take the 3, we will take the 4, we will shift it to this side. And then in the array, we will have something like 4, 3, 2. We have shifted them and then we will get an empty place here that was occupied by 2 earlier. And then that's where we will place 1. So in this solution, we are going through the entire list, right? All the time. So it is going to take order of n time complexity because we are just going through the list, we are shifting elements and we are just inserting it. So this is a linear time complexity algorithm. But to make this solution pass on the LeetCode, you have to do even better. Order of n will not cut out. So in order to do better, we need to understand how does the sorted array works. So suppose that we have 1, 2, 3, 4, and let's just say 5 also. So if I want to find the median, I can simply take the middle element, right? This is the median. I can get the length and I can divide it by 2 and I will get the index of this element and I can get it in order of 1 time complexity, right? But if we really look at it, what we are really doing is that we are dividing the length of the array or the list by 2. What it means is that we are dividing the array or the list by 2, right? We are dividing it in the half or trying to divide it in the half. And so we will have two separate sections. One will be this section and another one will be this section. And then we are taking the maximum value from this section, right? So the maximum is 3. So that's what we are taking as the median. And we are doing this when the length of the entire list is odd, right? Odd means we will actually have a middle element and we can find it. But what if it was even? We can have 1, 2, 3, 4, 5, and 6. What will we do in this case? We can again take the length of the list, we will divide it by 2, and that will divide the list by 2 from here. We will again have two sections, this one and this one, right? In this section, we want to find out the maximum here. And in this section, we want to find out the minimum value, right? So from one section, we want to find out the maximum. From another section, we want to find out the minimum. And then we will take these two values and then we will simply add them. So 3 plus 4 divided by 2, and this will give us the median. So 7 by 2 is equals to 3.5 or something, right? So 3.5 is the median. So this gives us a hint that we want the maximum from a particular section and we want the minimum from another section. And we want to make sure that finding the maximum and the minimum is order of 1 complexity, or at least as low as we can get. And in this kind of situation, we can use a data structure like heap. So heap is a data structure that gives you the maximum or the minimum element that is present in the list. So if you have the max heap, it will give you the maximum element. If you have min heap, it will give you the minimum element. If you want to know how heaps work, I have already created a video that you can look at, because heaps are a very simple data structure and they are really useful. So we know that we will have an array or a list and we will divide it by 2. Okay. So what we want to do is, instead of having a single list, we want to do is we will have 2 lists, or basically 2 heaps. One will actually be a min heap and another one will be a max heap. Now we know that the list is actually divided like this. We want the maximum from this section and we want the minimum from this section. So what it means is that we will store 1, 2, 3 in this section and we will have a max heap here. So this will be a max heap because we want the maximum element from these elements. And then we will store these elements here, 4, 5, 6, and it will be a min heap. Why? Because we want to get the minimum element in the least time complexity. So instead of having one single list, we will actually have 2 heaps, and these heaps will actually help us to find out the median. To find out the median, we can simply take the max heap and we can get the maximum element in order of 1 time complexity, and then we will take it here, and then we will have the min heap and we will get the minimum element in order of 1 time complexity, and we will get the 4 here. We will add them divided by 2, we will get the 3.5 in order of 1 time complexity. Now the question is, how do we insert elements in these heaps, right? So suppose that we will get an element like 4 first. So we will take the 4 and we will insert it in the max heap first. We will not insert it in the min heap, we will insert in the max heap. And right now the length of the max heap is 1 and the length of the min heap is 0, right? So the difference between the max heap and the min heap can only be 1 at max. If it is greater than 1, well, that is not correct. Why? Because ideally we would like the max heap and the min heap to be equal to each other. Okay, their length should be equal. But we know that we have a case where we can have odd number of elements. So we can have 1, 2, 3, 4, and 5. And if we divide this list, we will get 3 elements in the max heap and we will get only 2 elements in the min heap. But this case is also valid, right? Because we have a middle element and we want to return it. So that is why the maximum difference between the length of max heap and min heap can only be 1. If it is greater than 1, we will have to do something. We will see what we need to do later on. But now that we have inserted 4 here, we can move on. Okay, now we will try to insert, like just say 3. And I want to take the 3 and I will place it right here. Notice that I have not sorted it. Okay, I have placed the 3 right here. But now as you can see that the length of the max heap is now greater than the min heap. So what I need to do is I need to take out the maximum element here. Okay, so I will take out the 4, and taking out 4 is simply order of 1 time complexity because we are using heap. So I take out the 4 and I will place it inside of the min heap. So I will place it here, and insertion in a heap is basically order of log n. Simple as that. So it is not order of n, it is order of log n, which is very low time complexity. So whenever the difference between the length of max heap and min heap is greater than 1, that is 2 or 3, then you will take the element from the heap that have more elements and place it in the heap that have less elements. Right now max heap had more elements, so we placed it inside of the min heap. So 4 is no longer here. Now let us try to add 1 here. So I will take the 1, I will place it here in this place. Length of max heap is 2, length of min heap is 1, and the difference is simply 1, so it is fine. Now we will take another element, like just say, I don't know, 5. Okay, and I will take the 5, place it right here. And now the length of max is 3, length of min is 1, right? So 3 minus 1 is equals to 2, and this is not okay, right? So now we will take the element from the heap that have more elements and we will place those elements in the heap that have less elements. So right now max heap has more elements, and so we will take the max element from the max heap, that is 5. So 5 will be taken out in order of 1 time complexity, and then we will place it inside of the min heap. So 5 will come here, and this will take order of log n time complexity. Now let us move on and add 2 here. So if I take the 2, I will end up inserting it in the max heap first. So I will have 2 here, and then I will check the length. So the length of the max heap is 1, 2, 3. It is 3, and the length of the min heap is, well, 2. So the difference between them is 3 minus 2 is equal to 1, which is okay. we can accept this. And now that we have inserted all the elements that we wanted to insert, if we want to find out the median, what we can do is we can simply take the max heap, find the maximum element, that is 3 here, and then we will take 3, and we will take the min heap, find the minimum element, that is 4 here, and we will take the 4 and we will add them and divide by 2 if we want to. But since the length, okay, the length right now is 3 and 2, so 3 plus 2 is basically odd length, so we will not do this. Okay, we will simply take the element from the max heap 3 and we will return it as median. And actually there is a simpler way to do this. If the length of max heap is greater than the length of min heap, so right now it is 3 and it is 2, so we will simply take the element out of max heap and we will return it as answer. So right now we will take the 3 and return it as answer. If the length of min heap is greater than the length of max heap, we will take the element from the min heap and we will return that. But if both of them have the equal length, then we will take an element from the max heap, then we will take an element from the min heap, we will add them, we will divide them by 2 and then return that as answer. Simple as that. So now that we understand the answer, let us look at the code. Now here is the code. First of all, we are initializing the object with small list and large list. Small list will be the max heap, so it will contain all these elements. Why? Because they are the smaller elements. These elements are actually smaller than this element. And the large heap will actually contain this section of the element, that is 4, 5, 6, which means large heap will actually be a min heap. And this is actually a max heap. The names may be counterintuitive. We have max heap for the small one and the min heap for the large one, but the logic that we discussed earlier does not change. So we have initialized the list and now we have these functions, add number. So during insertion of element, we are taking the number and we are pushing it in the small heap first. And the reason I'm using -1 is because you have to multiply the value by -1 in Python and then store it in the heap to actually make a max heap, because Python does not implement the max heap by default, so you have to use this hack around to actually use a min heap as a max heap. This is a very Python specific thing. You don't have to do this in other languages. So now that we have placed the num in small heap, we can move on. Now we have to check a few things. If there is some element in the small heap, there is some element in the large heap, and the element at the small heap is actually larger than the element at the large heap, we will pop the element from the small heap and place it in the large heap. The reason we have that kind of condition is because suppose I want to place 100 in the list, okay, or maybe 1,000. I want to place 1,000 in this heap. So I will take the 1,000 and I will place it inside of this heap, the max heap right here, okay. Now the length of this max heap is what? It is 3. The length of min heap is what? It is 2, right? So it means the difference between their lengths is 1, okay? So it means we will not actually take out any element and place it inside of the min heap. We will not do that, right? But if we really look at it, we have 1, 2 and 1,000. We have 4, 5. So if we try to look at it in a sorted way, so we will have 1, 2, 4 and 5. And then we will have 1,000 in a normal list, in a normal sorted list, right? And then if we will try to find out the median, we will take the length, that is 5, and then we will find the median, and then we will find the middle element, so it will be 4, and this will be the answer, right? But in this case right now, if we check based on the previous logic, then we will see that the length of the max heap is more than the length of the min heap, so we will take out the element from the max heap, right, the maximum element, and that will be the answer. So in that case, I will just end up taking out the 1,000 and I will say that 1,000 is the median, which is clearly wrong. And that is because the 1,000 was supposed to be in this section, right here, and that is because the 1,000 was supposed to be in this section, not in this section, right? But since we are adding everything in the max heap first and then we are checking for the length and then we are dealing with the other logic based on the length of these heaps, in this kind of situation we will actually keep these kind of very large elements in this max heap, but they should not be in the max heap, they should be in the min heap, right? And that's why we will always check if the largest element in the max heap is actually larger than the smallest element in the min heap. We know that we need to take that largest element out and we have to place it inside of the min heap. So that's what that condition is talking about. Now once this is done, we are checking the other conditions. If the length of the small list or the max heap is actually greater than the length of the large list or the min heap by 2, we are adding +1 to make sure that the difference between them is not just 1, it is greater than the 1. So if the difference between them is actually greater than the 1, we will take element from the small heap or basically the max heap and then we will push it inside of the min heap or basically the large list. And the same condition is copy pasted right here. In case the min heap have a greater length than the max heap, then we will pop from the min heap, that is a large list, and we will push it in the max heap, that is a small list, to make sure that we will get the right answer. Now one thing to take care of is -1. You need to make sure that you are multiplying -1 in the right directions if you're using Python. If you're using some other language like C, C++, Java, or C Sharp, you will have the concept of Max-Heap there. But since we don't have Max-Heap here, that's why we have to use this hack, okay, to actually use a Min-Heap as a Max-Heap. So you need to make sure that you are actually using -1 in right places. So you can look at the code right here and see where I'm using the -1 and just try to understand why I'm using it. Because multiplying by -1 is a Python language specific issue. It is not a DSA problem. Now here we have the next function, that is find median, and this is the simpler function. So if the length of the min heap, that is the large list, is actually greater than the length of the max heap, that is the small list, then we will simply take the element from the large list or mini heap, because we will have the odd element with the extra element present in the large list or the mini heap. Now if the things are other way around, that is if the max heap or the small list have greater length than the large list or min heap, then we will take out the element from the small list or basically the max heap, and we are multiplying that by -1 to make sure that we are returning a positive value, because small list or basically the max heap will be having negative values inside of it. This is a Python specific thing. Else, if the length of both heaps is equal, then we will take out one element from each of the heaps and we will add them and then we will divide them by 2. Here I am multiplying -1 with the small list because this small list or the max heap will have negative values inside of it. So getting an element from this small list will return a negative value, and we will need to multiply it by negative to make the entire result positive here. And then we can add it to the other element and then divide by 2. Now here I can simply divide by 2 and it will give me a float value, that is decimal point values. But if you're in other languages, then you will need to use data types like float or decimal or basically double or some other kind of data type to make sure that you are getting point values. Otherwise, you will simply get integers which will actually make your entire answer wrong. Because as you can see that we can have 2.5, that is a decimal or floating point value, as a median also. So keep the data types in mind. So now let us try to run this thing and see what happens. So yeah, it runs in 196 milliseconds, beats 46.45% solutions on LeetCode, and passes all of the 22 test cases. It's a pretty efficient solution. So now let us look at the time and space complexity for this particular solution. So for insertion of the element, we will have the time complexity as order of log n, because we are using heaps. We are just taking out elements from the heap and inserting in the heap, and insertion and deletion from the heap actually takes order of log n time complexity. That's why we have order of log n here. The space complexity is going to be order of n because we are going to have two heaps that are going to store all the elements on the stream. So if the stream have n elements from 1 to n, then we will end up storing n elements together combined in both the heaps. So eventually taking up order of n space complexity when both of the heaps are combined together. Now for finding the median, we have the time complexity as order of 1 because we can take out the elements from the heap in order of 1 time complexity, and the space complexity is also order of 1 because even if we have the same length for both of the heaps and we take out 2 elements, this entire operation will take at max 2 extra variables, right? And 2 extra variables are always going to consume the same amount of space no matter how many elements are present in the heap, because we are only going to take 2 extra elements always. So this extra space does not depend on the input size, which means no matter how many elements we have in the list or in the heaps, this particular space will always remain constant, that is fixed, and that is why we have order of 1 space complexity, that is constant space complexity. We are using constant space complexity for this operation. Hello everyone, today we are going to understand what is backtracking. It is one of the most important topics to understand when you're trying to solve DSA questions or interview questions. It is also a prerequisite to understand the subsets DSA problem pattern. That pattern is really important because it is asked a lot in interview questions. So that makes backtracking essential to have in your arsenal. So the first question is, what exactly is backtracking? And backtracking is a very simple thing, guys. Backtracking is a simple recursive algorithm. So it means it's a simple recursive function that helps to explore all possible solutions of a particular problem. So basically backtracking is used to explore all the possible solution of a particular problem, and it helps us to do that by allowing us to make different decision at each step. Now this is the important part. What this means is that we can go through each and every solution of a particular problem by making different decision. So by looking at the definition, it is very clear to us that we need to know what is a recursive algorithm. So if you do not know how recursion works or how recursive algorithms are written, this is the time to go ahead and watch some recursive algorithm videos, because backtracking is nothing more than a recursive algorithm. That's all it is. Most of the time backtracking is explained like this. You are going in this direction, you made a change in the input, okay, and then you found an answer. Now, once you found the answer, you go back, you undo the change, and then you go into another direction. But this is not the way to explain it, because you're not really undoing anything. This word undo is a very confusing word, and to be honest, it is a very misleading word. What you are doing is you are making a decision. So what you are really doing is that you will be at a particular point in your execution, right? You will have some kind of input. Now you can do something with that input. You can add something in the input, you can remove something in the input, right? It's a decision that you are making. Suppose I decide to add one simple integer. Suppose that this is an integer like 8, and I decide to add 1. So it will become 9, and I pass this 9 into my recursive function in that particular spot. Okay. Now I find particular answer or find some kind of end result after the entire recursive function happens. And now I'm going back, and when I reach this particular point again where I choose to add 1 in the input, now I can make another decision. I can make a decision that I do not want to add 1. Okay. I want to add nothing. Then that will actually just go in another direction, find another answer. Okay. And then we can also come back here. Okay. Now suppose this time I want to add 2. So I will add 2. 8 plus 2 is 10, right? So it will become 10, and 10 will be passed into another recursive function call, and that will return an answer. And then we will come back here, right? So this is what we are doing. We are making a decision. We are passing that decision into the recursive call somehow, and then that recursive call will eventually go ahead and get a result. And if we are not happy with that result, we can choose to make another decision. We are not really undoing anything here, right? Even if we had something like array, okay, we had 1, 2, and 3, and we decide to add 4 inside of it. So 4 will be here, and then we pass it into the recursive function call. It will get us an answer. Then we will come back. Okay. And now people say that we are going to undo this change. Okay. We added something in the array, and now we are going to undo this by popping the element. Well, do you really think you are undoing something? No, you're not really undoing something. You are just removing this element. Okay. And this element was never present in the array in the first place. So what you really did is that you made a decision to pass 4 in the array, and then pass the entire array into the recursive function call. And once you get back answer, you are making another decision that, hey, I do not want 4 in the array. So I will pass a simple array 1, 2, 3, which was anyways the original array, right? So it's a decision whether you want to pass 4 or you do not want to pass 4. It's a simple decision. There is nothing undoing happening. It just so happens that you need to remove 4 by popping it from the list, and then you simply pass the list without 4 into the recursive function call. You can also pass some other element like 7, right? That is also a decision. So what you're doing is that you're making a decision, you're going through that decision, you get an answer somewhere here, you go back, you check if the answer is correct for you or not. If the answer is not correct, or if the answer is not to your liking, you basically change this input. You basically decide that you want to make another decision, and then go through the entire recursive call again. And to represent this idea of making decisions, here is a simple template. So here we have our function, the recursive function, my recursive function, and we are passing an input. It can be an array, it can be a single integer, it can be an object, okay? It can be any input that we want to pass. Then here is the base case, okay? Since it is a recursive function, we will need to have some kind of base condition, otherwise it will go into a simple infinite loop, right? So here's the base condition, and here we can decide to do whatever we want. Whenever we hit a base condition, we can store the answer, or we can basically check the answer. If it is the correct answer, we simply return directly. Basically, we do something with the answer and we return, okay? But if this condition is not hit, what do we have here? We are making a decision here, okay? We have two recursive calls, one recursive call and second recursive call. So in this particular call, the decision one call, what we are doing is we have this particular input, and we are adding a decision A. This decision A can be a simple number. We are adding 1 in the input, okay? This decision A can be anything. So we are adding a decision A in the input, and then we are calling this my recursive function. It will do something, okay? We will end up storing an answer. We will end up getting an answer depending on the function implementation. If your function returns something like int or something, so decision 1 will store the answer. Otherwise, we are storing the answer anyways here in some other global variable, right? But at the end of the day, this function call will do something with this input and this decision A made, okay? And after doing that, we will come back automatically. We don't have to come back manually. It will happen automatically. When the recursion will end, we will simply end up coming back to this particular line again. And so by now we have gone through the decision 1, okay? Now, depending on whether you like the decision 1 answer or not like the decision 1 answer, you can do multiple things. But here I'm just saying that, okay, you know what? I want to go through the decision 1, and I want to go through the decision 2 also mandatorily in every single recursive call. So I made the decision 1, I went through the entire DFS call, got the answer, stored the answer somewhere in the global variable, and then came back. And now I'm going to make a decision 2 here, okay? I'm going to use the same recursive function call, and then I'm going to take the input, and I'm going to make a decision B. The decision B can be some other number. Okay, it can be 2, it can be 0, whatever you want it to be. So we have a decision B, we add this to the input somehow, and then we basically perform this recursive call. Okay, this recursive call will do something, will get an answer. That answer will also be stored in some kind of global variable. Okay, and we will come back. And this is basically what backtracking is. When you come back, okay, you make another decision on the next line. That's literally all backtracking is. You are not really undoing anything, you are just making a different decision. And sometimes you just have to remove an element from the array, or you have to just subtract something from the input. That's not undoing, that's just making a different decision, and that's it. And that's it. That is literally the backtracking that we have been afraid of for so long. It is nothing more than you making decisions and going in different direction, just like normal teenage people do. So in my experience, there are two cases where we need to use backtracking. First of all, when we want to find a particular solution. So it means we will have a lot of solutions for a particular problem. Some of them will be valid, some of them will not be, and we want to find a particular solution. There we can use backtracking because we can always make a different decision to arrive at a different solution. And then the second case is to find all the possible solution. So this is a kind of problem like subsets, where you want to find all the subsets of a particular given array. So you will use backtracking for that also. And we are going to see both of these things in this video itself. First of all, let us try to go through this first case, find a particular solution. So one of the best places to use backtracking is inside of a maze. You will have many different possible paths to go into, and there can be many dead ends in the maze, right? So how do you represent a simple maze inside of a computer? You actually use 2D grid, that's all. So you will have this starting point, then you will have this wall. This W represents a wall or a dead end. And then this is the ending place or the ending cell. So you somehow want to go from start to end cell somehow, okay? And this dot simply means that, okay, you can go into this direction. So how will you start solving this problem visually? Well, we can start from the starting point, right? We have this particular place, and this is where we can start from. Now pay attention, because now we are going to use a decision tree to actually understand how we are going to solve this problem. And decision trees are really important in backtracking. So this is how decision trees work. Okay, we are at a particular position, that is the starting position. So this represents 0, 0, starting position. Now we can make a decision. We can go in this direction, right decision, or we can go in this direction, down decision. Okay, and let us place some constraint also in the problem. So you can either go right or you can go down. So these are the two constraints that we are placing on the problem. So I cannot go up and I cannot go left, only right and only down. So here I have two decisions. I can go to this particular cell or I can go to this particular cell. So suppose I made a decision. Okay, now we are going for decision. I made a decision to go right. So it means I will end up in this cell. The coordinate of the cell is 0, 1, right? So I will be here, 0, 1. Now from here also I can go here or I can go here. Now if I decide to go right again, what will happen? I will come to this particular place, 0, 2, right? So I will be on 0, 2. But now I will see that, oh, it's a wall. So this W will be a string stored inside of this grid. Okay, so I will just check the string. Since it is a W, it means it's a wall. We cannot go anywhere else. We should not even be here, right? So it means we have hit a base condition and we will simply not go anywhere else here. Now the function call will automatically end and we will come back to the original choice, that is this particular cell. And this is the back part of backtracking word. Now we can go to this direction, the down direction. So I will make a decision and I will go here. So I made a decision to go on the down direction. Here we had right direction. Now what we will get here? Well, we will get this particular 1, 1, right? Because that is the middle cell. So I will be on 1, 1 cell and we will check what the value is on the cell. It is a W, right? It's also a dead end. So we cannot go anywhere else from here, right? So from here also we will go back. Okay, now it is a back part of backtracking. Now we are tracking back to the place where we made the decision to go down. And now that we have made both of these decisions, so this does not work, this does not work, right? So we will simply go back. Now we are going back to this particular original place. So we will simply go back to this particular original choice. This is where we made the decision to go to right, correct? And we are going back just because the recursive functions keep on ending, that's all. Now once we are on the 0, 0, we are basically back on the starting position. And now we can make a decision to go to the down direction. So I will go to the down direction here and I will get what? I will get 1, 0, because it is 1, 0 cell. So I have 1, 0 here. And now from here also I can go to down direction or I can go to this direction. Suppose I go to the right direction. So I have a line like this. I have right here and I will reach 1, 1 again. Now we know that it is a dead end. So we will simply backtrack. We will go back to the original choice and now we will try to go into different direction. So now we can go into the down direction, and then we will reach where? We will reach 2, 0, and that is on the down direction. Now here also we have two choices. We can either go this side or we can go this side. Okay. Now if I try to go to the right from this place, I will reach the 2, 1 cell. Okay. And from here also you can go to the right or you can go to the down. If I go to right again, I will reach 2, 2. And here we see that E is written. E means end. So we have found the solution and we will simply backtrack, and simply keep on backtracking and then keep on backtracking from here. We will get the result and we will store the result and send it back. Simple. But you might be asking that, okay, Satyam, this is fine and cool, but what if instead of going right, I would have gone down? What will happen? Well, simple. If you try to go down, you will hit another base condition that, hey, you are out of bounds. Okay, out of bounds, and because of that you will again simply backtrack to this particular place and you will simply make the another choice of going right. Similarly here, if you try to go to the down, here you will again have to see out of bounds error, and you will have to again go back to the original choice and you will have to make the choice to go right, and eventually you will reach this particular ending state and you will simply backtrack and go back to the original 0, 0, and you will simply return the answer. So this is the code for the problem that we discussed above. Here we just want to find out whether we can reach the end cell or not from the starting cell. So initially we are saying that we cannot reach the end cell. Result is false. Now we will try to use this function can reach end, and we are going to pass the row and the column of the starting cell. In our case it would have been 0 and 0, but we should be able to start from any cell, so I'm using this row and column variables. Now here we are checking the out of bound conditions. If the row is greater than the number of rows present in the grid or the maze, we are simply saying return, it is out of bound. Otherwise, if the column is greater than the number of columns that are present in the grid, we are saying return, it is out of bound. Then here we are checking another base condition, that is, if the value at this particular row and column cell is W, that means a wall, we know that we have hit a dead end. We need to just return from here, right? Then here is another base condition in which we are saying that if we found the E on this particular row and column cell in the maze matrix, we can simply set the result to true and we will simply return from here. Simple as that. Simple. Here we actually got the result that we wanted to get, and that's why we are updating the result variable to true, so that we will simply return result variable as true as the answer. And here we are simply returning from the recursive call. Now if none of these base conditions are hitting, here are the lines where we are making the decisions for going right and for going down. So on this line we are making a decision to go right. What will happen if I go to right first? That's why we are adding 1 to the column. In order to go to right, we need to add to the column. So this is basically where we are making a decision. We are adding 1 to the column, and that is a decision that we are making. And once we have made this decision, once we have gone on this particular path, we will get some answer, we will get a dead end, or we will have something. Okay, we will come back to this place. Okay, and now we can go to the other decision, that is going down. Okay, so for going down we have to make a decision to add 1 to the row. So we have rows like 0, 1, 2, right? In order to go down, you need to add 1 to the row. And once you have made this decision, you will go in the direction, you will do something, you will get some answer, you will come back here, and this function will end. And once this entire recursive function runs, going through all the possible paths, we will know that we have found the result. Either it will be true or it will be false. It will remain false if in the maze we can never reach this ending position, because that's one of the cases that can happen for a maze. Maybe the point that you started from is actually an isolated point. There is nowhere to go from that point, so you will never reach the end. So we have discussed one of the use cases of backtracking, where we need to get a particular solution from all the solutions or all the possibilities that we have from the question. Now we can move on to the next use case, where we want to get all the possible solution of a particular problem. And to explain that, there is no problem better than the subsets problem. So in the next section, you will see me solving a particular LeetCode problem of subsets, where we will go through the entire decision tree of how we can find all the subsets of a particular array. Hello everyone, let's solve some LeetCode today. Today we have LeetCode 78, that is subsets problem. In this problem, we have been given a nums array that contains unique elements. It means we are not having any duplicate elements to skip. Now we have to return all the possible subsets from this particular array. What this simply means is that we have to return the power set of this array. The solution set must not contain any duplicate subset. Return the solution in any order. Here we have a simple array nums with 1, 2, 3 as elements to create a subset. As we can see here that we have a few subsets for this particular array. So what is a subset? A subset is nothing more than a collection of elements from the given array. For example, here we have the nums array as our input that contains 3 elements 1, 2 and 3, and here we have all the subset that we can generate from this particular array. So if we look at it here, we have a subset 1, 2. 1, 2 is actually nothing more than a simple collection of these particular two elements. In the same way, we have 1, 3. So we have 1 and 3 as a collection in this particular subset. So that is what a subset is. You basically take a few elements from the array or take none of these elements from the array and create a new list, and that is simply a subset. And since we are taking elements from the array itself, the maximum length subset we can create is the array itself 1, 2, 3. So this particular array is a subset of itself also. Here are all the subsets for this particular array. Let us see how these are made. When we have 3 elements and we decide to choose none of them in our subset, we get an empty subset because it does not contain any element. Now when we only try to choose one and remove these two particular elements from the subset, then we have only a single element in the subset, so we create a subset with element 1. The same way for 2. If we only choose 2 and remove all the other elements, we get another subset that only contains 2. In the same way, if we decide to choose 1 and 2 to contain in our subset and remove the 3, we get this particular subset 1, 2. In the same way, if we decide to remove 1 and 2 and only contain 3, we get another subset that only contains the element 3. In the same way, if we decide to take 1 and 3 in our subset and we remove the 2, we get a subset with elements 1 and 3. In the same way, we can decide to remove 1 and only contain 2 and 3 in the subset, so we get another subset that contains 2 and 3. In a similar way, we can decide to take all the elements from our nums array and then it will create the nums array itself again as a subset. So as you can see that we are just basically choosing an element, removing other element, choosing another element, removing another element, choosing a group of elements and then removing the other group of elements to create any subset that we want. In the question, we can see that we have been explicitly told that the solution must not contain the duplicate set. So what is a duplicate set? Well, if we think about it, if I try to take 1 and 2 only in our subset, then it's a subset, right? But what about if I try to take 2 and 1? Are these two different subsets? Well, no, they are the same subset because they contain the same elements. These are equal subsets. So that is why we are saying that if we have 1, 2 in our answer here, then we must not contain 2, 1. And we can see that here also. In this particular output also, we have 1, 2 as our subset. So it means we cannot have 2, 1 as another subset because that will be a duplicate. So how do we know that how many subsets we can create from a particular given array? And this is where the permutation and combination works. At each of these elements, we have two choices. We can either take it or we can either skip this element and we don't take it. The same way we can do for 2. We can take it and we can skip it. In the same way we can do for 3. We can take it or we can skip it. If we take 1, we skip 2 and we take 3, we get a subset of 1, 3. In the same way, if we take 1, we skip 2 and then we also skip 3, then we get 1, 2. In this way, we can create all the possible subsets. So we have two choices at each given index. It means the number of choices or the number of outcomes from these choices will be 2 multiplied by 2 multiplied by 2 is equals to 2 raised to the power 3. And as we can see that we have 3 elements in our array 1, 2 and 3. It means the n or the length of this array is 3. So here we can say that the number of subsets will be equals to 2 raised to the power n, where n is the number of elements in the array. And so we have to figure out 2 raised to the power n subsets in our answer. Let us see how to create subset. Here we have an array with 1, 2 and 3 as elements. The index for these elements is 0, 1 and 2 respectively. Now at each index we know that we have a choice whether we can take that index or we can skip it. So that's exactly what we are going to do in our code also. So right now we are going to first of all create a decision tree. So the first index that I have is 0. I can either take this index or I can skip it. If I take it, then what will happen? I will have 1 here. If I skip it, my array will be nothing. It will be empty. Now let's move on to the next index, that is the index 1 or the element 2. I can decide to take this 2 or I can decide to not take this 2, and it will need to be decided on both these branches. So if I decide to take 2 on this branch, I will have 1, 2 as a subset. If I don't decide to take it, then I will again have just 1 in my array. Now here also I can decide to take 2. If I decide to take 2, I will have 2 in the array because it was an empty set. If I don't decide to take it, then I will again have an empty set here. In the same way, at each of these positions, I can decide whether I want to take 3 or or I want to skip it. So if I decide to take 3 here, I will have 1, 2, 3 in my subset array, and if I do not take 3, I will only have 1, 2 in my subset array. In the same way, if I decide to take 3 here, I will have 1, 3. If I don't decide to take it here, I will again have only 1 as my subset. Here also, if I decide to take 3, I will have 2, 3. If I decide I don't want 3 here, then I will again have only 2 as my answer. Here also, in the empty subset, I can decide to take 3, then I will put it here. And if I decide I don't want 3, then I will simply again have an empty subset. Now we have gone through all the elements in our nums array. If we try to go further, we will reach the index 3 that does not exist in our nums array. So we can definitely stop the execution now. So we have figured out all the subsets of this given array. All these leaf nodes are representing the subsets. Now understand that this structure that you can see here is not actually a tree. So all these things are actually not a node. These are simple choices or decisions that we made throughout the execution of code. And these decisions eventually led us to these particular outcomes, all these outcomes. So this decision tree is basically a way for us to understand how our choices will affect the given output. Here we are choosing between taking 1 or not taking 1. Here we are choosing between taking 2 or not taking 2. Here we are choosing between taking 3 or not taking 3. So this is basically a visual representation for us programmers to understand how our choices are going to affect the particular input and the output. Now, of course, we are going to use DFS and backtracking to solve this particular problem. We can see that we are going to need recursion to solve this particular problem. So let us see how the recursion flow will work. First, our code will be on 0th index. Then we will decide whether we want to take it or we don't want to take it. So suppose we decide we want to take it in the first line, then we will go here. So the recursion will go to this particular place. Remember that we are not touching this right now. Now in our subset array, we only have 1. Now we move on to the next element and we see 2. Now we have to decide here whether we want to take 2 or not. So in our code, we decide to take 2 and we will reach at this particular position. So we have 1 and 2 in our subset till now. Now we move on to the next one, that is 2, and we decide whether we want to take 3 or not. Then here we decide to take 3 and we have this particular subset. Now we will have a result array in which we are going to store a copy of these subsets. So suppose that this subset is called S1 and I'm storing this S1 here. Now the index will shift again and we see that we are out of bounds. So we will not go anywhere after this particular step, and since it is a recursion, this particular call will end and we will go back to this particular state. We can choose not to take 3 and we go to this particular branch. Now we are reaching the S2 subset. We only have 1, 2 subset, and if we try to further go to the next index, we see that we are going to get out of bound index. So we are going to get 3 here, so we can stop and we store the S2 subset also in the result array. Now the function call will end here and we will go back from this position back to the 1, 2 again. And here this entire thing is done. So we will go back to this particular state. Now we only have 1 in our subset, and here we go to the other path. We decide that we don't want to take 2. We go to this particular place. We have 1, and when we backtrack, we also change the index. So right now we are on index 1 here. Now at this particular position, we again move to the next index 2 and we decide whether we want to take 3 or not. If we decide to take 3, we will have another subset as 3. We will make a copy of this subset. We will store it here. Then we will go back because we will run out of indexes, and we will of course go back to the index number 2. And here we can decide that we don't want to take 3 elements, so we will go to this S4 set. We will now store this S4 set and then we will go back to this particular position. The index is again 1. Now since this particular place is done, we will go back to this particular one. The index is again shifted here. Now from this particular one, we go back to this particular 0th index. Now here we can actually go to the next branch, that is we decide that we don't want to take 1, that we don't want to take this first element. So we will go here. We have an empty element now because we did not take anything. Now the index is 1. We are at this particular position. Now we can decide whether we want to take 1 or not. So in the code, we are always taking the particular index in the first choice and then we are coming back and neglecting it. So first in the code, we will take it. So we are taking the 2 and then the index will shift again. So now we are deciding between 3. We will take or not take 3. So first we will take the 3 and then we will get the S5. Then we will make a copy of S5. We will store it in the result array. Then we will go back. Then the index will also shift again. So index is not this anymore. So the index is now 1 again. Now we will take the another possibility, that is not taking 3. We will reach this particular subset as 6. We will make a copy of it. We will store it. Then we will go back to this particular one. The index will again change to first index. Right now this particular place is done. So we will go back to this particular index. So now we are back here. Now we go to the next possibility of not taking this particular element. So we again have an empty array. We did not take it. Now we can decide between this one. Now we decide to take it, then we get this S7, store here S7, then we come back and then we go to the next possibility, that is not taking it. So we again have this S8, that is empty set. Then we go back here. Since it is done, we go back here again. Then we again go back here, and now it is completely done. So this is basically how our result will be formed, and this is the result that we need to send back as answer. Now let's go through the code. First of all, I have defined the result array here, in which all the subsets will be stored. Then this is the function that will actually generate all the subsets. In this function, first of all, we are taking the index at which we are starting. Then we are taking a subset array in which the intermediate subset will be stored. Since it is a recursion function, we have a base condition here. We are saying that whenever this source index will become greater than or equal to the length of this particular nums array, we know that we have gone out of bounds for this particular nums. So we have reached a particular subset. At that point, we are saying that, okay, make a copy of this particular subset and store that into the result array and simply return, because there is nothing else to do after this index. If this condition is not true, it means that we are still in the middle process of creating the subset, and so we will go on. Here we are making a choice of taking it first and going in that direction. I will append the current element into the subset array, and then I will send this subset array into the next DFS call or the next recursive call for the next index. Now here I am deciding that, okay, I don't want the current element. So yes, here I actually added the current element, right? So I will again have to remove this particular current element. So I will simply pop and then I will send the subset. So right now this particular subset does not contain the current element, so it does not have it. And of course I'm passing the next index that I would like to make this choice on for both of these DFS calls. Now this entire function runs in the same way we discussed here, how the code will flow. And here I'm calling the function with start index as 0 and an empty subset array. We are going to add and remove the elements in this subset array within our code, and at the end we will simply make a copy of it and then append it in the rest. And here I'm simply returning the answer. One thing to notice is that I'm creating a copy of this subset array here. The reason is that when this particular DFS call will end and we will go back to a previous call, this subset array will change. Here we are actually popping the elements from this particular subset array, and the value in these functions are passed by reference, not by value. So it means that if I just say, okay, append subset, not a copy, then this subset will change inside of our res array itself, and that is not what we want. We want to make a separate copy that will not change in our result array. So that is why we are making a copy and storing it in the result array. Now let's run it and see what happens. So it works, beats 100% in 0 milliseconds. Don't trust LeetCode compiler. Now let us talk about the space and time complexities. We know that we are going to have to deal with 2 raised to the power n subsets. So anyway, we will have to make 2 raised to the power n calls. It means that time complexity will anyways become 2 raised to the power n. The tricky part is space complexity. Usually people say that it is order of n, and they are somewhat right also, because they are talking about auxiliary space. Auxiliary space is basically a space used by recursion call stack. So yes, in case you are talking about recursion and its call stack, the space complexity is order of n. But if you are talking about the output array, the output array is basically a list of lists, and that is not order of n. So when we talk about output, we know that the output will contain 2 raised to the power n lists themselves, and each list will have an average size of n by 2. N is the number of elements in the given array. Why is the average size of list n by 2? It is because some list will have 1 element, some list will have 2 elements, some list will have 3 elements, some list will have 4 elements. Then at the end, there will be a list that will contain all elements. So when you take the average of sums of all these lists, you will get n by 2. So what we are saying is that we are going to store these many lists, and each list will have a size of n. So it means that I have list of n by 2. I am storing it this number of times. So it will become 2 raised to the power n. So basically the space complexity will become n by 2 into 2 raised to the power n. And since we do not actually consider the constant stuff, we can say that order of 1 by 2 into n into 2 raised to the power n is simply equals to order of n into 2 raised to the power n. This is basically the total space complexity for the given output. So today we have LeetCode 90, that is subsets 2 problem. We have already solved the subsets 1 problem, in which we were given an integer array of unique elements and we had to figure out the subset for it. Here in this problem we have been given an integer array of nums. The only difference is that the elements can be duplicate. So we can have duplicate elements in the array, and now we have to return the possible subsets of this entire array. Here we can see we have duplicate elements in the nums, and we are only supposed to return the unique subsets from this particular array. Let us understand how to solve this problem with the help of an example. Here we have 1, 2, 2 and 2 in the nums array, and we will try to create its subsets. The indices for these elements is 0, 1, 2, and 3. So we start the 0th index and we will decide whether we want to take this element or not. If we decide to take this element, then in the subset we will have 1, and now we will reach the first index. If we decide that we don't want to take this element, the subset will stay empty and we will reach the first index also. Now we are done with the possibilities of this 1. Now we are at this element, so we will decide whether we want to take 2 or not. If we decide to take 2 in the subset, then we will have subset like this 1, 2, and then we will reach the index number 2 for this particular one. If we decide that we do not want 2, then we will again have just 1 in the subset here in this branch, and we will reach the second index. Similarly, on this branch also, we have an option. We can either take the element 2 or we can decide we don't want it. So if we decide to take 2, then the subset will contain 2, and then we will reach at the second index. If we decide that we don't want it, then the subset will again contain empty, and then we will start considering the element at index 2. So this 2 is actually element and this 2 is actually index. So here we have element 2 at index 2. Don't confuse it. I have colored the indexes in blue. So now we are done with the possibilities of this element and this element. Now we are dealing with this particular 2. So we can decide whether we want to take this element 2. So if I decide to take it, I will be having 1, 2, 2 in this branch of my subset, and then I will reach the index number 3. If I decide that I don't want it, then I will again just have 1, 2, and then I will reach the third index. Now, if I decide to take the element at index 2, then here in this branch, I will have 1, 2 in my subset. Otherwise, if I don't decide to take it, I will only have 1 in my subset, and then I will reach 3 here. In this branch also, if I decide to take 2, I will have 2, 2 in my subset. If I don't take it, I will only have 2 in my subset, and then I will reach the third index. Now here also, if I decide to take 2, I will have 2 in my subset, and if I don't decide to take 2, I will have an empty subset, and then I will reach the index 3 for all these branches. Now here you need to notice something. So first of all, we have a subset here which is 1, 2, and now we again have this subset here 1, 2. So basically there are two branches where we got the same subset, and this will propagate till the end. So we will get two copies of this subset. So why did this happen, right? That is the question. And the reason why it happens is very simple, really. So we started with this 0th index. We decided whether we want to take the 1 or not. So we made our choice that, okay, we want 1. Now we went this direction. Now we are dealing with this particular element 2 in this place. So what we are deciding at this particular place is that whether we want to take the element at index 1 or not in the subset. And in this branch, we are taking it, and in this branch, we are not taking it. So here I said that, okay, I want the element at index 1. That's why I have 1, 2 in my subset. But in this branch, I said I don't want it. That's why I have only 1 in my subset. Now, when we go further in this branch, we reach the index 2. Now we are deciding here whether we want to take this 2 or not. Now I decide that I want to take this 2, and then we again get 1, 2. So what's really happening is that this element 1 is actually making a subset with this 2 at this position, and then it is making a subset with this 2 at this particular position. So yes, if you really look at it properly, you will realize that the 1 here is actually the 0th index element, and the 2 here is actually the first index element. And here the 1 is actually 0th index and the 2 is actually second index element. So yes, from the point of indices, these two subsets are different. But when you actually look at them, elements are actually the same, 1, 2 and 1, 2. And that is why we are calling them duplicate subset. Simply because the elements are same, even though the index wise they are different subsets. And guess what? We still have another 2 here. So from this third branch, we will end up creating more and more and more. So basically this one will create a subset with this 2 also. So we will have again another copy of 1, 2. In the same way, this particular subset 1, 2 will end up creating subset with this 2 and this 2 separately. It means that we will have 1, 2, 2 and 1, 2, 2 at two places. We will have a copy of this subset also. And that is why we will end up having many duplicates. So the question is, how do we avoid duplicates? And it's simple, guys. The reason we are creating duplicates is because this particular element first create a subset with this element and then create a subset with this element in another branch. And it is okay if this particular element was something else like 3, then we would get 1, 3 as a subset in other branch, which is a unique element, right? Which is a unique subset. It's not a duplicate. But the only issue is that we don't have a 3 here. We have 2. It means that we end up repeating 1, 2 and 1, 2 in different branches. And if we look at our decision tree, we realize that once we actually take this 1, 2 and we said that, okay, I do not want this particular 2 in this branch, then later on, I actually encounter this particular 2 and I end up creating this particular 1, 2 again. So now the way to avoid this thing is to make sure that when we are saying, I do not want this particular element 2 in this particular branch, I actually skip all these two. I skip this two, I skip this one, I skip this one, and then I actually go to this branch. Otherwise, I will simply keep creating duplicate subset. So suppose we had three here, we will skip this, and then we will actually take this index, that is fourth index. So we will actually have a choice on the index number fourth here, not two. And then we will actually have 1 comma 3 here or 1 here. Now we have actually avoided the duplicate easily. If we decide we do not want to take this element, then we skip all these elements in this branch. Now similarly, here we are taking 1 comma 2. We are at the index 2. So you can see that this index 2 was not left out. This index 2 was taken care of in this particular branch. Now here also, what we are saying is that if I decide to take this 2 here in this particular place, in this type, then in this side, I must remove or I must skip all the remaining 2's from here to here. Okay, otherwise I will create duplicate of 1 comma 2 comma 2. This thing will be duplicated on this branch. And that is how you find the unique subset in this question. Once you have taken an element A in this side, you will make sure that you skip all the A's. Okay, all the elements that are equal to A will be skipped in this branch. That's how you avoid duplicates in your subset. Now let's go through the code also. So here I'm creating a result array which will actually contain all the unique subsets, and here I'm actually having a subset array which will contain the intermediate subset results. And here we have the DFS. In this I'm passing the source node which is the index of the elements of nums array, and here I have a base case. In case the source node ever becomes greater than or equal to the length of the nums, we know we have created one of the possible subsets from one of the branches of the tree. So we will simply copy that subset, make a copy of it, and we will append it in the rest. The reason we are making copy of this subset is because this subset array is actually going to change throughout the code execution because it is passed by reference, not value. So we are making a copy of the subset and appending it in the array. And then we simply return because there are no more elements in the nums array to deal with. Now, if this base condition does not hit, first we make a choice of having the current element in the subset. That's why we are adding the nums of source node, calling the DFS on the next index. So the left sides of branches everywhere. So this branch, and then this branch also. So all the left side branches are actually controlled by that particular code. Now once we complete all those branches, we will now deal with the branches where we decide that we don't want to take this particular element in the subset. So here I'm just popping the element, the current element in the subset. Here I'm avoiding the duplicate. So here in the while loop, I'm saying that if the source node plus 1 is less than the length of the nums array, so that we do not go out of bound of the array, and if the current element at this particular index or source node is actually equal to the next element, we simply increase the source node by 1. We are simply skipping this element, and once we do this, once we actually reach a unique element or a new element, we skip all the duplicates of this particular element. We will then call the DFS on source node plus 1. And here our function actually ends. So once this entire function runs, we will have result in our res array. Now here we are sorting the nums first of all. And the reason we sort the nums is because we want all these duplicate elements to be together. Otherwise, if they are not together, then I will not be able to skip them, eventually leading to duplicate subsets or wrong answer. So that's why we are sorting it here. Then I'm simply calling the DFS at index 0 of this nums array. And after this happens, we know that we will have a result in the rest. So we will simply return it. Now, in case you are having any issues in understanding how the DFS works, please look at the subsets one problem that I have made a video on already. That video will actually tell you how this particular DFS works with complete flow diagram of recursion calls also. So I highly recommend you to please check out that video if you have any trouble in understanding how DFS or recursion works. So now let us run it and see what happens. So yeah, it runs in 0 milliseconds and beats 100% of the solutions on LeetCode. That's great, right? I mean, yeah, you cannot trust this number definitely, but I believe it's a pretty efficient solution. So now let us look at the time and space complexity for this solution. So in this question, we were supposed to return all the subset by generating them. And that is why the time complexity is order of 2 raised to the power n. Because there are 2 raised to the power n subsets for any array. And it means to create all these 2 raised to the power n subsets, we call the DFS recursively 2 raised to the power n times. And that's why the running time or the time complexity is 2 raised to the power n. Now in terms of space complexity, we have n multiplied by 2 raised to the power n. And the reason is very simple. So we are talking about our output result. So res actually contains how many elements? 2 raised to the power n elements. Because we know that we have 2 raised to the power n subsets for an array. So yes, this will contain 2 raised to the power n elements for sure. So we will have array like this and it will have 2 raised to the power n arrays. Now, how many elements do you think is existing in each of these arrays? Some arrays will have 1 element, some arrays will have 2 elements, some arrays will have 3 elements, some arrays can have 4 elements. So different arrays will have different number of elements, and that's why we will take the average number of elements per array. So we will sum them up and we will find the average, and the average number of elements per array will be n divided by 2. So it means we are storing n by 2 elements 2 raised to the power n times in this particular array. So you can say that res stores n by 2 multiplied by 2 raised to the power n elements in total. And so the space complexity will become order of n by 2 multiplied by 2 raised to the power n, because that is the amount of storage we are taking. But we know that in space complexity, or basically bigger complexity, we do not deal with constants. And here the constant is 1 by 2 multiplied by n multiplied by 2 raised to the power n, right? So we can simply drop this constant because it's a big O notation. So we will simply write n multiplied by 2 raised to the power n, and that's how you calculate the space complexity for this solution. So today we have LeetCode 1255, that is maximum score words formed by letters. You see, the classic technique to make a problem hard is to just make the title confusing and crazy. And the same technique is also used in the description. It can also be confusing to read for beginners. So we will directly try to understand this entire question with the help of this example. So in the question, we have words array, letters array, and the score array. So the basic premise or the basic thing that the question is asking is that we have these words, okay? We can make these words with the help of these given letters. And we have a few letters, okay? We don't have all the letters available in the entire world. We can only use these letters that are present in the letters array to create the words that are present in the words array. And each letter actually contains a value, or you can also call it a score. So this particular score array actually tells you the score of each and every letter. Now this score array actually tells the value of each and every letter in the English alphabet. What it means is that this tells you the value of each and every letter from A to Z in the small case letter. So this 1 represents the value of A, this 0 represents the value of B, this 9 represents the value of C, this represents the value of D. This is for E, F, G, H, I, J, K, L, and so on till Z. So the value of Z is 0 here. So what it means is that you will get the letters from here and you will just search for the value of that letter. For example, A is the letter and the value of A is 0 here. And then C here is the letter. The value of C here is 9, right? So we can search for the value of that particular letter. And since these letters actually have a value associated with them, these words that are actually made up of letters also have a value. For example, if I take the dog letter, I have dog. Then what is the value of dog? Well, it is equal to the value of each individual character or letter. So the value of D plus value of O plus value of G represents the total value of dog word. So currently the value of D is 5, the value of O is 2, and the value of G is 3. So the total value is going to be 10. So the value of dog word is going to be 10, or the score of dog word is going to be 10. In the same way, all of these words actually have a value associated with them based on the letters that they are made up of. And also the letters array actually have duplicates. So if I try to make a word like good, what I will need is I will need one O, then this O, and then I will need G, and I can take one D, right? So these many letters are now used, right? We cannot use these many letters for any other word. So what it means is that if I try to create dog again, okay, after creating good, I will realize that I cannot create dog again because I have already used the G word or the G letter to create the good word, right? So it means once I create the good word, I cannot create the dog word because I don't have enough G instances, right? I have a few extra D here, but I don't have G or any extra O here. So it means that I cannot create dog. I can create the word dad. So I also have a dad word. So I can take this D, I can take this A, and I can take again this D. So then by now we have used all the D's and we have used one A. It means we only have C and A left. So what this means is that the word that you create first is going to decide what other words you can actually create in that way, right? So if you never create good, then you will be able to create dog. If you create dog, you will not be able to create good. And this is what the question is asking. You are supposed to tell what is the maximum value or maximum score that you can have based on the given letters and the words that you can create from them. For example, here we see that we have a few possibility. We can create a set of dad and dog words. So I will have something like this. I will have dad inside of it and I will have dog word inside of it, right? And the value is going to be 21. But I also have one more possibility that I can create dad and I can create good, right? So that will actually give me a score of 23. So I can create another set. So this will give you a value of 23 and it is the maximum value that I can generate based on the given letters and given words. So that is exactly what we need to do. We have to figure out the maximum score that we can generate based on these words and these given letters. So by now you have already seen that we are actually creating sets. Okay, so we have a set like dog and dad, and we are actually trying to get its entire value. The entire value will be just 21,
and then we will have another set like dad and good, and this set will actually have its own value which is equal to 23. The value is just the value of this word plus the value of this word, that's all, right? And both of these are nothing more than subsets of this entire words array. What we are doing is that in one subset we are taking the dog and then we are skipping the cat, we are taking the dad and we are skipping the good, right? And in another subset we are taking the dad and we are taking the good only, skipping this cat and dog, right? So what this means is that I need to go through all the subsets of this words array and just calculate the value for each subset and return the maximum value. That's all. That's all I need to do this. So this entire hard question has now just become simple subsets question. So while creating the subset, we can simply have this index I and we can just create subset with the help of it. So we will basically have a decision tree. I can decide to take the element at index I. Currently it is at dog. So I can decide to take dog or I can decide to skip it. So I don't have dog here, right? Then this will increment, it will go to cat, right? So I can decide to take cat or I can decide to skip it, right? It does not exist. Here also I can decide to take cat and I can decide to just skip it. In the same way, I can decide to take dad also. So I can take dad here or I can just skip it, right? Here also I can take dad and I can just skip it. Here also I can take dad, I can skip it, right? Here also dad I can take and I can skip it. In the same way, the entire recursion tree can be made. But here's one thing that you need to understand. I cannot really create the cat word. Why? Because I have C, I have A, but I do not have T anywhere in the letters array. And that's why creating this cat word is not possible. So on this state, you will not have any branch where we are actually taking the cat word. So what this means is that on this place, there will be no branch in which we are taking the cat, right? So this entire branch will actually just go away and we will only have this branch where we are not taking the cat. That's all. And a similar case will happen when we will run out of the letters, right? So for example, at some point we actually end up creating good. And after that, I cannot have dog. I cannot have dog. Why? Because there are no more G's available inside of the letters array, right? So it means once I create the good, I cannot have dog. And vice versa. If I ever create dog word and then if I try to create good word in the branching, I cannot do that, right? Because there is no G letter available to create the good word. So what it means is that while creating the subsets, there will be times when you will not be able to create a subset or basically a word, and that will be the end of that branch. That's all. So now there are a few optimizations that you can actually do to make things a little bit faster for you, right? So right now we have been given an array for the frequency of the elements right here. And that array is called the letters array, right? So this letters array actually stores the elements or the set of letters that we have at our disposal to use. But suppose if you have this word good, okay, and you try to see if you can actually create this word, then you will have to go through the entire letters array to find the G letter, the O letter, the O letter, and the D letter, right? You have to go through the entire array, which is going to be order of n. So you can simply use something like a hash map, okay, hash map for reducing this time complexity, or you can use a simple frequency array. Okay, if you don't know what is frequency array, we will see in the code, don't worry about it. But you can definitely use these two things to reduce the time complexity from order of n to order of 1, which is pretty good. And in the same way, some of you might be thinking that, okay, we might actually just store the value of each and every word in some other array in the starting itself. But the reality is that while you are actually going in the recursion tree, while you are actually creating the subset, you will have to check for each word whether you can actually create it or not. And the way you check for each word whether it can be created or not is by going through all the characters in that word, right? So I have dog here. So I will have a pointer like k here. The k will be at d first, and then I will check is D still available in my hash map. If it is available, okay, I will shift to the O. Then I will check is O available, okay, if it is available. Then I will shift to the G, and if I find that G is not available in my hash map, then I will not go in this direction. Otherwise, if I have G available, I will simply create the dog word and I will keep on continuing the recursion function. So what it means is that in each iteration, I have to go through the entire word anyways, which means that creating an extra space for storing the values of words does not make sense. I might as well go ahead and calculate the value while I'm checking whether we can create this word or not, right? And yes, there will be some bookkeeping also involved in this question. What it means is that you will have a simple hash map or a frequency array in which you will store the count of each and every character that you have, right? So for example, at some point you started creating good in your recursive function. So what you will do is you will take the G, the double O, and the D, and you will reduce their frequency in the hash map or frequency array by 1, right? You will have to reduce it to indicate that you have used these particular letters.
any other word cannot have access to them, right? So if you reduce them by 1, your hash map will update and you will continue the recursive function from the good, right? But once you come back after calculating everything and you have to go through other branch where you are not taking the good, you will actually have to make sure that you are incrementing the character count of these characters by 1 again, so that these characters, the D, G, double O characters, will be free again for other words to use in other branch, right? So this is the backtracking part of this question, where you are actually increasing the count of each and every character that was present inside of this word again, so that those characters will be available for use in another branch. That is the backtracking part. So now we understand the logic behind solving this question. We will simply have a hash map or a frequency array to keep track of the count of letter that we still have available to create more words, and then we just get all the subsets for this words array and then calculate the maximum value that I can find in all of those and then just return the maximum value out of them. Simple as that, right? So here we have the code. We have used the comments to indicate what each step is doing right now. So currently, first of all, we are creating a count array. This is going to be the frequency array in which we are going to store the count of each and every character that we still have from the letters array. So that's what we are doing. We are creating a frequency array right now. So this frequency array is going to be the size 26 because we only have 26 characters in the English alphabet from A to Z. So for each character that is present in the letters array, we will take that character and then we will just have the integer value for that character and the integer value of A, and this expression will give us an integer number. What it means is that suppose if the character is A, okay, so the character here is A and the character here is A also, right? So if I subtract these two integer values, I will get a 0. What it means is that at count 0th index, we will have a single A, right? That's what we are doing here. So this will help us to create a frequency array. You can go ahead and use a hash map also. You can just go ahead and code a hash map. That is also a very good option. But here I just use a frequency array because it is usually less used, less common. So I just wanted to use it here. So it is good to see these kind of operations once in a while to make sure you do not forget them. Then we have this backtrack function inside of which we have the main logic. First of all, we have this base condition, that is, if we ever reach the end of the words list, which means we have found a particular subset of the words array, we will simply return 0. Because we have reached an index where we don't have a word, so the value of a non-existing word is simply 0. And that's what we are returning in this base condition. Now, once the base condition is done, here we have a few choices. Okay, first of all, we are making a choice to skip the current word, okay, to create the subset. So we are choosing the skip option first because it is simpler to implement. We have the max score variable here and we are running the backtrack function on the index plus 1 element. Here we are simply skipping the current word to create the subset. Now if we want to include the current word, we have to get access to it. So here we have access to the current word. Then the current word score is a simple variable that I'm setting to 0 here. And here we have a variable which will tell whether we can actually create this word with the help of currently available letters or not. So in the starting, I'm setting it to true. And then here in this particular loop, we are checking whether we can actually form the word with the help of currently available letters or not. So for each character in the current word, we are taking the index of that character. We are figuring out the index by taking the integer value of character, subtracting the integer value of a character out of it. And then we will use the index to get the count of the current character in the count array or the frequency array that we created above. Okay, so here in this line we are simply subtracting the count for that character in the frequency array by 1. Okay, and here we are taking the score for that character from the score array and adding it in the current word score variable. And here we are checking if the count of the current character from the word is negative or less than 0 in the count of the frequency array. We will simply set the can form to false. Here we are not breaking, okay, we are not breaking. We will keep going through the entire word, probably making the count of characters less than 0 or negative, but it is fine because we are going to revert these changes later on in the code. So once the for loop runs, we have the answer whether we can form this word with the help of currently available letters or not. If we can form it, then only we will go in the other branch where we will actually take this particular word in the subset, right? So I'm running the backtrack function recursively on the index plus 1. The difference this time is that the hash map or the frequency array have a different value now. Okay, we have updated the frequency array or hash map. In case that we were skipping the current word, we were not actually updating the hash map or the frequency array. But right now we have updated the hash map or the frequency array based on your code, and then we are actually running the backtrack on the index plus 1, which means the next recursive call will have a different set of available characters to use. and then this call will actually return some value. Okay, we will add that value to the current word score, and then this is going to be the total value that we can generate till now. Okay, and then we will compare it with the maximum score that we generated for skipping this particular word. So whatever choice returns us the greater value or the greater score, we will pick that. If skipping the current word gives us greater value or greater score, we will take that. Otherwise, we will take this particular value and store it in the maxs variable. And at the end here, regardless of whether we can form the word or we cannot form the word, we are just making sure that our hash map is now updated again to be in the previous state. So what here we are doing is that we are taking each character from the word here, and then we are just increasing the count of that character in the count array or the frequency array or the hash map. Simple as that. Earlier we were decrementing it. It was minus equals to 1. Now it is plus equals to 1. To make sure whatever we did in this earlier for loop right here, we are actually making sure that these changes are no longer present in the hash map for the other branch. So that's what we are doing here. We are making sure that those changes are reverted. And then at the end, we are returning the maximum score that we found till now. So that was our backtrack function. And here outside the backtrack function, we are actually calling this function to get the answer that we need. So we use the backtrack function and we call it on the index 0. So we are starting from the first index in the words array. And this will give us the answer, the maximum value that we can generate. So yeah, let's run this thing and see what happens. So yeah, our solution runs in 3 milliseconds and beats 99.73% solutions on LeetCode, and it has also passed all the 53 test cases. So it is a pretty efficient solution. Now let's look at the space and time complexity for the solution. So the time complexity is 2 raised to the power n multiplied by L, where L is the length of the largest word that is present in the words array. So suppose that we have words like go, we have get, right? And we have something like LeetCode. So out of these, we have LeetCode as the largest word because it has the maximum number of characters. So the length of this word is basically the L here. This 2 raised to the power n is coming from the fact that we have to run the DFS recursive call 2 raised to the power n times to find all the possible subsets. Okay, because in worst case scenario, we might need to find all the possible subsets for the words array. And while finding the subsets, each time we have to run that loop in which we were checking whether we can actually create the current word based on the available letters we have. And that loop is going to take at max, okay, at max in the worst case, this particular length. So that's why I have L here. And the space complexity is going to be order of n because in the hash map, the maximum we can go for is 26, right? Hash map or frequency array, all of them at max can store 26 characters only because there are only 26 characters in the English alphabet dictionary, right? So this is going to be basically a constant space complexity, right? But this n is coming from the fact that we are going to use recursion, and recursion is going to have a stack, right? A call stack, and that call stack can go at max order of n. So that is why we will have space complexity as order of n. Okay, guys, so you have finally finished the course. You have actually reached this point. You have gone through entire 10 hours of course and you have finally understood what is DSA. The thing is that you will not be able to master DSA until and unless you actually practice. Let me tell you guys, I solved almost 250 plus problems just to understand all of these things. What it means is that you don't need to solve 500 problems. Go ahead and solve 250 quality problems. Go on LeetCode.io, go on Blind 75 list problems, and just solve them all, right? Remember this thing. What this course taught you is a plan. It's a plan, it's not execution. You still have to execute. Just like you go in a gym, you get a plan, but you still have to go there every day, execute that plan, right? That is exactly what you have to do. DSA is not something that you can just watch a video and understand completely. You have to get into the trenches, you have to go for it. You really have to solve problems every day on LeetCode. You don't have to solve 10, 20, 30 problems. Just two. Solve just two problems every day on LeetCode, and that will make sure that you understand everything. Believe me, guys, in enough time, in reasonable time, you will be able to understand the DSA properly, completely, believe me. And once you have understood these 8 patterns properly, no matter the kind of question that you are going to see in the future, you will have some way, some particular way to solve that question. Now, yes, there will be some crazy questions, crazy, just insane questions that will expect you to understand some kind of concept, some kind of algorithm beforehand. But let me tell you guys, those kind of questions are rarely asked. Rarely asked. Like most of the companies that you're going to go interview for, they will not ask those kind of questions. So what it means is that if you just practice properly these 8 patterns on LeetCode, just solving problems every day, just putting in the reps on the LeetCode every day, 2 questions a day, you will be able to solve most of the questions asked in any technical interview in any company across the globe. So yeah, I hope that this video was helpful to you. If you have some kind of question or you have some kind of confusion, you can definitely reach out to me on my LinkedIn, that is at Satyam-Shivhare. You can go there. I will provide a link in the description. You can also reach out to me in the comments. I will see them. If I can reply, I will reply. Otherwise, I will make a video on that comment if it's really that important. But yes, guys, feel free to reach out to me if you ever need to talk. And I wish you all the best for your future endeavors and your future interviews. And with that, I'm signing off. We will meet in the next video. Till then, bye.